Hello everyone, welcome to this data science course by Intellipaat. Ronald Coase, a famous economist and a Nobel Prize laureate, has famously quoted that torture the data and it will confess to anything. And you know what? Every company, be it MNC or a startup, believes in this. I mean, just think about this. Every other company is tracking where you are clicking on the website, how much time you are spending on their pages, which product page you are visiting multiple times. And by churning all this data, they are sending recommendations, WhatsApp messages, or even once in a while advertisement that you see on your social media feeds. And how all of this is happening? All of this is happening by churning out vast amounts of user data. Without a doubt, on an absolute note, data science is one of the strong reasons behind why companies are able to make big fat money. That is the reason why the science of dealing with data or making sense out of it has become one of the best career opportunities with lakhs of jobs available on the job boards worldwide. But what exactly do people do with this job? Let's consider that you are working in a company and they want you to understand what their sales will look like in the upcoming 3 months. Now, you do have monthly sales data of around last 10 to 15 years. So the first thing as a data scientist you'll do is you'll understand your data and clean it for further processing. Once cleaned, you'll do multiple processes and extract the pattern within data. Next, you'll feed details like monthly marketing budget for the next few months, sales personnel count, etc., and you land at a prediction that tells you what your business will make within the next few months. This is also called as predictive modeling or analytics. Now, during this entire process, lots of small tasks have to be done. All of them are done using Python programming language and its different libraries. How? That is something we are going to understand and decode within this complete data science course designed for beginners. This course has been taught by India's best data science trainers and is designed to make you job ready. Within this course, you'll not only learn the fundamentals of data science, but you'll also understand how to apply data science algorithms to different problems end to end. So make sure to stay tuned till the end of this particular course. Now let me take you guys through the agenda for this particular course. We'll kickstart your learning journey by understanding what exactly data science is. After that, we'll get ourselves introduced to the concept of machine learning, what it is and how it works. After that, we'll dive into understanding regression and classification problem setting. We'll explore what is regression, what exactly logistic regression is all about, what is classification, and we'll also explore the concept of confusion matrix. Next up, we'll deep dive into AI and neural networks. We'll learn why artificial intelligence matters, what exactly recommendation engines are, topology of a neural network. We'll get introduced to deep learning, then we'll talk about deep learning frameworks and what exactly tensors are. After that, we'll start talking about how we can go ahead about optimizing neural networks. We'll talk about limitation of single layer perceptron, backpropagation algorithm, gradient descent, Adam optimization algorithm, and how we can do modeling with the help of Keras. Next up, we'll talk about advanced neural network architectures such as convolutional neural network and recurrent neural network. Following that, we'll look into natural language processing and chatbot project. We'll get introduced to a natural language processing library, that is NLTK, and we'll also create chatbot of our own. Once we are done with that, we'll quickly run you through some of the top important data science interview questions that you should know in order to get placed in the top companies such as MNCs and startups. So stay tuned till the end of this video and get ready for data science jobs.
Data science. In a world that is increasingly becoming a digital space, organizations deal with zettabytes and yottabytes of structured and unstructured data every day. Evolving technologies have enabled cost savings and smarter storage spaces to store critical data. Now, organizations can analyze this data to understand global market trends and enable their business to thrive. Data science can also predict future events based on the present and past data. Data science is a field of computer science that involves creating algorithms and models to extract, process, visualize, and find hidden patterns from the raw information. data extraction and transformation, statistical analysis, data manipulation, visualization, machine learning, and predictive modeling are some of the most popular fields in computer science that utilize data science techniques. Every day, 2.5 quintillion bytes of data are generated, and it is more accelerated with the growth of IoT. This data comes from all possible sources such as sensors used in shopping malls to gather shoppers' information, post on social media platforms, digital pictures and videos captured on our phones, and purchase transactions made through e-commerce. Now this data is known as big data. Companies are flooded with colossal amounts of data. Thus, it is very important to know what to do with this exploding data and how to utilize it. Amazon needs data scientists to find out customer mindset and enhance the geographical reach of both e-commerce and cloud domains among other business-driven goals. Similarly, Visa is an online financial gateway for many companies. Visa does transactions worth hundreds and millions in a single day. Due to this, the need for data scientists is huge at Visa to generate more revenue, check fraudulent transactions, and customize products and services as per customer requirements, etc. Now we have 5 stages of data science life cycle. We have data discovery. It includes ways to discover data from various sources, which could be in an unstructured format like videos or images, or in a structured format like in text files, or it could be from relational database systems. Next stage we have is data preparation. It includes converting disparate data into a common format in order to work with it seamlessly. This process involves collecting clean data subsets and inserting suitable defaults, and it also can involve more complex methods like identifying missing values by modeling and so on. Third stage we have is mathematical models. These models are planned and built by the data scientist in order to suit the specific need of business organizations. Then we have getting things in action. Once the data is prepared and the models are built, it is time to get these models working in order to achieve the desired results. And the last stage we have is communication. The data scientists need to be liaison between various teams and should be able to seamlessly communicate his findings to key stakeholders and decision makers in the organizations so that actions can be taken based on the recommendations of the data scientist. In India, data analysts with 1 to 4 years of industry experience earn an average salary of 4,14,000 per year. Expert data analysts with experience of more than 10 years can earn 9 lakhs per year. In the USA, at the entry level, you can expect around $66,994. A data analyst with 3 to 5 years of experience would take around $74,860, while an experienced data analyst with 10 plus years of experience would be around $83,673.
Need to be analyzed to determine the best course of action. This is the main function of the control algorithm and software, and this is where reinforcement learning comes into picture. This is the most complex part of the self-driving car since it has to make decision flawless. A flaw like in case of Uber's self-driving car can be fatal. Okay? In today's world, the most famous self-driving car are those from Tesla and Google. Tesla cars work by analyzing their environment using a software system known as Autopilot. Autopilot uses high-tech cameras to view and collect data from the world, same as what we do with our eyes. It's called as computer vision or sophisticated image recognition. It then interprets this information and makes the best decisions based on it. So this was one of the use case of reinforcement learning. Iris flower dataset. Well, the project which we are going to perform is generally known as the hello world of machine learning. So it's the best project to start with because it's so well understood. Okay. And why it's so well understood? Because so all the attributes in this dataset is numeric. So all you have to do is figure out how to load and handle the data. So it's a classification problem, thereby allowing you to practice with perhaps an easier type of supervised learning. Okay. It also supports a multi-class classification problem that may require some specialized handling. So this iris dataset consists of 4 different attributes: sepal length, sepal width, petal length and petal width. And it consists of 150 rows, meaning it is very small and it can easily fit into the memory. All the numeric attributes are in the same unit and the same scale. Okay, so this dataset doesn't require any special scaling or transformation to get started. Okay, so let's get started to your Hello World machine learning project in Python. So let's get started with your Hello World machine learning project in Python. Okay, so this is my Jupyter notebook. So the very first thing that I'll be doing up here is importing all the required libraries. So I'm importing pandas, and from pandas I'm importing scatter matrix. Next I'll be importing matplotlib as PLT. Then we are importing model selection from sklearn, classification report from sklearn.metrics, confusion matrix from sklearn.matrix, accuracy score again from sklearn. And these are various machine learning models. Okay, KNN classifier, linear discriminant analysis, Gaussian naive Bayes and support vector machine. Okay, so we are importing all these models from our scikit-learn library. Okay, so let's execute it. Our next step is to load the dataset. So the very first parameter that I'm passing up here is the URL of my dataset. Okay, or the path of my dataset basically. So this is my dataset, just to show you. So this link consists of my dataset. Okay. Next, I'm defining an array as names. This consists of the name of the attribute, sepal length, sepal width, petal width, and class. Okay. And next, I'll be defining a variable as dataset. And next, I'm defining a variable dataset. So dataset equal pandas.readcsv URL comma names equal names. So what it is basically doing, it is fetching the data from here, from this link, URL from this URL, and it is giving the name of the attribute as all these: sepal length, sepal width, petal width, and class. Okay, so this will basically load your data set. Fine, let's execute it. So our data set is loaded. Now let's summarize the data set. Now let's check how many rows and columns do our data set have. So let's execute this and check the shape of our dataset. So our dataset consists of 5 different columns and 150 rows. Okay. Next, if you want to check the sample dataset, then you have a head function over here. So this will give you first 20 result of your dataset. Okay, 0 to 90. Fine. Next is the dataset.describe function. So this will give you the various description from your dataset like count, mean, standard deviation, minimum, percentile, 25 percentile, 50 percentile, 75 percentile, and max. So count is basically the total count of sepal length, sepal width, petal length, and petal width. Okay. Similarly, mean of all, similarly standard deviation, and so on. Okay. Next, what if I want to check how many different classes are there or how many values contains in each class? So we'll group by the class and we'll find the size of each class. Okay. Let's execute it. So we got the output up here as iris setosa 50, iris versicolor 50, iris virginica also 50. So this means that we have 3 different classes: iris setosa, versicolor, and virginica. All 3 of them consist of 50 values. Okay, fine. So next is data visualization. So now that we have some basic idea about our data, let's create some visualization out of it. So we are going to look at 2 different types of plot. The first would be a univariate plot, that is to understand about each attribute, and next would be the multivariate plot to understand the relationship between the attributes. Okay, so first let's plot a univariate plot, that is plot of each individual variable. Okay, so this is the univariate box and whiskers plot. So let's consider just sepal length. So the bottom part of here, this represents the minimum value and this is the maximum value. Okay, and this green bar over here, it represents the mean value. So if you see the mean of sepal length, it's around 5.84. It's also representing the same. So it's 5.84. Okay. These circles above and below the minimum point are nothing but the outliers. Okay. Yeah, one more thing, the minimum and the maximum value, right? So minimum is 4.3 for sepal length and maximum is 7.9. Okay, so the minimum value you got up here is 4.3. Okay, so this is my 4.3 minimum value, and here we have the maximum value as 7.9. Okay, and these are the outliers, these circles. Similarly for sepal width, my minimum value was sepal width was 2.0 and maximum 4.4. So minimum from here is 2.0, this value, it's an outlier, and the maximum value is 4.4, this value 4.4, it's also an outlier. And the mean value of sepal width is 3.05. So we got mean somewhere around here. Okay. So in order to understand our data in a better way, we created a univariate box and whiskers plot. Okay. This gives us a much clearer idea about the distribution of the input attributes. Okay. Well, if you want, you can even create a histogram of each input variable to get an idea of the distribution. Okay, so let's execute it. So there's my histogram. So in sepal length and sepal width, I can find the Gaussian distribution up here. Okay, so this is a useful to note as we can use algorithms that can exploit this assumption. Okay, next we have is the multivariate plot. Well, multivariate plot is used to check the interaction between the variables. Okay, so let's just execute it and see what's the output. So here's a scatter plot of all pairs of attribute. So this can be helpful to spot structured relationship between input variables. Okay, so as you can see, we have diagonal grouping of some pair of attributes. So this suggests a high correlation and a predictable relationship. Okay, so from here you can say that sepal length is more dependent on sepal width as compared to petal length and petal width. Similarly, same thing over here, right? So petal length is more dependent on sepal width as compared to sepal length and petal width. Okay, and the petal width, it's more dependent on sepal length as compared to sepal width and petal length. Okay, so these are the things that we can conclude after visualizing our data. Okay, now it's time to create some model and estimate their accuracy on unseen data. Okay, so here we'll follow step-by-step procedure. Okay, first we'll separate out a validation dataset, that is divide our dataset into train and test part. Then we'll use a 10-fold cross-validation technique that will randomly distribute our data into 10 different data sets. Okay, so that we can perform training and testing on each part. Then we can finally combine the result of all of them to get a better accuracy. Okay, then we are gonna build 5 to 6 different models to predict species from flower measurement. Okay, and then finally we'll select our best model. So our first step is creating a validation dataset, that is dividing our dataset into train and test. So here what we are doing, dividing our dataset into train and test. Fine. Array equal dataset dot values. So it consists of all the values inside your dataset. Here you're defining x equal array starting. So here you're taking a portion of the array. Okay, and you're placing it in x. So what is that? So your row up here is nothing. So it will start from the very first row and the column 0 to 4. So it will take up to 4th column. So 4 column from the first row, that is x is storing all the name of the attribute. Fine. Similarly, we are defining a variable y. So y will consist of the 4th column. Next, I'm defining a variable y, array of starting from first row and 5th column. Okay, as 0, 1, 2, 3, 4. So here number 4 represents my 5th column. Okay. Next, I'm defining a validation size as 0.20. So here validation size means it will split my data as 80% in one part and 20% in other. Okay. So next we are defining a seed value. So this seed value is used to initialize a randomization. Saving or setting it to same number each time guarantees that every time you execute the algorithm, it will come up with the same result. Okay. Next we are defining scoring as accuracy. And here we are defining x train, x validation, y train and y validation. So here we are defining x train, x validation, y train and y validation. So x train would be my training data from this part and x validation is the testing data from same. Okay, so according to my above code, my 80% of the data will lie in the training part and the rest 20% would be treated as a validation data or the test data. As I have already mentioned, the validation size is 0.20 or 20%. So this means that 20% of my data is test data. Fine. Similarly, we'll define y train and y validation. That is 80% of the training data from this array and rest 20% of the testing data from same array. Okay, so here we are basically splitting our data set. Okay, on the base of x, y, test size equal validation size that we have already specified as 0.20 and my random state equals c and my random state is c. So every time I execute it, the algorithm will come up with the same result. Fine. So now that we have created a split among our dataset and we have divided our dataset into train and test, so our next step would be to build our model. Okay, so this is how we are building our model. Okay, so from the scikit-learn library we are calling logistic regression, we are calling linear discriminant analysis, KNN, decision tree, Gaussian Bayes and SVM or support vector machine. Okay, here what we are doing, we are creating 10 folds. Okay, so 10 folds, let me just go step by step. So here we are defining a variable as k-fold. So k-fold equal model underscore selection. K-fold, how many split we want to perform is 10 split, and random state again, see, that is 7. So every time it will perform the same random split. Okay, so this is how my data would be splitted into 10 different parts. Okay, now once the data is split into 10 parts, then we'll define a variable as cv underscore results. Okay, so cv underscore results equal model selection dot cross validation score. Inside that we are passing our model, what model we are choosing. We are passing the X train data, the Y train data, CV equal K fold, whatever the value of K fold is there, and then finally scoring, which we have initialized up here as accuracy. Okay, then what we are doing, we are appending our result. So our CV result would be appended to results, that is to this list. So next we have is result dot append CV underscore result. So this list would be updated with the CV underscore result value, and here we are appending the name, and finally we are printing our desired result. So one by one this will go in a loop. Okay, so every time this loop execute, you will get the accuracy of one of the model. Okay, so here right now our model consists of all these values. Okay, as we are appending it, that is we are adding all these values one by one to our model. It consists of logistic regression, decision tree, Gaussian naive Bayes, and support vector machine. All of them are in our model. Okay, and finally it is printing the message. Let's check the output. So we got the output as this. So here the accuracy of a logistic regression is 0.96, that of linear discriminant analysis is 0.97, KNN 0.98, decision tree 0.96, naive Bayes 0.97, support vector machine as 0.99. So from this we can say that support vector machine is having the highest accuracy. Okay, so now our next step would be to compare the algorithm and select the best model. So just by looking at this output, we can say that support vector machine is having the highest accuracy. But let's compare all these algorithms and see which one fit the best. So for that, I'll be plotting a box and whiskers plot for the accuracy versus the name of the algorithm. Okay, so there's my algorithm comparison. Here I have the name of my algorithm and this is the accuracy for them. The green point which you can see up here is nothing but the mean values or this value. Okay, for linear regression I had 0.96, for linear discriminant analysis I had 0.97, and so on. So from this graph, what I can say is KNN, naive Bayes, and support vector machine, these are having the highest accuracy. Okay, as there is no minimum and maximum value, only they are having a maximum value and few outliers, these outliers. Okay, so in case if you are removing these outliers, like this one, these two, and this, so by removing them, KNN will give you the 100% accuracy result. By removing these two outliers, naive Bayes would give you the highest accuracy result or 100% accurate result. So even in case of SVM, if you remove this outlier, you will get a model with 100% accuracy. Okay. Now next is making the prediction. Well, just accuracy shouldn't be your metric to decide that this is your best model. Okay. So for selecting a model, you have several other features which you should decide apart from accuracy. Okay, so your accuracy will not always be the metric to select the best model from. Okay, so let's move ahead and see how to make the prediction. So we have already calculated the accuracy, right? So now from this graph we know that support vector machine is giving the highest accurate result even with the outlier. If this outlier is removed, then it's the best one. Okay, now let's make some prediction on it. Okay, so let's execute this. So here we are printing the accuracy score, we are printing the confusion matrix and the classification report for Y validation and prediction, that is testing and predicted value. So here we are printing the accuracy score for the tested value and the predicted value. We are printing a confusion matrix for the tested value and the predicted value, and finally a classification report, same for the tested value and predicted value. So if you check the score for tested value and predicted value, like accuracy score while using SVM or support vector machine is 0.93. So there's my confusion matrix up here. And finally, we have a precision, recall, F1 measure, and support data for all these three classes: Iris setosa, Iris versicolor, and Iris virginica. So let me just explain you what is precision, what is recall, what is F1 score, and support. So this precision, it tells how accurate or precise is your model. That is, out of those predicted positive, how many of them are actual positive. So this is precision. Okay, next is recall. It calculates how many of the actual positives our model has captured through labeling it as positive. Okay, next is F1 score. It is used when you want to seek a balance between precision and recall because of a large number of actual negative values. Okay, and finally we have support, which is the number of sample of the true response that lies in that particular class. Okay, so while predicting with SVM, we had 7 true responses in case of Iris setosa. 12 in case of iris versicolor, and 11 in case of iris virginica. Okay. Similarly, I made prediction using SVM model. If you make prediction using KNN, you'll get a different result up here. In this case, we got the accuracy as 0.9, and the precision score, recall score, FN score, and support score all are different. Okay. So here in case of KNN algorithm, you can see that we have the accuracy as 0.9 or 90%. The confusion matrix provides an indication of the 3 errors that we made. Finally, the classification report provides a breakdown of the class by precision, recall, FN score, and support. Okay. So we use Python to create few machine learning model and select the best model out of them. So our best fit model is SVM, as it is giving the highest accuracy and high values of precision and recall.
Here's a quiz question for you guys. What is machine learning? Your options are a type of computer hardware, a programming language used for data analysis, a branch of artificial intelligence that focuses on the development of algorithms that can learn and make predictions based on data, or a type of advanced robotics technology. Please mention your answers in the comment section.
Guys, I have a special announcement for all of you. For all of you dedicated individuals who are looking forward to master data science, we are offering a straightforward 20% discount on our data science course, which is in collaboration with iHub IIT Roorkee. So do make sure to check the link given in the description and fill the inquiry form. Shortly, our team of course advisors will get in touch with you to activate the offer. Don't miss this chance and take your career to the next level. Click on the link given in the description right now.
So regression is a technique of finding the relationship between two or more variables. Okay. It is based on the fact that a change in dependent variable is associated with a change in one or more independent variable. Like you can see over here, a regression is a technique that displays the relationship between variable y based on the values of variable x. For example, as the temperature drops, people puts on more jacket to keep them warm. So the selling of jacket and the drop in temperature are both directly related, right? Here, temperature is an independent variable and the selling of jacket is directly dependent on temperature. Okay, so the jacket selling is a dependent variable and it depends on what? On the temperature. Fine. So let's move ahead. Next is regression use case. Let's see some of the use cases related to regression. First, we have temperature versus number of cones sold at ice cream store. So again, temperature is an independent variable and number of ice cream cones sold at ice cream store depends directly on temperature. It's like if it's a summertime or when the temperature is high, so number of ice cream cones sold will be more, right? Next is inches of rainfall is an independent variable and new cars sold directly depends on it. Fine. If there would be more rain, then the number of cars sold in the market would be more. Fine. Next is daily snowfall versus number of skier visits. Again, daily snowfall is an independent variable. It does not depend on anything. But the number of skier visiting directly depends on snowfall. If there would be no snowfall, then there would be no skier visit, right? More snowfall means more skier visit. So these type of problem come under the regression category. So if you think there is a relationship between two things or two variables, then regression would help to confirm it. For example, temperature has one variable and number of cone other variable. If you think that there is a relation between temperature and number of cones sold, then you can use regression to confirm it. Okay, let's move ahead. Next we have is the type of regression. Well, there are various types of regression, but for now, we'll mainly focus on linear regression and logistic regression. So let's see what is linear regression and logistic regression. So linear regression generally deals with continuous variable. Okay, so what do I mean by continuous variable? For example, the amount of rainfall. Okay, so it's a continuous variable. It can range from 0 to 100 centimeter, anything. Or the price of the house. Again, it's a continuous thing, right? The price of the house can range from $100 to around $5,000, anything. Okay. On the other hand, logistic regression deals with categorical variable. These are the kind of variable in which you have to just predict either yes or no, like whether it will rain tomorrow or not. Okay. So these are categorical variable. Next, linear regression. It is used to solve the regression issues. We already discussed some of the regression issues previously. For example, selling of the car directly depends on amount of rainfall in a year. If it is raining more, then the amount of cars sold in the market would be more. So it's a regression issue and it deals with continuous variable. Okay. On the other hand, logistic regression. Logistic regression is used to solve classification issues like, is this mail a spam or not? Okay, or will it rain tomorrow or not? So these kind of problem comes under classification. You have to classify either yes or no. Okay. Next is when you have to predict a new point, the point is predicted using a straight line in case of linear regression. But the prediction in case of logistic regression is done by drawing a S-curve. Okay. Don't worry, we'll see in detail how these lines are plotted. Alright, for now we'll mainly focus on linear regression and how the straight line is formed. So what is linear regression? Well, linear regression is plotting a straight line of a form y equal mx plus c such that it predicts a new data point. In other words, you can understand that if your model is well trained using linear regression, then in that case, the predicted point would lie on the regression line. Okay, and your aim is to draw that regression line. A simple linear regression is useful for finding relationship between two continuous variables. One of them is independent variable and the other is dependent variable. Let's understand linear regression in depth. Let's suppose we have two axes over here, x-axis and y-axis. X has independent variable and y has dependent variable. And your aim is to draw a line of regression. Okay. Now let's suppose we have a data point on the x-axis. It's an independent variable. So if the independent variable is increasing, what should be the change in dependent variable? So if the dependent variable is also increasing, then in that case, we'll get a positive line, right? Both the independent variable and the dependent variable is increasing. So we get a positive line. Next, if the dependent variable is decreasing, and for the decrease in dependent variable, we have an increase in the independent variable. Okay, it's like dependent variable is decreasing and independent variable is increasing. So in that case, we'll get a negative line. Alright. So the line I'm talking about is the line of linear regression. Alright, let's move ahead. Let's suppose this is our observation. Let's add some observation. Okay. Now our aim is to draw a regression line that would help us to predict the point in future. And we'll be doing this using the least square method. Let's understand what exactly is least square method. So suppose this is our estimated or the predicted value and this was the actual value. The difference between actual value and estimated value is nothing but the error, and our main goal is to reduce this error. Okay, and remember this red point which I am plotting over here is the predicted point and it lies on the linear regression line. Okay, so closer the regression line lies to the actual value, the more better it will be. Okay. So coming back, your main aim is to reduce this error or reduce the difference between the actual value and the estimated or the predicted value. Okay. You have to repeat this step for every single point. Okay. And your goal is to minimize the error. Fine. So this is what a least square method is. Don't worry, we'll understand about it in detail. Okay. For now, let's just continue. So let's suppose we have speed on the x-axis and distance on the y-axis. So if you plot a graph, you'll get a positive relation between both of them. It's like for a constant time, if the speed is increasing, the distance would also increase. Okay. We get an equation of line as y equal mx plus c. Here y is the distance traveled in a fixed duration of time. X is the speed of the vehicle. On the other hand, m is the slope or the positive slope of the line. And c is the y-intercept of the line, or the point where the line y equal mx plus c cuts the y-axis. Okay. Now let's consider another example. Suppose we have speed on the x-axis and time on the y-axis. Then for a fixed distance, if the time is increasing, the speed would decrease, or if the speed is increasing, the time would decrease. Both are inversely related to each other. So we'll get a negative relation in that case. So here our equation of line would change to y equal minus of mx plus, where y is the time taken to travel a fixed distance, m again. Here we'll get m as negative. So m is the negative slope of the line. x again speed, and c is a point where the line y equal minus of mx plus c cuts or intersect the y-axis. Okay, let's move ahead. So when you plot a graph between the dependent and independent variable and you get a regression line of y equal mx plus c, in that your y is dependent variable and x is independent variable. Okay, so let's understand linear regression in depth. For this, we'll be plotting few random points and check whether the two variables which lie on the x-axis and on the y-axis are actually even related to each other or not. Okay, we'll see the relationship between x and y variable. So on the x-axis, we have 1, 2, 3, 4 and 5. Let's plot them. X-axis 0, 1, 2, 3, 4, 5, 6. Okay. And on the y-axis, we have 4, 3, 4, 2, 5. So let's plot it again on the y-axis. 1, 2, 3, 4 and 5. Maximum is 5. Okay. Now let's plot our point. So we need to plot x1 and y4. So x equal 1 here and y equal 4. This point. So the coordinate of this point would be 1, 4. Okay. Similarly, the next coordinate that we have is x2 and y3. So x2, y3. Similarly, next coordinate is 3, 4, then 4, 2, then 5, 5. Okay. Now our goal is to create a regression line which passes through all these points with the least error. Okay. So for that, the very first step that we'll do is calculate the mean of both x and y. Remember, the line would pass through the mean of x and y always. So the very first step that we'll do, we'll calculate the mean of x and y. So mean of x is 1 plus 2 plus 3 plus 4 plus 5. That is 15. 15 by 5 is 3 again. So we'll draw a line x equal 3. So there's our line. Next, we'll calculate the mean of y. That is 4 plus 3 plus 4 plus 2 plus 5. That is 18 by 5. Okay. And we'll draw the line y equal 3.6. Okay. The equation of green line is y equal 3.6. So the intersection of both the lines would be the point from where a line of regression would cross. So the coordinate of this point is 3 and 3.6, and the equation of the line is y equal mx plus c. Okay. Now goal is to find the value of m and c. Let's see how we are going to find it. So for finding the value of m, our formula is summation of x minus x bar multiplied by y minus y bar upon summation of x minus x bar whole square. Okay. So let's calculate each point one by one. So first let's see for x minus x bar. So x minus x bar is nothing but the distance of all the point from the line x equal 3. Okay. So first point that we have is value of x is 1 and x bar is 3. So 1 minus 3, that is minus 2. For next point we have x is 2 and y is 3. So 2 minus 3, that is minus 1. 3 minus 3 is 0, 4 minus 3 1 and 5 minus 3 2. Okay, so we got the value of x minus x bar as minus 2, minus 1, 0, 1 and 2. Now we'll calculate the value of y minus y bar. And what is that? It is the distance of all the points from the line y equal 3.6. Okay, so y minus y bar, we have y as 4 and y bar as 3.6. So 4 minus 3.6, how much? 0.4. Next, 3 minus 3.6, that is minus of 0.6. Next is 4 minus 3.6, that is 0.4. Then 2 minus 3.6, that is minus of 1.6. Then 5 minus 3.6, that is 1.4. Okay. Now we'll calculate the value of x minus x bar whole square. Okay. So let's calculate the value of x minus x bar whole square. So there's the square of this green box. So minus 2 square is 4. 1 square 1, 0 square 0, 1 square 1, 2 square 4. Okay. Now we have to calculate the multiplied product of x minus x bar and y minus y bar. This is x minus x bar multiplied by y minus y bar. So minus 2 multiplied by 0.4, that is minus of 0.8. Similarly, minus 1 multiplied by minus of 0.6 is 0.6. then 0, then 1 multiplied by minus of 1.6 is minus of 1.6, then 2 multiplied by 1.4, it's 2.8. So we got all the values. Now next our turn would be to summate them. So summation of x minus x bar multiplied by y minus y bar upon summation of x minus x bar whole square. So let's calculate the summation of each one of them. So summation of x minus x bar whole square is 4 plus 4, 8 plus 2, 10. Okay, and summation of minus of 0.8 plus 0.6 minus 1.8 plus 2.8 is 1. How? So it's like 2.8 plus 0.6, it's 3.4. 3.4 minus of 2.4 minus of 1.6 minus of 0.8, right? It's 2.4. So 3.4 minus 2.4 is 1.0. So we'll get the value as 1 by 10. So we got the value of slope as 0.1. Now let's talk about our equation of regression line. So for that we have to find an equation of a line such that we have a slope and it passes through a particular point. So our slope is 0.1 and it passes through the point 3 and 3.6, which we have already calculated, right? Where I said that the regression line would definitely pass through the mean of all these points. Okay, so we have y as 3.6, this line, m is 0.1, and we have x as 3, right, this line. So we have to calculate the value of c. We have the equation 3.6 equals 0.3 plus c. So c equal 3.6 minus of 0.3, that is 3.3. So we got the value of c as 3.3. So now we know that our regression line would intersect y-axis at the point 3.3 and it will cross through the point 3.6 and 3. So for the regression line for m equals 0.1 and c equal 3.3, we'll get the equation as y equals 0.1x plus 3.3. So this is our regression line. Okay, so now that we have drawn our regression line, we have to check whether the independent variable is even dependent on the dependent variable or not. Or in other words, we have to find out if our independent variable is even related to the dependent variable or not, right? So for that, what we'll do, for given m equals 0.1 and c equal 3.3, we have to predict the values for y when x equal 1, 2, 3, 4 and 5. So for x equal 1, m equals 0.1 and c equal 3.3, the predicted value of y would be 3.4. Okay. Similarly for x equal 2, y predicted is 3.5. X equal 3, y predicted as 3.6. Similarly for x equal 4, y predicted is 3.7. And for x equal 5, y predicted is 3.8. Alright. And the line passing through all the predicted values of coordinate x and y predicted is nothing but the line of regression. So next is finding the best fit line. So in order to find the best fit line, you have to do multiple iteration for different values of m and b. What you'll do, you'll calculate the error for different values of m and b, and the line having the minimum error would be your final line or the best line of regression. For now, just check if our independent variable is even related to dependent variable or not, right? This was our main goal. So for that, we have to calculate R square. R square is a parameter which tells us whether the independent variable is related to dependent variable or not. If yes, then by how much factor? If no, then by how much? Okay. So the formula for R square is predicted distance minus mean whole square divided by actual distance minus mean whole square and summation of both. So it's like summation of y predicted minus y bar whole square divided by summation of y minus y bar whole square. Okay, so let's calculate it. So what all we have? For now we have x and y predicted. For x equal 1, y equal 3.4, 2, 3.5, 3, 3.6, 4, 3.7, 5, 3.8. So for now, let's plot the value of y as we need it in the calculation. So we had y as 4, 3, 4, 2, 5. Okay. Now we'll calculate yp minus y bar, the numerator of r square. That is yp minus y bar. So yp minus y bar is 3.4 minus 3.6. Okay, it's minus of 0.2. Next is minus 0.1, then 3.6 minus 3.6 is 0, then 3.7 minus 3.6 is 0.1, and 3.8 minus 3.6 is 0.2. So next we'll calculate is y minus y bar, that is 4 minus 3.6. that is 0.4. Okay. Next 3 minus 3.6, that is minus of 0.6. 4 minus 3.6, that is 0.4. 2 minus 3.6, that is minus of 1.6. Then 5 minus 3.6, that is 1.4. Okay, so let's move ahead. Next, what we have to do, we have to square them. So first we'll calculate y predicted minus y bar whole square. So it's minus of 0.2 square, that is 0.04. Then minus of 0.1 square, that is 0.01, 0 square 0, 0.1 square again 0.01, 0.2 square, that is 0.04. Okay. Then we'll calculate the value of y minus y bar whole square, that is 0.4 whole square, that is 0.16. Then minus of 0.6 whole square, that is 0.36. Again 0.4 square, that is 0.16. Minus of 1.6 whole square, that is 2.56. Then again 1.4 square, that is 1.96. So if you summate them, so for the formula of r square, we have to summate the value of yp minus y bar whole square and y minus y bar whole square. Okay, so you have to summate them. So summation of yp minus y bar whole square is 1.0 and summation of y minus y bar whole square is 5.2. So if we put these values in the formula, we'll get r square as 0.1 divided by 5.2, which is approximately equal to 0.019. That means the value of r square is almost equal to 0. So when you get r square value tends to 0, then in that case you can say that independent variable is not at all related to your dependent variable. Okay. So it's like more the value of r square, more you can say that your independent variable is dependent on the or related to your dependent variable. If you have the value of r square as 0.6, you will find that error in this case, or the difference between the actual point and the predicted point, is less as compared to the line where r square is almost equal to 0. So if you keep on increasing the value of r square, the error would keep on reducing, or the distance between the actual point and the predicted point would keep on reducing. For the line r square tends to 1, that would be a line in which your predicted point and the actual point almost overlaps each other. Okay. Now let's just move forward and perform a hands-on in Python, and let me show you how you can calculate and plot the linear regression in Python. So this is where I'm going to write my linear regression code. Well, if you see, there are multiple datasets available out there on the internet, but for now we'll implement the simple linear regression on our own dataset. For this, we'll be considering two variables, x and y. X would be the house size, which ranges from 1000 square feet to 10,000 square feet, and y, which is an independent variable, that would be the cost of house, which ranges from 300,000 to 1200,000. Okay. Now, since we are using simple linear regression, so we have only one factor, that is size of the house, which is affecting the price of the house. Right. When you are dealing with multiple linear regression, we would have more than one factor affecting the house, like locality or the number of room, etc. Don't worry, we'll deal with them later. But for now, as we are dealing with simple linear regression, so we have one variable which is dependent on the other one. Okay. So now our goal is to find a regression line, a line which fits the best if we plot both our variables x and y. So both x and y, so that we can predict the response y, that is the cost of the house, for any new value of x, that is size of the house. Okay. So let's start coding. So first of all, let's import the required libraries. So we'll be needing NumPy and Matplotlib. So import NumPy as np. And I'll be importing matplotlib.pyplot as plot. Okay. As we have discussed already what is NumPy and what is matplotlib, so just to give you a recap, so NumPy is a library for Python programming language which is generally used in machine learning because we have to deal with large data in machine learning, and this is faster than the normal array or the list. So a NumPy is a library for the Python programming language which is generally used in machine learning, as we have to deal with large data in machine learning, and this is faster than normal array or the list. Okay. And Matplotlib is a plotting library for Python which is generally used for plotting the graph. Okay. So here we are using NumPy as np and matplotlib.pyplot as plt. This is done to rename the huge name to something smaller. Okay, just to ease it. That's it. So instead of writing numpy.array, the short form is np.array. That's it. Or matplotlib.pyplot.plot x and y, the short form would be plt.plot x and y. That's it. That's just for ease of coding. Okay, so now that we have imported our libraries, our next task would be to create a function. So we have to create a function to estimate the coefficient of x and y values that are passed into this function. So we'll start as define name of the function, estimate the coefficient of x and y. In this, what we have to define first, the size of the dataset or the number of observation of point. So the number of observation or the point, let's say n, my n equal np dot size of x, size of y, anything. Okay, then we'll calculate the mean of x and y. Since we are using numpy, so just calling the mean of numpy is sufficient. Okay, there's a predefined function mean in that. So mean of x and mean of y equal np dot mean of x and np dot mean of y. Fine. Next we'll be calculating ss underscore xy and ss underscore xs, which is nothing but the sum of squared errors. So my ss underscore xy will be equal to np dot sum y cross x minus of n multiplied by total mean of y multiplied by mean of x. Fine. These two variables, mean x and mean y. N is what? So np dot size of x. So total size of your observation multiplied by mean of y multiplied by mean of x. Okay. Next, sum of square of x and x equal np dot sum x multiplied by x minus of n multiplied by mean of x multiplied by again mean of x. Fine. Now we'll be calculating the regression coefficient, that is the amount or the value by which the regression line need to be moved. So for that, let's say b1 equal ss underscore xy divided by ss underscore xx, and the value of my b0 will be equal to mean of y minus b1 times mean of x. Okay, and from this function I want to return the value of, and from this function I want the value of b0 and b1. So this is my coefficient estimation function. Okay, so this is my estimate coefficient function, which will be used to determine or estimate the coefficient when x and y values are passed into the function. So my next function would be to plot the graph based on the calculated values. So I'll create a function for plotting my graph. So plot my regression line. Inside that I'll pass three parameters, x, y and b. Okay. So now we'll be plotting our point as per our data set. So since this is a function, so let's define a function for that. So I need a scatter plot, plt.scatter. Inside that x coordinate, y coordinate, these are the location of the point on the graph. Then I'll specify the color. So I'll select the color as M. Color here is basically the color of the plotted point. You can change it to red or green or orange or any color depending on your need. Then we'll define a marker. So marker is the shape of the point, like a circle or any other symbol. Okay, so I'll specify marker as circle and marker equal O. So these are basically optional. You can just write plt.scatter, that is also enough. Okay, next what we'll do, we need to predict. So next we have to create a predicted response vector. So predicted values of y, so y predicted equal b0 plus b1 times of x. Next, we'll plot the regression lines. So plt dot plot x and the predicted values of y underscore red, and let's say the color is green. Okay, so next we'll plot the label of both the coordinates. So plt dot x label, it's what? Size. And plt dot y label, it's what? Cost. Okay, and finally plot dot show to show the plotted graph. Okay, fine. Now finally let's create our data set and call these function. Now let's add some point on our x-axis. So x equal np dot array. All things I want to add: 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. These are house sizes ranging from 1000 square feet to 10,000 square feet. Okay, here 1 represents 1000 and 10 represents 10,000. Okay, and y equal np dot array, the cost of the house 300k comma 350k comma 500k comma 700 800 850 900 again 900, then 1000 and finally 1200. So these are our array. Our next task would be to estimate the coefficient. So b equal estimate the coefficient of x and y. Both the values will be taken from here. Then print estimated coefficient estimated coefficient slash n b naught equal this slash n b1 equal this dot format p of 0 comma p of 1, and finally we'll call plot underscore regression line the values of x, y and b. Here b is the estimated coefficient. Okay, let's execute it. Got the error built-in function. Okay, I think we have messed these brackets over here and here. Okay, so we got the value of b naught as minus of 7.5 and b1 as 137.72. We got an error name plot regression line is not defined. Let's just copy this as it is. Okay. Double T, where is that? Okay, sorry. Okay, so we got our regression line. The plot which we got is a line of linear regression. So the plot which we got is our linear regression line. The screen line is nothing but linear regression line.
So what basically happens in simple linear regression is there is just one independent variable. So there is one dependent variable and one independent variable, and you try to understand how does the dependent variable change with respect to that independent variable. So let's go ahead and start a demo. So our first task would be to load the Boston dataset, and we'll be loading the Boston dataset with the help of pd.readCSV function. So again, for that we'd have to import the pandas library first. So I'll just type in import pandas as pd, and then what I'll do is I will load the boston.csv data file and I'll store this in this object and name it as data. Now after that I'll have a glance at the first few records of this dataset. Right, so this is our Boston data set and it comprises of all of these columns. So there is CRIM, ZN, Indus, CHAS, NOX, RM and so on. Now out of these, the main column which we are interested in is MEDV. So this MEDV column basically indicates the median price value of the houses in Boston. And for our simple linear regression, what we're going to do is we're going to take this as our dependent variable and we're going to take LStat as our independent variable. So here LStat signifies the percent of population which is below poverty line. Alright, now let's go ahead and have a glance at the shape of this data set. So we'll type in data.shape. So what we get is 506 and 14. Now this basically means that there are 506 rows in this data set and 14 columns in total. Now let me also go ahead and use the describe method on this data set. So I'll just type in data.describe. Right. Now this just gives me the different aggregate functions on top of all of these columns. So I've got the count, mean, standard deviation, the minimum value, the 25 percentile, 50 percentile, 75 percentile, and the maximum value, right? So let me actually take this crime rate over here. Now this count which you see, this basically tells you the number of records in each of these columns. And as we already know, since all of these columns belong to the same data set, and hence the number of records should be the same for all of these columns. And the mean crime rate, we see that it's around 3.6, the minimum crime rate is 0.006, the maximum is around 88, right? So these are the different summary statistics which you can get from this data set. Now, let's just have a glance at our two main variables, which would be our independent variable and the dependent variable. So as I've already told you guys, our independent variable would be this LStat column and our dependent variable would be this MEDV column. Now, from this entire data set, I'd be only segregating these two columns and storing that in data underscore. And after that, I'll have a glance at the first 5 records. Alright. So this is my independent variable and this is my dependent variable. Now let me go ahead and make a plot with respect to these two, and I'll be plotting the LStat column onto the x-axis and MEDV column onto the y-axis. So for that purpose, I'd have to load the matplotlib package. So I'll just type in import matplotlib.pyplot as plt. And I'll type in data.plot. So LStat is mapped onto the x-axis and MEDV is mapped onto the y-axis. And I'll just go ahead and give the labels to them. So the label which I'm giving to x-axis is LStat and the label which I'm giving to y-axis is MEDV. And then I'll go ahead and just plot this. So y-axis, we have MEDV, x-axis, we have LStat. Now what we see is there is sort of an inverse relationship. So as LStat increases, MEDV decreases, right? So as the population percentage which is below the poverty line increases, the median value of the price of the house decreases, which is actually quite intuitive, isn't it? So if the population is below poverty line, obviously they can't really afford luxury houses, can they? So what we basically understand from this is there is sort of an inverse relationship between these two columns, right? Now it's finally time to go ahead and build our model. And before we do that, we'd have to prepare our data first. So what I'm going to do is I'm going to take this LStat column and store it in X. And similarly, I'll take this MEDV column and store it in Y. So this is done. Let me have a glance at the size of these two objects. So this tells me that there are 506 rows in X and Y. Well, that is again very simple to understand. Now I'll finally go ahead and divide this data set into training and testing sets. Now it's very important to divide our data set into training and testing sets, because if you go ahead and just build our model on top of the entire data set, then there are chances of overfitting and it'll fail miserably when new data comes in. And that is the main reason why we'd have to divide our data into training and testing sets. So I'll go ahead and import train test split from sklearn.model selection, and I'll use this function. So I'm passing in all of these parameters. So X is basically all of my features, Y is the labels or the dependent variable, and then I'll set the test size to be equal to 0.2. So this basically means that 20% of the records should be in the test set and the rest of the 80% records would be in the training set. Right, and I'll be storing all of these results in xtrain, xtest, ytrain and ytest. So xtrain over here basically denotes the training set for LStat column. Similarly, xtest over here denotes the test set for LStat column. And then we have ytrain, which denotes the training set for MEDV column. And then we have ytest, which is basically the test set for MEDV column. Right. Now again, let me go ahead and have a glance at the shapes of all of these 4 objects. So the shape of xtrain is 404, 1. So this means that there are 404 records in X train, and then we have X test. So the shape of X test is 102. This means there are 102 records in X test, and it's the same for Y train and Y test. Alright. Now I'll go ahead and import linear regression from sklearn.linear model and create an instance of it, and I'll store that in regressor. And then finally I'll go ahead and fit this model on top of the train set. So I'll type in regressor.fit and I'll pass in these two objects, which are basically X train and Y train, which in turn is nothing but your training set. Right, so we've fit the model on top of the training set. Now, as you already know, linear regression is basically built on top of the linear line, or in other terms it is basically y equals mx plus c. So here y is your dependent variable and x is your independent variable, and you're trying to understand how does y vary with x. Now, apart from y and x, you have two other terms over here. So the two other terms are m and c. Now, m is your slope and c is your intercept. So let's go ahead and find out the values of m and c. Right. So I'll go ahead and print the value of c, which is basically the y-intercept. So I'll print regressor.intercept. So we see that the value of intercept is 34.33. And similarly, I'll go ahead and also print the value of coefficient, which is nothing but the slope. So the slope value is minus 0.92. Now, when you see that there's a negative value associated with the coefficient, and this basically means that as the independent variable increases, the dependent variable would decrease. Or in other terms, there is an inverse relationship between the independent variable and the dependent variable. So now that we've built the model, let's go ahead and predict the values on top of the test set. So I'll print in regressor.predict and I'll give xtest as the parameter inside this. Alright. So I have also predicted the values on top of xtest. So it's finally time to go ahead and find out the error in prediction. So for that, we'll be importing metrics from sklearn, and I'll be having a glance at different metrics such as mean absolute error, mean squared error, and root mean squared error. I'll click on run and we have these values. So mean absolute error comes out to be around 5.07, mean squared error comes out to be 46.99, and root mean squared error comes out to be 6.85. Now, what you need to understand is the lower the value of root mean squared error, the better the model. And this basically helps you to compare multiple models. So let's say you have model 1 and model 2, and model 1's root mean squared error is around 10 and model 2's root mean squared error is around 5. So now when you see these two metrics, you can clearly say that model 2 is better than model 1 because its root mean squared error is less than model 1. Alright, so we have successfully built a simple linear regression model. Now let's go ahead and build a multiple linear regression model where we'll have multiple independent variables. Right. So we'll pretty much perform the same steps over here. I'll go ahead and load the pandas and numpy package, and I'll load up this Boston dataset and store this in this dataset object. Again, I'll have a glance at the dataset, which is basically the same dataset which we were dealing with. Now this is where the change comes. So I'll be taking all of the columns except the last column into this X object, and this X object basically denotes all of my independent variables, and in Y object I am just taking the final column. So here the final column represents this MEDV column, right? So all of these columns over here, that is the first 13 columns, would be my independent variables, and the 14th column would be my dependent variable, right? So I'm storing this in X and Y. Now I'll do the same thing. I'll go ahead and divide this data set into train and test sets. And over here I'm setting the test size to be equal to 0.3. So this means that 30% of the records should be in the test set and the rest 70% of the records should be in the training set. Right. Now I'll also go ahead and fit the model on top of the train set. So I'll just say regressor.fit and I'll pass in X train and Y train as the parameters. I'll click on run. Right, so we've successfully fit the model, and we'll also go ahead and predict the values on top of the test set. So over here, I'll type in regressor.predict and I'll pass in xtest as the parameter. Right. So we have also predicted the values on top of the test set. Now I'll go ahead and find out all of the metrics. So we'll see the same metrics, which are basically mean absolute error, mean squared error, and root mean squared error. Right, and this is what we get this time. Let me compare these values with the first model. So For the first model, we saw that the root mean squared error came out to be 6.85. And for the second model, the root mean squared error comes out to be 5.54. So, as I have already told you guys, if the root mean squared error is lower for a model, it basically means that this model is better than other model. So we can basically conclude that model 2 is better than model 1. And guys, this is how we can implement linear regression with the help of sklearn.
So this is Lauren. She's looking for a property to buy, but she's confused how to start. So she goes to one of her friend, Josh, and asks him if he could help her to find a property with bigger garden area for X bucks. Our guy, Josh on the right, agrees to help her to find a property, but he himself doesn't know how. So what he do, he goes to another friend of him, explains him the whole situation, and asks him if he can do anything about it. He immediately says yes and start doing some calculations. Then he says to Josh that spending X bucks can get her a property of area Y. Now Josh is confused and asks him how did he find out. The friend goes like, simple linear regression. Now let's see how exactly he used simple linear regression to solve his issue. So here are our dependent variable and independent variable. Property size being the dependent variable and money being the independent variable. What this guy want to do? He want to find out a relation between the property size and money. So it's like if you want a house of bigger area or bigger property size, then you have to spend more money. So both of them are directly proportional, right? So in this case, we'll get a positive linear regression line, right? That is, spending more money will get her a bigger property. Okay. In other case, but again, our next scenario is she wants a bigger garden area, right? So imagine the scenario keeping the property area constant. The house area is inversely proportional to the garden area. It's like if you want to increase the garden area, so you have to reduce the house area. So take it like this. Suppose you have already fixed the property and you want to construct a house with a garden in it. But now your demand is you want to have a bigger garden area. So if the size of the property is fixed and if you increase the size of the garden, then obviously you have to reduce the size of your house, right? So in this case, if you try to plot a regression line, you'd get a negative regression line, right? Bigger garden area means smaller house, right? Now let's take an example to see how exactly did he predict the value of the house. So in order to find the regression line, what he did, he took the historical data of property area sold in the particular price, okay, and he plotted it on the graph. So this was the plotted point of property area sold in past for a particular price, okay. Now what he did, he drew a regression line. Now to find out what property area she can buy with X bucks, he plots X on the independent variable scale and project it to the regression line. And then against that point, there he has the area Y. This is the area Y. So this is how he predicted Lauren can buy Y area of property in X bucks. Alright. Now let's see what he can and what he cannot say from this. So he can say that if Lauren spends X amount of money, she can buy a property area of Y. But what he cannot say is, will the property would have a good neighborhood or not? Or will the location be noiseless suburb or a bustling city? Right. So these are the questions which even he cannot answer using this graph. So the questions like, will the property will have a good neighborhood? Or will it rain tomorrow or not? Or is this mail a spam or not? All these kind of problems fall under a particular category known as classification problems in machine learning. Now with linear regression algorithm, we could not answer these problems. So that is where logistic regression comes into picture. Now let us see where this logistic regression algorithm that we just talked about lies in the machine learning algorithm tree. So in machine learning, we use two traditional learning techniques to build a predictive model: supervised learning and unsupervised learning. Again, look at the supervised learning. There are two categories, regression and classification, right? In regression, we have linear regression, and in classification, we have logistic regression and SVM. So our today's topic of discussion is logistic regression, which comes under the category of classification. Okay. So now that we have got a little bit idea about logistic regression, let's go a little bit deeper and discuss about what exactly is logistic regression and why do we use it. So what is logistic regression? Well, logistic regression is a statistical classification model that deals with categorical dependent variable. Again, you must be wondering, what are these categorical dependent variable? Well, these are some of the discrete variables that have two or more categories without having any kind of natural order. For example, temperature, area, or gender. Okay. So you can say that logistic regression is generally used where the dependent variable is binary, or where the dependent variable is binary. That is, only two outcomes are possible. Either yes, no, true, false, 1, 0, etc. Right. And also remember a fact that you can use both continuous and discrete input data with logistic regression. So before moving ahead, let's look at the graph. See, there are two variables. One is independent and other is dependent. Can you figure out which one is dependent and which one is independent? So before moving ahead, let's take a look at this graph. So over here, we have two different variables, hours studying and probability of passing exam. Can you figure out which one of them is dependent and which one of them is independent? So if you have guessed that hours of studying is your independent variable and probability of passing the exam is dependent variable, then I'd say that you are 100% correct. So now that you know what exactly is logistic regression, let's move ahead and see why do we use logistic regression. Well, logistic regression can be used as a tool for applied statistics and discrete data analysis. Why? Because it gets the output in the form of probabilities, which help us to easily classify the given data. Okay, so this is why we are using logistic regression. So now that we have successfully established the basic of logistic regression by understanding what and why of it, let's go ahead and see how logistic regression can be applied for classifying data with the help of an example. So here we are using an example of spam email classifier. We need to build a predictive model that would classify whether a mail is spam or not. So let's look at the approach that we are going to take while building this model. First, we'll try to understand the variable that on the basis of which we are classifying the mail. Next, we'll plot the label data. Once we are done with plotting the label data, we'll draw the regression curve. And finally, we'll try to find out the best fitted curve using maximum likelihood estimator. Alright? So let's get started. So step 1 is defining the variable. So let's start off by understanding what is independent variable in our case. So in our case, the independent variable is count of spam words. Well, here are some examples of commonly used spam words. Word like buy, get paid, guarantee, winner, unlimited, etc. Okay, so these are the kind of words which when found in the mail is treated as spam. If the number of these kinds of words are more in a mail, then that mail would definitely be a spam mail. Okay, just for a better representation, let me put them in a bag of spam words. Let's put the bag. So there's a bag of spam words. Let's put all the words in them one by one. Buy, get paid, guarantee, winner, and unlimited. Okay. Now, what about our dependent variable? Well, our dependent variable is going to be the probability of mail being a spam. If the probability is 1, that means the mail is spam. If it's 0, it means it's not a spam mail. Well, in general, the mail with less number of words from the list of spam words will be treated as a spam mail. With 5 or more spam words in a mail would be treated as a spam mail. But there can be cases where you might find mails with less spam words being spam. Also, you might find cases where mails with more number of spam words is not a spam mail. So here our aim is to build a predictive model to classify the mail with minimum error. Okay, let's see what is our next step. So our next step is plotting the label data. Let's say this is a set of data that we'll be using to build the model. This is a very small data set, but just remember that whenever you are using logistic regression, make sure that you are using a large amount of data. Logistic regression works pretty well with large amount of data. It doesn't work that good with small amount of data. Okay, here just for the purpose of understanding, we are using small data set. Alright, so we have two variables, number of spam words and the probability of mail being spam against each mail. Okay. Next, as a step 3, we'll draw the regression line. So next what we'll do, we'll plot our data set on x-axis and y-axis with independent variable on the x-axis and dependent variable on the y-axis. So number of spam words in a mail is an independent variable, right? And the probability of that particular mail being a spam or not a spam is a dependent variable. It depends on the number of spam words in a mail, right? So let's plot these words one by one. So first we have is one word and the probability of this mail being a spam is 0. So it will be plotted up here. So next we have is 5 spam words in a mail and the probability of that mail being a spam is 1. So it will be plotted somewhere here. Next is 3 spam word is a spam mail. So it will be plotted again here. 2 words, it's not a spam mail. So I'll be plotting up here. 7 words, again a spam mail up here. 4 words, not a spam mail here. 9 words, it's a spam. 8 spam words, again, it's not a spam. So once we are done with the plotting, this is how our plotted data would look like. Now let's say that we have a new mail and now we want to figure out whether it's a spam or not. So before moving ahead, let me just tell you, in real world scenario to perform logistic regression, you need a large amount of data set. And also you might find many cases where a spam mail might contain only 2 words, where a spam mail might contain only 2 spam words. Or also it might be possible that you get a mail where you are having more than 5 spam words and even in that case, your mail is not a spam. Okay, so here we are building a predictive model with primary aim to reduce the error. Okay, now let's say we have a new mail up here. Now we need to figure out whether this mail is spam or not. But how do we do that? Well, first of all, we need to plot a regression curve which would fit the best. And that curve would be our logistic regression curve. But now the question comes, how to find out which is the best regression curve? Okay, well, this will contain 3 steps. Well, the first step is to convert the y-axis from the scale of probability confined between 0 and 1 to a scale of log odds. Then drawing a random regression line out of the data that we already have. Then with the help of sigmoid function, we'll convert the log odds to the probability of mail being spam. We'll plot each mail on the basis of their new probability values. And this will form our regression curve. Then finally from this plot, we'll find out the log likelihood values of each mail. Now from this plot, we'll find out the log likelihood values of each mail. The individual likelihood. At last, we'll find the log of likelihood. That would be our log likelihood of the regression curve. Now the question comes, what are these terms such as log odds or log likelihood means? So before moving ahead, let's discuss that. So what does log of odds mean? Let us explore this with the help of an example. So before we proceed any further, let me just clarify you one thing. This probability and odd, these are not the same thing. Let me explain you this with an example. Suppose this guy, he goes to fishing 5 times a week. So out of 5 times, he catches a fish 2 times and he failed to catch 3 times. Okay. So now in this case, what is the probability and odd for getting a fish for dinner? So let's first calculate probability. So probability is chances for divided by total chances. So chances for catching a fish. So what is the probability of catching a fish? That is how many times he caught a fish. That is 2 divided by total chance he had to catch the fish. So that was 5, right? So here probability of getting a fish for the dinner is 2 by 5. Okay. Next comes the odd. Chances for divided by chances against. That is the ratio of how many times he caught the fish divided by how many times he failed to catch a fish. Okay, so he caught the fish for 2 times and he failed in catching the fish for 3 times. So the odd for getting a fish for dinner is 2 by 3. Okay, so now that we know odds, now let's see what log of odds and log odd ratio are. Are they same? Let's find out. For your information, log odds is also called as logit function. Okay. So in our previous example where the fisherman was catching a fish, let's add another factor to his fishing. Let's add a factor as weather. So then we can recreate the entire scenario as he was successful 2 times on a rainy day. But on a sunny day, he was successful for 3 times. Now the odds of catching fish on a sunny day is how much? It's 2 by 3, right? And the odds of catching on a rainy day is 3 by 2, right? As it's already mentioned that on a sunny day, he catches 3 times. So he is successful for 3 times and he failed for 2 times. So let's see, he was successful 3 times on a rainy day and 2 times on a sunny day. So odds for catching a fish on a sunny day is 2 by 3. That is, he's successful 2 times on a sunny day and he failed for 3 times in a week. So odd for catching fish on a sunny day is 2 by 3. Similarly, odd for catching fish on a rainy day is 3 by 2. And now log of odds of catching a fish on a sunny day is just log value of 2 by 3. And similarly, log of odds of rainy day is log of 3 by 2. Now log of odds ratio is nothing but the log of odds on a rainy day divided by odds on a sunny day. Okay. Next is log of odds ratio. So log odds ratio is nothing but the ratio of log of the odds on a sunny day to log of the odds on a rainy day. That is log of 2 by 3 by 3 by 2, which is nothing but log of 0.44. So here we can say that odds and odd ratio are both different things. Now let us go back to this step. So now that we have understanding of log odds, so we are ready to perform this step. Okay. So let's see how we converted the 0, 1 axis to minus infinity to plus infinity axis. So here we'll be converting the probability scale to scale of log odds. Okay. So for the log odds, we have a formula as log of probability of spam divided by 1 minus probability of spam. So here the probability of a mail being a spam is 1. Okay. So we get the value of log odds as log of 1 divided by 1 minus 1. That is log of 1 by 0. It's positive infinity. How we got that? So log of 1 by 0 is nothing but log of 1 minus log of 0. And log of 0 up here is minus infinity. So minus of minus infinity is what? Plus infinity. How log of 0 up here is minus infinity? Let's see. So in general logarithm, so we have log 0 with base b equals c. So if you convert it into exponential form, we get 0 equal b to the power c. Right. So if the value of b is less than 1, so the value of c has to be extremely small or closer to minus infinity for this equation to be true. Okay. And we'll get a positive infinity in the case where b is greater than 1 or our base is greater than 1. Okay. So coming back up here. So here log of 1 by 0 is nothing but log of 1 minus log of 0. And we got the result as positive infinity. As log of 0 up here is minus of infinity. And minus of minus infinity is what? Plus infinity. How we got the value of plus infinity? Let's see. So log 0 with base b equals c. If we convert this into exponential form, we get something like this. 0 equal b to the power c. Right. So for the equation 1 to be true, if the value of b or the base is less than 1, then in that case the value of c will be positive infinity. Okay. For example, 0.1 to the power 1000 would be smaller than 0.1 to the power 100. Right. So more the value of c up here, more closer will the number get to 0. Right. And in next case, if the value of b is greater than 1, so for this we have to make the value of c closest to minus infinity. Why? For example, we have 10 to the power minus 1. Okay. Or 10 to the power minus 10, which is more smaller. 10 to the power minus 10. Right. So which is much smaller or closer to 0? 10 to the power minus 10. Right. So that's why we have to keep the value of c as less as we can. So here, if the value of b is greater than 1, the value of c would have to be close to minus infinity in order to make the equation true. So in this case, log of 1 by 0, by default we have base as 10. Okay, so that's why we took the value of c as minus infinity. So minus and minus of infinity is plus of infinity. So that's why we got the plus infinity up here. I hope this thing is clear to you. How we got the value of log odds as plus infinity. So I'll plot this up as plus infinity log odds. Now next, let's find the log odds of non-spam mail. So here we have the formula as log of probability of a mail not being a spam divided by 1 minus probability of mail not being a spam. So log of 0 divided by 1 minus 0. So we have log of 0 by 1, which is log 0 minus log 1, which tends to minus infinity. Okay, similar concept. Now we have our data up here. So first we'll assume one regression line. So now we have our data up here. So first we'll assume one regression line. Then we'll project our data onto the regression line. Okay. Now let's just go back to this step where with the help of sigmoid function, we'll convert the log odds to the probability of mail being spam. Okay. But what does this sigmoid function mean? So sigmoid function is the standard logistic function. The logistic function is defined as L multiplied by e to the power k times of k minus k dot upon 1 plus e to the power k times of x minus x naught. So here L is the curve's maximum value, k is the steepness of the curve, x naught minus x is the value of sigmoid point. Okay. So here the sigmoid function e to the power x divided by 1 plus e to the power x, here k equal 1 and x naught equals 0 and L equal 1. So this mathematical sigmoid function forms S-shaped curve which is confined between 0 and 1. Let's try to understand how logistic function works with the help of an example. So let's say we have a set of unspecified data, and on these data we need to apply a sigmoid function. So let's see what a sigmoid function can do by visualizing this graph. So let's say we have a unspecified data, and on these data we need to apply a sigmoid function. So plot this data and find out the respective y for these points. Okay, so what a sigmoid function is doing, it can be visualized from this graph, right? So you are giving some values on your x-axis, and using sigmoid function you can predict its probability on the y-axis, right? So this is the reason why sigmoid function is very useful while solving the classification problem. It takes any real valued number and maps onto a value between 0 and 1. Okay. Well, now that we have an idea of how sigmoid function works, let us move ahead with our spam email classifier. So we are ready to perform this step. That is converting the log odds graph into a sigmoid function graph. Now we have to find out the best MLE. Okay. Best maximum likelihood estimator. So we are going to replace the log odd value of each mail to get the probability of each mail being a spam. So we have the formula up here, probability equal e to the power log odds divided by 1 plus e to the power log odds. So one by one we'll place the log odds of each mail into this formula and calculate the probability for each mail. Okay. For example, I have this mail which after projecting into the regression line gives us log odd value of minus of 3.2. Okay. So what we'll do up here, we'll calculate the probability using the value of minus 3.2. We'll place the value minus 3.2 in our formula, e to the power log of minus of 3.2 divided by 1 plus e to the power log of minus of 3.2. So from here, we'll get the probability as 0.03. So plot it accordingly onto the new graph between probability of mail being spam versus spam word count. So on the basis of probability, our mail would lie somewhere near to 0. So according to the prediction, this mail is not a spam mail. Again, for another mail which is projecting on a regression line, this gives us a log odd value of 5.6. So when we put the value of 5.6 in the formula, we get the probability as 0.99. So the probability of this mail being a spam is 0.99. So again, we put this into this graph. Similarly, one by one, we'll calculate for each one of them. For this mail, after projecting onto the regression line, we get the log odds value as minus of 4.5. So minus of 4.5 when put into the formula, we get the probability as 0.01. So the prediction of this mail is not a spam mail, which is same as actual, right? So again, we plot this mail onto a graph, alright? So similarly, you can repeat this step for the rest of the email as well. And finally, we got the S curve up here. So this is our regression curve. But you must be wondering, is this the best fitted curve? Or how do we find out whether it's best or not? Well, this is when the concept of maximum likelihood comes into picture. So now that we have regression curve, let's find out the likelihood of this curve. So first find out the individual likelihood of each mail. Again, you must be thinking, how do we get the likelihood value? Well, likelihood of each mail is nothing but the probability value of each mail being spam. So likelihood of first mail being spam is 0.01. Likelihood of second mail being spam, again 0.01. Similarly, third 0.03, fourth 0.05, and so on till 8th mail being 0.99. Okay. So once you get the individual likelihood of each mail, multiply them to find out the likelihood of the entire curve. Okay. Then calculate the log of likelihood for calculating the log of likelihood, you can just take the log of the previous result. Okay, you can just take the log of previous multiplied result. Here we are adding all the logs because log of A multiplied by B equal log of A plus log of B. Okay, so we got the value of log likelihood of this curve as minus of 0.084. Now let us rotate this line to find out the best fitted regression line. So we got the log likelihood of this curve as minus of 0.084. Now let us rotate this line to find out the best fitted regression line. Again we calculate the individual log likelihood of each male. For this one, let's say we got log likelihood which is shown on your screen. So final value we got up as minus of 0.207. So we got the value as minus of 0.207. So now if we compare the log likelihood values for these two regression lines, we'll see that line A has bigger value of log likelihood than line B, right? As line A has log likelihood value of minus of 0.084. So the log likelihood value for line A is minus of 0.084, whereas for line B is minus of 0.207. So minus of 0.084 is bigger than 0.207, right? So therefore we can say that line A has better likelihood value than line B. Now again we'll rotate the line. We'll keep on rotating the line until we get the maximum value of log likelihood. And then finally we'll choose a line which is having the maximum log likelihood, and that line would be the best fitted regression line.
So let's quickly go to Jupyter Notebook and start with a demo, right? So this is Jupyter Notebook, guys, and our first task would be to load up the heart disease dataset, and for that purpose we would have to import the pandas package. So I'll just type in import pandas as pd, and I'll use this read_csv method from the pandas package. So I'll type in pd.readcsv and I'll pass in the name of the dataset, which is basically heart.csv, and I'll store this in this dataset object. Now let me have a glance at the first few records of this dataset. So this is our dataset which comprises of all of these columns, and we're going to build the logistic regression algorithm on top of this column over here, which is basically target. So target would be our dependent variable and the rest of the columns would be the independent variables, right? And this target basically means that, so you have 1 and 0 values over here. The 1 value means that the person or the patient has the heart disease, and 0 basically means that the patient does not have heart disease, right? Now let me also have a glance at the shape of this dataset. So I'll just type in print dataset.shape, and this gives me a value of 303 and 13. So 303 means that there are 303 records in this dataset and 13 columns. Now let me actually have a glance at the value counts of this target column. So this value counts basically tells me the frequency of these two values. So I have these two values in this column, which is basically 1 and 0. So there are 165 records where the value is 1, and there are 138 records where the value is 0. So this basically means that in this data set there are 165 patients who actually have the heart disease and 138 patients who do not have the heart disease. Now I'll go ahead and actually visualize this. So I'll load up the matplotlib package and seaborn packages, and I will pass in this target column onto the x-axis, and the data is our data set, which is basically this heart disease data set. And what I'm doing is basically building a histogram, and I'll plot this up over here, right? So this is the bar plot for the value of 0, and this is the bar plot for the value of 1. And this basically tells us the same thing. So 165 is the value of the number of patients who actually have the heart disease. So this basically is for all of those patients who do not have the heart disease. Alright, now let me go ahead and divide the data set into features and label sets. So I'm storing all of the features into this X object. So all of these 12 columns would be my features, and this target column would be my label or would be my dependent variable. Alright, and this is how I'm going to divide the data set. So I'm going to extract all of the columns except the last column and store it in this X object. And similarly, I'll only take the last column and store it in this Y object. Alright. Now let me have a glance at these individual independent variable and target variable. So x.head gives me all of the independent variables and y.head gives me the target, right? So now that we have our independent variables and the dependent variable, let me go ahead and divide this dataset into training and testing set. And for that purpose, I'd have to load up the train test split method from sklearn.model selection. And over here, I'm setting the test size to be equal to 0.2. So this means that 20% of the records are in the test set and the rest 80% records are in the training set. Alright, I'll click on run again. Now we have divided the dataset into training and testing sets. Now finally it's time to build the model, and for that purpose I'll be importing logistic regression from sklearn.linear model. And I'm going to create an instance of this, so I'll just use this method logistic regression and I'll name that instance to be log model, and I'm going to fit this model on top of the train set. So I'm basically passing x train and y train as the parameters. Right, I'll click on run. Right, so we have successfully built the model on top of the train set. Now we're going to go ahead and predict the values on top of the test set. So I'll type in log model.predict and I'll pass in x test as the parameter and I'll store the result in ypred. So we have also predicted the values. Now it's time to calculate the accuracy. So I will type log model.score and I'll pass in x test and y test. So I want to calculate the accuracy for the prediction on top of the test set. Right. So the accuracy comes out to be 73%, which is actually not that bad. And let me actually also build a confusion matrix. So confusion matrix would give me a table of values, which actually comprises of the correctly predicted values and misclassified values. So I'd have to import confusion matrix from sklearn.metrics. And again, I'll just pass in ytest and ypred as the parameters inside this function. And I'll print this out. Right. So this left diagonal which you see, this left diagonal actually represents all of those values which have been correctly classified, and this right diagonal represents all of those values which have been misclassified. And if you want to get the accuracy, all you have to do is add up 20 plus 25 and divide it with all of the values and you'll get the same accuracy. So let me actually add up a new cell over here and calculate the accuracy from this confusion matrix. So I have to divide this left diagonal with all of the values. So that would be 20 plus 25 divided by 20 plus 25 plus 10 plus 6. And this gives me a value of 73.77, which is the same as I got over here. So the accuracy is 73%, right? So we have built the confusion matrix. Now I'll also go ahead and build the ROC curve. So the ROC curve, it sort of gives me the right trade-off between the true positive rate and the false positive rate. So let me go ahead and plot this, and this is what we get over here. So on the y-axis we have the true positive rate, and on the x-axis we have the false positive rate. And basically you can understand this plot this way. So the closer this curve is to this top right corner over here, the better the model. That is, this curve needs to cover greater area. And this, what you see, red line, so this basically represents a classifier which would give you around 50% accuracy, and your model would be as better as it is far away from this red line.
So classification is a process of grouping things according to similar features they share. The example given up here represents a set of different garbages which are segregated as per the category into different bins. For example, paper, metal, plastic, e-waste, glass, organic, everything are segregated properly and are separated in different bins. So here we are classifying what? So here we are classifying the waste and adding them into different bins. Okay. So let's move ahead. Next is classification versus regression. Well, there's a very important thing to understand. So what is the difference between a classification and a regression? I'm assuming you know that both are related to prediction, right? Regression is used to predict a value from a continuous set. That is, it deals with continuous variable. On the other hand, classification is used to predict the class or to which class that particular variable or that particular data belongs to. So basically, it deals with categorical variable. For example, the price of the house depends on its size, right? Size here is a numerical value which can be continuous. So this relates to regression. Similarly, prediction of price can be in words like very costly, costly, affordable, cheap, and very cheap. So this relates to classification. So this was about regression and classification. I hope now you know when to use regression and when to use classification. So let's move ahead. Next is the types of classification algorithm. So we have logistic regression, we have decision tree, random forest, k nearest neighbor, and neighbors. Let's have a look at them one by one. So first is the logistic regression. So we have already learned about it in detail in our previous session. Let me just summarize things for you. So logistic regression is used when the dependent variable is categorical. For example, you have to predict whether the given mail is spam or not. Okay, so in that case, you'll be using a logistic regression. So for detailed understanding on logistic regression, I'd suggest you to go through our previous session. Okay, for now, let's move ahead. Next is the decision tree. Well, decision tree is a graphical representation of all the possible solutions to a decision. Here, the decisions are mainly based on some conditions, and the decision and the output generated can be easily explained. From the image shown here, you can see that the main stem of the tree is nothing but the issue at hand. The branches of a tree or the subtree are the possible decisions, okay, and the leaf nodes or the leaf of the tree are possible scenarios. Let me just give you an example of a decision tree. For example, you have to predict whether the given person is fit or not. So the very first thing that you will be looking for is age less than 30. If the condition is true, then you will check if the person eats a lot of pizza or not. If the person eats a lot of pizza, then he is unfit. In case he doesn't eat a lot of pizza, then you can say he is fit. But what if the person's age is greater than 30? Then in that case, you'll check another condition. Like you'll go for whether he exercises in the morning or not. If he does, then he is fit. If not, then he is unfit. Okay. So this was about decision tree. Next is the random forest. Well, random forest builds multiple decision tree and merges them together to get a more accurate and stable prediction. So you can say that decision tree is a basic building block of a random forest. Okay. Now the question arises, why it is called random? Well, it's called random because each decision tree in a forest considers a random subset of features when forming questions. Now the question arises, why it is called random? Well, it's called random because each decision tree in the forest considers a random subset of features when forming questions, and they only have the access to a random set of training dataset. So this increases the diversity in the forest, leading to a more robust overall prediction and the name random forest. Okay. So now when it comes to prediction, random forest takes an average of all the individual decision tree estimate. Well, you can say that there are two main fundamental ideas behind the random forest, and both of them are well known to us in our daily life. The first is constructing a flowchart of questions and answers leading to a decision. And the next is the wisdom of the random and diverse crowd. So the random forest is the combination of these ideas that has led to the power of random forest model. Well, if you talk about its training, the training is done using bagging method. Now, you'd ask what exactly is bagging? Well, we have already discussed it. Not the terminology, but I have explained you the concept. Bagging is building multiple decision tree by using random set of the training dataset and finally voting the trees for a consensus prediction. One last thing. So using random forest, you can correct the decision tree's habit of overfitting the training dataset. So this was about random forest. Let's move ahead. Next we have is k nearest neighbor. Well, KNN algorithms use the data and classify new data points based on a similarity measures. The k in KNN algorithm is the nearest neighbor we wish to take vote from. It is one of the simplest and most used learning algorithm. Well, KNN is a non-parametric, lazy algorithm whose purpose is to use a database in which the data points are separated into several classes to predict the classification of a new sample point. And when I say it's non-parametric, it means that it does not make any assumptions on the underlying data distribution. And when I say it's lazy learning algorithm, it doesn't mean that it's lazy like a polar bear or something. Okay, it means that it does not use the training data points to do any generalization. In other words, there is no explicit training phase, or it's very minimal. So this implies that training phase is pretty fast. And the lack of generalization means that KNN keeps all the training data. So all of them are needed during the testing phase. So in this example, you can see that we have a test sample up here in green. We need to classify, we have to predict whether it belongs to a red triangle or whether it belongs to a square. So the test sample should be classified either to the first class of the blue square or to the second class of a red triangle. If k equal 3, that is, it's outside the circle, so it is assigned to the second class because there are two triangles and only one square inside the circle. Now, if for example k equal 5, then it is assigned to the first class, which has 3 squares versus 2 triangles outside the outer circle. Okay, I hope the example is clear to you. So let's move ahead. And finally, in the end, we have naive-Bayes classifier. Naive-Bayes classifier is a probabilistic machine learning model that is used for classification. It is completely based on Bayes theorem. We can find the probability of happening of A given that B has already occurred. So here B is the evidence and A is the hypothesis. So the assumption made here is that the features are independent. That is, the presence of one particular feature does not affect the other. Hence, it is called naive. Okay. So this was the summary of all the different types of classification algorithm tree. So let's say this is our data set. So our data set consists of 3 different attributes: color, diameter and label. Label consists of different types of fruit. So we have 3 different types of fruit up here: mango, lemon and cherry. And if you talk about color, so in color we have 2 varieties of mango. One is of green and one is of yellow. Okay. Now our task is to create a decision tree for this data set. So now we'll split this data set on the basis of some condition and create a decision tree. So for splitting the data set, let's consider this attribute, diameter. So as you can see, we have 3 different fruits with common diameter of 3 and 2 diameters which are less than 3. So we have a condition of split over here. So we can check if the diameter of the fruit is greater than or equal to 3 or not. If the condition is true, then we'll have green mango, yellow and yellow lemon as a part of our splitted data set. And if the condition is false, then in that case, all we'll get is cherry. Okay. So here you can say that this is our leaf node. So in case if you reach till here, so you can predict your value and say that it's a 100% cherry. Okay. But if the diameter is greater than equal to 3, then what will you predict? Is it a green mango? Is it a yellow mango? Or it's a yellow lemon? You can't say, right? So again, you have to split this data set. So how can we split? Let's see if we have any common feature to split this data set. So as you can see, we have a common color over here. So we have a yellow mango and a yellow lemon. So again, we got the condition of split over here. So we'll check here if the color is yellow or not. So if the condition is true, we'll get all the yellow fruits in this data set. And if the condition is false, we'll get all the non-yellow fruits in it. So we got green mango over here. So if you reach till this node, then you can say that the probability of finding green mango at this particular node is 1, or it's 100%. And at this leaf node, you can say that the probability of finding a yellow mango is 50% and the probability of finding a yellow lemon is also 50%. Okay, so now you can see that we have some terms over here like Gini impurity equals 0 or Gini impurity equals 0.44. So what does this mean in this visualization? So for any particular node, if Gini impurity equals 0, it means that that particular node is a pure node and it does not have any mixed values. So as you can see, we have all cherries in it. So if you focus to this node, you can see that the Gini impurity value is non-zero. So it means that it's a mixed data set or it's a mixed value. Okay, it's not a pure value, and there is a further chance to split the data set on some condition. Okay, so now if you focus on these conditions like is diameter greater than 3 or is color equal 0, so they have some value of information gain. So it's like you can gain maximum information at your root node, and as you reach towards the leaf node, the information gained is decreased. So as you can see, this is the parent node for this node, right? Or this is the child node for this node. So the value of information gain at the parent node would always be greater than the value of the information gain at child node. Okay, so this was about how you can visualize a decision tree. Now let's move ahead and understand about the decision tree terminologies. So the very first thing that we have is the root node. The root node represents the entire population or sample, and this population further gets divided into 2 or more homogeneous set. Okay, so when we pass the entire data set to one particular node, so that node is root node. Okay, next is leaf node. Well, leaf nodes are the node which cannot be further segregated into further nodes. Like in our previous example, the point where we got 100% lemon or 100% mango, so those nodes were leaf nodes. So it's like we cannot further segregate it down. It's the last point of that particular branch or that particular node. Next is splitting. Well, splitting is dividing the root node or the sub node into different parts on the basis of some condition. Like in our example, we divided the tree on the basis of two conditions. The first one was, is the diameter greater than or equal to 3? And the second one was, if the color equals yellow or not. So next is branch or subtree. Well, a branch or subtree is formed by splitting the tree or the node. Next is pruning. Well, pruning is just opposite of splitting. Pruning is basically removing unwanted branch from the tree. So it's like if you want to reach to a particular scenario, so you would remove all the unrequired decisions and the condition from between. Okay, so this is the concept of pruning. Next is parent node or child node. Well, root node is the parent node and all the other nodes branch from it is known as child node. Okay, so any doubt up till here? If you have, please reach out to us. Okay, so this was all about decision tree terminology. Now let's move ahead and see how we can create a decision tree. So there's a sample dataset. Our dataset consists of outlook, temperature, humidity, windy and play. So based on outlook, temperature, humidity and windy condition, we have to predict whether a person can play or not. Okay, so how will we do that? So in order to resolve this query, I'll be creating a decision tree for it. Now in order to create a decision tree, the very first thing that I would have to do is we have to pick one of the attribute. So now the question arises, which one among outlook, temperature, humidity and windy should you pick first? So the answer is determine the attribute that best classifies the training data. But how do we choose the best attribute? Or how does a tree decide where to split? So how do we split a tree? So in order to split the tree, we have various concepts. Let's have a look at them one by one. So on number one, we have entropy. Entropy defines the randomness in the data. It is a metric which measures the impurity. It is the very first step to solve the problem of a decision tree. Now once you find the entropy, your next task would be to calculate the information gain. So the information gain is the decrease in entropy after a dataset is split on the basis of an attribute. Constructing a decision tree is all about finding an attribute that returns the highest information gain. Okay? And the attribute with the highest information gain will be the attribute which would be selected as a root node or a node from where we'll split. Now, once you calculate the information gain, the next thing that you will calculate is the Gini index. So now that your data set is divided, now you have to check whether the splitted data is pure or not. So for checking the purity of the data, we have a measure as Gini index. It is the measure of impurity or purity used in building a decision tree. Okay. And finally, we have reduction in variance. Well, reduction in variance is an algorithm used for continuous target variable, that is regression problem. The split with lower variance is selected as a criteria to split the population. So as I said earlier, the very first thing in order to construct a decision tree is to calculate its entropy. So this is the formula for entropy. Entropy of S total space equals minus of probability of yes multiplied by log of probability of yes minus probability of no multiplied by log of probability of no with base 2. So if you take a look at the graph and the formula, so from here you can say that, so if number of yes equal number of no, that is probability of total sample space becomes 0.5, that is this point. Okay, so here entropy becomes 1. And if it contains all yes or all no, then in that case probability of total sample space is 1 or 0. If it consists of all yes, that is all 1 or all 0, then in that case the entropy is 0. Okay, now let me just show you what I just told you. So the formula for entropy was minus of probability of yes times of log of probability of yes minus probability of no multiplied by log of probability of no. So now when probability of yes equal probability of no, that is total sample space consists of equal number of yes and no. So in that case both would have the equal probability of 0.5. So if you put 0.5 in the formula above, you will get minus of 0.5 times of log 2 0.5 minus 0.5 times of log 2 0.5, okay, which will evaluate to 1. So here it proves that entropy for the case when probability of yes equal probability of no would be 1. Or you can say that there is maximum randomness in the dataset when probability of yes equals probability of no. Let's take another case where we have all yes. Okay, so probability of yes equal 1. Our total sample space consists only of yes. Okay, so for that we'll get the formula as E of S equal 1 of log base 2 times of 1, which is nothing but 0. This point, when the probability of yes is 1, then in that case the total entropy that you would get is 0. Now what if the probability of no is 1? That is, your entire data set only consists of no. There is no yes in the entire data set. So similarly, you will get the value of entropy as 0. Okay, I hope I made my point clear. So let's move ahead. So now coming back to our data set. So our data set consists of 14 different instances. Out of them, we have 9 yes and 5 no. So now if you add the value of yes and no to the formula, so it results to minus of 9 by 14 times of log of 9 by 14 minus 5 by 14 times of log of 5 by 14. So it drills down to 0.41 plus 0.43, which equals 0.94. So here the total entropy for my entire sample space is 0.94. Fine. So now that we have calculated the entropy for our data set, our next task would be to calculate the information gain. So information gain equal entropy minus weighted average multiplied by entropy for each feature. So in order to find the root node, you have to calculate information gain for each attribute. And the attribute having the maximum value of information gain will be the attribute that will be selected as the root node. Okay, so let's do it one by one. So starting with Outlook. So if we choose Outlook, we have 3 different parameters: sunny, overcast and rainy. In sunny, we have 2 yes and 3 no's. In case of overcast, we have all yes. And in case of rainy, we have 3 yes and 2 no. So moving on ahead, we'll calculate the entropy when Outlook equals sunny, when Outlook equals overcast, and when it equals rainy. So we'll calculate all 3 individual entropies. So starting with when Outlook equals sunny. So in that case, we had 2 yes and 3 no's. So if we put those values in the formula for calculating the entropy, it would look something like this. And we'll get the result as 0.971. So in case of overcast, we'll get the value as 0. As the probability of yes in case of overcast is 1, we have all yes over there, right? And the probability of no is 0, as it is not available there in the dataset, right? So from here you can see that we calculated the entropy for Outlook equal overcast is as 0. Now entropy for Outlook equal rainy. In case of rainy, we had 3 yes and 2 no. So if you put all those values in the formula, so you'll get the result as 0.971. Okay. So now we have calculated entropy for each feature of the Outlook. So next we'll be calculating is the information from Outlook. So for calculating the information, we had the formula weighted average multiplied by entropy of each feature. So total information from the Outlook equals, so summation of all the information from different features. Starting with sunny. So in case of sunny, the weighted average is 5 by 14. So how did we get this 5 by 14 value? Like in case of sunny, we had 2 yes and 3 no's. So 2 plus 3 is 5 divided by total number of data points, that is 14. So 5 by 14 is the weighted average for sunny multiplied by the entropy value of sunny, that is 0.971 plus 4 by 14. How we got 4? So we had 4 yes in case of overcast, right? So here we got the weighted average as 4 by 14 multiplied by the entropy, which was 0, plus again 5 by 14, 3 plus 2 multiplied by 0.971. So if you calculate all these values, this result to 0.693. So the total information from the Outlook is 0.693. Now we'll calculate the information gained from Outlook. So total information gained from Outlook is total entropy minus information from Outlook, which equals to 0.94 minus of 0.693, which results to 0.247. Okay. Now similarly, we'll calculate entropy for each feature. We calculated the entropy for Outlook, temperature, humidity. So as you can see, in case of Outlook, we got an information gain of 0.247. In case of temperature, the information gain was 0.029. And in case of humidity, the information gain was 0.152. So here we can see that our Outlook is having the maximum information gain. So here we can conclude 2 things. First, our Outlook would be our root node, as it is having the maximum value of information gain. Okay. And secondly, we won't use temperature to create a decision tree, or we can avoid using temperature in our decision tree, as the information gained from the temperature is very less. Okay. So here we got our root node as Outlook. So here we got our root node as outlook. We can split it into sunny, overcast and rainy. But now sunny and rainy both have some numbers of yes and no, right? Overcast is the only feature which consists of only yes. So our overcast would be treated as a leaf node. But again we have to decide which node would be used when outlook is sunny and which node would be used when outlook is rainy. So again we have to decide which node would come when outlook is sunny or outlook is rainy. Okay, so let's see how we'll do that. So again we'll select it one by one. Next we'll calculate the entropy for windy. Okay, so in case of windy you can see we have two different features, false and true. In case of false we have 6 yes and 2 no. In case of true we have 3 yes and 3 no's. So next we'll calculate the entropy of windy equal true, which we got as 1. Why? Because it has equal number of yes and no. Okay, so in this case the probability of yes equal probability of no. So remember the first case where I told you if you would be having an equal number of yes and no, so for that case the total entropy that you'll calculate, you'll get it as 1. Okay, and for windy equal false you'll get it as 0.811 using the same formula again. Okay, so if you calculate the information from windy, you'll get it as 8 by 14 multiplied by 0.811. This is for windy equal false, plus 6 by 14 multiplied by 1 for windy equal true. And if you summate it, you'll get the value as 0.892. Now information gained from windy is total entropy minus information from windy, which is 0.94 minus 0.892, that is 0.048. Okay. So similarly, you will calculate for other features as humidity and temperature, and finally you will get this decision tree as the final output. So there's the final decision tree that you'd get. Okay. So let's see how does it answer our query and see the scenario where we can play. So first, outlook. So if outlook is sunny and the humidity is normal, then we can play. Or if outlook is overcast, then we can definitely play. No further condition attached to it. Or if the outlook is rainy and it's windy and the wind is not strong enough, it's a weak wind, then in that case also we can play. Okay, so this was about how you calculate entropy and information gain to create a decision tree using CART method, that is classification and regression.
Here's a quiz question for you guys. What is supervised learning? Your options are a machine learning technique where the model learns from labeled data to make predictions or decisions without human intervention. A machine learning technique where the model learns from unlabeled data to make predictions or decisions with high accuracy. A machine learning technique that doesn't involve data labeling, making it highly efficient. Or a machine learning technique used exclusively for image recognition. Please mention your answers in the comment section.
Guys, I have a special announcement for all of you. For all of you dedicated individuals who are looking forward to master data science, we are offering a straightforward 20% discount on our data science course, which is in collaboration with iHub IIT Roorkee. So do make sure to check the link given in the description and fill the inquiry form. Shortly, our team of course advisors will get in touch with you to activate the offer. Don't miss this chance and take your career to the next level. Click on the link given in the description right now.
Decision tree regressor. That is, we'll be using decision tree as a regression algorithm, and we'll be implementing this decision tree algorithm on top of the Boston dataset. So before we go ahead and load up the dataset, let me actually import the requisite packages. So we would require the NumPy, Pandas and Matplotlib package, and with the help of this read_csv function, which comes from the Pandas library, I'll load up the Boston.csv dataset. Alright. So now that we have loaded up the dataset, let me have a glance at the first few records of this dataset. So I'll just type in boston.head, and these are all of the columns present in this dataset. Alright. Now for our first model, we'll be taking MEDV as our dependent variable and RM to be our independent variable. So RM basically stands for the average number of rooms per dwelling, and MEDV denotes the median price value of the house. So we basically want to understand how does the median price value of the house change with respect to number of rooms per dwelling. And I'll go ahead and make a scatter plot between these two columns. So I'll map RM onto the x-axis and I will map MEDV onto the y-axis. Right. So let me click on run, and this is what we get. So what we see is, as the average number of rooms increase, the median value of the price of the house also increases. And this again is quite intuitive, isn't it? So if the number of rooms increase, the size of the house would also increase, and this would in turn increase the price of the house. Alright. So now that we've done a bit of visualization, let me actually go ahead and extract the features and the target from the original data frame. So I'll extract this RM column and store it in the X object. Similarly, I'll extract the MEDV column and store it in the Y object. So X basically denotes my feature column and Y basically denotes my target column. Alright. Now I'll go ahead and divide this dataset into training and testing sets. So for that purpose, I'll be importing train test split method from sklearn.modelSelection, and I'll be passing in all of these parameters. So X and Y, I'll just pass in features and target, and I'll set the test size to be equal to 0.20. And this means that 20% of the records would be in the test set and the rest of the 80% records would be in the train set. Alright, so we have our testing and training sets ready. Now it's time to finally build the model. So I'll be importing decision tree regressor from sklearn.tree. So again, I'm restating it, guys. So even though we're using the decision tree algorithm, we are able to perform regression with this, right? So now I'll create an instance of this. So I'll just call in this method decision tree regressor, and I'll name that instance to be regressor, and I'll fit this model on top of the train set. So the parameters which I'm passing inside this are xtrain and ytrain. So now that I've built the model, let me go ahead and predict the values on top of the test set. So I'll type regressor.predict, and the parameter which I'm passing inside this is xtest. Alright, so now we have also predicted the values. Now it's time to find out the RMSE value or the root mean square error value. And we'll be importing mean squared error from sklearn.metrics, and I'll be using this method, and I'll just pass in ypred and ytest. So ypred contains all of the predicted values, ytest contains all of the actual values, and I want to find out the error in prediction. Now since I've imported mean squared error, I'd actually have to find out the square root of it. So I'll type in np.square root and I'll pass in the value of MSE into this, and this will give me the root mean squared value. So the root mean square value for the model which we've built is 7.102. Now again, the model which we've built, that just has one independent variable. So this is a simple model. Now we'll go ahead and add multiple independent variables. So this time our features are RM, LStat and age columns. So in the first model, we just had one independent variable, and in the second model which we are building, we'll be having three independent variables which are RM, LStat and age, and again our dependent variable is the MEDV column, and I'll store them in X and Y again. Now I'll go ahead and divide this dataset into train and test split, and another difference which I'm making over here is I'm setting the test size to be equal to 0.30. So this means that 30% of the records would be in the test set and the rest 70% of the records would be in the training set. Right, I'll click on run, and then again I'll import the decision tree regressor, and I will fit the model on top of xtrain and ytrain, and I'll predict the values on top of xtest. Now again I'll find out the RMSE value. Alright, so this time the RMSE value comes to be around 5.509. So now let me compare it with the RMSE value of the first model. So the RMSE value of the first model is 7.10 and the RMSE value of the second model is 5.50. So this basically means that the second model produces less error, or in other words, second model is better than the first model. Right, so that was an example where we use decision tree as a regression algorithm. Now we'll go ahead and use decision tree as a classifier, and we'll be building this decision tree classifier on top of the iris dataset. So over here I'll type in pd.read_csv, and I'm loading up the iris.csv file, and now I'll have a glance at the head of this. And these are all of the columns. So I've got sepal length, sepal width, petal width, and the species column. So now what I basically want to understand is what is the species of this flower based on these four columns over here. So these four columns would be my independent variables and species would be my dependent variable. So that is what I'm doing over here. From this entire iris data frame, I'll extract these four columns and store them in the X object, and I'll just extract the species column and I'll store it in the Y object. Alright, now I'll go ahead and divide this data set into training and testing set. So again, I'd have to import the train test split, and I'm setting the test size to be equal to 0.30. Now, since we are building a classifier, we'd have to import decision tree classifier from sklearn.tree, and I will create an instance of this. So I'll just use this method decision tree classifier, and I'll store the result in this new object. I'll name that object to be classifier, and I will fit this model on top of xtrain and ytrain. Right, so we have successfully built the model on top of the train set. Now we have to go ahead and predict the values on top of the test set. So I'll type in classifier.predict, and the parameter which I'm passing in this is xtest. So this is also done. Now let me go ahead and find out how the prediction has been done. So I'll start off by creating a confusion matrix. So I'll import confusion matrix from sklearn.metrics, and this takes in ytest and ypred. So ytest comprise of all of the actual values and ypred comprise of all of the predicted values. So I'll click on run over here. Now this left diagonal which you see, this left diagonal tells you all of the values which have been correctly predicted, and the rest of the values have been misclassified. So what we see is there is just one value or one record which has been misclassified. The rest of the records have been correctly classified. Right. Now I'll go ahead and calculate the accuracy score, and the accuracy score comes out to be 97.77%. Right, so this is how we can use a decision tree algorithm.
So the confusion matrix shows the ways in which your classification model is confused when it makes predictions. It is basically a summary of prediction result on a classification problem. The main key to a confusion matrix is summarize the count value of correct and incorrect prediction. So the image shown on your screen represents a confusion matrix. Let's see what exactly does it mean. But before that, let me just tell you how to create a confusion matrix. This would make things more clear for you. So let's see how. So for creating a confusion matrix, you would be needing a test dataset or a validation dataset with expected outcome values. Then make a prediction for each row in your test dataset. Then from the expected outcome and prediction, count the number of correct prediction for each class and the number of incorrect prediction for each class, organized by that class that was predicted. Okay, let's see what exactly does it mean. So here's an example. We have some expected output and a predicted output for that. So from here you can see that all the red color results are the incorrect predicted values and the green ones are the correct ones. So in total we have 7 correct prediction out of 10. Okay, so from here you can say that the accuracy of your model is 70%. Now here men classified as men are 3, 1, 2 and 3, and women classified as women are 4, 1, 2, 3 and 4. And now men classified as women, men as women 1 and men as women 2. Okay, so 2, and women classified as men 1. Now if you create a confusion matrix out of it, you will get something like this. Men classified as men 3, men classified as women 1, women classified as men 2, and women classified as women is 4. So from here you can say that total actual men 3 plus 2 is 5. Total actual women 1 plus 4, again 5. And total correct values, men classified as men and women classified as women, that is 3 plus 4, it's 7. So from here you can say that there are more errors while predicting men as women rather than predicting women as men. Okay, so this was about how you can calculate a confusion matrix. Now let's come back and see how to interpret a given confusion matrix. This is the sample of a confusion matrix. So here we have created a confusion matrix for a fire alarm. So this represents an actual alarm, this represents no actual alarm. Here predicted fire positive and here predicted fire as negative. So if the alarm goes on in case of fire, so it's a true positive event. The alarm goes on and there is no fire, so it's a false negative event. There is no alarm in case of fire, so it's a false negative event. And there is no alarm and there is no fire, then that means it's a true negative event. Okay, so let me just explain you this example. This should make things more clear to you. So actual alarm and predicted fire. So total true positive events we have 40 and total false negative event we have 10. So from here you can say that total number of times the alarm rang was 40 plus 10, that is 50. Okay, here we have false positive event as 5 and true negative event as 95. So the total number of times the alarm did not rang was 5 plus 95, that is 100. And this one is the predicted fire or not. So true positive plus false positive, that is 40 plus 5. How many times the machine positively predicted the fire? So that is 40 plus 5, 45. And how many times the machine was not able to predict the fire? That is 10 plus 95, that is 105. And total number of events, that is 50 plus 100, or 45 plus 105 is 150. So we have mentioned n equal 150 up here. That is total number of events. Okay. So this is how you interpret a confusion matrix. So let's move ahead. So now let me just show you in my Jupyter notebook how you can create a confusion matrix. Let me just open my Jupyter notebook. So this is my Jupyter notebook, and what we are gonna do is create a confusion matrix in Python. So the very first thing that I'll be doing up here is importing the required libraries. So from sklearn.metrics, so I'll be importing confusion matrix. Next, let's create some expected value. Let's say expected equal. So let's add some values in it, like 1, 1, 0, 1, 0, 0, 1, 0, 0, and 0. Now this is my expected value. Now let's create some predicted values for that. So predicted equals, first it's predicting correct. Next, let's say 0, 0, 1, 0, 0, 1, 0, 1. So this is a predicted value. Now let's calculate the confusion matrix. So let's say results equal confusion underscore matrix. Inside this we'll pass our expected and predicted value. Expected, comma, predicted, and print the result. That's it. Let's execute it. So here you got the result as 4, 2 and 1, 3. So what does it mean? So first we have is 4. So 0 predicted as 0 is 4 times. 1, 2, 3 and 4. So 0 predicted as 1 is 2 times. 0 predicted as 1, 1. 0 predicted as 1, 2. Okay. Next is 1 predicted as 0. So 1 predicted as 0 is just once here. Okay. And next is 1 predicted as 1, that is 3 times. 1 predicted as 1, 1, 2 and 3. So this is a confusion matrix. And what we can say from here, so total number of correct prediction made by machine is 4 plus 3, that is 0 classified as 0 and 1 classified as 1. Okay. And total number of incorrect prediction is 2 plus 1, that is 3. So we have 7 correct prediction and 3 incorrect prediction. Okay. And the total number of times the machine predicted the value to be 0 is 4 plus 2, that is 6 times. And total number of times the machine predicted the value to be as 1 was 4 times. Okay. So from here we can say that our machine predicts the result 7 times correct and 3 times wrong. So the accuracy of our machine is 70%. So this was all about how you can create a confusion matrix in. Well, naive-Bayes classifier is a commonly used algorithm in machine learning. It is a classification algorithm which is mainly based on Bayes' theorem. According to naive-Bayes algorithm, the presence of a particular feature in a class is completely unrelated or is independent to the presence of any other feature. For example, a fruit may be considered to be an apple if it is red, round, and about 3 inches in diameter. A naive-Bayes classifier considers each of these features to contribute independently to the probability that the fruit is an apple, regardless of any correlation between the features. But these features are not always independent, and this is one of the disadvantages of the naive-Bayes algorithm. And this is the reason why it is called naive, because it makes assumptions that may or may not be correct. So in a nutshell, you can understand that this algorithm allows us to predict a class from a given set of features using the probability. So in some other fruit example, you can predict the class like whether the fruit is an apple, orange or banana based on its feature, like its color, shape, etc. Okay, so let's move ahead. Now before we move ahead and see how a naive-Bayes classifier works, we need to understand the basic of it. Okay, so the very base of the naive-Bayes classifier is conditional probability. Okay, so what exactly is this conditional probability? Well, it is used to calculate the probability of happening of the second event given that the first event has already happened. For example, drawing a second ace from a deck given that we already got the first ace, or finding the probability of a disease given that you were already tested positive, or finding the probability of liking Game of Thrones given that the person likes fiction. Okay, let's see what exactly it is. So basically you're defining two events over here. Event A is the probability of the event that we are trying to calculate, and event B is the condition that we know or the event that has already happened. So conditional probability is represented as probability of A bar B, which means the probability of the occurrence of event A given that B has already happened. So probability of A by B equal probability of A intersection B divided by probability of B, that is probability of the occurrence of both A and B divided by probability of B. Okay, let's understand this with the help of an example. So suppose you have a jar containing 6 marbles, out of which you have 3 black and 3 red. So what is the probability of getting a black given that the first one was black too? So let's see how we'll calculate it. So we have P of A as the probability of getting a black marble in the first turn. P of B is the probability of getting a black marble in the second turn. So probability of A, that is probability of getting a black marble in the first turn, is 3 by 6. Okay. And probability of B, so how many marble remained after we have taken one out? So we are left with 2 black marble and in total of 5 marbles. So the probability of again getting a black marble would be 2 by 5. Okay. And next is probability of A and B, or probability of A intersection B equal probability of A multiplied by probability of B. Okay, so that is 3 by 6 multiplied by 2 by 5. 3 by 6 is nothing but half. So half multiplied by 2 by 5, that is 1 by 5. Okay, so probability of B given A equal probability of A intersection B upon probability of A, which equals to 0.2 divided by 0.5, that equals to 0.4. Clear? Fine. Let's take another example. Let's say John's favorite breakfast is cereal and his favorite lunch is pizza. So the probability of John having cereal for breakfast is 0.6. The probability of him having pizza for lunch is 0.5. And the probability of him having a cereal for breakfast given that he eats pizza for lunch is 0.7. Okay. Now, what if I want to know the probability of having a pizza given you had a bowl of cereal for breakfast? So you have to calculate probability of B by A. So that is, you have to calculate the reverse probability. So here in this example, you already know the probability of him having cereal for breakfast. But after having a cereal for breakfast, you have to calculate what is the probability of him having a pizza for the lunch. Okay. So now this is where Bayes' theorem comes into picture. Bayes' theorem describes the probability of an event based on the prior knowledge of the conditions that might be related to the event. In simple words, Bayes' theorem shows the relation between a conditional probability and its reverse form. If conditional probability is probability of A by B, then you can use Bayes' rule to find the reverse probability, that is probability of B given A. Okay? Let's see how. Here's a proof of Bayes' theorem. So according to conditional probability formula, so if you compute over here, probability of A given B equal probability of A intersection B upon probability of B, and probability of B given A equal probability of A intersection B upon probability of A. Correct? So from this equation, we have probability of A intersection B common in both. So we can equate them, right? So probability of A intersection B equal probability of A given B multiplied by probability of B, which in turn equals probability of B given A multiplied by probability of A. So here, if you reverse the conditional probability, you will get the formula as probability of B given A equal probability of A given B multiplied by probability of B divided by probability of A. And this is nothing but Bayes' theorem. So in this formula, the probability of A given B is the probability of A being true given that B is already true. Probability of B given A is the probability of B given true given that A is already true. And probability of A is the probability of A being true, and probability of B is probability of B being true. Okay, so coming back to where we left. So now what if I want to know what is the probability of having a pizza given that you had a bowl of cereal for the breakfast? So you have to calculate probability of P by A. That is, you have to calculate the probability of him having pizza for the lunch given that he already had cereal in his breakfast. So that equals probability of cereal given that he's having pizza for the lunch multiplied by probability of having pizza upon probability of having cereal, okay, which in turn equates to 0.7 multiplied by probability of pizza, that is 0.5, upon probability of cereal, that is 0.6. Okay, so let's move ahead. So here's a Bayes theorem use case. Like, find out a patient's probability of having liver disease if they are an alcoholic. So here we are defining an event and the test. So a event is patient has liver disease. So from the past data, you can tell that 10% of the patients entering your clinic have liver disease. So here probability of A equal 0.10. Okay. So next is the test that a patient is an alcoholic. So 5% of the clinic's patient are alcoholic. So from here you can say that probability of B equal 0.05. Okay. Now you might also know that among those patients diagnosed with liver disease, from that 7% are alcoholics. So this is your B given A, correct? It is the probability that a patient is alcoholic given that they have liver disease is 7%. Okay. So now according to Bayes theorem, probability of A given B equal 0.07 multiplied by 0.1 divided by 0.05, which in turn equals to 0.14. So in other words, if the patient is an alcoholic, their chances of having a liver disease is 0.14, that is 14%. There's a large increase from 10% suggested by past data, but it's still unlikely that any particular patient has liver disease. Okay. So coming back to our Bayes theorem formula, so probability of A given B is posterior. Probability of B given A is the prior, that is what you believed before you saw the evidence. Probability of A, this is likelihood of seeing that evidence if your hypothesis is correct. And probability of B, this is likelihood of that evidence under any circumstances. Okay, so this was all about conditional probability and Bayes theorem. And whatever information or whatever knowledge you gain till now, will be using them to learn naive Bayes in a step-by-step way. So next is step-by-step to naive Bayes classifier. So here's my dataset consisting of 14 different rows with 5 different attributes. From this, I have to predict whether I'll play today or not. Okay. So from here, outlook, temperature, humidity and windy are the main attribute which will help us to predict the class play, whether we are going to play or not. Okay. So total sample here is 14, total yes is 9, total no is 5. So probability of getting yes is 9 by 14 and probability of getting no is 5 by 14. Okay. Now, the very first thing that we'll do is calculate frequency table for each attribute. So for outlook, we have sunny, overcast and rainy. So how many yes and how many no's are over there? So we'll calculate the frequency for that. So we have 2 yes for sunny, 4 yes for overcast and 3 yes for rainy. So total number of yes again 9. And we have 3 no for sunny, 0 no for overcast and 2 no for rainy. That is in total 5. Okay. Next is temperature. So we have 2 yes for hot, 4 yes for mild and 3 yes for cool. And similarly 2 no for hot, 2 no for mild and 1 no for cool. Again back to humidity. We have 3 yes when the humidity is high. We have 6 yes when the humidity is normal. And next we have 4 no when the humidity is high. And we have just 1 no when the humidity is normal. Similarly for windy. For windy, so if the weather is not windy, we have 6 yes. But if the weather is windy, we have 3 yes. And next, if the weather is not windy, we have 2 no. And if the weather is windy, we have 3 no. So now that we have calculated the frequency table for each attribute, next thing that we are going to do is probability for each attribute. That is, we are going to calculate probability of A. Okay. So from here you can see that total times we'll get sunny is 5 out of 14. Total times we'll get overcast, that is 4 by 14. Total times we'll get rainy, 3 plus 2, that is 5 by 14. Okay. Similarly, you will calculate it for temperature, humidity and windy. Okay. So here we got the probability for each attribute, that is probability of A. Next is the probability for each attribute, that is probability of B. Probability of B is nothing but probability of playing the game or not, right? That is probability of yes and probability of no. That is 9 by 14 and 5 by 14. Next, we'll calculate the likelihood for each attribute. That is, we are going to calculate probability of A given B. So let's have a look on this example. So when outlook is sunny, so the probability of getting yes in that case is 2 divided by 9. And how many no are there? 3 out of 5, right? So we got 3 by 5. Similarly, for overcast, we got 4 by 9 and 0 by 5. For rainy, 3 by 9 and 2 by 5. Okay. Similar calculation you'll do for temperature, humidity and windy. Okay. So now we have to calculate probability of B given A. So we have the formula probability of A given B equal probability of A intersection B upon probability of B, that equals to probability of A multiplied by probability of B given A upon probability of B. Correct? From here I want to find this value. I have this value and this value. Okay. So let's see. So if I want to play, what would be my ideal condition for playing? The outlook should be sunny. So the probability for outlook to be sunny is 5 by 14. Correct? The temperature should be cool. So the probability of the temperature to be cool is 4 by 14. Next is humidity should be normal. So the probability of humidity to be normal is 7 by 14. And the weather should not be windy. So the probability of the weather not being windy is 8 by 14. Okay. So now if you calculate total probability of the ideal condition, that is P of x equal 5 by 14 multiplied by 4 by 14 multiplied by 7 by 14 multiplied by 8 by 14, which in turns come out to be 0.029. Okay. So this was the ideal condition. Now ideal condition to play the game. So probability of outlook equals sunny when play equal yes, that is 2 by 9. Probability of temperature being cool when play equal yes, that is 3 by 9. Next is probability of humidity being normal when play equal yes, that is 6 by 9. And probability of windy equal false when play equal yes, that is 6 by 9. Okay. So the probability of playing game in ideal condition is, so probability of x given yes equal multiplication of all these values, that is 2 by 9 multiplied by 3 by 9 multiplied by 6 by 9 multiplied by again 6 by 9. So you'll get the value as 0.033. Okay. So the probability of playing the game in ideal condition. So we have to calculate probability of yes given x. So probability of yes given x equal probability of x given yes into probability of yes upon probability of x. So probability of yes given x equal 0.033 multiplied by probability of yes, that is 9 by 14 upon probability of x that we just calculated 0.029, which in turn result to 0.73. So from here you can say that the probability of playing the game in ideal condition according to Ney-Bayes classifier is 0.73.
What exactly is support vector machine? Well, it is a supervised machine learning algorithm which classifies data based on its features. So let's say we have this input data comprising of apples and tomatoes. Now we'll feed this data to a support vector machine. Now SVM will basically learn all the features associated with the input data and separate apples and tomatoes into different classes. So now that we know what exactly is SVM, let's understand the working mechanism behind SVM. So support vector machine separates or classifies data based on hyperplanes. So over here, this is our hyperplane which separates apples and tomatoes into different classes. But the problem is there could be infinite possibilities to draw this hyperplane. So there could be a hyperplane like this, and this is also another possibility. And it could be any one out of all these different hyperplanes. So how do we determine which is the best one? So this is where we'd have to take the help of support vectors. So support vectors are basically the two nearest data points to our hyperplane. And we have to choose a hyperplane in such a way that the distance between two support vectors is maximum. And the distance between these two support vectors is known as margin. So the aim of the model is to maximize this margin between the support vectors. Now let's say we add a new data point to our sample and then implement the SVM model. So we'd have to draw a hyperplane in such a way that it best separates these two classes. So we'll start off by drawing a random hyperplane, and then we'll find the support vectors, and then we'll go ahead and find the margin between the support vectors. Now similarly, we'll draw another hyperplane like this, and again find the support vectors and also calculate the margin between the support vectors. So now when we compare these two hyperplanes over here, we see that the margin for the first hyperplane is greater than the margin for the second hyperplane. And that is why the first hyperplane would be the optimal one for the scenario. So till now, the data which we saw was linearly separable. But what in this case? So can we actually draw a line over here to separate the circles and the triangles? Well, let's check it out. So I've drawn three hyperplanes and we see that in all these three cases, it is not able to separate the data into different classes. So this is where SVM uses something known as a kernel function. So this kernel function helps in transforming the 2D nonlinear data into higher dimensions so that we can separate the data using a hyperplane. So obviously, when we look at this image on the right side, we see that we can separate the circles and the triangles by drawing a hyperplane along the z-axis. And these are some of the kernel functions which we can use along with our SVM model. So we have polynomial kernel, Gaussian radial basis kernel, and Laplace RBF kernel. Now it's time to head on to the demo. So we'll be using this cancer dataset to implement SVM. So this dataset is computed from a digitized image of a fine needle aspirate of a breast mass. And the columns basically describe characteristics of the cell nuclei present in the image. So there are different features such as mean radius, mean texture, concavity error, and so on. And the target column comprises of two labels, which are malignant and benign. So you're basically trying to classify whether the tumor of the patient is malignant or benign on the basis of all the features. So our first task would be to import the package and the dataset required for this demo. So from this sklearn library, we are importing all the datasets, and then the dataset which we need is breast cancer. So I'll just use this function load breast cancer, and I will store this in this new object called as cancer. I'll click on run. So we have successfully loaded this dataset. Now let me have a glance at the features and the target values. So all I have to do is use this print function, and with the help of cancer.featureNames, I'll get all the names of the features. And over here with cancer.targetNames, I'll get the target names. I'll click on run. So these are all of the different features which are present in the dataset. So we have mean radius, mean texture, concavity error, symmetry error, worst concavity, and so on. And then in the target, we have two labels. First is malignant and then second is benign. And then again, as I already told you guys, we are trying to determine whether the patient's tumor is malignant or benign. So now that we've had a glance at the features and the labels, let's have a glance at the shape of this dataset. So for that, we'll just type in cancer.data.shape. I'll click on run. So we have this value 569 and 30. So this means that there are 569 rows in this dataset and 30 columns. Now, let me have a glance at the first 5 records of all of the features. So cancer.data, and then I want to have a glance at the first 5 records. So this will go from 0 to 5, right? So these are the first 5 records, or the values for the first 5 records. Now, similarly, I'll have a glance at the target values. So cancer.target, I'll just print it out. See that we have the values which are 0 and 1. So wherever we have the value 0, it represents that the patient's tumor is malignant. And wherever we have 1, it represents that the patient's tumor is benign. Now it's time to go ahead and build the model. So before we go ahead and build the model, we are actually supposed to divide our data set into training and test set. So for that, we'll be importing this train test split method from sklearn.model_selection. And after that, using this train test split function, I will go ahead and divide this into training and testing sets. So this over here takes in these parameters. First parameter is the list of all of the features, which will come from cancer.data. Next parameter is basically the target values, which is this result over here. And then we'll set the test size. So here I am setting a test size to be 0.3. So this will mean that 30% of the records from the dataset will be in the test set, and the rest of the 70% of the records from the dataset would go into the training set. And then again, I'll just set a seed value so that I can build the same model again. Now over here on the left hand side, we see that we are storing this result into X train, X test, Y train, and Y test. So these X labels basically represent all of the features, and these Y labels basically represent all of the target values. So this X train is the training set for all the features. X test is the test set for all the features. Similarly, this Y train is the training set for all the target values, and this y test is the test set for all the target values, right? So now we have successfully split this data set into training and testing set. Now it's time to go ahead and build the model on top of the training set. So now what I'll do is I'll go ahead and import svm method from sklearn library, and after that I'll go ahead and build the model. So for that I would have to set the kernel. So as we saw in the slides, we can have different kernels. So for this demo, I'm just setting the kernel to be linear. That is, we are building a linear model over here. So I'll use svm.svc and kernel is equal to linear, and I'll store this in clf. Now after that, I will fit the model. So clf.fit, and it takes in two parameters. First is xtrain, next is ytrain. That is, I'm basically building this model on top of the training set for both the features and the target values. And after I build the model, I'll go ahead and predict the values on top of the test set. So it'll be x_test. I'll click on run. So we've built the model, we've predicted the values. Now let's go ahead and find out the metrics of the model which we've built. So I'll import metrics from sklearn, and then first we'll go ahead and build a confusion matrix. So again, metrics.confusion matrix, this over here takes in two parameters, which is y test and y pred. So this y test comprises of the actual values, and this y pred comprises of the predicted values from the model which we've built. Now I'll click on run, and this gives me this confusion matrix. So the 61 which you see, it represents all of those values where the actual label was malignant and it has been correctly classified as malignant. So 61 are such cases. And then we have this 104, which basically represents all of those values where the actual value was benign and it has been correctly predicted as benign. And that's what you see. So over here, the actual was malignant, but it has been predicted as benign. And this 4 what you see, so this represents all of those cases where the actual was benign, but it has been predicted as malignant. So this left diagonal represents all of those values which have been correctly classified, and this right diagonal represents all of those values which have been misclassified. So this is the information which we can get from the confusion matrix. Now I'll go ahead and also calculate the accuracy. So this again, metrics.accuracy score takes in two parameters. First is y test, and then we have y pred. So see that the accuracy is 96%. So you can actually get this accuracy value from this confusion matrix. So as I have already told you guys, this left diagonal represents all of those values which have been correctly classified. So we'd have to divide this left diagonal with all of the values. So let me go ahead and do that. It'll be 61 plus 104 divided by 61 plus 104 plus 2 plus 4. Now I'll click on run. So you see that we get the same accuracy, which is 96.49. So we have successfully built the SVM model and we've got an accuracy of 96%. So you can consider ensemble modeling to be a collection of multiple models. So we basically combine several base models in order to produce one optimal predictive model. So let's take this example to understand ensemble modeling better. So let's see there's this data set on which you want to do some prediction. Now, instead of building one model on this entire data set, we can take samples of this data set and build a model on each of the sample data set. So let's say we take k samples and then we'll build k models in total. Now, each of this model will give us a result. So we'll take the aggregate of all the results and that would be a final answer. Now, one such ensemble method involving decision trees is bagging. So let's understand bagging with this example. So let's say we have this data set A and there are n records in it. Now what we'll do is draw samples from this data set. So this actually will be sampling with replacement. Now I'll take one record from data set A, take note of it, enter the same sample in data set A1 and then put the record back to where it came from. And I'll repeat this process n times so that there are n records in data set A1 as well. So what you need to keep in mind is, out of these n records in A1, some of them might have come twice, thrice, or even several times over, while some records from A might not have made it at all to A1. So this is how I've created A1. And then I'll go ahead and create multiple data sets the same way. So I have A1, A2, and it'll go on till AX. And each of these have the same number of records as A. And the X over here, it could be anything. Let's say 100, 500, or even 1000. So from just one data set A, we're able to create multiple data sets for our advantage. So again, just for our sake, let's say data set A has 1000 rows and the value of X is also 1000. So this would be 1000 cross 1000, which would give us 1 million rows. That is, from just 1000 rows of data, we are able to get 1 million rows. Now what we'll do is, for each of these X data sets, we'll fit one decision tree each. So we have X decision trees coming from X data sets. So now we have a group of trees, or in other words, what we have over here is ensemble of trees. Now let's say a new record Ri comes our way, then we are going to pass this record to each of these X trees, and we're going to get each tree's prediction on what class this new record is going to represent. And since we have X trees, we'll have X predictions in total. That is, let's say if X was 500, we would get 500 predictions. Similarly, if X was 1000, we would get 1000 predictions. Now, to get the final prediction, all we have to do is select that class which would have the majority of the votes across all the predictions from individual trees. So what we are really doing is aggregating the predictions across all of these trees. So guys, this is the concept of bagging. Now we'll head on to random forest. So random forest is just an extension of bagging. So till here the process would be the same. We'll be creating X bootstrap samples from the original dataset. And this is where the difference comes. So now what we'll do is, for each of these X datasets, we'll fit one decision tree, but the process of building the decision tree changes over here. So let's say this A1 dataset has 10 independent variables. Now, when it came to bagging, we considered all of these 10 independent variables to be a choice for the split candidate. But what happens in random forest is, each time a node is being split in a decision tree, not all 10 variables will be provided to the algorithm. This is important, so I'm reiterating this, guys. Each time a node is being split in a decision tree, not all the columns will be provided to the algorithm. So now the question arises, what will be made available to the algorithm? So only a random subset of these 10 columns would be available to the algorithm. So let's say I want to split this root node. Now instead of providing it all the 10 columns, only a subset of columns will be provided. So let's say 3 columns. Now it could be any 3 out of the 10. And with those 3, the algorithm goes on to split the node. And similarly for the left node over here, it is again going to be provided with a random set of variables. And it is not necessary that the left node should get the same 3 variables. It can be a different set of 3 columns altogether. So whenever we are splitting a node, it is given a random set of m predictors from the entire predictor space. And the reason this is done is to make each of these X trees very different. So let's compare bagging and random forest. So in bagging, all trees had the entire predictor space available to them. So the eventual trees which you would end up building would be very similar to each other. And in the case of random forest, we bring in randomness with respect to the columns provided. That is, only a random set of columns are provided to the entire predictor space. And that is why the set of decision trees which we get would be pretty different from each other. So now we'll head on to the demo. So we'll be implementing random forest on top of this iris dataset. Right, so we'll go ahead and load this iris dataset. So first we'll import the datasets module from sklearn library, and then we'll load the iris dataset, and I'll store this in the iris object. I'll click on run. Now I'll go ahead and have a glance at the target names and feature names. So all I have to do is use iris.targetNames, which would give me the target names. And then I have iris.featureNames, which would give me the feature names. I'll click on run. So these are the target names. So this is the target variable, which comprises of these labels. So the iris species, it could either be setosa, versicolor, and virginica. And these are the features. So we have sepal length, sepal width, petal length, and petal width. Now I'll have a glance at the top 5 records of this iris dataset. So iris.data, and it'll go from 0 to 5. So these are the first 5 records of this iris dataset. And this will give us only the feature values. Now if I want to have a glance at the target values, I'd have to print iris.target. So these are the target values. So if the value is 0, it represents that the iris species is setosa. If the value is 1, it represents that the iris species is versicolor. And if the value is 2, it represents that the iris species would be virginica. Now let me go ahead and have a glance at the type of this iris data and iris target. So we see that both of them are NumPy arrays. And for a model building process, first we'd have to convert these two NumPy arrays into data frames. So I'll take the first column from the iris data and I'll name it as sepal length. Similarly, I'll take the second column from iris data, I'll name it as sepal width. The third column, I'll name it as petal length. And the fourth column, I'll name it as petal width. And finally, I'll take these values from iris.target and I'll name them to be species. So we are creating this data frame which would comprise of 5 columns, and those 5 columns would be sepal length, sepal width, petal width, and species. And I'm storing this in this data object. I'll click on run, and we also have the head of this new data frame which we've just created, right? So these are all of the columns which are present in this data frame. So now, before we go ahead and build the model, we are again supposed to separate the features and the target column. So I will store all of the features in this X object and I will store the target in this Y object. I'll click on run. So all of these features are sepal length, sepal width, petal length, and petal width, and our target would be species. Or in other words, we're trying to determine what is the species of the iris flower on the basis of these feature values. Now, I'll have to divide this data set into training and testing set. And for that purpose, I'll be importing this train test split function from sklearn.modelSelection. And after that, inside this function, I'll give in these parameters. So the first parameter is the object which comprises of all of the features. The second parameter is the object which comprises of all of the target labels. And then I'll give in the test size, which is 0.3. So this basically states that test data would have 30% of the entire data and the training data would comprise of 70% of the entire data. So this is the train test split. And we are storing this in these 4 objects. So we have xtrain, xtest, ytrain, and ytest. So this xtrain is basically the training set for the features. This xtest is the test set for the features. And then we have ytrain, which is the training set for the target. And then we have ytest, which is the test set for the target. So we've went ahead and we've also divided the data set into training and testing sets. Now it's time to build the model on top of the training set and predict the values on top of the test set. So I'd have to import the random forest classifier from sklearn.ensemble and I'll create a model from it. And I'll set the number of decision trees to be 100. So over here, this parameter which you see, n estimators equals 100. So this basically means that the random forest algorithm which we'll be creating, it'll have 100 decision trees. So we'll get the aggregate result of these 100 trees. Now I'm storing this in this CLF object. Now I'll go ahead and fit or build this model on top of the train set. So we have xtrain and ytrain. Now after I build the model, I would have to predict the values. So I'll predict the values on top of the xtest. So now that we've predicted the values, it's time to build the confusion matrix and find out how good is a model. So I'll import this matrix from sklearn and then I'll go ahead and build the confusion matrix, which takes in the ytest object, which basically has all of the actual values. And then the next parameter is the ypred object, which has all of the predicted values. Now I'll go ahead and build this confusion matrix. So this first row represents the setosa species, second row represents the versicolor species, and the third row represents the virginica species. And this left diagonal which you see, this diagonal represents all of those values which have been correctly classified. So if we take this row here, then this means that so in total there was 14 species which were actually setosa, and all of them have been correctly classified as setosa. And over here we see that in total there were 16 species of versicolor. Out of them, 15 have been correctly classified as versicolor. And this row if we take, so we see that there were 15 values of virginica. Out of them, 14 have been correctly classified. Now, if you want to get the accuracy of this model which you've just built, we'll use this accuracy score and we'll pass in the same objects, ytest and ypred. I'll click on run. So see that the accuracy for the model which you built is 95.55%. Now I'll go ahead and predict values for a single item. So let's say if I give individual values for each of the columns. So these are the values for sepal length, sepal width, petal length and petal width. So let's say if sepal length was 3, sepal width was 5, petal length was 4 and petal width was 2, then what is the species of this iris flower? I'll click on run. So see that if these are the values for the columns, then it belongs to array 2. Or in other words, it basically belongs to the Virginica species. Similarly, and if these are the values for sepal length, sepal width, petal length and petal width, then let me predict this. So again we see that this time also the species would be Virginica. Now I'll go ahead and have a glance at the importance of the different features. So inside this pd.series, I'll get the importance of each of the individual features. So clf.feature importances, and I'll also have the feature names along with the feature importances. And I'm basically creating a pd.series object out of it, and I am sorting it in descending order. So this parameter ascending is equal to false. This would basically give us these feature importances in descending order, and I've stored that result in feature IMP. I'll click on run, and these are the different feature importances. So we see that the most important features or the most important independent variables are petal width and petal length. So now I'm going to go ahead and make a plot of the feature importance. So I'll import the Seaborn and Matplotlib packages, and then I'll make a bar plot for the feature importance. So on the x-axis, I would have the feature importance, and on the y-axis, I would have the labels for each of these features. I'll click on run. So see that the X label is feature importance score, Y label is features, and the title is visualizing important features. And again, we get the same result. So petal width and petal length are the two most important features when we build this model. Now, since we've understood that the two most important features are petal width and petal length, we're going to go ahead and build a model with only these two features. So this time in the X object, I will take only petal length and petal width as the features, and again the target would be the species column. Now I'll again go ahead and divide this data set into train and test sets, and again I'll set the test size to be 0.3. So in other words, test set would comprise of 30% of all of the data values, and training set would comprise of 70% of all of the data values. I'll click on run. So we've divided the data set into training and test set. Now again, it's time to build the model and predict the values. So we'll use this random forest classifier, we'll build the model, and then we'll fit the values, and then we'll predict the values on top of X test. Now it's time to build the confusion matrix. I'll click on run, and this is the confusion matrix which we get. So we see that all of the Setosa species have been classified correctly. When it comes to versicolor, out of the 16, 15 have been classified correctly. And when it comes to Virginica, out of the 14, 13 have been classified correctly. Now again, we'll calculate the accuracy. So we see that the accuracy is 95.55%. So in the first model which we built, the accuracy was 95.55%. And also in the second model which we built, the accuracy is also 95.55%. So we've understood that we don't have to include the other two independent variables. So without including sepal length and sepal width, we've got the optimal accuracy value for this data set. So my first task would be to import the pandas library. So I'll type in import pandas as pd. Now it's time to load the data set. So I will use the read CSV function. And inside this, I will give in the name of the dataset. So the name of the dataset is iris.csv, and I will load this in a new object, and I will name that object to be iris. So I have loaded the file. Now I'll go ahead and have a glance at the top 5 records of this dataset. So I would have to use the head function for that. So iris.head, and this would give me the top 5 records which are present in this dataset. So we've got all of these columns which are present in the iris dataset. So we've got sepal length, sepal width, petal width, and the species column. Now, our task for this session would be to implement the XGBoost classifier on top of this dataset to find out what species does this iris flower belong to on the basis of the rest of the columns. So on the basis of sepal length, sepal width, petal length, and petal width, I'd want to know what is the species of this particular flower. So we've got 3 different species of iris flower. We've got setosa, versicolor, and virginica. Right. So before we go ahead and implement the algorithm, we'd have to divide the dataset into training and testing set. Now again, before that, we'd have to divide all of the predictors and the response variable. So all of these would be the predictors and this would be the response variable. So let me extract that. So inside the X object, I will go ahead and I will store the rest of the columns except the species column. So it would be sepal length. Let me type in sepal length over here. So after sepal length, I would also require the sepal width. And before this, I'd have to give in the name of the data frame over here, right? So from iris data frame, I would require sepal length. I would also require the sepal width. So let me type in sepal width over here. And after sepal width, I would require the petal length column. So I'll type in petal width, and after petal width, I would require the petal length column. So I'll type in petal dot length. So these are all of the columns, the first 4 columns which I'm storing into the X object. And then I'd also need the dependent variable, which would be the species column. So inside this, I'll just give in species. So I've got all of the independent variables stored in the X object, and I've got my dependent variables stored in the Y object. So now that I have my dependent and independent variables with me, I will go ahead and divide this data set into train and test set. So for that purpose, I'd need to import the train test split from model selection. So I'll type from sklearn dot model selection. I'd be importing train test split. Now I have the train test split method. Let me use it, and inside this I will pass in X and Y. So X consists of all of the predictors, Y consists of the dependent variable, and after this I will give in the test size. So the test size is equal to 0.3. So this would mean that 30% of the records would go into the test set and the rest of the 70% records would go into the train set. Now this would return 4 objects, and those 4 objects I'd be storing in X train, X test, Y train, and there would be Y test after this. Right, so I've divided all of this into 4 parts. I've got X train, X test, Y train, and Y test. So X train basically consists of the independent variables of the train set. X test consists of independent variables of test set. Y train would have the dependent variable of the train set, and Y test would have the dependent variable of the test set. So now that is done, it's time to go ahead and import the XGBoost classifier model. So I will type import XGBoost as XGB. Now I will go ahead and create an instance of this. So I'll type xgboost.xgb classifier, and let's say I'd want 10 decision trees inside this. So I will set the value for n estimators. So with the help of the n estimators attribute, I can decide the number of trees which should be present in this XGBoost classifier. And I'd want 10 trees to be present in this. And also I can set the tree depth. So I'll set the maximum tree depth for all of these decision trees to be equal to 5. And I will store this in a new instance and name this to be XGBC. So XGBNC. Right, so I have created an instance of this XGBoost classifier. Now it's time to fit the model. So xgbc.fit, and inside this I will pass in the xtrain and ytrain objects. So I'm basically fitting this model on top of the train set. So I have successfully built this XGBoost classifier on top of the train set. Now it's time to predict the values. So to predict the values, I'll just type xgbc.predict, and I will pass in the X test inside this. Right, because X test is basically all of the independent variables which are present in the test set. Now for all of these values, I am going ahead and predicting a result, and I will store this in, let's say, y pred. So I have also predicted the values on top of the test set. Now it's time to build the confusion matrix and see how much classification is correct. So from sklearn.metrics, I'd be importing the confusion matrix. Now once I import the confusion matrix, inside the confusion matrix I'll pass in the actual values which are present in the test set and the predicted values which are present in ypred. So this is our confusion matrix. So this, what you see are the actual values and these are the predicted values, and this left diagonal would tell you how many of the values have been correctly predicted. So this is for Setosa, versicolor and virginica. So we see that all of the Setosa species have been correctly classified. When it comes to versicolor, 12 of them have been correctly classified, 2 of them have been incorrectly classified. Similarly for virginica, 12 of them have been correctly classified and 2 of them have been incorrectly classified. To find out the accuracy, I'll just divide the left diagonal with the rest of the values. So it'll be 17 plus 12 plus 12 divided by 17 plus 12 plus 12 plus 2 plus 2. So this gives us an accuracy of 91.11%. And this is how we can build the XGBoost classifier. Click on run. Right. So we have successfully created this list of lists. Now let me have a glance at the first list. So you see that the first list, or in other words, the first row, this is our first row, and this contains these items: burgers, meatballs and eggs. So this is the first transaction which contains these items. So now that we've converted the pandas data frame into a list of lists, we can finally go ahead and build the a priori model on top of this list of lists. So for that purpose, we'll be using this a priori function, which takes in all of these predefined parameters. So first we'd have to give in the object on which we are supposed to build the a priori model. So the object is obviously records, and then we'll set the values for minimum support, minimum confidence and minimum lift. So in this model, we are setting the minimum support to be 0.0045, or in other words, the minimum support threshold is 0.45%. Now this basically means that out of all of the transactions, this model should include at least 0.45 of the transactions. Next, we have minimum confidence set to be 20%. So this minimum confidence level of 20% states that out of all the antecedents, at least 20% of them should also have the consequence with them. And then finally, we have the minimum lift threshold. So we see that the minimum lift threshold which we've set is 3. And then we have the minimum length which is equal to 2. So this minimum length of 2 states that there needs to be at least 2 elements in the rule. Now I will store this result in association rules, and then I'll go ahead and convert this object into a list, and I'll store this in association results. I'll click on run. Now let me go ahead and have a glance at the number of rules this algorithm has given me. So I'll just use the len function, which will basically give me the length of this list. So you see that this algorithm has generated 48 rules in total. Now I'll go ahead and have a glance at the first rule. So I will just type in association results, and since I want to have a look at the first rule, I'll set in the index value to be equal to 0. Over here we see that this is our rule: light cream, chicken, and over here we have item base, which is light cream, and items add, which is chicken. So over here, light cream would be our antecedent and chicken would be our consequent. And we are trying to determine the association between light cream and chicken. Or in other words, we are trying to determine if someone buys light cream, what is the association or what is the correlation of him buying chicken along with light cream. So for this, the support value is 0.004, the confidence value is 0.29, and the lift value is 4. So the support is 0.4%, confidence is 29%, and left is 4. So this confidence value of 0.29 states that out of all the antecedents, at least 29% of them have the consequent, which is chicken, present in them. Now again, similarly, let me have a glance at the second rule. I'll click on run. So this is our second rule, where the antecedent is mushroom cream sauce and the consequent is escalope. So we're trying to determine if someone buys mushroom cream sauce, what is the probability of him also buying escalope with the mushroom cream sauce. So for this, the support value is 0.005, the confidence value is 30%, and the lift is 3.79. So this was our first model. Now similarly, we'll go ahead and build another model where we'll give different threshold values. So this time over here, I am setting the minimum support to be equal to 1%, minimum confidence to be equal to 50%, and minimum lift to be equal to 2. I'll click on run. Now again, let me have a glance at the number of rules given by this algorithm. I'll click on run. So you see that there are just 4 rules with these minimum support, minimum confidence and minimum lift values. So now again, I will go ahead and have a glance at the first rule. So in this first rule, we see that the antecedent comprises of eggs and ground beef and the consequent comprise of mineral water. So we are trying to determine if someone buys eggs and ground beef together, what is the correlation of him also buying mineral water after he or she buys eggs and ground beef. And for this rule, the support is 1%, the confidence is 50%, and the lift is 2.12. Now similarly, let me also have a glance at the second rule. So this is the second rule where the antecedent is milk and ground beef and the consequent is mineral water. So this time we're trying to determine if someone buys milk and ground beef, what is the probability of him also buying mineral water along with these two. And this time the support is 0.11, the confidence is 0.50 and the lift is 2.11. So guys, this is how we can find out association rules in Python. Now what is a recommendation engine? So a recommendation engine is basically a filtering system that seeks to predict and show the items that a user would like to purchase. Now it may not be entirely accurate, but if it shows you what you like, then it is doing its job right. So recommender systems have become increasingly popular in recent years and are utilized in a variety of areas, including music, news, books, social tags, and any other products in general. So mostly used in the digital domain, majority of today's e-commerce sites like eBay, Amazon, and Alibaba make use of this proprietary recommendation algorithms in order to better serve the customers with the products that they're bound to like. And if it is set up and configured properly, it can significantly boost revenues, conversions, and other important metrics. So moreover, they can have positive effects on the user experience as well, which translates into metrics that are harder to measure but are nonetheless of much importance to online businesses, such as customer satisfaction and retention. And all of this is possible only with the recommendation engine. So recommendation engines basically are data filtering tools that make use of algorithms and data to recommend the most relevant items to a particular user. Or in simple terms, they're nothing but an automated form of a shop counter guy. So you ask him for a product. Now not only he shows you that product, but also the related ones which you could buy. So they are well trained in cross-selling and upselling. And with a growing amount of information on the internet and with a significant rise in the number of users, it is becoming important for companies to search, map, and provide them with a relevant chunk of information according to their preferences and tastes. So let's consider an example to better understand the concept of a recommendation engine. So if I'm not wrong, almost all of you must have used Amazon for shopping, right? And just so you know, 35% of Amazon.com's revenue is generated by its recommendation engine. So let's understand the strategy. Now, Amazon uses recommendations as a targeted marketing tool in both email campaigns and on most of its website pages. So Amazon will recommend many products from different categories based on what you're browsing and pull those products in front of you which are likely to buy. So like the frequently bought together option that comes at the bottom of the product page to lure you into buying the combo. And this recommendation engine has one main goal: increase the average order value. That is, to upsell and cross-sell customers by providing product suggestions based on the items in their shopping cart. So Amazon uses browsing history of a user to always keep those products in the eye of the customer. And it uses the ratings and reviews of the customers to display the products with a greater average in the recommended and best-selling option. Now Amazon wants to make you buy a package rather than just one product. Say you bought a phone, it'll then recommend you to buy a case or a screen protector. It'll further send these recommendations to your email and keep you engaged with the current trend of the product or the category. So now that we have defined recommender systems, their objective and usefulness, next we'll go through the different types of popular recommender systems in use. So mainly there are 3 types of recommendation engines. So collaborative filtering methods are based on collecting and analyzing a large amount of information on users' behaviors, activities, or preferences, and predicting what users will like based on their similarity to other users. while content-based filtering methods are based on a description of the item and a profile of the user's preference. So in a content-based recommendation system, keywords are used to describe the items, and a user profile is built to indicate the type of item this user likes. So recent research has demonstrated that a hybrid approach combining collaborative filtering and content-based filtering could be more effective in some cases. So hybrid approaches can be implemented in several ways by making content-based and collaborative-based predictions separately and then combining them, or by adding content-based capabilities to a collaborative-based approach and vice versa. Or we can even unify the approaches into just one model. So Netflix is a good example of a hybrid system. They make recommendations by comparing the watching and searching habits of some similar users. That is, collaborative filtering, as well as by offering movies that share characteristics with films that a user has rated highly. That is, content-based filtering. So now we'll discuss collaborative filtering recommender systems in detail. So in this type of recommendation engine, filtering items from a large set of alternatives is done collaboratively by users' preferences. So the basic assumption in a collaborative filtering recommender system is that if two users share the same interests as each other in the past, they will also have similar tastes in the future. So if, for example, user A and user B have similar movie preferences, and user A recently watched Titanic, which user B has not seen yet, then this movie Titanic is recommended to user B. So the movie recommendations on Netflix are a good example of this type of recommender system. So there are two types of collaborative filtering recommender systems. So first is user-based collaborative filtering. So in user-based collaborative filtering, recommendations are generated by considering the preferences in the user's neighborhood. So this user-based collaborative filtering is done in two steps. By identifying similar users based on similar user preferences and recommending new items to an active user based on the rating given by similar users on the items not rated by the active user. So another type of collaborative filtering is item based. Now in item based collaborative filtering, the recommendations are generated using the neighborhood of items. So unlike user based collaborative filtering, we first find similarities between items and then recommend non-rated items which are similar to the items that active user has rated in the past. So item-based recommender systems are constructed in two steps. So we calculate the item similarity based on the item preferences and find the top similar items to the non-rated items by active user and recommend them. So now let's discuss each of them in depth. So first, let's try to understand how does user-based collaborative filtering work. As previously mentioned, the basic intuition behind user-based collaborative filtering systems is that people with similar tastes in the past will like similar items in the future as well. For example, if user A and user B have very similar purchase histories, and if user A buys a new book which user B has not yet seen, then we can suggest this book to user B as they have similar tastes. So from here we know that we need to compute the similarity between users in user-based collaborative filtering. So how do we measure the similarity? So there are basically two options: Pearson correlation and the cosine similarity. So let U of ik denote the similarity between user I and user k, and V of ij denote the rating that user I gives to the item j. So now both the measures, Pearson correlation and cosine similarity, are commonly used. So the difference is that Pearson correlation is invariant to adding a constant to all the elements. So now we can predict the user's opinion on the unrated items with this equation over here. So now let us illustrate it with a concrete example. So in the following matrix, each row represents a user while the columns correspond to different movies, except the last one which records the similarity between that particular user and the target user. So each cell represents the rating that the user gives to that movie. So assume user E is the target over here. Since user A and user F do not share any movie ratings in common with user E, their similarities with user E are not defined in Pearson correlation. Therefore, we only need to consider user B, C, and D. So based on Pearson correlation, we can compute the following similarity. And this is the resultant table that we see over here. So in this table, you can see that user D is very different from user E, as the Pearson correlation between them is negative. So he rated me before you higher than his average rating, while user E did the exact opposite. So now we can start to fill in the blanks for the movies that user E has not rated based on other users. Now, although computing user-based collaborative filtering is very simple, it suffers from several problems. So one main issue is that users' preference can change over time. So it indicates that pre-computing the metrics based on their neighboring users may lead to bad performance. And to tackle this problem, we can apply item-based collaborative filtering. So now we'll look at how does item-based collaborative filtering work. So now instead of measuring the similarity between two users, the item-based collaborative filtering recommends items based on their similarity with the items that the target user rated. So likewise, the similarity can be computed with Pearson correlation or cosine similarity. And the major difference is that with item-based collaborative filtering, we fill in the blanks vertically as opposed to the horizontal manner that user-based collaborative filtering does. So the following table shows how to do so for the movie Me Before You. It successfully avoids the problem posed by dynamic user preference as item-based collaborative filtering is more static. However, several problems remain for this method as well. So the first main issue is scalability. The computation grows with both the customer as well as the product. And the worst case complexity is order of mn with m users and n items. In addition, sparsity is also another concern. So take a look at the above table again. Now, although there is just one user who rated both Matrix and Titanic, the similarity between them is 1. So in extreme cases, we can have millions of users and similarity between two fairly different movies could be very high, simply because they have similar rank for the only user who ranked them both. Or in other words, the genre of Matrix and Titanic is completely different. And even though the similarity over here is given to be 1. So while building collaborative filtering recommender systems, we need to know how to calculate the similarity between users, how to calculate the similarity between items, how recommendations are generated, and how to deal with new items and new users whose data is not known. So the advantage of collaborative filtering system is that they are simple to implement and very accurate. However, they have their own set of limitations such as the cold start problem, which means collaborative filtering systems fail to recommend to the first time users whose information is not available in the system. So let's understand what is dimensionality reduction. So dimension reduction refers to the process of converting a set of data having vast dimensions into data with lesser dimensions, in turn ensuring that it conveys similar information concisely. In general, it is used to reduce the complexity of data while keeping the relevant structure intact. So this method is typically used to solve machine learning problems to obtain better features. Now let's have a look at the types of dimensionality reduction. Broadly, dimensionality reduction has two classes, feature elimination and feature extraction. So feature elimination is the process of removing some variables completely if they are redundant or if they're not providing any new information about the dataset. And this helps us to keep our dataset small. However, one major drawback is we might lose some information. On the other hand, feature extraction is nothing but extracting the information of new variables from old variables. For example, say you have 10 variables in your dataset, then feature extraction will create 10 new variables which will also include all the 10 old variables. Well, PCA is one such technique that works on feature extraction. So why do we need dimensionality reduction? The main motto behind this technique is to decrease the unwanted dimensions in machine learning. For example, consider a motorbike rider in racing competitions. So the rider position and movements are measured by various factors, such as GPS sensors on bike, gyrometers, multiple video feeds, and smart devices. Now the data analyst has to analyze the racing strategy of a biker, where he'll have a lot of variables or dimensions which are similar and of little incremental values. Hence, such data has to be treated to reduce the number of dimensions or remove unwanted dimensions. Now, let's have a look at some applications of dimensionality reduction. The best example which we can give is image processing. So, I'm sure you might have come across this Facebook application. Which celebrity do you look like? Concept behind this is a dimension reduction technique. To identify the matched celebrity image, the algorithm uses pixel data, and each pixel is equivalent to one dimension. So in every image there is a high number of pixels, that is a high number of dimensions, and every dimension is important here. Now you can't just omit dimensions randomly to make better sense of your overall dataset. So in such cases, dimension reduction techniques help you to find the significant dimensions using various methods. Now let us move on to principal component analysis. So what is principal component analysis? The process of reducing the number of random variables of the dataset under consideration by obtaining a set of principal variables is nothing but PCA. So the main idea behind PCA is to find the low dimension set of axes that precisely fit the data. For better understanding, consider a data set of vehicle properties which includes different variables such as number of wheels, the color of the car, the number of seats, and so on. Well, many of these features are measure related and will be redundant. Hence, this redundant data has to be eliminated to describe the car with fewer features. So this is where the PCA comes into the picture. For instance, think about the number of wheels. Almost all cars and buses will have 4 wheels, and only in very rare cases some buses will have 6 wheels. And hence we can say that this feature has less variance. So this feature will make the bus and car look the same, but in fact they're actually not. Now let's consider the height variable. Now it's very obvious that cars and buses will have completely different values when it comes to height. Well, this property can be taken into account to separate them, as PCA does not take information of classes into account. It will just consider the variance of each feature. Now let us move on to the working mechanism of PCA. So consider that some data is placed in an oval shape on the coordinate axis. In order to find the direction with more variance, we'd have to find the line where data is more spread out when projected onto it. Here the data is not spread out widely. Therefore, it will not have large variance and probably it is not the principal component we are looking for. Now let us try using the horizontal line. So on this line we can see that the data is more spread out and has large variance, and hence it can be considered as the direction for our principal component. Now you might be thinking, how can we find out this principal component? Well, we have eigenvectors and eigenvalues to find the principal component rather than drawing lines and unevenly shaped triangles. So what are these eigenvectors and eigenvalues? So these two exist in pairs. Every eigenvector has a corresponding eigenvalue. The line or the vector which we drew in our previous example is nothing but the eigenvector, and the variance is the eigenvalue. So in the example above, the eigenvalue is a number telling us how spread out the data is on the line, and the eigenvector with the highest eigenvalue is therefore the principal component. For better understanding, let us consider that you have two measures, age and hours on the internet. So there are two variables, and hence it will be a two-dimensional data set, and therefore it will have two eigenvalues and two eigenvectors. The reason for this is that eigenvectors put the data into a new set of dimensions, and these new dimensions have to be equal to the original number of dimensions. So this sounds complicated, but again an example should make it clear. So we can see that the oval is on x and y axis, where x refers to age and y refers to hours on the internet. Now let us split the data by drawing a line. So the eigenvectors should be able to span the whole xy area, and therefore they need to be orthogonal to each other. Hence the second eigenvector would look like this. Now we'll just reframe the data in these new dimensions, and the resultant is as shown below. So you can also make sure that nothing changes by moving the data to the origin. So these eigenvectors basically give us a new set of axes, and these axes are much more intuitive to the shape of the data now, as these are the directions where most of the variation occurs. Now let us see how PCA is used to reduce the dimensions of a given data set. So it reduces the data down into basic components by taking out the unnecessary parts. So consider that you're measuring three variables: age, hours on internet, and hours on mobile. Now imagine that the data forms an oval shape on a plane as shown in the figure. Since we have considered three measures, it will have three eigenvectors and three eigenvalues for the data set. And out of these, two eigenvectors will have large eigenvalues and one eigenvector will be 0. Here EV1 is the first eigenvector, EV2 is the second eigenvector, and EV3 is the third one. And since it has an eigenvalue of 0, we'll not consider that. So we can now rearrange the axis to the origin, and we'll also represent the data in 2 dimensions as EV3 is 0. So what we've done here is nothing but dimension reduction, and hence the 3-dimensional problem is now reduced to 2-dimensional problem. So reducing dimensions helps to simplify the data and make it easier to visualize. So this is how PCA algorithm works.
So here we have a multi-dimensional movie rating dataset where every dimension or column is a movie and different users are rows. So we'll call this matrix as A, and if you have learned about the PCA, which is the principal component analysis, so if you use PCA on this particular dataset, so it can boil down this dataset to a much smaller number of dimensions, and those dimensions will best describe the variance in the data, and often those dimensions that or PCA will find that will correspond to the features that we have learned as humans in the real world. So for example, if you run PCA on this particular dataset, so it will find those latent features and extract them from the data. So PCA actually would not know what those features mean, but still it will find those features. So we'll ask PCA to find 3 dimensions in this data, and if you run PCA on this data to find 3 dimensions, so it will boil down our data or ratings down to 3 latent features that it identified. So PCA would not know what those features are and what to call them, but let's say that they end up being measures of each person's interest in action, sci-fi or comedy movies. So for example, we might think of user 1 as being defined as interested in 30% action, 50% interested in sci-fi movies and 20% interested in comedy movies. So now let's take a look at the columns in this new matrix. So each column here is a description of users that make up that particular feature. So we can say that the action can be described as the 30% of user 1 and the 10% of user 2 and the 30% of user 3. So let's call this matrix as V. So just like we can run PCA on our user rating dataset to find profiles of different kinds of users, so we can now flip things around and try to run PC on profiles of different kinds of movies. So if we rearrange our input data so that now the rows are the movies and the columns are the users, so it will look like this. So we'll call this as the transpose of the original ratings matrix, or A of T for short. So now if we run PCA on this particular dataset, so it will identify some latent features again, and it will describe each individual movie as some combination of them. So now each column is now a description of some typical movie that exhibits some latent feature. So again, these columns have no inherent meaning, but in practice they might fall along the movie genre lines. But in reality, it is more complex to name these features. So now let's call this particular resulting matrix that describes typical movies as U. So how do these matrices actually help us to describe typical users and typical movies to help us predict ratings? So it turns out that the typical movie matrix, which is U here, and the typical user matrix transpose, which is V of T, and they are both the factors of the original matrix A that we started with. So here A is a M by N matrix with M rows and N columns, and U here is M by M matrix, so it has M rows and M columns, and S is M by N matrix, and V of T is your N by N matrix. So if we have both U and if we have V, so we can reconstruct the whole matrix A, and even if there are missing values or missing ratings, and if we have both U and V, so we can fill in all those missing values using these two matrices in A. So that is why we call this as matrix factorization. So we'll describe our training data A in terms of smaller matrices, and that are the factors of the ratings that we want to predict. So there is also a matrix S, which is in the middle. So it is just a simple diagonal matrix, which means that the non-zero elements will be on the diagonal of this matrix and rest of the elements will be 0. So the only purpose of this matrix is to scale the values so that we end up into the proper scale of the values that we calculate using U and V. So here U and V are both orthogonal matrices, which means that if you multiply these matrices with their transpose, so you'll get the identity matrix. And S is the diagonal matrix, which means that the non-zero elements will be on the main diagonal and rest of the elements will be 0. So that is why we call this as matrix factorization. So you can just multiply the scaling matrix into V or U, and you will still think of R as just, or A as just the product of the two matrices. So you can just multiply the scaling matrix into V or U and still think of A as just the product of the two matrices, that is V and U. So you can reconstruct whole A at once by multiplying these factors together and get the ratings for every combination of the users and the items or the movies in this particular case. So once you have these factors, so you can also just predict a rating for a specific user. So here is a screenshot for a real data set that we'll code in our coding environment, and then you can, if you want to calculate the rating, or if you want to predict the rating for the customer 7 for the movie 3, so the columns represent the movie IDs and the rows represent the customer IDs or the user IDs. So if you want to know or predict the rating for the customer 7 or user 7 for the movie 3, so we can do that by taking the dot product of the respective row in U and for the user and the respective column in V of T for that particular movie, so which will give us the predicted rating for the user ID 7 for the movie 3. So finally we are going to tie this all together. So later on in this course we'll use a built-in recommender called the SVD. So SVD is known to produce very accurate results, and SVD stands for singular value decomposition. So it is just a way of computing the matrix U, S and V all together all at once very efficiently. So all SVD does is to run PCA on both the users and the movies, and it gives us back the matrices that we need, which are the factors of the original rating matrix that we had. So SVD is just a way to get all of these factors in one go. So mathematically we can represent the expected rating or the predicted rating as the dot product of U and V of T, where P of U is here is your U and Q is your V. So what SVD does is it tries to minimize the values of P and Q such that we minimize this particular loss function. So now the problem arises when we have missing data in our rating dataset, so which is most of the times we will have. So this is an actual screenshot of the Netflix price data where you can see most of the values are missing. So when our original matrix, that is A, has some missing values, so we cannot actually run PCA on this matrix because it has missing values, so it must be a complete matrix to run PCA. So one way to solve is to just fill these missing values using the mean values, but there is a better way to do that. So if we remember from the previous slides that every rating can be described as a dot product of some row in the matrix U and some column in the matrix V of T. So if you want to find the rating for user 1, so we'll take a dot product of the corresponding row in the matrix U and the corresponding column in the matrix V of T. So let's assume that if we have at least some known ratings for any given row and column in both matrices U and V, so you can treat this as a minimization problem where we actually try to find the values of those complete rows and columns that best minimize the errors in the known ratings for the matrix A. So there are a lot of machine learning techniques that we can use to solve this problem. So one technique is called the stochastic gradient descent, which is SGD for short. So basically what it does is it just keeps iterating at some given learning rate until it arrives at a minimum error value. So again, SGD is just one way of doing it. So there is another method called the ALS, which is alternating least squares, that we can use to solve this problem. And when we say that we are using SVD for recommendations, it is not really just SVD because you cannot actually apply SVD to missing data. So it is just an SVD inspired algorithm, not a pure SVD. So a specific variant of SVD is called the SVD++. So, and there is another technique called the restricted Boltzmann machines, which are used to solve these problems. So the important points that you have to take away is that you can think of all the rating metrics as a set of users and items as a matrix A, and the matrix A can be factored into smaller matrices that describe the general categories of the users and the items that can be multiplied together. So a quick way to get those matrices is by using a technique called SVD, which is called the singular value decomposition. So once we have those factored matrices, so you can predict the rating of any given item. So the rating is predicted by taking a dot product from each matrix. So techniques such as SGD and ALS, which is alternating least squares, can be used to learn the best values of those factored matrices when you have missing data. So now let's implement the SVD algorithm in Python on the movie lens dataset. So I'll start by importing the required libraries, that is NumPy as NP and Pandas as PD. So once you have imported these libraries, now let's import our datasets. So we have two datasets called ratings and movies. So first of all, I'll import the ratings.csv, which I have already uploaded to the Jupyter notebook. So we have 4 columns in this dataset, that is user ID, movie ID, rating and timestamp. So we'll use these columns and we'll store the dataset in ratings data frame. And after that, if you want to see the head of this data frame, that is the first 5 rows, so you'll run the ratings.head and it will print the first 5 rows of this dataset. So we have user ID for a particular user, and the movie ID that this particular user has rated, and then the rating that this particular user has given to these movie IDs, and then the timestamps. So now let's see the second dataset, that is our movies.csv. So we'll use the read_csv function to read this dataset, and we have 3 columns, that is movie ID, title and genres. So we'll store this in movies data frame. So once we have imported these 2 datasets, now let's look at the heads of both of these datasets. So our movies.head, it prints these three columns. So we have movie ID as the first column, which corresponds to the movie IDs in our ratings dataset, and then we have the title of these movies, the year of the release, and then we have the genres of these movies. So if you want to look at the head of the ratings dataset, we have user IDs, movie IDs, ratings, and timestamps. So this is our movie lens dataset, and we are going to make an SVD recommender system using SVD algorithm. So before that, we'll calculate how many unique users are there and how many unique movies are there in our dataset. So in our ratings dataset, our user ID columns contains the user ID for different users. So each user might have given ratings to more than one movie. So here you can see this particular user with the user ID of 1 has given movie number 2 a rating of 3.5, movie number 29 a rating of 3.5. So there are different movies and movie IDs and the different ratings. So if you want to know how many unique users are there, so we'll use the unique method of the column, that is user ID, and then we only want to get the first element. So if you omit the dot shape method from here, if you run this, so you'll get an array, and if you just write the shape, so you'll get a tuple where the first element of the tuple is the number of users or unique users in our dataset. So if you want to access the first element, you will just write the indexing. So in the indexing or the slashing, will write the 0 or the first index, that is our users. So we have around 7120 users in our whole dataset. And then if you want to know how many movies or unique movies are there in our dataset, so we'll use the same unique method on the movie ID column, and then we'll get the first element. So once we print this, so we have printed it using the f string. So an f string is just a string that is used to print Python expressions. So if you have a Python expression that you want to print including a string, so we have written number of users, and you have to keep the Python expression in these braces, and these Python expressions are the variables that we have just calculated above, that is number of users and number of movies. So once you print this, you'll get number of users as 7120 and number of movies as 14026. So we have 7100 unique users. We have given different ratings to 14026 movies. So now before moving ahead, as I've already told you that our algorithm, SVD algorithm, it takes a matrix which is a real rating matrix. So that matrix should be in such a way that the columns are movie ratings or the movie IDs, and the user IDs are represented by rows. So we'll do that by using the pivot method of the data frames. So our data frame is ratings, so we'll use the pivot method. So it will create an array that corresponds to the movie IDs on the column side and the row IDs or the user IDs on the row side. So the index of this particular matrix will be user ID, and the columns will be represented by movie IDs, and the values in the columns and the rows will be represented by our ratings. So these are the different ratings given by different users to different movies in this ratings dataset. And if you want to fill all the missing values with 0, so we'll write fill NA 0. And if you delete this particular method from here and you print it, so you will get all the missing values represented by NaN values. And if you want to replace these NaN values by 0, so we'll replace it with fill NA 0, so it will replace all the NA values with 0. So now to implement the SVD algorithm in Python, we're going to use the library called scikit-surprise. So if you want to install this library, you have to run this particular command in your Anaconda prompt. So if you go to your Anaconda folder, and in the Anaconda prompt, you have to type this particular command, and once you run it, so you will be asked to press Y or no. So you press 1, and then this particular package, which is scikit-surprise, it will be installed in your Anaconda system. So since I've already installed this package, so I will not install it again. So now I will import all the required libraries and classes that we need to implement the SVD algorithm. So from the surprise package, we'll import the reader class, the dataset class, and the SVD algorithm. So there are different versions of SVD algorithm that are present in our surprise package. So we are going to use the SVD, and there is also one algorithm called the SVD++. So we are going to firstly use the SVD algorithm, and also we want to evaluate the performance of our model. So for that, we'll import the cross validate function from the model selection package or the model selection module of the surprise package. So once you've imported these two, now you can instantiate an object of the reader class. So we'll use this object to read datasets, and we'll convert those datasets to your dataset object that is used by your SVD algorithm. So once you run this particular code, your dataset will be loaded. So to load the dataset, we have the dataset class, and we'll use the load from df method of this class, and inside the method we have to mention our data frame and a different column. So there is a format that this particular class requires. So the format is that your first column is your user id, the second column is your movie id, and the third column should be your ratings. And we'll use the reader class to read this particular data frame, and it will convert this particular data frame to a dataset object that will be used by your svd algorithm. And after that we'll instantiate an svd class object that is called svd that we'll use later on to fit the model. And then first of all we'll evaluate the performance of the model using the cross validation. So we're not going to implement training and test sets, we'll implement the cross validation, and using the cross validation we'll get to know the performance of our model. So we have used the cross validate function that we've just imported from the model selection package, and this function takes two arguments, that is svd, your model, and the data that you're going to run on, and the data that you want to run svd on. The measures will be your two measures or more than two measures that you want to evaluate the performance for. So we'll calculate the RMSE values, which is the root mean square errors, and the mean absolute errors. And then CV equals 3 means that we want this algorithm to run cross validation 3 times. And then we have verbose equals 2, so it will also print whenever it runs cross validation, so it will print the results along with the process. So after running this, it might take some time because the cross validation process takes some time. So once it's over, so we'll move ahead with the rest of the code. So here are the results for our threefold cross validation. And if you want to know more about these functions, so you can press shift and tab here, so it will open the documentation. So in the documentation you can see that if you want to use a custom data set that is stored in a pandas data frame. So it takes two arguments, that is your data frame and the reader object of the reader class. And if you want to know more about this, so you can read this particular documentation. And after that, if you want to know more about the cross validate function, so you can click here. So it takes your algorithm as the first argument. So our algorithm is svd, and then the data is data, and different measures as RMSE and MAE. And cross validation is the number of times it will perform the cross validation. So it will be a threefold cross validation. So these are different results for our cross validation. So for the fold 1, we have an RMSE of 0.84, and for fold 3 we have an RMSE of 0.8473, and this is the mean and the standard deviations. So now if you look at the head of your ratings dataset, so you will see we have different user IDs, movie IDs, and rating. So now if you want to predict the ratings for the user one for different movies which this user has not rated yet, so that we can recommend those movies, and we'll recommend all those movies where the prediction is 5 or the highest rated movies by this particular user. So first of all, let's create a matrix, or let's create a data frame. So now before moving on, let's see how many movies this particular user has rated as 5 stars. So we'll take all the movies which are rated by user 1, and we'll take all the movies which are rated by user 1 as 4. So if you write 5 here, so it will display all the movies which have been rated by user 1 as 5 stars. Then we have set the index of this particular data frame as movie ID. So these movie IDs will be treated as an index, and now after that we'll join movie IDs and our ratings. So we'll join our ratings and the movies data frame using the title column. So once you run this, you'll get this particular data frame that will contain all the movie IDs along with the movie names that have been rated as 4 stars by this particular user. So you can see these are the movies that have been rated as 4 stars by this particular user, and if you write 5 here, so it will display all the movies that have been rated as 5 stars by this particular user. So based on these results and based on the movies that have been rated 5 stars by other users, we will recommend different movies that this particular user has not seen that other users have seen. So now first of all, let's copy our movies dataset which contains the title of the movies. So once you use the .copy method, so it will create a copy of this particular dataset. It will store in user 1. So if you now make any changes to the user 1, so our original data, that is our movies data, will not be affected. So that is why we use the copy method. So once we have used the copy method, so now we'll reset the index. So reset the index is when you start the index from 0 again. So if the index was movie IDs before, so now it will be reset to 0s and 1s. So this is how our movie ID or user one dataset looks like. So we have indexed from 0 to 1 again, and this is the movie IDs, these are the titles, and these are the genres. So now we'll train our SVD algorithm using this particular dataset. So we'll use again the dataset class, and we'll use the load from df method from this class, and we'll pass our data. So our data is ratings data, so it contains 3 columns, that is user ID, movie ID, and our rating. And then we'll use the reader class to read this particular dataset, and it will convert into our dataset object that will be used by our SVD algorithm. So after creating the dataset, we'll build the training set. So if you want to build the training set, we have a method called build full train set. So it will take all the set or all the dataset, and it will build a training set from that particular dataset. So we'll store that dataset in train set, and then we'll pass our train set to our SVD algorithm. So we have already instantiated an object of the SVD class, that is SVD. So we'll use the fit method of this particular object, and we'll pass our training set to this particular method. So once we pass our training set to this particular method, so our SVD algorithm will be fitted to this particular training set. So after fitting our algorithm to our training set, we'll now estimate the scores or the ratings by this particular user for different movies. So we'll store that in a new variable in our data frame, that is user1. The variable name is estimated score. So we'll write user1 then movie ID. So we'll take all the movie IDs and we'll apply this lambda function on all the movie IDs. So this lambda function will take all the movie IDs as an input, and we'll use the dot predict method. So our lambda function is a function which is an unnamed function. So it will use this particular method, which is the predict method of our SVD object, and it will pass x, which is our movie IDs here, and it will find the estimated ratings for different movies that is not yet given by this particular user. And based on those estimated ranks or estimated ratings, we'll only recommend those movies which are estimated to be the highest rated movies by this particular user. So after we pass this, we will have all the estimated or predicted ratings for this particular user for different movies. So that object or that data frame will also contain these columns as well. So movie IDs will be there, genres will be there, indexes will be there. So we don't want these 3 columns, we just want the title of the movies and the movie IDs which will be already stored as the index. So we'll drop all these 3 columns, and we write x is equals 1 if we want to drop anything from the column side, and we'll store all the results, or we'll store the results in the data frame called user1. And now we'll sort the values of the user1. So our user1 now will contain the estimated values or the predicted ratings for this particular user whose ID is 1. So we'll start the values of the estimated scores by descending order. So we'll have to write ascending equals false, so it will be sorted in descending order. So then we'll print the first 10 ratings, which is the highest 10 ratings for our user 1. So it will also contain the movie titles. So once you run this particular code, so we'll have all the highest rated movies, or the movies that are highest rated, and those are predicted by our particular SVD algorithm. So after this code finishes executing, you'll get the first 10 titles or the movie titles which are expected or which are predicted to be the highest rated by this particular user. So the highest rating this particular user will give is 4.7 to these movies. So we'll recommend these movies to this user, which this user has never seen these movies based on the rankings that have been given by other users. So this is how we use the SVD algorithm to build a recommendation system that will recommend different movies to a user based on the UCBF, which is the user-based collaborative filtering.
Now, there are many ways of knitting the nodes of a neural network together, and each way results in a more or less complex behavior. Possibly the simplest of all topologies is the feed-forward network. So when feed-forward neural network, signals flow in one direction without any loop in the signal paths. And typically, artificial neural networks have a layered structure. The input layer picks up the input signals and passes them on to the next layer, known as the hidden layer. And there can be more than one hidden layer in a neural network. And at last comes the output layer that delivers the result. Now, the first question to pop into your head would be, what is the inspiration behind these artificial neural networks? Well, the answer to that is the biological neural network of our brain. So let us first understand the architecture of a biological neuron. So as you can see in the slide, our biological neuron has these 3 main components. So we have the dendrite, the cell body, and the axon. These dendrites receive the signals, and the cell body processes these signals, and the axon finally sends out these signals to other neurons. So just like the biological neuron, The artificial neuron has a number of input channels, a processing stage, and one output that can fan out to multiple other artificial neurons. So now let's understand these artificial neurons in detail. These artificial neurons are the most fundamental units of deep neural network. It takes an input, processes it, passes it through an activation function, and returns the output if the condition is met. Or else it will process it again until you get the correct output. And such type of artificial neurons is called as a perceptron. So they are basically like a linear model which is used for binary classification. So as the figure shows, we have x1, x2, x3 and going on till xn as inputs in the input layer. Now, to which we add the weights and the bias that are randomly selected. So here we have w1, w2, w3 going on till wn as weights. So we multiply these weights with the corresponding inputs and add all the values together, and finally we add bias to that sum. So this final sum is passed through an activation function which finally gives us the output. So let us see this in detail. So here we have 3 arrows which correspond to the 3 inputs coming into the network. Now for these 3 inputs, we have corresponding weights associated with them. So input 1 is associated with a weight of 0.7, input 2 is associated with a weight of 0.6, and input 3 is associated with a weight of 1.4. Now, these inputs are multiplied with their respective weights and their sum is taken. So if the 3 inputs are x1, x2 and x3, the sum would be x1 into 0.7 plus x2 into 0.6 plus x3 into 1.4. And to the sum, we add an offset which is called as bias. So this bias is just a constant which is used for scaling purpose. Now let us understand the concept behind these weights. So these weights basically determine the relative importance of the inputs. So let's say we have 2 inputs, humidity and wearing a blue shirt. So here we can see that wearing a blue shirt has almost no correlation with the possibility of rainfall. So that is why the weight assigned to input x2 would be low in order to bring down its importance. Now let us see why do we need activation functions. So consider this scenario where you have 2 different classes. One class is represented with triangles and the other class is represented with circles. Now let's say I ask you guys to draw a linear decision boundary which can separate these 2 classes. So is that really possible? Can we draw a linear line which can segregate these 2 classes? Well, the answer is obviously no, isn't it? So let me tell you guys how can we do this. So we'll have to add a third dimension to create a linearly separable model which is easy to deal with. So the logic is when you're going from 2D to 3D, you're making your equation non-linear. So with the third dimension, I have introduced non-linearity in our data, which helps in creating a linearly separable model. And in real-world situations, you don't always get linear problems. So you should know how to deal with non-linear problems as well. And this is where activation functions help us to convert the linear equation to non-linear form. So these activation functions bring in non-linear functional mappings between the input and the response variable. Their main purpose is to convert an input signal of a node in an artificial neural network to an output signal. And if we do not apply an activation function, then the output signal would just be a simple linear function. Now there are many types of activation functions, and today we'll be discussing some of the widely used ones. So let's start with the identity function. So the identity function gives out the same output as the input. So no matter how many layers we have, if all the activations are identity functions, then the final output of the last layer would be the same as the input given to the first layer. And the range of the identity function goes from -infinity to +infinity. So after that, we have the binary step function. So this binary step function is usually denoted by h or theta, and it is a discontinuous function. So if the input is less than 0, then the output would be 0. And if the input is equal to or greater than 0, then the output would be 1. And this is why binary step function is used to solve a binary classification problem. So after that, we have the sigmoid function. So the formula for the sigmoid function is denoted by 1 upon 1 plus e power minus x. The sigmoid function basically scales the values between 0 and 1. So if the input is a large negative number, it is scaled towards 0. And similarly, if the input is a large positive number, it is scaled towards 1. Then we have the tan h function. It is a hyperbolic trigonometric function which scales the values between minus 1 and 1. So one advantage of tan h function over sigmoid is that it can deal more easily with negative numbers. And after that, we have the ReLU function, which stands for rectified linear unit. So this function will give out 0 if input is less than 0. And on the other hand, if input is equal to or greater than 0, then it will act as an identity function and give out the same value as the input. And this ReLU function is the most widely used activation function and is primarily implemented on the hidden layers of the neural network. Then we have the leaky ReLU, which is just a modified version of ReLU. So the leaky ReLU, instead of just completely removing the negative part, it just lowers the magnitude. And finally, we have the softmax function, which is ideally used in the output layer for classification problems. So the softmax function basically gives a set of probability values for each class of the output. And that particular class, which would have the maximum probability, will be our output class. So that was all about activation functions. Now let us learn more about perceptrons. So like we were taught how to behave in certain conditions, perceptrons also require training. So they have a learning algorithm through which they produce the output. By training a perceptron, we try to find a line, plane, or some hyperplane which can accurately separate these two classes by adjusting the weights and biases. So consider this image where we give the dogs and horses as input. So here, after the first iteration, error value is 2 since the horse has been classified as dog and there is one dog which is placed in the horses class. And in the second iteration, the error value is reduced to 1 as it is just the dog which is classified as a horse. And finally, in the third iteration, we get the correct output as the perceptron has been trained well with no error. So all the dogs have been placed in one class and all the horses have been placed in one class. Now let's understand the perceptron training algorithm. So this perceptron over here receives multiple inputs and each input is initialized with a random weight. So after these, we multiply these weights with their corresponding inputs and then we get the sum. Now this input is passed through the activation function, which would give us a non-linear output. So this process until here is known as feed forwarding. Now, if the output which we get is not optimum, we calculate the error in prediction and then go back and then update the weights and bias. So this process where we go from output to the input layer is known as backpropagation. And we keep on backpropagating until we get the desired output. So that was the perceptron training algorithm. Now let's have a look at the benefits of using artificial neural networks. So the artificial neural networks can learn organically. This means an artificial neural network's outputs aren't limited entirely by inputs and results given to them initially by an expert system. So artificial neural networks have the ability to generalize their inputs. This ability is valuable for robotics and pattern recognition systems. Artificial neural networks also help in nonlinear data processing. So nonlinear systems have the capability of finding shortcuts to reach computationally expensive solutions. These systems can also infer connections between data points rather than waiting for records in a data source to be explicitly linked. This nonlinear shortcut mechanism is fed into artificial neural networking, which makes it valuable in commercial big data analysis. Artificial neural networks also have high potential for fault tolerance. When these networks are scaled across multiple machines and multiple servers, They are able to route around missing data or servers and nodes that can't communicate. And these artificial neural networks can also self-repair themselves. So if they're asked to find out specific data that is no longer communicating, these artificial neural networks can regenerate large amounts of data by inference and help in determining the node that is not working. This trait is useful for networks that require informing their users about the current state of the network and effectively results in a self-debugging and diagnosing network.
Here's a quiz question for you guys. What do you mean by artificial intelligence? Your options are the ability of a machine to think and learn like a human, the use of computers to solve complex mathematical problems, a computer program that performs repetitive tasks automatically, or the study of natural intelligence in animals and humans. Please mention your answers in the comment section.
Guys, I have a special announcement for all of you. For all of you dedicated individuals who are looking forward to master data science, we are offering a straightforward 20% discount on our data science course, which is in collaboration with iHub IIT Roorkee. So do make sure to check the link given in the description and fill the inquiry form. Shortly, our team of course advisors will get in touch with you to activate the offer. Don't miss this chance and take your career to the next level. Click on the link given in the description right now.
So why AI? Well, AI is actually everywhere. It's omnipresent like God. And AI's applications are present in every single industry, from banking and finance to medical science and also in aerospace. Now, it is actually a known fact that many banks have numerous activities on a day-to-day basis which need to be done accurately. And most of these activities take up a lot of time and efforts from the employees, and at times there is also a chance of a human error in these activities, so to speak. So, some of the works that banks and financial institutions handle are investing money in stocks, financial operations, managing various properties, and so on. And with the use of AI system in this process, the institutions are able to achieve efficient results in a quick turnaround time. So the strategic implementation of artificial intelligence in the bank helps them to focus on every customer and provide them quick resolution. And similarly in medical science field as well, it has wide applications. So AI has completely changed the way medical science was perceived just a few years ago. So there are numerous areas in medical science where AI is used to achieve incredible value. So with the help of AI, the medical science was able to create a virtual personal healthcare assistant. So these are used for research and analysis purpose. There are also many efficient healthcare bots introduced in the medical field to provide constant health support to patients. And it is also used in the aerospace industry. So in aerospace, there are a lot of features from booking the tickets to the takeoff and operation of the flights that AI takes care of. AI applications make air transport efficient, fast, safe, and also provides a comfortable journey to the passengers. And it has also changed the face of gaming. So these days we're able to play TV and computer games on the whole new level, all thanks to artificial intelligence application. So these are just some of the applications where artificial intelligence is used. And all in all, it is used to reinvent the world. So scientists are riding on the back of AI when machine intelligence will surpass the human intelligence. Scientists believe that once the AI system starts working in its full capacity, it will reinvent the world that we know today. So think of the world where all the menial tasks such as garbage disposal, construction, digging, and so on will be taken care of by AI applications. So it'll all be a time when the hierarchical order dictates the limits of a human. It'll be the world where no one will be looked down upon and every human will be considered equal. So this way, humans can then focus their strengths on higher levels of work to accomplish a lot more and always taking technology to new heights. So now that we've understood the importance of artificial intelligence, let's learn more about AI. So, AI is basically a field of computer science which emphasizes on the creation of intelligent machines which can work and react like humans. So, I am reiterating it. So, AI is that field of computer science where we create machines which can work and react like humans. So let's keep this definition at the back of our head. Using this definition, let's actually look at some applications of AI which are currently existing in today's world. So we have simple chatbots like OK Google and Siri, which help us in assisting whatever we want. So let's say I want to know the current time. All I need to do is ask Siri, Siri, tell me what is the current time. Similarly, if I want to know the distance between India and Malaysia, I'll ask Siri, tell me what is the distance between India and Malaysia. Again, let's say I'm just sad and I want to listen to a simple joke. I'll ask Siri, tell me a simple joke. Right? So these are some of the applications of artificial intelligence. And then we have Sophia. So Sophia is the first humanoid robot. So she is the first humanoid robot who can actually speak to us like natural humans. So Sophia can show some wide range of emotions exhibited by humans, but she is actually a robot. Another application of artificial intelligence is the self-driving car. So you have self-driving cars by Google and Tesla, which actually drive by themselves. So they do not need any external driver to drive, right? So these cars work by themselves. So similar to self-driving cars, we also have self-flying drones, which do not need any human intervention and they can navigate by themselves. So now let's actually get a bit deeper and understand what is intelligence. So intelligence can be defined as one's capacity for understanding, one's capacity for self-awareness, one's capacity for learning, and one's capacity for problem solving. That is, how well is something or someone able to understand? How well is someone able to learn new things? And how well is someone able to solve problems by themselves? So, now that we know what is intelligence, let's understand what is artificial intelligence. So when you apply the same intelligence to machines, this is known as artificial intelligence. Now just imagine there's a machine which can understand things which are normally understood by human. There is a machine which is self-aware, and there is a machine which can solve problems by itself. Now that's just amazing, isn't it? Right. So this is the artificial intelligence which I'm talking about. So now that we also know what is intelligence, I'll ask another question. So tell me, what is it that makes humans intelligent? Well, we as humans can reason, we as humans can learn, we can perceive, we can solve problems, and we also have linguistic intelligence. That is, we can figure out what is someone else saying, and we can also understand the grammatical intricacies of different languages. So again, my question would be, what if a machine could exhibit all of these factors normally shown by a human? Again, that's just amazing, isn't it? So this is what is known as artificial intelligence. So a machine which can show traits normally shown by a human, that is known as artificial intelligence. Alright. So now that we're clear with artificial intelligence, let's segregate AI, ML, and DL. So normally most people get confused between artificial intelligence, machine learning, and deep learning. So this is where I'm going to help you out in understanding the difference between these three. So we have AI at the top, and you can consider machine learning and deep learning to be subsets of AI. So again, machine learning and deep learning are just ways to achieve artificial intelligence. So I'll restate it again. Machine learning and deep learning are just ways to achieve artificial intelligence. Now, machine learning is that part of artificial intelligence which aims to teach the computers the ability to do tasks with data without any explicit programming, right? So we don't need to do any explicit programming, and the algorithms do tasks by themselves. And in ML, we mostly use numerical and statistical approaches to achieve artificial intelligence. And then we have deep learning, which is actually a subset of machine learning. So first we have AI, and then we have ML, and then we have DL. So deep learning comes in where machine learning fails. And we apply deep learning through something known as artificial neural networks, about which we'll obviously learn later. Right. So now let's understand artificial intelligence in a bigger set. So as I've already told you, artificial intelligence is the superset under which comes machine learning, under which comes deep learning. And then machine learning and deep learning are basically ways to achieve artificial intelligence. Now these are the different areas of research of artificial intelligence. So you have ML. Again, a part of ML is deep learning. Then we have natural language processing. So over here we basically understand what is spoken or written by a human. And then we have speech, where we either translate the speech to text or we translate the text to speech. The next subfield is robotics, and then we have autonomous vehicles under robotics. So Google's self-driving car is an example of this over here. So now that we've also understood the difference between artificial intelligence, machine learning, and deep learning, let's see different examples of machine learning around us. So most of you would have shopped on Amazon. Now, when you go into Amazon, you see that there are some products recommended to you. Now, how do you think that would happen? So this is something known as recommendation engine. And recommendation engine is nothing but a component of machine learning. So let's say you and your friend buy similar products. So your friend buys 5 products and you buy 3 products. Now, out of those, whatever 3 products you buy are same as what your friend buys. So let's say the common products are an iPhone, a back cover for the iPhone, and a Bluetooth headset. Now let's say the other 2 products bought by a friend would be a MacBook and a mouse. Now since there are 3 products which are same between you two, this is why the products which your friend has also bought, those are the products which will be recommended to you. So on the basis of the commonality between you and your friend, you will be recommended a MacBook and a mouse as well. So this is nothing but a concept of machine learning. And then we have Amazon Alexa. So Amazon Alexa is a really good example of speech recognition. You know, when you say Alexa, turn on the lights, it'll turn on the lights. When you say Alexa, book a ride for me, it'll do exactly that. When you say Alexa, order a cheese pizza, and that is exactly what Amazon Alexa will do. Now Alexa is just a machine, right? But when you say do something, order a pizza, book a cab for me, turn on the lights, how is the machine able to understand all of this? So the idea behind this is speech recognition, and that is again a component of machine learning. And then we have Netflix's movie recommendation. So let's say you watch 2 TV series. First TV series is Friends and the next TV series is Big Bang Theory. And since you watch these 2 TV series which belong to the genre comedy, that is why maybe you will be recommended How I Met Your Mother, or you can be recommended Silicon Valley or some other TV series belonging to the comedy genre. So this again is machine learning. And then we also have Google traffic prediction. Let's just say you're traveling in your car and there is huge traffic there. You desperately want to get out of the traffic. So you turn on Google Maps and Google Maps tells you the best direction from where the traffic would be the least. Now, how does Google Maps do this? This again is machine learning. So now that we've looked at different real-world applications of machine learning, let's actually understand what exactly is machine learning. So, as I've already told you, machine learning is a subset of artificial intelligence which gives the machine ability to learn without being explicitly programmed. So over here, Data is the key, or in other words, you basically teach a machine how to learn without any explicit programming, and the machine learns with the help of data. Right. So now that we know what exactly is machine learning, let's also understand how does machine learning work. So as I've already told you, machine learning depends totally on data. So first, we take in a data set and divide it into two parts. So the first part would be the training set and the second part would be the testing set. And we will train the model on top of the training set. So now, once we train the model, we will give it new data and check for its accuracy on top of that new data. And if the accuracy of that new data comes out to be good enough, then we will go ahead and use that machine learning model. On the other hand, the model which you built, if the accuracy of that model is not good enough, then we'll go ahead and fine tune that model till we get the desired accuracy. This is the basic premise behind machine learning. Now let's look at the subcategories of machine learning. So we have supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, you can consider that the learning is guided by a teacher. So we have a data set which actually acts as a teacher, and its role is to train the model or the machine. So once the model gets trained, it can start making a prediction or decision when new data is given to it. So let's take this example. So over here, we are training this machine by giving it samples of data. So over here, the data is nothing but different images of apple. And along with each image of apple, we are also giving it the label of the image, right? So this image goes with its label, which is apple. Again, this image goes with its label, which is apple. Again, the same with these two, right? So we are teaching this machine that whenever it sees an image something like this, it is nothing but an apple. And after time, when we give it a new data, from whatever learning it has done, it will predict whether it's an apple or not. So on the basis of its learning, this machine predicts that there is a good possibility. There is actually 97% possibility that the image which has been fed to the machine is nothing but an apple. So a use case of supervised learning could be spam classifier. So spam classifier basically means that whether the email which we get it's a spam or not, and that is done on the basis of different textual parameters. So let's say a genuine email wouldn't contain too many exclamation marks, it wouldn't contain a catchy headline and so on. But on the other hand, if it's a spam email, maybe it will contain a lot of exclamation marks with maybe a lot of numbers, and it'll have statements like, hey, congrats, you've won a lottery, or hey, could you help me out? So this spam classification is basically an example of supervised learning. Then we have unsupervised learning. So in unsupervised learning, the model learns through observation and finds structures in the data. So once the model is given a data set, it automatically finds patterns and relationships in the data set by creating clusters in it. So what it cannot do is add labels to the cluster. Like it cannot say this is a group of apples or mangoes, but it will separate all the apples from mangoes. So over here, we have this set of images. Now, this unsupervised learning model which is applied on this, it will segregate these fruits on the basis of similar characteristics. So over here, we have segregated these four into one cluster, these three into second cluster, and these three into the third cluster. Now, even though the unsupervised learning does not have any labels, it has still segregated these three into three clusters, right? So the machine over here does not know that these are apples or these are oranges or these are bananas. Yet it has segregated these three on the basis of similarity of characteristics. So it found out that these four objects are similar to each other, and there is quite a bit of variability when it comes to these four objects and these three objects. Similarly, this machine was able to figure out that these three objects, they are quite similar to each other. But when compared with these three objects, they are very dissimilar. So this is the underlying concept of unsupervised learning. And a good example of unsupervised learning would be again Netflix movie recommendation. So over here, the movies are segregated on the basis of different genres. So over here, TV series like Friends, How I Met Your Mother, and Silicon Valley are clustered into one group because those come into the same category. Similarly, movies such as Secret Superstar and Dangal could come under the same category because they have the same lead actors. So over here, we are segregating the movies on the basis of similar characteristics, even though there are no labels in it. And it's finally time for the third machine learning type, which is reinforcement learning. So over here, there is an agent and there is an environment, and the agent interacts with the environment and finds out what is the best outcome for it. So it basically follows the concept of hit and trial method. The agent is rewarded or penalized with a point for a correct or a wrong answer. And on the basis of positive reward points gained, the model trains itself. So let's take this example. So over here, this self-driving car would be our agent and the road is the environment. And this car is interacting with this environment. So it will observe the environment and it has two choices over here. So either to go straight or turn right. Now, let's say this agent or the self-driving car decides to go straight. Then what happens is it goes and bangs straight into this barricade. So then it realizes that the action taken by it was not in its best interest, and that is why it is penalized. So since it is penalized, it realizes that the action taken by it was wrong, and that is why from the next time onwards, it will do the opposite action. So instead of going straight, it will take the right turn. And when it takes the right turn, it realizes that the road is correct and the agent is rewarded. So this is how reinforcement learning basically works. So the agent interacts with the environment, it takes an action, and if the action turns out to be incorrect, it is penalized. And if the action turns out to be correct, it is rewarded. So this cycle goes on and on till it completely learns its environment properly. And the best use case of reinforcement learning is again self-driving car. So companies such as Tesla and Google are working on these self-driving cars. So just to sum it off, these are the three different types of machine learning algorithms. So we have supervised, unsupervised, and reinforcement machine learning. So under supervised, we have regression and classification, and in unsupervised, we have clustering techniques, association analysis, and hidden macro model. And then the third is obviously reinforcement learning, which works on trial and error method. And if you want to do some really cool machine learning projects, you can check the sites out. Now let's look at some limitations of machine learning. So when it comes to machine learning algorithms, they would require massive stores of training data. So again, as I've told you, machine learning is totally based on the data which it has. So if you have more amount of data, only then it will be able to give correct accuracy. So let's say you take in very small amount of data, and there's a good possibility that the results which you're getting are very biased or very incorrect. And also, error diagnosis is quite difficult when it comes to machine learning, because again, the amount of data is very huge, and wherever there's a mistake, you'd have to go through the entire algorithm which you've written and then find out that particular mistake by yourself, which is very difficult. And also when it comes to machine learning algorithms, they're not really that creative. So these ML algorithms are built only for one specific purpose. So let's say I'll build a machine learning model which will predict whether it will rain or not today. Now, if I want to use the same model to predict the stock prices, that will not work, right? So basically one model is built only for one particular task. So this is the lack of creativity that I'm talking about when it comes to machine learning. And also there are a lot of time constraints as the model has to learn through a lot of historical data. So that was everything about machine learning. Now let's start off with deep learning. So deep learning is a subset of machine learning where it learns through data representations as opposed to task-specific algorithms. So we saw that the drawback in machine learning models was that the models are specific to only one particular task. But this is not the case with deep learning models, as these deep learning models are based on the data representations. And these deep learning models are mostly built with something known as deep neural networks. So this is how a deep neural network looks like. So these deep neural networks completely learn the data which is fed to it. So this is the data. So let's see if this image of woman is fed as the data to the deep learning model, then it will completely extract all the features of this data by itself. Again, the difference between ML and deep learning over here is that the feature extraction in machine learning is manual. But when it comes to deep learning, the feature extraction is automatic. So the deep learning model automatically extracts all of the features associated with that image. And when new images are fed to it, it automatically is able to tell whether the image is same to this or not. So this over here we have a graph which tells us how does performance vary with respect to the amount of data. So what happens in machine learning is that as we keep on increasing the data, the performance increases only up to a particular threshold. After that, if we increase any more data, there is no increase in performance. So this is another problem when it comes to machine learning. But on the other hand, when it comes to deep learning, the more amount of data you give it, the better will be its performance. And that again is because deep learning is based on learning data interpretation. So the more data you give it, it will automatically learn all those features of the data by itself and it will be keep on increasing its performance gradually. Now let's look at some applications of deep learning. So speech recognition is one application of deep learning. Now you need to understand that you cannot build speech recognition applications with machine learning. So this is where machine learning fails and deep learning comes in and helps you to build speech recognition applications. Also another application of deep learning is self-driving cars. So we see over here that the person is just sitting. He is not even touching the steering wheel and the car is driving by itself. So just an amazing application of deep learning. And then we have language translation over here. So this again is a part of deep learning. So over here we are typing something in Spanish and it is being automatically converted into English. So we also have visual translation over here. So over here this text or this board is in some random language and this app over here which uses deep learning automatically converts this visual into English. So those were some applications of deep learning. Now let's actually understand how does deep learning work. So most deep learning methods use neural network architectures, and that is why deep learning models are often referred to as deep neural networks. So a deep neural network basically has these three models: an input layer, the hidden layers, and the output layer. And the term deep usually refers to the number of hidden layers in the neural network. So traditionally, neural networks only contain 2 to 3 hidden layers, while deep networks can have as many as 150 hidden layers. Now that's a very huge amount, isn't it? So deep learning models are trained by using large sets of labeled data and neural network architectures that learn features directly from the data without the need for manual feature extraction. So all of the input data is given to this input layer and this input layer automatically extracts the features by itself. Now, that data is sent to this hidden layer which performs all sorts of processing tasks, and then the final result is given out through the output layer. So now let's also understand what exactly is a neural network. So a neural network is a computing model whose layered structure resembles the network structure of neurons in the brain with layers of connected nodes. So it can learn from data which can be trained to recognize patterns, classify data, and forecast future events. So the neural network is based on the biological neural network of our brain. So that is why it is given the name neural network. So the layers are interconnected via nodes or neurons, with each layer using the output of the previous layer as its input. So its main function is to receive a set of inputs, perform calculations, and then use the output to solve the problem. Now, as I've already said, these artificial neural networks are based on something known as a biological neural network. So, our biological neural network has dendrites, cell body, and axon. So dendrites are where the input is taken, cell body is where the processing is done, and axon is where the message is transferred to other neurons. And the same thing happens in artificial neural network as well. So first we give in the data, that data is processed, and then the final processed result is given out as the output. So over here, let's say we train the data with images of cat, and the labels would be either cat or not cat. After that, we give in a new image of a cat, and then we basically try to predict whether the model correctly classifies this as cat or not cat. And since the model has learned the data properly, it correctly classifies this image as cat. Now, to implement these artificial neural networks, we would need the help of a deep learning framework. So the first question to pop into your head would be, what are the different deep learning frameworks available? So TensorFlow is arguably one of the best deep learning frameworks that we have today. It is an open source software library developed by the researchers and engineers from the Google Brain team for high performance numerical computation. One well-known use case of TensorFlow is Google Translate. So Google Translate is coupled with capabilities such as natural language processing, text classification, forecasting, and tagging. So TensorFlow basically comes with two tools, TensorBoard and TensorFlow Serving. So building massive deep neural networks could be complex and confusing. This is where we can use TensorBoard to visualize our TensorFlow graph and plot quantitative metrics. And then we have TensorFlow Serving, which is a flexible, high-performance serving system and can be used for rapid deployment of new algorithms while retaining the same server architecture and APIs. So now let's look at the next deep learning framework, which is Keras. So Keras is actually a high-level API which can run on top of other deep learning libraries such as TensorFlow, Theano, or CNTK. And with the help of Keras, we can implement both convolutional neural networks as well as recurrent neural networks. And the best thing about Keras is, model building is extremely easy. It's like stacking layers on top of each other. So next, we have PyTorch, which is a scientific computing framework developed by Facebook. So we can get from the name itself that PyTorch is Pythonic in nature. That is, it can leverage all the services and functionalities offered by the Python environment and also smoothly integrates with the Python data science stack. Another great feature of PyTorch is that it offers dynamic computational graphs which can be changed during runtime. This is highly useful when we have no idea how much memory will be required for creating a neural network model. And the next deep learning framework is DL4j. So unlike deep learning frameworks which we saw till now, which were all based on Python, Deep Learning 4j is a deep learning programming library which is written for Java and the Java virtual machine. And the biggest advantage of DL4j is it includes inbuilt integration with Apache Hadoop and Spark. So it helps in getting state-of-the-art results on image recognition tasks. So it shows matchless potential for image recognition, fraud detection, text mining, parts of speech tagging, and also natural language processing. And finally, we have MXNet. So MXNet is a deep learning framework developed by Apache Software Foundation specifically for the purpose of high efficiency, productivity, and flexibility. And the beauty of MXNet is that it gives users the ability to code in a variety of programming languages, such as Python, R, Julia, and Scala. This means that you can train your deep learning models with whichever language you're comfortable in without having to learn something new from scratch. And this deep learning framework is known for its capabilities in imaging, speech recognition, forecasting, and NLP. So when you hear the term TensorFlow, the first question to pop into your head would be, what exactly is a tensor? So in TensorFlow, data is represented in the form of tensors. Simply put, a tensor is a multi-dimensional array in which data is stored. So you can consider these tensors to be the building blocks in TensorFlow. Now, these very tensors are given as the input to the neural network. So as I've said, a tensor is nothing but an n-dimensional array. So the number of dimensions used to represent the data is known as its rank. So if a tensor has just one element, in other words, if it has just magnitude and no direction, then its rank will be 0. If a tensor has magnitude and direction in one plane, then its rank will be 1. Similarly, if a tensor has magnitude and direction in two planes, then its rank will be 2. And this goes on higher up the order. Now, TensorFlow, as the name states, is a combination of two words, tensor and flow. Here, the data is stored in tensors, but the execution is done in the form of a graph. So this is not like your traditional programming where you just write a bunch of lines and everything gets executed in sequence. So first, you'd have to prepare this computational graph, and then this computational graph is executed inside something known as a session. Now, in this computational graph, all the mathematical operations are depicted inside the nodes, and all the tensors are represented on the edges. So the entire computation process is done in two stages. In the first step, the code is depicted onto the computational graph, and in the second step, a new session environment is started and the graph is executed inside this session. So that was all about the computational graph. Now let's look at the program elements in TensorFlow. So we have three program elements: constant, placeholder, and variable. So let's start with constants. So constants are program elements whose value does not change, or in other words, the value is fixed. So let's head on to Jupyter Notebook and work with these constants. Right, so my first task would be to import the TensorFlow framework. So I'll type import TensorFlow as TF. I'll click run. So let me just wait till the import is done. Right, so we have successfully imported the TensorFlow framework. Now, as I've said, let's go ahead and start working with the constants. So let me just type in constants over here. So I'll create the first constant and name this constant as con1. Now this is how we can create constants in TensorFlow. So I will use this TF and then put in a dot and then type in constant. Now inside this, I will give the value of the constant. So let's say the value is 10. So this is an integer type constant. Now similarly, I'll also create a floating type constant and I'll store this in con2. So I'll type tf dot constant and the floating value would be 3.14. Now after this, I'll create a string type constant. So again, this would be tf dot constant and the string which I'd be giving would be this is Spara. And finally, we have a Boolean type constant and I'll store this in con4. So this will be tf dot constant and let's say the value is false. Now I'll run. Now let me print all of these values. So I'll use the print function and then I'll go ahead and print all of these values, con3, con4. Right. So we see that this first constant is a tensor of type integer. This second constant is a tensor of type float. This third constant is a tensor of type string, and this fourth constant is a tensor of type boolean. Now we see that we only have the data types of all of these tensors, but we don't have their values. This is because, as I've already told you guys, we have to create a computational graph and then execute that computational graph inside a session. But till now, we have not started our session. So let's go ahead and start a session first. So I'll type sys equals tf dot session and I'll hit run. Now I will run all of these inside this session. So I will type sys dot run and let me go ahead and run all of these con1, con2, con3 and con4. So this time we have the values of all of these tensors. So the value of constant 1 is 10, the value of constant 2 is 3.14, the value of constant 3 is this is Sparta, and finally the value of constant 4 is false, right? So first we'd have to create all of the constants, then we'd have to create a session, and inside this session we'd have to run all of these constants. Now let me go ahead and perform some simple operations on all of these constants. So let me just type in operations over here. So I'll do a simple addition operation. So I'll type addition over here. And let's say the value of the first constant is 20. I'll put a plus symbol and then I'll take in the next constant and the value of the second constant would be 30. So I am basically adding two TensorFlow constants. The value of the first constant is 20, the value of the second constant is 30, and I'm storing that result in addition. Similarly, I will multiply these two constants now. So multiplication tf dot constant. So I'll give the value of 20. Now I'll put the asterisk symbol and then this would be tf dot constant of 30. So this time I'm multiplying these two values, right? So I'll hit on run. So now again, if I'd have to see the resultant addition and multiplication values, I'd have to run these two inside a session. So I'll type sys dot run and then put in these two values over here, addition and multiplication, right? So we see that 20 plus 30 gives us an addition value of 50. And similarly, when we multiply 20 with 30, we get a result of 600. Right. Now, so this was basic operation with scalars. And we already know that tensors can have higher dimensions. So let's go ahead and perform addition and multiplication with these higher dimension tensors. Right. So again, I'll just put in addition over here. And I will take in the first constant. And inside this, I will give in a list of values. So let's say I will take in 1, 2, 3, 4 and 5 and I will add this list with the next constant. And this time the second constant has the values of 5, 4, 3, 2 and 1. Similarly, I'll also multiply. So multiplication equals tf dot constant. And this will have values, let's say the same values 1, 2, 3, 4 and 5. Let me put a comma over here. Right. Now I'll put the asterisk symbol. Again, I'll type tf dot constant and I will give in the list of the values 5, 4, 3, 2 and 1. Now I'll hit run. Again, I need to run these two inside a session. So sys dot run. Let me put in addition over here. After that, I would also need the multiplication value. Right, so this is a result. So when we add 1 plus 5, we get 6. When we add 2 plus 4, we get 6. Similarly, when we add each of the corresponding elements with these elements inside the list, we get all of the 6s over here. Now let's take this multiplication result. So over here, when we multiply 1 with 5, we get 5. When we multiply 2 with 4, we get 8. 3 cross 3 gives us 9. 4 cross 2 gives us 8. And again, 5 cross 1 gives us a 5. So this was addition and multiplication with respect to lists. Now let me also do a simple operation on strings. So let me take in the first string and name it as str1. So this is a constant. So tf dot constant. And let's say I type over here, I love, and then I give a space. Now I will take in the second string, which would be str2. And inside this, and again, this would be a constant. So tf dot constant, and the value of this constant would be TensorFlow. Right. Now I will run this and let me execute this inside a session. So ses dot run of str1 plus str2. So the result which you get is I love TensorFlow, right? So the first string is I love, and then there's a space, and the second string is TensorFlow. So when I add these two strings, the resultant is I love TensorFlow, right? So that was all about constants. And then we have placeholders. So when it comes to placeholders, we don't have to provide an initial value and can specify it during the runtime. So this allows us to build our computational graph without needing the data. And this is how we can create placeholders. So tf.placeholder is the syntax, and inside that we just give the data type of the variable which we will substitute later on during execution. So let's head back to Jupyter and work with these placeholders. So let me just type in placeholder over here. So let me create my first placeholder. So I'll name that as A, and tf dot placeholder, and this would be of integer type. So tf dot int 32. Now I will create another variable which would be b, and the value of b would be actually a cross 2. So let me run this. Now I will run these two inside a session. So ses dot run, and I want to see the result of b. So I'll put in b over here. Now since we know that a placeholder takes in a value during runtime, so this is when I'll feed the value to this placeholder a over here. Now to do that, I would have to create something known as a feed dictionary. So feed dict equals, let me create a dictionary over here. So it would be a, and the value which I'll be giving to a would be, let's say, 5. Now let me run this and let's see what do we get. Right. So during the execution time, I have assigned a value of 5 to a. And when we multiply this 5 with 2 over here, we get the value of b, which is 10. Right? So all of this is happening during runtime because with the help of a placeholder, we can assign it a value during execution. Now, similarly, let me go ahead and give a list of values over here. So instead of 5, let me give the list of values 1, 2, 3, 4, and 5. Now I'll run this. So over here, 1 cross 2 gives us 2, 2 cross 2 gives us 4, 3 cross 2 is 6, 4 cross 2 is 8, and 5 cross 2 is 10. So you get an array of values during runtime. Now similarly, let me also create a placeholder for strings. So I'll type string placeholder over here. So now let me create this variable and name this as string name, and this would be your placeholder. So tf dot placeholder, and I am taking in a string. So tf dot string. Right. Now let me create another string over here. So the name of this string would be my name, and let's say the value of the string is I am. All right. Now let me run this. And I'll execute this inside a session. Ses dot run, and I want the result of my name when I add it with respect to string name. Now let me also create a placeholder for strings. So I'll just type string placeholder, and let me create the first placeholder. So I'll name that as str1 name, and since this is a placeholder, tf dot placeholder, and I will be giving in a string during execution time. Now I'll also create another string value over here and name that to be my name, and the value of this string is I am, and then I'll give a space. Right, so now I'll hit run and let me execute this inside a session. Now let me also create a placeholder for strings. So this will be string placeholder. Right, so let me create this placeholder. I'll name this as str name, and since this is a placeholder, I need to use tf.placeholder, and I will be assigning a string to this during execution time. Now I will also create another string which would be my name, and this would be equal to I am, and there's a space, and I will be adding this with str name. So let me hit run. Right, now I'll execute this inside a session. So for that, I'll type sys.run, and I want the result of my name. So I'll just put in my name over here, and then I'll provide the feed dictionary. Feed dict equal to, let me put in the dictionary over here, and I will assign the values of str name over here. Right. So the values of str name would be Sam, Bob, and Charlie. Now let me hit run and let's see what do we get. Right. So what we are basically doing is we are adding this with the placeholder value over here, and we are giving the values during the execution time. So I am Sam, I am Bob, and I am Charlie. Now these three values are coming from this feed dictionary during the runtime. Right. So this is all about placeholders. And finally, we have variables. So a variable is just a program element which allows us to add new trainable parameters to the graph. And this is the syntax to create a variable. tf.variable, and then we give the value, or we initialize the value, and then we specify the data type of that variable. Right, so let's head back to Jupyter now. I'll just type in variables over here. Right, so let me create my first variable, and the name of that variable would be var1. And we can create a variable like this, tf.variable. So guys, you need to keep in mind that this v over here is actually capital. Right. So now after this, I would have to assign a value to it. So let's say I assign this variable a value of 20. And this is of integer type. So tf.int32. I'll run this. Now another thing to be kept in mind is whenever we are declaring values in TensorFlow, they have to be initialized. So this is how we can initialize all of the variables. So we have something known as global variable initializer, and when we invoke this function, all of the variables which we have declared would be initialized. I'll hit run. So now let me execute this inside a session. So sys.run of init, and I have initialized this variable over here. Now let me also go ahead and run that variable, sys.run var1. Right. So we have the result of var1, which is 20. Now, since this is a variable, the value of a variable can be actually updated. So let me go ahead and update the value of this. So I will name this as updated var1, and the function would be tf.assign. And inside this, the first parameter would be the variable which I'd want to update. And after that, I need to give the value to which I'd want to update this. So I want to make this value of 20 to 25. Right. Now I will run this. So now this is actually a variable. We can actually update the values. So let me go ahead and do that. So the name of the updated variable would be, let's say, updated var1. And the function for that would be tf.assign. And this takes in two parameters. The first parameter would be the variable which we are supposed to update. And the second parameter would be the value to which we are updating it. So I want to make this 20 to 25. I'll hit run. Right now, let me run this inside a session. Sys.run. And I need to pass in the variable which would be updated var1. Let me make it small v over here. I'll run this. Right. So initially the value of var1 was 20, but we have updated it and made its value to be 25. Now let's also go ahead and create a small linear model. So let me just type in linear model over here, and this is how our linear model would look like. Wx plus b, where w and b would be variables and x would be a placeholder. Right, so let me start off by creating w. So w is a variable, so w would be equal to tf dot variable, and I am initializing it with a value of, let's say, 10, and this is of integer type. So this would be tf dot int 32. Now similarly, I will also assign the value for b. So b is also a variable and its initial value would be 5, and this is also of integer type. And finally we have x, which is a placeholder. So x is equal to tf dot placeholder. And since placeholder does not actually take an initial value, it just takes a data type. So the data type is again tf dot int 32. So I'll run this, and now what I'll do is I will multiply w with x and add b to it. So the equation would be w cross x plus b, and I will store it in a variable and name that variable to be linear model. Right, so this is w cross x plus b. I'll run this. Now again, if I have to execute this, I have to run this inside a session. And since also I have created two new variables, I'd have to initialize them first. So init1 equals tf dot global variables initializer. I'll hit run. So now I will create a session. So sys dot run, and I will execute init1 first. So I have successfully initialized these two variables w and x. Now I can go ahead and run this linear model. Sys dot run. Now I would want the result of linear model. So linear model, and then I will use the feed dictionary. Now inside this feed dictionary, I would have to assign a value to this placeholder x. So x equal to, let's say I give a list of values over here, and the list of values would be 1, 2, 3, 4, and 5. Now I'll run this and let's see what do we get. Right. So if the value of x is 1, we get 15. So this basically means that 10 into 1 plus 5, which is 15. Now after that, if the value of x is 2, so this would mean 10 into 2 plus 5, which is 25. Similarly, if x is 3, that would mean 10 into 3, which is 30, plus 5 is 35, right? And same is the case for 4 and 5.
So these two commands will update your TensorFlow version for the CPU and the GPU both in your Jupyter notebook. And once you have updated your TensorFlow, now we'll import the TensorFlow package or the library as TF. And if you run this command, your TensorFlow package will be imported into the Jupyter notebook. And once you have imported the TensorFlow into Jupyter notebook, now we'll verify whether the version of the TensorFlow that we're using is 2.0 or not. So we'll use the print. So we'll print tf dot underscore version underscore underscore. So once you print this line, you will see that we have the latest version, which is 2.0.0. And once you are sure that you are using the version 2.0, so now we'll move ahead and build some tensors. So a tensor is just a fancy name for an n-dimensional array, and you can also think of it as a general representation of a vector in higher dimensions. So we'll start by making a constant tensor, which means that its value cannot be changed later on. So we'll use the tf.constant method. So if you run this particular line here, and if you press shift and tab here, so it will open this documentation where you can check different attributes of this particular method. So the first is your value. The first attribute is the value, or the parameter is the value, where you put the value of your tensor. So here we have passed a string hello, and you can also mention the data type of the value that you're passing, and also the shape that you're passing if it is a multi-dimensional tensor, and it will create a constant tensor for you. So we have passed hello, so it will automatically create a string tensor for us. So once you run this, and we have stored the tensor in hello, and if you check now the type of the tensor, so you will see that it is not a string, it is a tensor object. And before in TensorFlow 1, if you wanted to print the value of this particular string, you would have to create a session. But in TensorFlow 2.0, our sessions are not valid now. So if you want to just print the value of a tensor, we can directly print it using the tf.print function. So this function will print the value of any string or the tensor that we have built. So if I use tf.print and I pass my tensor to it, so it will print the value that is actually contained in that particular tensor. So now let's create another tensor using tf.constant, which is a constant tensor, and we'll pass the string world to it, and we'll store the tensor in world. And now let's print the world tensor using the tf.print. So now we have two tensors, hello and world. And before, if you wanted to perform any operations on tensors, you would have to create a session, and inside this session you have to add or perform different operations. So now we can directly perform operations on tensors. So we'll perform the addition, we'll concatenate these two strings which are contained in hello and world tensor, and we'll store the result in result, and then we'll print the result. So you can see that our result is hello world. So it means we do not have to create a session in order to perform different operations on these tensors. So now let's move ahead and create a tensor which contains a numeric variable. So we'll pass numeric value as 10, and we'll store the tensor in A, and then we'll create another tensor, constant tensor with value 20. And now we'll perform the addition operation on these tensors without using a session. So once you perform the addition operation, it will display you this particular tensor object. So it will not actually display you the actual value of this particular operation. And here you can see, if you run this operation multiple times, so every time the ID here will be different. So the TensorFlow implicitly stores different functions or operations as IDs. So now if you want to print the value of this particular operation on these tensors, so you can use tf.print again. So once you use tf.print and you will pass the operation that you want to perform, so it will directly print you the value of that particular operation performed on these two tensors. So now let's build another tensor using the fill method. So if you run this command first and then you press shift and tab, so this will open this documentation, and this fill command or the fill method will create a tensor which is filled with a scalar value. So you have to pass a value, and it will create a tensor with the following dimensions. So here we have passed the dimensions as 5 by 5, so it will create a tensor with 5 rows and 5 columns, which are the dim's argument, and then we have to pass the value. So we want a 5 by 5 tensor which will contain the value 5. And if you want to print this particular tensor, so you can use the tf.print method, so it will print the value of this particular tensor. And you can also print this value as the numpy array. You just have to write the value, the name of your tensor, and then you can use the numpy method. So once you run this, it will represent your tensor, or it will display your tensor as a numpy array. So now let's build another tensor using the constant method. So we'll build a two-dimensional tensor. So it will be a tensor with 2 rows and 2 columns. And once we run this, we'll build a tensor. And now if you want to know how many rows and columns are there in your tensor, and that is the shape of your tensor, so you can use the get shape method. So if you use the get shape method, it will display you the number of rows and the columns present in your tensor. Clearly we can see that we have 2 rows and 2 columns in our tensor. And similarly, if you create this particular tensor which has 2 rows and 1 column, and to get the shape of this tensor, so it will be displayed as 2 rows and 1 column. So now we can also create random numbers using tensors. So we'll create a tensor which contains normal distribution or random numbers from the normal distribution. So we'll use the random.normal method. So in this method we'll pass the dimensions, and then we'll pass our mean and the standard deviation. So if you press shift and tab here, so it will, first of all, the first argument will be your shape, and then your mean of this particular normal distribution and your standard deviation of the normal distribution. So we want a 4 by 4 tensor which will contain 4 rows and 4 columns, and then we want the mean to be 0 and the standard deviation should be 1. So it will be a standard normal distribution. So once you run this and you store the tensor in my tensor, and now if you print the value of tensor, you will see that we have 4 rows and 4 columns in this particular tensor, and the numbers are from the standard normal distribution. So now let's discuss what do we mean by eager execution that is implemented in TensorFlow 2.0. So if you talk about TensorFlow 1.0 or 1.x, so it requires you to manually build a syntax tree, which is also called the graph, using different API calls. And then when you build a graph, then you have to manually compile the graph, and you have to pass the set of input and output tensors in the sessions.run function. But in TensorFlow 2.0, we execute eagerly, which means it executes like a normal Python programming language, that is line by line. So you don't have to create sessions, and your code will be executed line by line. So if you want to know more about the effective changes that have been made to TensorFlow 1 in TensorFlow 2, so you can go to the following link, and if you go to the following link, you will find a whole documentation that discusses different changes that have been made to TensorFlow 1 to migrate to TensorFlow 2. So now let's move ahead, and after performing this, we'll first of all check whether we are running eager execution or not. So in TensorFlow 2, this is the default execution, eager execution, and if you want to enable eager execution in other versions of TensorFlow, so you can use these commands. So first of all, we'll check whether the eager execution is enabled or not. So we'll use the if function here. So we'll pass our tf dot executing eagerly, and if this is true, it means we are running eagerly. So if it is true, it will print eager execution is enabled, and then if it is not true, then it will print that you are not running eager execution, and we'll also print how to run and how to enable and disable eager execution. So right now eager execution is enabled, and if you print this code here, and if your eager execution is off, so it means if you want to disable your eager execution, so you can run the following command. So you have to import this particular module from this particular package, and then you can use the disable eager execution function or the method to disable your eager execution. And if your eager execution is already turned off, and if you want to turn it on, so you can use this particular command here. So using this command, you can enable your eager execution, and if your TensorFlow is not updated, so you can use these two lines to update your TensorFlow to the latest version, that is 2.0. So now let's move ahead and perform simple operations using TensorFlow 2. So there are some of the common operations that we'll use while using TensorFlow 2. We'll make tensors using constant tf.constant and tf variable, and then we'll concatenate two tensors, and we'll make tensors using zeros and ones, and then we'll also learn how to reshape tensors, and we'll also learn how to cast tensors from one data type to another data type. So we'll start by making a constant tensor. So a constant tensor is a tensor that does not change. So we'll use the tf.constant again, and it is a tensor that has 3 rows and 2 columns. So the shape of this tensor will be 3 and 2, and once you run this command, your tensor will be stored in A. And if you want to print this tensor, there are two methods. So if you want to print the values of this tensor, so you can use the tf.print method, and you can pass your tensor value to it. And if you want it as a numpy array, so you can use the .numpy method to print the value of this tensor as a numpy array. This mostly represents the values of the weights of the inputs in our neural network. So we'll use the tf.variable method to create a tensor which is a variable tensor. So we'll create a tensor which has 2 rows and 2 columns, and we'll store the tensor in VA, which is a variable tensor, and then we'll create another constant tensor which has 3 rows and 2 columns. So the shape of the tensor is 3, 2, and we'll store the result in B. And then if you want to print B, so you can use tf.print, so it will print your B directly without running any session. So now let's move ahead and perform the concatenation of tensors using the tf.concat. So we'll create a concatenated tensor AB concatenated, and we'll concatenate values from the tensors A and B. So if you write x is equals 1, so the tensors will be concatenated according to the columns. So the new tensor will contain the columns from the two tensors that we have concatenated, that is A and B. And after we concatenate these two values, and if you press shift and tab here, so it will open the documentation, and in the documentation you can see that we have to firstly pass the values of the tensors, and then axis here represents the row or the column fashion. So if the axis value is 1, so our new tensor will have concatenated columns, and if the axis value is 0, so our concatenation will happen according to the rows. And after this we'll print the value of the concatenated tensors. So we'll write this f string. So in Python, this f string, which is started by writing f and then writing your string, so it will contain your Python expressions. So inside the f string, if you want to pass any variable, so you have to write your string, and then using these braces or using these brackets, inside the brackets you have to write the name of your variable. And once you run this command, so your tensors will be printed. So now you can see we have concatenated two tensors, that is A and B, and both tensors were, the A tensor was this particular tensor with 3 rows and 3 columns, and the B tensor was this tensor which is also having 3 rows and 3 columns. And we have concatenated these two tensors column wise. So the first 2 columns are of tensor A, and the second 2 columns are of tensor B. And now we'll see how to concatenate tensors according to rows. So inside the tf.concat function, you have to just write x is equals 0, and the values are of the tensors A and B. And once you run this code and you print the value of the tensor using the f string, so once you run this code, your tensors will be concatenated according to the rows. So the first 3 rows represent the tensor A, and the last 3 rows represents the tensor B. So now let's move ahead and make tensors using tf0s and tf1s. So we use TF0s to make tensors that contain zeros of a particular shape, and TF1s to create tensors of containing ones of a particular shape. So we'll use TF0s to contain or to make a tensor which is filled with zeros. And inside the tensor, if you run this particular code and then press shift and tab here, and inside this function you can see we have our shape argument where you can mention the shape of your tensor. So the first argument will be your row and the second argument will be your column, and you can also mention the data type of your tensor. So here we are creating a a tensor filled with zeros with 2 rows and 4 columns, and the data type of those zeros will be integer 32. So our 32-bit integers will be 2 rows and 4 columns. And once you make this tensor and store the value in tensor, and then you print the value of this particular tensor using the f string here, and since we have printed it as a numpy array using the dot numpy or the numpy method, so our tensor will look like this, which has 2 rows and 4 columns containing zeros. So now let's move ahead and make tensors using tf.ones. So tf.ones are used to make tensors with a particular shape containing ones. So we'll use tf.ones method and we'll pass the shape of our tensor, which is 4 rows and 5 columns here. And then we have also passed the data type of our tensor, which is float 32. So once you print this tensor using the f string, you will see that we have a tensor which contains 4 rows and 5 columns containing the float 32 type of number. So now let's move ahead and use tf.reshape to reshape our tensors. So later on in this course you will see that a lot of times we will have to reshape different tensors so that we can pass those to our neural networks as features. So we'll first of all create a tensor for reshaping. So this tensor is a constant tensor and it contains 4 rows and 3 columns. And first of all we'll build this tensor, and after making this tensor we'll reshape it. So we can reshape it in the following way. So we'll use the tf.reshape method, and then we have to pass the value of our tensor that we want to reshape. And if you press shift and tab here, so it will open this documentation where you can see the first value is your tensor and then the shape that you want to reshape it into. So firstly our tensor is this tensor particular, and then the shape that we want to reshape it into is 1 row and 12 columns. Since we have total of 12 elements in our particular tensor, so according to that we would have 1 row and 12 columns. So once you run this code, your tensor will be reshaped, and then now we'll print both the tensors, that is before reshaping and after reshaping using the f strings. So now here you can see that we have our tensor which was before reshaping, and now this is our tensor which contains 1 row and 12 columns after using the tf.reshape function. So now let's move ahead and use tf.cast method to cast one type of tensor into another type of tensor. So first of all we'll create a tensor which will contain values of 32-bit float type, and then we'll convert into a 32-bit integer values. So first of all let's create a tensor using tf.constant, which is a constant tensor. So this tensor contains 4 rows and 3 columns, and all of these numbers are floating point numbers which are 32-bit numbers. Then we'll first use the tf.cast method, and if you press shift and tab here, and the first argument is your tensor that you want to cast, and then your data type of the tensor that you want to cast it into. So we'll cast our tensor, which is tensor here, and then we'll cast it into a variable or a tensor which will contain values of 32-bit integers, and we'll store the result as tensors as int tensor. And once we have this tensor, we can use the f string to print both the tensors, that is before converting and after converting or casting. So we have just removed the decimal numbers, we have not rounded the numbers. So here you can see the 8.8 is converted to 8 because we have just removed these floating points without actually rounding these numbers. So now let's move forward and perform some linear algebra operations on tensors. So we'll start by first of all transposing a tensor. So we'll first of all create a tensor using tf.constant. So this tensor contains 2 rows and 3 columns and with different values. So when we transpose a tensor, we'll convert our rows to columns and columns to rows. So our first row will be converted to first column and our second row will be converted to second column. So we'll use the tf.transpose method and we'll pass our tensor value, that is a. So once we print this value using the f string, so we'll get our transposed tensor, that is a, with the first row of the original matrix as, or the first row of the original tensor as the first column and the second row of the original tensor as the second column. So now let's move ahead and implement matrix multiplication, which we'll use throughout the course, and most of the optimization algorithms also use matrix multiplication. So first of all, we'll create two tensors, or first of all we'll create a matrix and a vector v. So these both are two tensors. So our first tensor is a constant tensor that has 2 rows and 2 columns, and our second tensor is a vector which has only 2 rows and only 1 column. So we'll multiply these two matrices or these two tensors using matrix multiplication, and if you know the rules of the matrix multiplication, so you'll get this particular result. And we'll use tf dot matmul function. So we'll pass our two tensors, and this order is also very important. So our first tensor is a 2 by 2 and our second tensor is also 2 by 1. So our resulting tensor will be 2 by 1 according to matrix multiplication. So once we print the result, which we have stored in AV using the F string, and we have passed our expression AV inside the F string, so we'll get this particular tensor which has 2 rows and 1 column. That is the result of the matrix multiplication between A and V. And now we'll perform element wise multiplication, and we'll see how they are different. So we'll compare both matrix multiplication and element wise multiplication, and we can see both are different because the rules of matrix multiplication are different from element wise multiplication. So we use the same two matrices or the tensors, that is A and V, and we'll use the tf dot multiply, and the tf dot multiply used to multiply two tensors element wise. So we'll store the result in AV, and then we'll print the result using the F string, and our AV is our expression that we have passed inside the F string. So once we print this, we'll get this result which is totally different from what we got for matrix multiplication. This is our element wise multiplication of A and V, and here also the order of these tensors matters, the way we pass it into our multiply function or the matmul function. So now let's move ahead and see how to calculate or how to compute the identity matrix of a particular tensor. So identity matrix of a matrix is a matrix which when multiply with a particular matrix, it will result in the same matrix that we have multiplied it with. So if we have a matrix A, and if you multiply through the matrix multiplication an identity matrix of that particular matrix, then we'll get the result as the same matrix A. So here our matrix A, which is a tensor, we have created using the tf dot constant, and it has 2 rows and 2 columns. And now we'll calculate the number of rows and the number of columns that we have in our tensor using the shape attribute. So we'll use the a dot shape attribute of our tensor, and we'll assign the two values, that is 2 which is the number of rows and 2 which is the number of columns, and we'll print it using the F string. And now we know the number of rows and number of columns in our matrix. So now we'll create an identity matrix using the tf dot eye method. So in this method we can pass different arguments. So firstly we'll pass the number of rows argument as rows here, which is 2, and then number of columns argument as columns, which is 2, and then we'll pass the data type of our values that will be containing in our identity matrix, that is 32-bit integer, and then we'll store the result in A identity, and then we'll print the value of A identity using the numpy array. So it will be represented as a numpy array, and here you can see we have an identity matrix 1001. So an identity matrix contains 1 on the main diagonal and all other elements are 0. So now let's confirm whether this is an identity matrix or not. So we'll first of all multiply both the matrices, that is A and the identity matrix of A, and if the resulting matrix is A, then we can say that we have successfully computed the identity matrix for a particular tensor, that is A here. So we'll use the same matmul method. So we'll pass our both tensors, that is A and A identity, and then we'll store the result in AAT, and then we'll print AAT using the F string. So we can see we get the same result, which is the same matrix A or the tensor A that we created above. So now let's move ahead and see how to create a variable in TensorFlow 2.0. So in TensorFlow 1.x, you know that the variables are firstly instantiated, and then if you want to use those variables, you have to instantiate or initialize those variables using the global initializers. So in TensorFlow 2.0, we don't need to initialize variables. So to use the value of a variable in TensorFlow 2.0 graph, we'll simply treat it like a simple tensor without actually initializing using the global initializers. So we'll firstly see how to create variables. So we'll create variables using the tf.variable, and here we have created a variable with tf.0. So a variable is a tensor whose values can be changed, and these mostly represents the weight of the inputs in our neural networks. So we'll first of all create a tensor variable. So if you press shift and tab here, you will get different arguments, and you can check the different arguments that you can use here. So we'll pass the values as a tf.zeros tensor, and here we have Here we want to make a zero tensor which will have two elements with each element having 3 rows and 4 columns. And we'll store the result in my variable, and if you print my variable using the tf.print method, so we'll see we have two tensors or two zero tensors with each tensor having 3 rows and 4 columns. So this particular code here represents that we have two tensors with each tensor having 3 rows and 4 columns. And now we have different methods that we can use on a variable. So we'll first of all create a variable which will contain a floating point number 0, and then if you want to add anything to our variable, so our variable here is v, and if you want to add 1, so here w is a tensor which is computed based on the value of v. So here w is our new tensor which will be computed based on the value of v. So anytime a variable is used in an expression, it gets automatically converted to a tensor representing its value. So here we have passed 1, so it will be automatically converted to a tensor, and then the value of 1 will be added to the value of v, and then we'll get the result. So our result here should be 1 because our w is v plus 1. So this is unlike TensorFlow 1.x where you would have to initialize those variables before you actually use them. So here we don't have to initialize, we can just use them as normal tensors. So now let's print both v and w. So we'll write tf.print and then we'll pass our v and then w. So you can see our v was 0 which we had declared, and then we added 1 to it, so we got 1. Now let's see another command which is assign. So we can assign using the assign method to different tensors or different variables. So well, first of all we'll create a variable tensor which has a value of 0.0 floating point, and then we'll assign it a value of 2 using the assign method. So we'll write v.assign and we'll assign it a value of 2. So now it will be having a value of 2. So now it is a TensorFlow object. So if you want to print it as a numpy array, so you can just write numpy here. So it will be a numpy array, or the value will be represented, and you can also use tf.print, so directly the value of this particular tensor will be printed. So now let's see how to use the assign add method to perform the add operation on a tensor variable. So we have created a variable v with a floating point number 0 as its value, and now we'll use the assign add method to add 1 to the variable v. And if you run this, you'll get a variable object which is a TensorFlow variable object, and if you want to print the value of v after the assignment, you can use the tf.print method to print the actual value. So after printing the value, you can see that the value is 1 since we added 1 to our variable v using the assign add method. So now let's see how to use operations in TensorFlow 2.0. So in TensorFlow 1.x we used to define sessions, and inside of the sessions we used to declare our operations using placeholders. But in TensorFlow 2.0 we can just directly declare functions instead of declaring a session and a placeholder. So here we will first of all define an operation which is our add operation. So first of all I'll create a function which is add op with two inputs, that is a and b, and it will return the addition of those two inputs a and b. So now we'll print the sum of 10 and 20 using the add operation. So we'll call the add operation and it will sum the two numbers 10 and 20 and it will return the answer as 30. Now let's build a linear model using the TensorFlow 2.0. So first of all we'll create a variable w and a variable b, which are the parameters of an equation of a line, which is wx plus b. So before we used to create x as a placeholder, now we'll just pass the value of x directly to our function, that is our linear model function. So first of all we'll create two variables. The first variable is w. So the value of this variable is 10 and it is of integer 32-bit type, and the next variable is 5, which is also an integer 32 type, and the value of this variable is assigned to b. So now let's define a function which is a linear model function which will take one argument, that is x. So which once we plug x, we'll get the equation of a line, and the w and the b values are global variables, so we don't have to initialize it now in TensorFlow 2.0. So we'll directly call w and b, we'll directly use it inside this function, and once we define this function which will return us an equation of a line for different values of x. So now we'll call this function using different values of x. So we have passed a list which contains 5, 10, 15 and 20 as 4 numbers as different values of x, and once you run this particular line, so you'll get this particular object. So right now this is just a tensor object, so if you want to get the values as an array, so you can use the numpy method to get the values as a numpy array. So now we have got 4 values here. So if you plug x as 5 in this particular equation, so your y value will be 55, and if you plug x equals 10 in this particular equation with the respective values of w and b as 10 and 5, so your value will be 105. And if you plug 15 as x and w as 10 and b as 5, so you will get 155. And similarly for 20, you will get 205 for this particular equation using w and b as 10 and 5.
So let's understand the limitations of a single layer perceptron. So a single layer perceptron can only learn linearly separable problems. So if a non-linearly separable problem is given to a single layer perceptron, then it would not be able to come up with a solution. So we have the AND/OR problems and the XOR problem over here. So as it is stated over here, AND/OR problems are linearly separable, while an XOR problem is non-linearly separable. So over here, if we look at this AND/OR problem, we are actually supposed to divide these two balls into two separate groups. So there are green colored balls and there is a blue colored ball. And we are supposed to divide these into two separate groups using a single layer perceptron. And that is quite easy for a single layer perceptron. So all we have to do is draw a linear line, and it places all of the green balls on the left side of the linear line, and it places the blue colored ball on the right side of the linear line. So this is a case where the single layer perceptron works properly. But then again, let's take the case of an XOR problem. So what happens in an XOR problem is it is non-linearly separable. So we have a blue colored ball over here, and then we have two green colored balls, and then again there is a blue colored ball over here. So if you're asked to separate these four balls into two groups, then it wouldn't be possible with a single linear line. Right? So we can't create two separate groups with just a single linear line. So this is where a single layer perceptron fails. And it is very clear over here. So it's just not possible to draw a single line which would be able to separate the green colored balls and the blue colored balls into two separate groups. So this is where we'd have to use the help of multi-layer perceptrons. So now again, there are a lot of complex problems out there which cannot be solved with a single layer perceptron, such as image classification. Now what happens in image classification is there are a lot of dimensions and there is a lot of complexity associated with it. And there are a lot of factors which come into the equation. So taking care of all of these parameters, all of these dimensions, that is just not possible with the help of a single layer perceptron. And to find a solution for all of these non-linearly separable problems, we'd have to take the help of a multi-layer perceptron. So before we go ahead and find the solution for this, let's actually go through a use case. So consider that you own an e-commerce firm and you want to increase the traffic on your site. So you decide to give special discounts and you basically start an end season sale. And for this end season sale to work properly, you need to have a very good marketing strategy. And you have different options available with you. So to market this end season sale, you have different platforms such as the Google ads, personal emails, YouTube ads, LinkedIn, and so on. Now, you can either use a single platform to do all of your marketing, or you can use a combination of all of these platforms for your marketing. So as an owner, your priority should be to make as less investment as possible and come up with the maximum profits. And for a human to do all of this analysis, that could be a bit too complex. And if the owner decides to solve it with the help of a single layer perceptron, even that wouldn't be possible. So let's see what can be done over here. So these are all of the different marketing platforms which are available. And each of the marketing platform has its own advantages and disadvantages. Now, all of these factors have to be considered properly before we come up with the optimal solution. And that is just not possible with the help of a single layer perceptron. So again, we have the same thing over here. We have all of these different marketing platforms, and finding out the right permutation combination of all of these marketing platforms to come up with the perfect solution wouldn't be possible with this single layer. What I'm doing is I'm creating three numpy arrays, x1, x2 and x3. So x1 would basically be a numpy array which consists of 10 values in the range of 3 to 12. And then we have x2, which is again a numpy array which would again have 10 random values in the range of 9 and 18. And then we have x3, which is another numpy array which again consists of 10 random values in the range of 12 to 20. So we have x1, x2 and x3. And similarly, we'll also create y, which is our actual output, which would be x1 cross 7 plus 5 cross x2 plus 4 cross x3. So we have our input values and we also have the actual output with us. I'll click on run. Right. Now let me just print out the values of x1, x2 and x3. So this is x1, x2 and x3. So x1 is the numpy array which consists of 10 values between 3 and 12. x2 is the numpy array which consists of 10 values between 9 and 18. And x3 is the numpy array which consists of 10 values between 12 and 20. Now let me go ahead and find out the shape of this numpy array. Right. So the shape of this numpy array x1 comes out to be 10. Now let me also have a glance at the output, which is y. So this is my actual output, which is 176, 156, 146 and so on. So I have my actual values with me and I also have the actual output which I want. Now what I'll do is I'm going to reshape this. So I'll use this function y.reshape and I will pass in the shape over here. So here in the original value of y, so this is actually a numpy array where all of the values are present in one single row. But instead of having all of them in one single rows, I want to have them in 10 separate rows. So I'll use the y.reshape function and pass in the parameters, which is shape over here. So shape basically consists of the number of rows and then I just want one column. So shape, comma 1. So this tells me that y comprises of 10 values and all of those values are present in different rows. So I have my inputs and the output value with me. So now these inputs are actually individual values which are x1, x2 and x3. So I'll combine all three of them into a single numpy array. So I'll use the function np.array and pass in x1, x2 and x3 and I'll store that in capital X and I'll print it out. Right? So this becomes my new input. Now again I'll transpose this. So x.t would help me in transposing this numpy array and I'll store it back to capital X. I'll click on run again. So this numpy array which initially had 3 rows and 10 columns, when we transpose it, it becomes a numpy array with 10 rows and 3 columns. Right. So now that we have our inputs and the actual output value, this is where we go ahead and set the learning rate and also initialize the random weight values. So over here I am setting the learning rate to be 0.0001 and after learning rate I'd have to initialize the weight values. So I am basically creating a numpy array with 3 values in it and those 3 values would be generated randomly. And to generate random values I'll just use this np.random.randan and I'll pass in 1. So 1 basically means that it'll generate one random value. I'll click on run. So this is our weight matrix, which is a basically 3 cross 1 matrix and it comprises of these values. So now we have the input values, the actual output, the learning rate and the initial weight values. Now I'll go ahead and start the feed forward propagation. So again, this time the number of epochs is 50 and to get the predicted values, I'd have to use the mat_mul function. What I'm doing is basically multiplying the input matrix with the weight matrix. So the input matrix is present in capital X and the weight matrix is present in W and I can multiply these two with the help of np.mat_mul and I'll store the result in ypred. So again, as I've already stated, the initial predicted values wouldn't be equal to the actual values. And if you have to find out the error in prediction, we'll just subtract ypred from actual y values. So error would be equal to y minus ypred. And since we want the squared error, I'll take the whole square of it. So we've done the forward propagation and we've found out the error in prediction. So now that we have the error in prediction, we'd have to find out the change in error with respect to weights. So now that the forward propagation is done and we've also calculated the error in prediction, this is when we go back. That is, this is where we back propagate and find out the change in error with respect to each of the weights. So we'd have to calculate the change in error with respect to weight 1, change in error with respect to weight 2 and change in error with respect to weight 3. So where we are finding out the change in error with respect to weight 1. So when we take the partial differentiation of this with respect to weight 1, this is what we get. So 2 times of np.mat_mul and this is what we have over here, y minus ypred, and then we take a transpose of it. And we'd have to multiply this with minus x of 0 or the first input. So we are basically multiplying the change in this with respect to the first input. Similarly, when it comes to the change in error with respect to W2, we'll multiply this with respect to the second input. And when it comes to change in error with respect to W3, we'll multiply it with the third input over here. Now, since we have calculated the gradients with respect to W1, W2 and W3, we can go ahead and update these three weights. So the first weight which is present in W00, so we are basically updating the weight matrix over here. So in the weight matrix, we are supposed to update the first weight value, and to update the weight value, we just have to use the simple gradient descent algorithm. So we'll subtract the old weight value minus the learning rate into the gradient of the error with respect to weight 1. Similarly, when we want to update the second weight, this will be the old weight minus the learning rate into gradient of error with respect to W2. Similarly, for the third weight, it will be the old third weight minus the learning rate into change in error with respect to W3. So now the backpropagation is done and also the updation of the weights is done. So what I'll do is, I'll keep on adding all of the errors calculated through each of the backpropagation iterations, and I'll also print the value of W1, the value of W2, the value of W3 and error at each backpropagation or error at each epoch. Now let me print this out and let's see what do we get. So this is value of W1, value of W2, value of W3, and this over here what we have is the error matrix, right? So initially the values predicted had an error of 39,176, 30,733, 26,158 and so on for those 10 values. So this was the case of the first iteration. So in the second iteration, the error, it became 2.62 plus of 0.2. So this you can consider it to be into 10 power 2. So 2.62 into 10 power 2 would be 262. So from 39,176, the error came down to 262. Similarly, over here, the error was 30,733. So from 30,733, the error, it came down to 200, right? So this is how the error, which started at 39,176, it kept on decreasing and it finally reached till 2, right? So in 50 iterations over here or in 50 epochs, the error has reduced by a very great margin. Now, if we also want to have a look at this in a graphical way, I can just plot the error list which we had obtained through backpropagation. So I'll just plot it out. So we see that as the number of iterations increase, the error decreases significantly. So this would be maybe the third iteration or the fourth iteration. So here, as we saw, the mean error, it was somewhere around 40,000. So from 40,000, it came crashing down to around 10 in the second or the third iteration. So to get the global minimum error and to get the optimal weights value, we'd have to increase the number of epochs a bit more, and that'll give us the best result. Now again, let's understand backpropagation in a better way. Now let's say we have an image of a man over here and we give it as an input to this neural network. So this neural network will process it and then give us an output. But what happens with this neural network in the feed forward propagation mode is, it'll take the input, it'll do a bit of processing and it'll give us an output. But the output tells us that this is a gorilla instead of a smiling man, and that is actually an incorrect output. So to get the right result, we'd have to backpropagate and update all of these weights over here. So we give the input, we feed forward it, and then we get an output, and the output given is actually a gorilla. So what we do is we backpropagate, update all of these weights with all of these links over here, and when we get the optimal set of all of these weights, we'll get the final correct result, which tells us that the input is actually of a smiling human who's wearing glasses. Now let's again take another example. So over here we have the input which is 0, 1 and 2, and our desired output would be 0, 2 and 4. So let's say initially we give out the weight value to be 3 over here. So when we give out the weight value to be 3, the output which we get is 0 for the first input, 3 for the second input and 6 for the third input. But then again, these are not our desired outputs. So let's actually find out the error in prediction. So for the first input, the error is actually 0 because the desired output is 0 and the actual output is also 0. For the second input, the desired output is 2 and the output given by the model is 3. So this time the absolute error is 1. And again for the third input, the desired output is 4 and the output given by the model is 6. So this time the error in prediction is 2. Now instead of getting the absolute error, we'll actually have to work with a square error. So we'll square this up. So 0 is 0, square of 1 is again 1 and square of 2 becomes 4. Now what we'll do is, instead of keeping the weight as 3, we'll update the weight and change it to 4. Now, when we update the weight value to 4, we'll get these outputs. So for input 0, the output is 0. For input 1, the output is 4. And for the input 2, the output is 8. So this time the squared errors are very large. This time the squared errors are 0, 4 and 16. So we see that as we increase the weights, the error also increases. So initially when the weight was equal to 3, the squared error was 0, 1 and 4. And then when we updated the weight and increased it to 4, the squared error became 0, 4 and 16. So now what we'll do is, instead of increasing the weight, we'll actually decrease the value of weight. So from 4, we'll bring it down to 2. And when we bring down the weight to 2, these are the final outputs which we get. For input 0, the output is 0. For input 1, the output is 3. And for input 2, the output is 4. So this time we see that the squared errors are 0, 1 and 0. And the squared error has actually decreased. So for this case, what we've seen is as we increase the weight, the error also increased. And as we decrease the weight, the error also decreased. So this is how the backpropagation algorithm works. Now let's go through this graph to understand backpropagation in a better way. So we have this graph over here and our aim is to minimize the error. And to minimize the error, we can either increase the weight or decrease the weight. So let's take this side of the graph. So if you take this side of the graph, then the tangent which is passing over here, that would make a positive slope with this axis. And since it makes a positive slope with this axis over here, so if we decrease the weight, then the error would decrease. And if we increase the weight, the error would also increase. So similarly, if we take this side over here, then the tangent with this graph over here, that would make a negative slope. And since the tangent would give us a negative slope, that would mean it is inversely proportional. So if we start from this side, then if we increase the weight, then the weight would decrease. But if we decrease the weight, then the weight would increase. So basically the task of the backpropagation algorithm is to reach this global loss minimum. And to reach the global loss minimum, the backpropagation algorithm could either decrease the weight or increase the weight. And if it's on the right side over here, then it has to decrease the weight because it is directly proportional. And if it is on the left side over here, then it has to increase the weight because it is inversely proportional. So this is how the backpropagation algorithm works. So now that we've understood the theory behind backpropagation, let's understand the math behind it. So again, we have this neural network over here and these are the inputs. So for the given inputs 0.05 and 0.10, we'd have to get the outputs 0.01 and 0.99. And to get this result, we'd have to go through two steps. First would be the forward pass, where we'll go from the input layer to the output layer. And the second would be the backward pass, where we'll go from the output layer to the input layer and update all of these initially random weights. So let's just jump into all of the math. Now in the forward pass, what we have to do is go from the first layer to the second layer. So over here, we just have to multiply all of the weights with the inputs. So W1 is multiplied with I1, W2 is multiplied with I2, and the bias is multiplied with 1. And you then add them up. So after multiplying all of the weights with the corresponding inputs, that is W1 into I1 plus W2 into I2, and then we have bias. So multiplying this bias with 1, we get this. So we have a result of 0.3775. Now this is just a linear value. Now we'd have to pass this linear value inside an activation function. This activation function which you see, this is the sigmoid function. So 1 upon 1 plus e power minus net of h1. So this is the net of h1 which we've calculated. So h1 is the first node in the hidden layer and we've calculated this value and we've passed this inside this sigmoid function. Now this activation function will give us a value of 0.59. So similarly, we'll do the same procedure for h2. We'll calculate the linear value first and then we'll pass that through the sigmoid activation function and then we'll get the value for h1 and h2. So we've done the calculation and then we've got the values for h1 and h2. So net h1 comes out to be 0.3775 and net h2 comes out to be 0.59. So once this is done, we'd have to find out the value for O1 and O2. So this time what we'll do is again multiply the corresponding weights with the corresponding outputs of h1 and h2. So similarly, what we'll do is multiply W5 with O1 and W6 with O1 and also multiply the bias with 1. So this is how we can get the output for O1, and we'll do the same procedure for O2 as well. So W5 into output of H1 plus W6 into output of H2 plus B2 into 1. This gives us a value. And again, this value is passed through an activation function, which is basically the sigmoid function. And this gives us a value between 0 and 1, which is 0.75. So we've got the final output for O1. After this, we'd also have to find out the final value for O2. So we'll do the same thing. Multiply the corresponding weights with the corresponding inputs, and we'll pass down that linear equation through the activation function, and we'll get an output value of 0.77. So we've got the value for output of O1 and output of O2. Now we'd have to find out the error in prediction. And this is the formula to calculate the error in prediction. So we'll just subtract the target minus output. So we'll just subtract the output from the target and then square it up. So this was our initial value, which was 0.01, and this is the predicted value, which is 0.75. So we'll subtract the 0.75 from the 0.01 and then we'll square it up and we'll get a result of 0.27. So this is the error in prediction for the O1 layer. So the error in prediction for O1 node is 0.21. Similarly, we do the same process and get the error in prediction for O2. So the error in prediction for O2 comes out to be 0.0235. Now, to calculate the total error, we'd have to add up the error for O1 and the error for O2. And when we add up these two, we get a total error of 0.29. So now we're done with feed forwarding the input, and then we've predicted the result, and we've also calculated the error in prediction. So this is where the step 2 starts. So step 2 is basically backward propagation, where we start from the output layer and we keep heading back and keep on updating the values. So now we'll see how can we update the weight 5. So as I've already stated, to update the weights, we'd have to find out the change in error with respect to the change in weight. So we'd have to take the partial differentiation of total error with respect to W5. So this can be written as partial differentiation of E total with respect to output O1 into partial differentiation of output O1 with respect to net O1 into partial differentiation of net O1 with respect to W5. That is this entire process. So partial differentiation of E total with respect to output O1, partial differentiation of output O1 with respect to net O1, and partial differentiation of net O1 with respect to W5. And when we do this, we'll get the final result. So we'll start with this formula over here. So we have to find out the partial differentiation of E total with respect to output O1. So E total is basically this value over here, which is basically half into target O1 minus of output O1 whole square plus half into target O2 minus output O2 whole square. So over here, since we are differentiating it with respect to O1, this entire thing would be a constant and this would turn to 0. And when we differentiate this, this would become minus of target O1 minus of output O1. And we'll substitute the values for target O1 and output O1 and we'll get the value of 0.74. So the result for this would be 0.74. And then we'll come to the second term over here, which is partial differentiation of output O1 with respect to net O1. So we know that output O1 is 1 upon 1 plus e power minus net O1, and this is nothing but the sigmoid function. And when you differentiate the sigmoid function, you basically get the same value multiplied by 1 minus same value. So over here, this output O1 after differentiating would become output O1 into 1 minus output O1. So this is 0.75 into 1 minus 0.75, and this gives us a value of 0.18. So we got the value for the first term, which is 0.74. We also got the value for the second term, which is 0.18. And then we'll head on to the third term, which is differentiation of net O1 with respect to W5. And we have net O1 over here. Net O1 is W5 into output H1 plus W6 into output H2 plus B2 into 1. So over here, since we are differentiating this with respect to W5, all of these would be constant and would turn to 0. And when we differentiate this, this would become 1 into output of h1 into 1. So this basically is output of h1, and output of h1 we already know the value, which is basically 0.59. So we get the values for the final 3 terms. And all we have to do is multiply these 3 terms, then we'll get the partial differentiation of E total with respect to W5. So when we multiply these 3 terms, we get a value of 0.08. Now we've got the gradient. After getting the gradient, we have to pass this through the stochastic gradient. After we get the gradient, we'd have to pass this through the gradient descent formula. So this what you see is the gradient descent formula. So this is the new weight. This is the old weight. This n which you see is nothing but the learning rate, and this is the gradient which you've just calculated. So new weight is equal to old weight minus the learning rate into the gradient descent. Since we've already got the gradient descent, which is 0.08, what we'll do is we'll just multiply this gradient with the learning rate, which is 0.5. Now again, this learning rate is an arbitrary value, so you'd have to do the trial and error to get the best optimal value for this. So 0.5 into this, and you will subtract this from the initial weight value of W5. So the initial weight of W5 is 0.4. So when you subtract this value from 0.4, you'll get a value of 0.35. So initially W5 was 0.4, and after back propagating, its weight came down to 0.35. So we'll do the same procedure for the rest of the weights. Now when we apply the same procedure, W6, the new W6 value comes to 0. The new W6 value comes down. The new W6 value comes to 0.40, new W7 value comes to 0.51, and new W8 value comes to 0.56. So we are done through the first pass of backward propagation. After this, we have to go through the second pass and calculate W1, W2, W3 and W4. That is in the first pass of gradient descent, we calculated these 4 values. Now, we'd again have to go through another pass, and then we'd have to update these 4 values over here, which are W1, W2, W3 and W4. So this time, if we have to update W1, then we'd have to find out the change in total error with respect to the change in W1. That is, we'd have to get the partial derivative of E total with respect to W1. And this can be represented as partial differentiation of E total with respect to output H1 into partial derivative of out H1 with respect to net H1 into partial derivative of net H1 with respect to W1. So this is how it can be understood. So let's start with the first term over here. So if we take this first term over here, then H1 over here, it contributes to both the output of O1 and O2. And that is why it can be split into 2 parts. So partial derivative of E total with respect to output of H1 becomes partial derivative of EO1 with respect to H1 plus partial derivative of EO2 with respect to out H1. Right? So this is what we are doing over here. So if you want to find out the partial derivative of E total with respect to W1, we can get it by doing the partial derivative of E total with respect to out H1, and then we'd have to get the partial derivative of out H1 with respect to net H1, and then we'd have to get the partial derivative of net H1 with respect to W1. Now when it comes to the first term, E total can be represented as E01 plus E02, and this term over here can be broken down as partial derivative of E01 with respect to out H1 plus partial derivative of E02 with respect to out H1. Right. Now let's understand the math over here. So this is the first term which we have over here. Partial derivative of E total with respect to out H1, and as you already saw, this can be represented as partial derivative of EO1 with respect to H1 plus partial derivative of EO2 with respect to H1. Now with respect to this equation, we'll take the first term. So this first term over here can be represented like this. So partial derivative of EO1 with respect to H1 can be represented as partial derivative of EO1 with respect to net O1 into partial derivative of net O1 with respect to out H1. So these two would be cancelled out and we'll get what is there on the LHS. Now again we'll take the first term over here, and this first term can again be represented like this. So partial derivative of EO1 with respect to net O1 can be represented as partial derivative of EO1 with respect to out H1 into partial derivative of out H1 with respect to net O1. So these two would be cancelled out and we'll be getting what is there on the LHS. So we have already calculated these two values in the first backward pass. So the value for this would be 0.74 and the value for this would be 0.18. And when we multiply these two, we'll get a value of 0.13. So we've got the value for the first term, which is 0.13. Now we'd have to get the value for the second term. So the second term is partial differentiation of net O1 with respect to out H1. And we already know what net O1 is. So net O1 is W5 into out H1 plus W6 into out H2 plus B2 into 1. And since we want this partial derivative with respect to H1, these two would be constants. And when we differentiate this, we'll just be left with W5. And the value of W5 is 0.40. So the value for this term comes out to be 0.40. So we've calculated both the values for this. So that the value for the first term is 0.13 and the value for the second term is 0.4. And when we multiply these two values, we'll get the partial differentiation of EO1 with respect to out H1, which comes out to 0.055. And if we repeat the same process for EO2 as well, we'll get the partial differentiation of EO2 with respect to out H1, and this comes out to minus 0.019. So we've got partial differentiation of EO1 with respect to out H1 and partial differentiation of EO2 with respect to out H1. And when we add these two up, we'll get a final value of 0.03, and this is nothing but the partial differentiation of E total with respect to out H1. So again, this is not the final result. What we want is partial differentiation of E total with respect to W1. So we've just got the result for the first term. There are two more terms over here. So the second term is partial differentiation of out H1 with respect to net H1 and partial differentiation of net H1 with respect to W1. So let's start with the second term. The second term over here is partial differentiation of out H1 with respect to net H1. And we already know what out H1 is. It is this over here, which is basically the sigmoid function 1 upon 1 plus e power minus net H1. And we know that when we differentiate a sigmoid function, we get the same value into 1 minus the same value. So over here, this becomes output of H1 into 1 minus output of H1. So H1 is 0.59 and into 1 minus 0.59. So this gives us the value for the second term, which is 0.24. And then finally, we have the third term. So third term is partial differentiation of net H1 with respect to W1. And we already know what net H1 is. So net H1 is W1 into I1 plus W3 into I2 plus B1 into 1. And since we are differentiating this with respect to W1, these two terms become 0 and all we are left with is I1 and I1's value is 0.05. So we've got the values for all of the three terms. So the value for the first term or the value for partial differentiation of E total with respect to out H1 is 0.036 and the value for the partial differentiation of out H1 with respect to net H1 is 0.24. And the value for partial differentiation of net H1 with respect to W1 is 0.05. And then finally, all we have to do is multiply these three values to get the result for partial differentiation of E total with respect to W1. And that comes to 0.0004. So we've got the gradient with respect to W1. And since we want the new weight for W1, we have to pass this down to the gradient descent formula, which is new weight is equal to old weight minus the learning rate value into the gradient with respect to W1. So over here, the gradient is 0.0004, the learning rate is 0.5 and the initial value of W1 is 0.15. So when we feed in this value over here, W1 becomes 0.1497. And in the same way, we'll update the values for W2, W3 and W4 as well. So this is the entire backpropagation algorithm with which we were able to update all of the weights starting from W1 to W8. So initially when the inputs were 0.05 and 0.1 respectively and we forward propagated these inputs, we had an error of 0.29. But after applying the backpropagation once, the error came down to 0.29102. So even though we see that the difference is not much, but then again, when we implement this backpropagation algorithm around 10,000 times, the error plummets to around 0.0000351. So at this time, when we feed forward 0.05 and 0.1, the output neurons generate 0.015 for the first output and 0.98 for the second output, which are very, very close to the actual outputs. So we see that we keep on back propagating until we find the lowest error and also find out the optimal weights and the optimal bias. So backpropagation is basically used to optimize our neural network, and we have many such optimization algorithms with us. And through all of these examples, the optimization algorithm which we used was the gradient descent algorithm. So let's understand this gradient descent algorithm in a better way. So the gradient descent algorithm basically measures how much the output of a function changes if you change the input a little bit. So for all of the examples which you saw, you can consider the weight to be the input and the error to be the output. So you want to know how much does the error change with respect to a small change in the input. So the higher the gradient, the steeper the slope and faster the model learns. Or in other words, if the change in error is very high when there is just a small change in weight, then this means that the model is learning very quickly. So this is the concept behind gradient descent. So now let's understand how does gradient descent actually work. So this is the formula for gradient descent. B is the new weight, A is the current weight, this what you see is the learning rate, and this is the gradient. So new weight or the next value is equal to current value minus the learning rate multiplied by the gradient. So let's say we have this graph over here, and these are our initial values of weight and bias. So the task of the gradient descent function would be to find the optimal values of W and B and to minimize the error. So let's say we start from somewhere over here and we have a random values of W and B. So let's say there's a ball and that ball keeps on rolling to the bottom of the curve. So the gradient descent algorithm has to make sure that it reaches to this bottom of the curve or the bottom of the hill in the fastest manner and the right direction possible. So restating it, we have random values of W and B, and the task of the gradient descent algorithm would be to find out the optimal values by reducing the error. And the reduction in error is done by going in the right direction of the slope. So let's say if there's a ball which starts from over here, it keeps on rolling down and it has to reach over here, and this value would be nothing but the global minimum. So when it reaches over here, it'll get the global minimum, which is nothing but the lowest error, and this is where we'll find out the optimal values for W and B. Right, now let's understand the importance of learning rate. So when the ball is rolling down the hill, the speed of that ball is determined by the learning rate. So let's say if the learning rate is very high or if it's very large, then what happens is it might overshoot the global minima. So let's say if it starts over here, then from here it'll not come over here but it'll shoot over here. From here it'll come to the left side and from here it'll reach over here. So what is happening is since the learning rate is very high, it'll never reach the global minimum and it'll keep on oscillating between the two walls of this curve. So this is what happens when the learning rate is very high. Now let's understand what happens when the learning rate is small. So when the learning rate is small, let's say if the ball starts from over here, then the speed of the ball to come from over here to the bottom of the hill would be very, very slow. So it'll start over here, then it'll come over here, then over here, over here, over here, and over here. So from here to here, it'll take eternity and it'll consume up a lot of resources and a lot of time for this neural network to find the optimal values for the weight. So this is why we have to make sure that the learning rate is neither too big nor too small. So we also have to find out the optimal learning rate to get the optimal values of weight and bias. Now there are other interesting terms when it comes to gradient descent. So you have something known as an epoch. So one epoch is basically when we pass the entire data set forward and backward through the neural network once. So I'm again reiterating it. So when we pass the data set forward and backward through the neural network once, that is known as one epoch. Now when it comes to the neural network, it is very important that the data set is passed through more than one epoch. Because when we pass the data set through the neural network through only one epoch, then it leads to underfitting. Or in other words, it fails to learn all of the features associated with the data. Now, when we keep on feeding this data to the neural network, there'll come a stage where the curve would be the optimum for the data provided. But then again, if we keep on increasing the number of epochs and never stop, what happens is it'll lead to overfitting. So when it leads to overfitting, this would be good for that particular problem, but it is very bad at general problems. So when it is given some other data set, that will fail miserably. So this is why epoch is also important. So we'd also have to find out the right number of epochs for our model to be accurate enough. So after epoch, we have something known as batch size and iterations. So batch size is basically the number of training examples present in a single batch. Now we'll head on to iterations. So iterations is the number of batches needed to complete one epoch. Now let's understand these three terms through an example. So let's say there are 2000 entries in the data. And if we divide these 2000 entries into batches of 500, we'll have 4 batches in total. And it'll take 4 iterations to complete one epoch. So I'm reiterating it. Let's say there's a data set which contains 2000 entries or 2000 records in total, and if we divide this data set of 2000 examples into batches of 500, we'd have 4 batches in total. So we'd have to iterate through all of these 4 batches to complete one epoch. Right. So now, as I had already stated during the agenda, the gradient descent comes with a lot of variants. So we have the vanilla gradient descent, which is nothing but the batch gradient descent. And then we have the stochastic gradient descent, and another variation is the mini batch gradient descent. So let's start with the batch gradient descent. So we'll understand all of these variants through this example. So let's say we have a data set which comprises of these 6 images of cars. So let's start with batch gradient descent. So the batch gradient descent algorithm takes all of these images at one go. So it takes all of these 6 images of a car at one go, and it calculates the loss for all of these 6 images at a single time. So it'll take all of these 6 images, it'll backpropagate, and it'll calculate the loss or the error in prediction. Now, once it calculates the loss for each of these 6 cars, then it'll go ahead and update the gradient descent. So it'll actually calculate the average gradient descent with respect to the loss of all of these 6 cars. Now, keeping this in mind, we'll head on to the next variant, which is stochastic gradient descent. So in stochastic gradient descent, what happens is it takes one record at a time, or for this particular example, it takes one image at a time. So the first image is sent to the neural network, it reads the image, it backpropagates, calculates the error, and after calculating the error, it there itself updates the gradient. Now, once it updates the gradient, it reads the second record. Now, after reading the second record, it backpropagates and calculates the error with the updated gradient. And again, it'll update the gradient for this record as well. And then it'll head on to the third record, calculate the loss, update the gradient. Similarly, it'll do that for each of the individual records. So this is what is done in stochastic gradient descent. And then finally, we have the mini batch gradient descent, where the data is read in batches or mini batches. So over here, let's say with respect to this example, the mini batch size is 2. So in the first mini batch, 2 images are sent to this neural network over here. So it backpropagates, calculates the loss, and calculates the average gradient descent for these 2 records. And with the previously found gradient descent, it'll again backpropagate and find out the updated gradient descent. And then it'll head on to the next batch and then update the gradient descent again. So this is what happens with respect to vanilla gradient descent, stochastic gradient descent, and mini batch gradient descent. So now that we've understood the gradient descent algorithm properly, let's understand how can we work better with this gradient descent algorithm. So to find out that optimal value of weight and bias, we can plot the cost versus time graph. So time is plotted on the x-axis and cost is plotted on the y-axis. And the aim of the gradient descent algorithm should be to reduce the cost as the time progresses. So we'll most probably get a curve which will start at the far end of the y-axis and it'll come down to the bottom of the y-axis and then it'll stay constant. So basically as time progresses, the cost has to decrease, or in other words, the error has to decrease. The next step when working with gradient descent algorithms would be to modify the learning rates. So again, we are never sure what learning rate would work with what data. So that is why we'd have to start with small learning rates. So we'll start with these small learning rates which are specified over here, and then we can go ahead and randomly play with these learning rates so that we get the optimal value. And we should also make sure that we rescale the inputs. So sometimes it happens that the data which we feed into the neural network is distorted or it is skewed. Now when this happens, this neural network will not work properly. So that is why we'd have to scale this data in either the range of 0 to 1 or minus to 1 so that we get the optimal weight values and we can reduce the error as soon as possible. Right, so that was gradient descent. Now, apart from the gradient descent algorithm, we also have something known as the Adam optimization algorithm. So the Adam optimization algorithm basically stands for adaptive movement estimation, and it is a combination of gradient descent with momentum and RMS prop algorithms. Now the problem with gradient descent algorithm is, let's say if we take the example of that curve and we roll the ball down through the hill. Now what happens is, if there are a lot of crests and troughs in that hill, then there'll be oscillation along the vertical axis as well as the horizontal axis. Now, when there is oscillation along the vertical axis, this will reduce the speed of the ball and this will also increase the time of reaching the global minimum. So that is why when we add momentum along with the gradient descent algorithm, the speed of reaching the global minimum would become faster. And also another change when it comes to the Adam optimization algorithm is the learning rate is variable. So the learning rate is not constant. So as and when the momentum changes, the learning rate also changes to adapt with that momentum. So a feed-forward neural network just contains multiple nodes which are arranged in multiple layers. And simply put, we have an input layer, a hidden layer, and the output layer over here. And a feed-forward neural network can contain two kinds of nodes. So there could be a mono layer which does not contain any hidden layers. And then we have our multi-layer perceptrons where there is one input layer and there exists at least one hidden layer and there is one output layer. So all of the inputs are taken through the input layer. The processing is done in the hidden layer and the final output is received through the output layer. Alright, so now let's actually discuss the solution to our e-commerce firm problem with the help of multi-layer perceptron. So we have this input layer, all of the inputs are sent over here and the processing is done over here in these hidden layers. Now each of these hidden layers does a part of the processing work. So let's say stage 1 of the processing is done in the first hidden layer. Stage 2 of the processing is done in the second hidden layer. Stage 3 of the processing is done in the third hidden layer and so on. And then we'll have a final linear equation. Now this final linear equation is sent through an activation function. And that activation function converts this linear equation into a non-linear solution and sends that out to the output layer. Right. So over here in this multi-layer perceptron over here, we have these inputs, we have this hidden layer and we have the output layer over here. So let's start off with the input layer. So in the input layer, we have two external inputs, x1 and x2. And along with these external inputs, we also have a bias. Now the bias is generally 1. Now these inputs are sent to the hidden layer and these links between the input layer and the hidden layer, these links are basically associated with weights. Now once these inputs are sent to the hidden layer, all of the processing is done over here. So what happens in the hidden layer is the inputs are multiplied with these weights associated. So x1 is multiplied with w1, x2 is multiplied with w2 and 1 over here or the bias over here is multiplied with the weight w0. So in the hidden layer we get this equation w0 into 1 plus w1 into x1 plus w2 into x2, and this is our linear equation which we want. But then again we'd have to convert this linear equation into a non-linear solution, and to do that we'd require an activation function. So we'll basically pass this linear equation through an activation function and then we'll get a result, and that result is finally sent out through the output layer over here. Now, keeping these points in mind of how an input layer works, of how the hidden layer works, and how the output layer works, let's solve our use case. Alright, so again we have the input layer, the hidden layer, and the output layer. So over here, all of the different marketing platforms which we have, they are sent as the individual inputs. So marketing via emails, that would be our first input. Marketing via referral programs would be a second input. Paid ads is a third input, and then we have direct marketing, social media marketing, and then we also have the organic search. So all of these platforms together combined become our inputs. And these inputs are sent to the hidden layer, and all of these links which you see over here, all of these links have certain weights associated with them. And those weights are multiplied with the corresponding weights over here, and we get a linear equation. And that linear equation is passed through an activation function, and that provides us a solution which is finally sent out through the output layer. And that is how we'll get the result where we'll know what combination of all of these marketing platforms would be the best idea for us. Right. Now let's actually go through another use case to understand multi-layer perceptrons better. So we have this data set over here which comprises of these columns. So this column tells us the number of hours studied by the student. This column tells us the midterm marks scored by the student. And this column tells us whether the student would pass in the exam or not. So 1 over here tells us that the student has passed in the exam. And 0 over here tells us that the student has failed in the exam. So these two would be our inputs, and this would be our final result. Now, suppose we want to predict whether a student studying 25 hours and having 70 marks in the exam will pass the final term or not. So the input for number of hours studied is 25, and the input for number of marks obtained is 70, and we'd have to find out, or we'd have to predict the final result. So these are the three parameters which we have over here, and this is basically a binary classification problem. So it's either 1 or 0, and we'll solve this binary classification problem through a multi-layer perceptron. Right. Now we've understood what feed-forward propagation is. So in feed-forward propagation, we start from the input layer, and these inputs are sent to the hidden layer where all of the processing is done. And that processed output is finally sent out through the output layer. But then again, that wouldn't be our final solution. Now to get the final solution, the multi-layer perceptron uses something known as the backpropagation algorithm. And using this backpropagation algorithm, it will come out with the optimal solution. So we'll understand about backpropagation in the coming slides. Right. So coming to our use case, we have the input layer, the hidden layer, and the output layer, and these are our inputs. So number of hours studied by the student are 35, and the marks scored by the student are 67. And these are given as the inputs to the input layer, and there is also a bias over here. So these are the initial random weights which are W1, W2, and W3. Now, what happens in the forward propagation is we have predicted, and the prediction for this node over here, it comes out to be 0.4, and the prediction for this node over here, it comes out to be 0.6. But the actual results are different. So the actual result for this output is 1, and the actual result for this output is 0. So there's a difference of 0.6 and there's a difference of 0.4 over here. So there is an error in prediction. And normally for the final output layer, we'll be using the softmax function as the activation function. So the softmax function basically gives us probabilities, and when you add up all of those probabilities, the sum ends up to be 1. So as over here, we see that this probability is 0.4 and this probability is 0.6. And when you add these two up, you get a total probability of 1. And to get this probability in this way, we'll have to use the softmax activation function. And we have the same thing over here. So these are the inputs, number of hours studied and the midterm marks. So the number of hours studied are 35 and the midterm marks are 67. Now, these inputs are sent to the hidden layer where the processing is done. So W2 is multiplied with 35 and W3 is multiplied with 67. And then W1 is also multiplied with the bias, which is 1. So in total, the linear equation becomes 1 into W1 plus 35 into W2 plus 67 into W3. And this linear equation is passed through an activation function. Now, once this processing is done and it is sent to the activation function, we'll get an output, and that output is sent through the output layer. So again, as we see over here, the probability of passing is given out as 0.4 and the probability of failing is given as 0.6. But in actuality, this is wrong. So the probability of passing is 1 and the probability of failing is 0. So there's an error of 0.6 for the first output node and there's an error of 0.4 for the second output node. Now, this has happened because the weights and the bias were initially randomly assigned. So when you give in random weights, you'll also get a random result. So to correct this, we'd have to go back and optimize these weights and bias. So this is where backpropagation comes in. So what we'll do is, once we get the errors over here, we will go back and using an optimization algorithm, we'll update these weights. So we'd have to update W1, W2 and W3. And when we get the optimal weights for W1, W2 and W3, we'll get the optimal result, which would be 1 for the first node and 0 for the second node. And this is how the backpropagation algorithm works. So what we'll do is, we'll find out the change in error with respect to the change in weight. So we'd have to find out the change in Y with respect to the change in W4, W5 and W6. And when we get that, we will go back, that is we'll backpropagate and then we'll update the weights for W4, W5 and W6. That is how we'll get the optimal weights. So once the backpropagation is done and we've updated these weights W4, W5 and W6, we see that the result has also changed. So we see that after using the backpropagation algorithm, the probability of pass, that is the probability for the first node, has changed to 0.8. And the probability of failing or the probability for the second node has changed to 0.2. And this time, the error in prediction for the first node is 0.2. And similarly, the error in prediction for the second node is also 0.2. So after backpropagating and updating the weights, we find out that the error has reduced. So this is how backpropagation works to optimize the weights. So I'll start off by loading the required packages. We would need NumPy, Matplotlib and Pandas. So I'll import NumPy as NP, I'll import the Matplotlib package as PLT and I'll import Pandas as PD. I'll click on run. So let's say there is a hypothetical neural network and to that hypothetical neural network I'm giving two inputs. The value of the first input which is x1 is 2 and the value of the second input which is x2 is 5. And for these two inputs, I would want the output value which is y to be equal to 31. So I'm basically initializing the values over here. I'll click on run again. And this is where I'll do all of the backpropagation and gradient descent work. So starting off, I'll give in the value for learning rate. So I'll set the learning rate to be equal to 0.01. So after learning rate, I'd have to assign some random weight values. So I'll have W1 and I'll assign it a random weight value of 3. And then I have W2 and I'll again assign it a random value of 7. So now through backpropagation, my aim would be to find those optimal values of W1 and W2 which would give me the correct value of Y, which is 31. So what I've done is in this for loop, I've basically taken 50 epochs. That is, I will pass in these inputs through the neural network 50 times. And this is the forward pass over here where I'll go ahead and calculate the error in prediction. So that is basically W1 into X1 plus W2 into X2. So I've passed these inputs into the input layer. Now in the input layer, what is happening is the weights are multiplied with the inputs. So W1 into X1 plus W2 into X2. And I'm storing that into Y predicted. Now we obviously know that the predicted values would not be equal to the actual values in the first step itself. Then I'll go ahead and calculate the error in prediction. So error in prediction would be Y, which is this value over here, minus Y pred, which is basically over here. So Y minus Y pred and I'll square this. So I need the squared error. So once I calculate the error, this is when I'll backpropagate and find out the change in error with respect to individual weights. So initially I want the change in error with respect to weight 1. So when I differentiate this, this becomes 2 times of Y minus Y pred and partial differentiation. Since this is with respect to W1, this would be a constant, this would become 0 and then this will become minus X1. Similarly, when I partially differentiate this with respect to W2, I get 2 times of Y minus Y pred into X2 over here. So I've backpropagated and I've got the partial differentiation of error with respect to W1 and W2. Now after this is done, I'd have to use the gradient descent formula and update the weight values. So the new value of W1 would be W1 minus learning grade into the gradient with respect to W1. Similarly, new value of W2 would be old value of W2 minus learning grade into differentiation of error with respect to W2. Now finally, I'll print out W1, W2 and the error. So I'll run this. So let's see what is happening over here. So initial value of W1 is 2.6, initial value of W2 is 6.2 and the error in prediction is 100. So in second iteration, the error comes down to 17. In the third iteration, the error comes down to 3. So we see that we are going in the right direction and the error falls down very quickly. So after around 50 iterations, the error is 0. Now since the error is 0, let me find out the weight values now. So initially the weight values were 2.6 and 6.2. Now finally we have the weight values to be 2.3 and 5.27. And when we pass in these weight values into this formula, we get a value of 31.0, which is same as this actual output value. So the actual output value and the predicted output value, both of them are same. So initially we started with an error of 100. Now we kept on back propagating 50 times and we reduced this 100 to 0 and we got the final correct value. So there are a lot of deep learning frameworks available today. So now my question to you guys would be, why should we use Keras out of all of these deep learning libraries? Well, let's understand. So the number one reason to use Keras would be it prioritizes developer experience. So Keras is a framework which is developed for humans and not machines. That is, it is very easy to code with Keras. You just have to keep on adding layers which you can invoke with functions and you can keep on building neural networks. So it is that easy to work with Keras. And then Keras is also broadly adopted in the industry and also among the research community. So all of the PhD scientists over there and all of the data scientists, their most widely preferred deep learning framework is Keras. And the next reason would be it is very easy to turn all of these Keras models into end-to-end products. So let's say if you develop a simple prototype with Keras and if you want to launch it on some platform, then you can easily do it. So you build a model and then you can easily launch it on, let's say, Android, iOS or any other operating system as an end-to-end product. And Keras also supports multiple backend engines and does not lock you into one ecosystem. Now, what do I exactly mean when I say that Keras supports multiple backend engines? Well, Keras is basically a high-level API, and this high-level API can run on a lot of low-level APIs such as TensorFlow, CNTK and Theano. So now Keras is what works at the front end, and at the back end you have either TensorFlow, Theano or CNTK running. Right. Now Keras also has a strong multi-GPU support. So when I say Keras has a strong multi-GPU support, what I mean is you can basically divide the data or you can basically train the data on multiple GPUs. So let's say you have an input data which comprises of 100 records and you divide into 5 mini batches. Now you can train these each individual mini batches on separate GPUs. So let's say you have a model and you have the input data. Now you'll be making copies of this input data and each individual copy would run on each single GPU. And each of that GPU would give you an individual result which is aggregated and you'll get the final result. So this basically speeds up the model building process. And Keras development is also backed by all of the major companies out there such as Google, Amazon and Nvidia. Right. So now that we've understood why should we use Keras, let's actually understand what is Keras. So as I've already told you guys, Keras is basically a high-level API and it is written in Python. And this high-level API can run on top of Theano, TensorFlow or CNTK. And it is very easy to work with Keras. So you have individual modules and you can invoke each of these individual modules to keep adding layers on the neural network. So now that we understand what is Keras, now let's have a look at the different models in Keras. So there are basically two types of models available in Keras, which are sequential model and functional model. So let's start with the sequential model. So simply put, sequential model is just a linear stack of layers. So you have one layer, on top of that one layer you add another layer. On top of the second layer you add the third layer. On top of the third layer you add the fourth layer. So it is basically a sequence of layers. So as we see over here, this input layer would be our first layer, and on top of this input layer we'll add the first hidden layer. And on top of this first hidden layer, we'll add the second hidden layer. And finally, on top of the second hidden layer, we'll add the output layer. So simply put, a sequential model is just a linear stack of layers which processes the data and gives out the final output through the output layer. Right. And this is how we can invoke a sequential model through Keras. So first we'd have to import sequential from keras.models, and then we'd have to import whatever layers that we require. So the first step in creating a sequential model would be to create an instance of this. So we have to use the sequential method and we'll create an instance of it. So now that we've created a model, so with this model we can keep on adding layers. So what we are basically doing is, for this instance, I am adding the first layer. So this first layer is basically a dense layer and it comprises of 32 nodes, and the dimension of the input which this first layer takes is 784. And we are also adding an activation function to this first layer. So it is as simple as that. First, you create a model, and then whatever layers you want to add, you can just add it with the help of the add method. So this is how we can create sequential models in Keras. Now we'll head on to the second type of models, which are functional models. So functional models help us to create complex models. Now, the problem with sequential models is you can give inputs only at the beginning stage over here. So let's say if I want to add new inputs for the second layer, that wouldn't be possible. So once if you give the inputs, you cannot add anything else in between. So this is where functional models differ. So in functional models, it is not necessary to follow the same sequence. So when it comes to functional model, any layer can be connected to any other layer. And these three steps which you see, these are the three steps which have to be followed to create a functional model. So we start off by defining the input. And once we define the input, we start off by building a set of layers. And these layers can be connected anyway. So I can connect the first layer with the fourth layer, or the second layer with the 10th layer. So I start off by defining the inputs, and then I'll create the layers, and then I'll connect those layers. Now, finally, I will build the model. So these are the three steps involved. First, define the input. Second, build the layers and connect the layers, and then finally build the model. Right. So let's understand each of these steps properly. So when it comes to a sequential model, we actually have to create and define a standalone input layer that specifies the shape of the input data. So as you see over here, we are importing input method. So from keras.layers, we are importing input and we are defining the shape of the input data. And this is extremely important when it comes to functional models. So first, we have to start off by creating the input layer. And once we create the input layer, we can keep on adding other layers. So as we see over here, first we import input method, and after that we are importing the next layer, which is basically a dense layer. So as we see over here, first we create the input layer using the input method, and the shape of the input is 2, and I'm storing it in visible. After that, I'll add another layer. So this is basically a dense layer. Now, this dense layer has 2 nodes in it and it is connected with the visible layer over here, right? So we give out the name of the previous layer after we create the first layer over here. Or in other words, layers in functional model are basically connected pairwise. So this is the dense layer, and this dense layer is connected with the first input layer, which is visible. Right, so we are done with the first 2 steps. So first we created the input layer and then we connected the rest of the layers. Now after that we have to create the model. So defining the model is extremely simple. So first we'd have to import the model method from keras.models, and using this model method, all we have to do is pass in the input and the outputs. So as we have already seen this before, input is the visible layer and output is the hidden layer. So we are passing these 2 layers in this method and we are storing this in the model instance. So this is how we can create a functional model. And Keras already has a number of predefined layers. So these are some of the predefined layers listed over here. So Keras can have core layers, convolutional layers, pooling layers, recurrent layers, noise layers, embedding layers, and so on. Right. So now that we've understood the different models available in Keras, now let's understand some problems when we are building the model on top of input data. So the aim of model building should be to gain the maximum accuracy. But then again, it is not that easy to build that perfect model. Many a times what happens is our model is not able to learn the right amount of data. So let's take this case over here. So let's say we build a neural network model on top of this data, and our aim is to classify this data into two classes. So the first class would be this cross, and the second class is the circles over here. Now the problem with this model is it has not learned all of the features of the data properly. And since it has not learned all of the features of the data properly, the misclassification over here is quite high. So these three circles, which should actually be circles, have been classified as cross. And these crosses which you see, they have been misclassified as circles. And this misclassification is due to the underfitting of the model. So I again restate it. So underfitting of the model basically means that it is not able to learn all of the features of the data properly. And when it doesn't learn all of the features of the data properly, it is not able to predict, or it is not able to classify the problem in a correct way, or it doesn't give us the perfect accuracy. So let's say if this model is built on the train set, then the train set accuracy would be somewhere around 65%. And the test set accuracy would be somewhere around 63%, which is not really that good, right? So this is basically the problem with underfitting. Now, instead of drawing a straight line, what if I make the model a bit more complicated? So what I'll do is I'll build a polynomial curve over here. So this is a complicated model. So this complicated model is better than this model over here. So this model gives just about the right fit. So over here, all of the circles have been classified correctly as circles, and just these two crosses have been misclassified as circles. So let's say this gives an accuracy of around 95% on the train data and an accuracy of around 93% on the test data, which is actually good enough. Now, what if I get over enthusiastic and build a very complex model with lot of polynomial variables in it? So this would give me a curve, something like this. So over here, all of the crosses have been classified into one pool, and all of the circles have been classified into another pool. So this basically gives us 100% accuracy on top of the train set. But the problem is it fails miserably on the test set. So the problem actually is that it fails to generalize. So when it is given the train set, it learns all of the features of this train set perfectly. And when it comes to the test set, it has not seen the test set at all. And that is why it fails to perform properly on the test set. So when it comes to the train set, it gives out 100% accuracy. And when it comes to the test set, it might give only around 75% or around 80% accuracy. So that is why underfitting and overfitting should be avoided. And we need to find that appropriate fitting, or just the right fitting, to get that ideal accuracy on top of the test set. Right, so this graph over here explains this in a better way. So we have error on the y-axis and model complexity on the x-axis. As we see over here, as we keep on increasing the model complexity, the error, it decreases for the training set. But what happens with the test set is, as we increase the complexity, the error first decreases, but then again, the error increases as we keep on increasing the model complexity. Right? So to get that perfect accuracy on top of the test set, we need to find out that optimal model complexity. Only when we find out that optimal model complexity, that is when we'll get the maximum accuracy. Right. So now that we've understood why overfitting is harmful for a model, let's understand the solution to it. So the solution to overfitting is basically regularization. So there are some regularization techniques which help to reduce overfitting. So let's actually take this example over here. So here we see that we've built a very complex model and it learns all of the training data perfectly. But then again, since it learns all of the training data perfectly, this leads to overfitting. Now, the solution to this would be regularization. So when we apply a regularization technique on top of this data, what happens is it penalizes the weight matrices. So when it penalizes the weight matrices, so the values of those weight matrices and bias matrices would change a bit, and this would lead to a less complicated curve. Now also we need to make sure that we give the appropriate value for the regularization coefficient. So if we keep the regularization coefficient to be very high, then what might happen is some of the weight matrices would become 0. And when some of the weight matrices become 0, it would basically lead to a model which is underfitting the data. Right? So again, when we are applying this regularization technique or when we are tuning this regularization coefficient, we have to make sure that we don't alter the weights too much. And if we alter the weights too much, then we might end up actually underfitting the model. And that is something we have to avoid. So that is why we have to find out that right value of regularization coefficient which would give us this appropriate fitting. So we don't want a model which is too complex or too simple. We just want that right fitted model which is able to give us the perfect accuracy on top of the train set as well as the test set. Right, now let's actually see some regularization techniques. So one regularization technique could be to add dropouts in our neural network model. So now the question in your head would be, what exactly does a dropout do? A dropout basically means that we randomly remove or cancel some nodes during each iteration. So as we see over here, in the first layer, these two have been dropped out or these two have been removed. Similarly, in the second layer, these three have been removed, and in the third layer, these two have been removed. So this again is an arbitrary choice, and we can give any random value to each of these layers. So now that we know what exactly dropouts are, let's understand how they are helpful. So when we cancel out these nodes during every iteration, they do not memorize the data. And when they don't memorize the data, this actually in turn helps in not to overfit the data. So let's actually understand this through an example. So let's say we have this training data and we are building this model on top of the training data, and this training data goes through 3 epochs or 3 iterations. So in the first iteration, in this layer, these two are cancelled out. In this layer, these 3 are cancelled out, and in the third layer, these 2 are cancelled out. Now, this is only with respect to the first iteration. Now, in the second iteration, again, a random set of 2 nodes would be cancelled out. And it's not necessary that these would be those 2 nodes. So those 2 nodes could be either this one and this one, or this one and this one. So it could be any random combination of 2 nodes which are cancelled out from this first layer. Similarly, again, from this second layer, a random combination of 3 nodes is cancelled out. Again, in this third layer, a random combination of 2 nodes is cancelled out. Again, we'll come to the third iteration. Again, the same thing happens in the third iteration. So basically, adding a dropout layer works as an ensemble model. So every iteration gives slightly different model. So in the first iteration, we have different set of nodes which are giving the output. In the second iteration, we have another set of nodes which are giving the output. Similarly, in the third iteration, we have totally different set of nodes which are giving the output, right? So a dropout layer basically works as ensemble models through each iteration. So we can basically set a probability of number of nodes to be dropped out. So over here p is equal to 0.5. So this means that the dropout percentage would be 50%. That is, we'll be keeping 2 nodes and we'll be removing 2 nodes. And it's extremely easy to add dropouts with Keras. So first we'd have to import the dropout method from keras.layers.code. So once we do that, we'll build the model. And in this model, we are adding a layer over here. Now, for this layer, for this dense layer over here, we are adding a dropout, and the probability of the dropout, we are setting it to be 0.25. So it's as simple as that. So all we have to do is use this dropout method and set in the probability of dropout. So adding a dropout layer was one regularization technique. Now we also have another regularization technique, which is data augmentation. So the simplest way to reduce overfitting is to increase the size of the training data. Now, how can we increase the size of the training data? Well, we can basically modify the data to increase the size of it. So let's say we are dealing with images or images of these numbers over here. Now in this case, what we can do is we can augment the data. So let's say I have the input data, which is basically image of the number 2. Now if I want to create a duplicate of this image, what I can do is I can add some sort of transformation on top of it. Let's say the initial image which had the number 2 was over here at the center. So instead of keeping it at the center, what I'll do is I'll move it up. Similarly, let's say if I had the number 3 over here in the center, I'll move it down. Similarly, over here, the number 3, I'm pushing it to the right. And not just moving them to the top bottom, left. We can also flip the image. We can also scale the image. So let's say this is my input image 7. So instead of keeping it like this, what I'll do is I'll flip it inverted like this. So I'll flip it and it'll be inverted. And also I can scale it up, or in other words, I can also increase or decrease its size. So these are different transformations which I can apply on top of the input data so that I can create more records, or records which are similar to the original records. So let's say if my input data consists of images of the first 100 natural numbers. Now if I want 1000 records instead of 100 records, all I have to do is add some sort of transformations on those original records and have records which are pretty much similar to the original records. So this is how we can augment the data. Now, what is the importance of data augmentation? Well, when we have more data, obviously it'll be difficult for the model to learn all of the features of it. So when we have less training data, then it is very easy for the model to overfit it. And when we have a lot of data, the model will obviously take a lot of time to learn all the features, and it is difficult for the model to overfit it. So this is how data augmentation works. And when it comes to Keras, we can perform all of these data augmentation strategies using the image data generator method. So we'll have to import this image data generator from keras.preprocessing.image, and it has a big list of arguments, such as over here we are setting the horizontal flip to be equal to true. So MNIST dataset comprises of handwritten images of numbers from 0 to 9. So this is basically a classification problem. So we take in the input data and we'd have to classify them belonging to this particular number. So let's say if I take in the image of number 1, then I have to classify to which of the numbers starting from 0 to 9 does it belong to. So this is basically the data set which we are going to working with. So we'll start off by importing all of the packages that we need. So from Keras, we'll import models, and we'd require the dropout layer as well as the dense layer. And we have to convert some of the values in the data set to categorical. So we'll be doing one hot encoding, and to do one hot encoding, we'll be importing the to categorical method from keras.utils. And as we are working on top of the MNIST dataset, we'd have to import this from keras.datasets. And we'll also be visualizing how the model works. So to visualize that, we'll be importing model to dot from keras.utils.visutils. And we'll also be importing svg from ipython.display. So let me run this. Now I'll also import numpy. After that, I'll import the live loss plot. So live loss plot helps us to have a glance at the live training of the model. So we can actually visualize how the error is decreasing and how the accuracy is increasing for each of the epoch. So for that purpose, we'll be importing the live loss plot. And there are some initial variables which we are creating. So we'll set the number of rows to be 28, number of columns to be 28, the number of classes to be 10, the batch size to be 128, and the number of epochs to be 10. And then we'll go ahead and create a simple method which we can call again and again. So this method takes in 4 parameters: xtrain, ytrain, xtest, and ytest. So xtrain basically contains the train images, ytrain contains the train labels, xtest contains the test images, and ytest contains the test labels. And in this function, we are basically printing all of these things. So xtrain.shape, that is, we are basically printing out the shape of the training set images. After that, we'll print out the shape of the labels from the train set. And then we'll print out the shape of the images of the test set. And then we'll print out the shape of the labels of the test set. And finally, we'll just print out the train labels and the test labels. So I'll click on run. Right. So we've created the method. Now I will load up the data from MNIST dataset, and I'll store all of that data inside xtrain, ytrain, xtest, and ytest, right? And then I will pass in these 4 values into this method which I've just created. So I'm reiterating it. From the MNIST dataset, I'm loading all of the data, and I'm storing that data in xtrain, ytrain, xtest, and ytest, and I'll pass in these 4 values into this method which I've just created. So I'll click on run. Right. So this method basically gives me these things. So we see that the training images shape is 60,000, 28 cross 28, and the labels is 60,000. That is, this basically means that there are 60,000 entries in the training set, and this is basically the size of each image, which is 28 cross 28. And then again, this is the test images. So the shape is 10,000, 28, 28. This means that there are 10,000 images in the test set and the shape of these images is 28 cross 28. And these are the train labels and the test labels. So these are basically labelings of all of the images. So the first image in the training set is of the number 5. The second image in the training set is of the number 0. Similarly, the third image in the training set is of the number 4. So you basically have to build a model on top of the train set so that it learns all of the features properly, and then we'll check for its accuracy on top of the test set. So before we go ahead and build the model, we actually have to reshape it. Now the train image shape, it cannot be 28, 28. So it has to be of a single dimension. So what we'll do is we'll multiply this. So we have already stored the value of num rows and num calls over here. So num rows is 28 and num calls is 28. So this basically means that number of rows are 28 and number of columns are 28. And we'll multiply this and we'll convert this two-dimensional data into a single dimensional data. So we are basically reshaping this training data. Similarly, we'll take in this test data, which is of the shape 28, 28. And again, we'll convert this two-dimensional data into a single dimensional data by multiplying those two. So over here, I am passing this xtest.shape and I am reshaping this with just one dimension. So it'll be num rows into num calls, which is basically 28 cross 28. Right, so I've reshaped the image data. Now similarly, I'd have to reshape the labels as well, or in other words, I'd have to perform one hot encoding on top of this. So I just cannot have these values 5, 0, 4 individually. So what I'll do is, if there is 5, I will do one hot encoding and represent it as a numpy array of 10 values. So I am taking this Y train and I am encoding it into categorical values. So I am passing the original Y train value and the number of classes over here, I've set it to be 10. So I'll just pass in the parameter which is num classes over here. Similarly, I'll take in Y test and I will pass this inside this to categorical method. And I'll set the num classes again. So this basically gives in 10 classes. I'll click run now. Now again, I will pass in all of these modified data. So xtrain, ytrain, xtest, ytest, all of these have been modified. I'll pass these inside data summary method and let's see how these have been changed. Right. So initially train images shape was 60,028, and that has been changed to 60,784. Similarly, the train label shape was 60,000 and I've changed that to 60,010, and these have been changed like this. And also for the labels, we have performed one hot encoding. So over here, if we have a glance at these test labels, so this is 7, 2 and 1, right? So over here, 7 has been represented like this, 2 has been represented like this, and 1 has been represented like this. So this 1 represents the place of that value. So if you have 1 at the 7th position, right? So now we have our data ready. And since we have our data ready, we can go ahead and build a sequential model. So using this instance which I've created, models, I will call in the sequential method. So models.sequential. So I'll start off by creating an instance of a sequential model. So I'll call models.sequential and I'll store that in this model object. So now that I've created my model, I can finally go ahead and add all of the layers. So what I'll do is I'll add the first layer. So in this first layer, this is nothing but a dense layer. So this is a densely connected layer and this layer has 512 nodes, and the activation function which I'm using is relu. And since this is the first layer, it needs to have the input shape. So input shape is nothing but number of rows into number of columns. So this basically comes to around 784. So this is the first layer, and after the first layer, we are adding a dropout with a probability of 0.5. After that, we'll add the second layer, and the second dense layer has 256 nodes in it, and again the activation function is relu. And this time, the dropout probability is 0.25. And then we finally have the output layer, and the output layer comprises of 10 nodes. And we have 10 nodes because we have 10 classes in total. Or these 10 classes represent the numbers from 0 to 9. So we basically have to classify whether this is an image corresponding to number 0, number 1, number 2 and so on. And the activation function which we've used for the final output layer is softmax. So softmax function basically gives us probabilities for each of these nodes in the output layer. And when you add up all of these probabilities, it comes up to 1. Right, so I'll run this now. So we have build the model. So now that we've built the model, we have to tune it a bit. And to tune the model, we have to use model.compile. So this is where we'll be using 3 parameters. So first parameter is the optimizer which we'll be using. Second parameter is the loss function which we'd have to reduce. And the third parameter is the metric which we'd have to calculate. So over here, the optimizer or the optimization algorithm which I'm using is RMS prop. And the loss which we'd have to reduce is categorical cross entropy. And the metric which we are getting is accuracy of the model. Right. So this is basically the tuning part. And after that, we have to fit the model on top of the training set. And to do that, we'll be using model.fit. And this takes in all of these parameters. So we'll pass in X train, Y train. Or in other words, we are basically fitting this model on top of the train set. And we are validating this on top of the test set. So we have X test and Y test over here. And we also set the batch size and number of epochs over here. So the number of epochs are 10 and the batch size is 128. So I'll run this now. Now this is our first epoch. So our first epoch has just started. So we see that the loss, it is reducing. So this is our graph over here. So we have 2 graphs over here. So the first graph, this tells us how the error reduces with each epoch. And the second graph tells us how the accuracy increases with each epoch. So over here, this orange line, it is for the validation data. And this blue line, it is for the training data. Similarly, this is what we have over here. So we see that the error, it reduces considerably for the training data as well as the validation data as the number of epochs increases. And similarly over here, as the number of epochs increases, the accuracy also increases. So the accuracy for the validation data, it increases till over here, till the 6th epoch. Now after the 6th epoch, for the 7th epoch, the accuracy actually comes down and then it goes back up over here. Right? So we were able to visualize this because of the live loss plot which we had imported earlier. And we are done with all of the 10 epochs. And after the 10 epochs, we have the log loss and the accuracy over here. So we see that after completing the 10 epochs, the error, it comes down to 0.072 for the validation data. And the accuracy for the validation data is 0.983. Right. So we have successfully built the model. Now let's also have a glance at the summary of the model. So I'll use model.summary and I'll click on run. So this gives us a brief summary. So this is the first dense layer, this is the second dense layer, and this is the third dense layer over here. And this tells us the number of nodes with respect to each dense layer. So the first dense layer has 512 nodes, and then we have a dropout layer corresponding to the first dense layer. After that, we have the second dense layer, and the second dense layer comprises of 256 nodes. And then again, we have a dropout layer for the second dense layer. And then we finally have the output layer, which is again a dense layer. And this dense layer comprises of 10 nodes over here. So in total, the number of parameters are 535,818, and all of these are trainable parameters over here. So now that we've seen the summary, let's just actually visualize how our model has progressed. So for that, I will use the SVG method, and inside that I will pass in my model inside model2 dot, and I'll create a dot plot. So I'll click on run. So this is what we have over here. So I have taken the input and I have passed that input through the first dense layer, which is nothing but our hidden layer, which comprised of 512 nodes. And after that, I passed the result through the first dropout layer. And this result was then sent to the second hidden layer. And then this again was sent through a dropout layer. And then finally, the result from this dropout layer was sent to the output layer. So this was the entire process which we performed in this Keras sequential model. So now we'll work with the second type of model, which is the functional model. And again, we'll be applying the functional model on top of the MNIST dataset. So again, we'll start off by loading all of the required packages. So we have to import Keras, and then we have to import model from Keras, and I'll import all of the optimizers from Keras. I'll click on run. After this, I'll load in the training set and the testing set of the MNIST. So pd.readcsv helps me to load both of these CSV files. So training set has the train set of the MNIST data, and test.csv has the test set of the MNIST data. Again, I'll click on run. Right, so we've stored the train set in df underscore train and we've stored the test set in df underscore test. Now let me have a glance at the training set first. I'll click on run. So df underscore train dot head. So this gives me the first 5 rows of the training set. So this is our training set which comprises of 785 columns. So this what you see, pixel 0, pixel 1, pixel 2. So we have 784 pixels in total and these are the corresponding labels for each of these images. So the first image, it is basically the image of number 1. The second image, it is the image of number 0. The third image, it is the image of number 1, right? So we have the labels over here and then we have the 784 pixels which combine to make up this image. Now similarly, let me have a glance at the test set. So df underscore test dot head. I'll click on run. Now this is a dataset which comprises of 784 columns. Actually had a glance at the original training and testing set. What I'll do is I'll divide the training set into features and labels. So from the entire dataset, I'll select the columns starting from column number 2 to the final column. That is starting from pixel 0 till pixel 783. And I will store it in df underscore features. So this basically represent all of my independent variables, or these basically represent all of my features. And similarly from the training set, I'll just select this first column and I will store it in df underscore label. So I have my features and labels ready with me. And similarly, I'll also create the test set. So from the test set, I'll extract all of the rows and all of the columns and I'll store that in x underscore test. Now let me print out the shape of xtest. I'll click on run. So we see that there are 28,000 entries in the test set, or in other words, there are 28,000 images in the test set. So now we have our features and labels ready with us. We have to divide these features and labels into validation data and training data. And for this purpose, we'll be importing train test split from sklearn.model selection. And I'll be passing both the features and labels inside this. And the test size, I'll be setting it to 0.2. That is 20% of the data points would be present in the validation data set and 80% of the data points would be present in the training set. And I'm setting a random state of 1212 so that I can use the same result again whenever I want. Now I will store the result in xtrain, xcv, ytrain and ycv. So this xtrain comprises of the training data of the features. This xcv comprises the validation data of the features. And we have ytrain which comprises of all of the features of the training set. And then we have ycv which comprises of all of the labels for the validation data. Now after this, again we have to reshape this. So we are going to reshape the xtrain and xcv. So we are going to reshape this xtrain and xcv into a matrix, and we are going to set the number of rows to be 33,600 and the number of columns to be 784 for xtrain. And for validation, I'm going to have 8,400 rows and 784 columns. And finally, we have the xtest. So I'll use xtest.as matrix. I'm converting this into a matrix and then I'm reshaping it to the same thing, which is 28,784. Right, now I'll run this. Right, now let's have a glance at the minimum and maximum values of the pixels present in the training set. So I'll click on run. So you see that the minimum pixel value is 0 and the maximum pixel value is 255. So these are basically grayscale images, and the values of these pixels of the grayscale images, they range from 0 to 255. So now that I've reshaped the data, I also have to normalize this data. And to normalize this data, I'll be dividing xtrain, xcv and xtest with 255. So first I will convert them to float, and after I convert them to float, I'll just divide them with 255. So I'll say xtrain by 255 and I'll store it back to xtrain. Similarly, I'll say xcv divided by 255 and I'll store it back to xcv. And then again, I'll divide xtest with 255 and I'll store it back to xtest. So we have also normalized our training data. Now, after this, we have to perform one-hot encoding of the labels. And to do this, we'll be using keras.utils.toCategorical. And this takes in 2 parameters. First is the object on which we'd have to perform one-hot encoding. And next is the value, which represents the number of classes this object has to be divided into. So over here, we have given the value of 10 to num digits. So basically, we want to represent this ytrain in the form of a numpy array where there are 10 values, and each of these individual numpy array would actually represent the value of the image. Right. So we'll do the same thing for y underscore train and y underscore save. That is for the training set as well as the validation set. I'll click on run. So we have normalized the data and also we have performed one hot encoding on top of the labels. So now let me actually have a glance at the labels after performing one hot encoding. Right, so we see that the first image in the training set, its label was actually 2. So now this 2 has been represented like this. So 0, 0, 1 and then we have zeros following it. So this basically means that wherever we have 1 over here, this represents that index position. So this is the 0th index, first index, second index. And since we have 1 at the second index, this basically denotes that the label of this image is 1. And then we have the third image from the training set. So over here, the label is actually 7 and it has been represented like this. So we have 0, 0, 0, 0, 0, 0 and 0, 1 and then we have 2 zeros following it. So we have 1 present at the 7th index position. And since it is present at the 7th index position, this basically means that the label of this corresponding data is 7. Right, so now before we go ahead and build our functional models, we'll set in all of our parameters first. So first I will set the number of features, that is the number of features are 784 and I'll store it in an input object. And then I'll add the number of nodes to be present in each hidden layer. So the first hidden layer has 300 nodes, the second hidden layer has 100 nodes, the third hidden layer again has 100 nodes and the fourth hidden layer has 200 nodes. And after this, I will have num digits, which is basically 10. So this basically tells me that the number of digits are 10. Right. So now I have set all of my parameters. I'll click on run. And this is finally time to build my model. So we'll be building a bunch of models. So we are going to build at least 3 to 4 models. And we are going to change the hyperparameters a bit. And we'll compare the accuracy of all of these models. And we'll see which model gives us the best accuracy. So we'll go ahead and build our first model. So our first model over here, as we already saw during the theory part, first we have to create the input layer. So I'll be using the input method and I'll pass in the shape of it. So the shape is 784. So this basically means that there are 784 inputs. And after that, I will create my first hidden layer. So over here, I will use the dense method and I will pass in n hidden 1. This basically means that there are 300 nodes in the first hidden layer. And the activation function which I'm using for the first hidden layer is relu. And I'll name this as hidden layer 1. Now I will give in INP inside braces over here. So this basically means that this hidden layer 1 is connected with the input layer. Or input layer is my first layer. After that, it is followed with the hidden layer 1. And then I'll go ahead and create my second hidden layer. Again, I'll use the dense method. I'll pass in n hidden 2, which is basically the number of nodes. So in the second hidden layer, the number of nodes are 100 and the activation function used by me is relu. Now, after this, I'll name this as hidden layer 2 and I'll connect it with x again. So I am connecting this second hidden layer with the first hidden layer. Again, I'll create the third hidden layer. I'll do the same things. I'll use the activation function as relu. I'll name it and then I'll connect this with the previous layer over here. And then finally, I'll create the fourth hidden layer and I'll pass in the number of nodes. After that, I'll set the activation function and then I'll name it. And then again, I will connect this fourth hidden layer with the third hidden layer. And finally, I'll set the output layer. So over here, output layer, num digits, this is basically 10. So this basically means that there are 10 nodes in the output layer and the activation function used by me is softmax. So again, I am using softmax because it will give me a bunch of probabilities for each of these nodes. And when I add up all of these probabilities, this will amount to 1. And I am naming this as output layer. Again, I am connecting this output layer to the fourth hidden layer. So what I've basically done is, first I've created the input layer. After that, I have created 4 hidden layers and I've connected them with each other. And finally, I've created an output layer and connected that output layer with the fourth hidden layer over here. So now that the connection of all of the hidden layers is done, we have to pass the input and the output layer inside the model method. So we'll do that and I will store that in model. And let me have a glance at the summary of the model which I've just created. Right. So this is what I have. I have the input layer and then I have 4 hidden layers and then I finally have the output layer. So this is the shape of the first input layer. So there are 784 nodes or 784 inputs for the first input layer. And then we have 4 hidden layers. Number of nodes in first hidden layer is 300. Number of nodes in second hidden layer is 100. Number of nodes in third hidden layer is 100. Number of nodes in fourth hidden layer is 200. And then the output layer comprises of 10 nodes. Right, I'll click on run. So this is where I'll set all of the hyperparameters. So I'll start off with the learning rate, and I'll set the learning rate to be 0.1, and I'll keep the number of epochs to be 20 and the batch size to be 100. And the optimizer which I'll be using is SGD. Or in other words, I'm using the stochastic gradient descent as my optimization algorithm. And inside this, I'll pass the learning rate over here. Alright. Now I'll go ahead and compile my model. This is where I'm basically tuning my model. So this takes in 3 parameters. First is the loss which I have to reduce. Next is the optimizer. Next is the metric which I have to calculate. So the loss which I have to reduce is categorical cross entropy, and the optimizer used by me is SGD as we saw over here, and then the metrics which I want to calculate is accuracy. So I'm building a model and I want to find out the accuracy of the model which I built. Right, I'll click on run. Now I've built the model, I've also tuned the model. So this is when I can go ahead and fit the model on top of the train set. So this takes in all of these parameters. So I'm basically fitting this model on top of X train and Y train. I'll give the batch size and number of epochs over here, and I want to validate this on top of XCV and YCV, which is basically my validation data. I'll click on run. So my first epoch has started. So in my first epoch, I see that the validation accuracy is 76%. Similarly, in the second epoch, I see that the validation accuracy is 87%, and this goes on. So the number of epochs are increasing. So we see that the accuracy is increasing. At the 12th epoch, the accuracy is 94%. At the 14th epoch, the accuracy is 94.69. So at the end of 20th epoch, we see that the validation accuracy is 95.82%. So we've built our first model, and our first model gave us an accuracy of 95.82%. Now, I'll go ahead and build another model. But this time what I'll do is, I'll not use the stochastic gradient descent optimization. So instead of stochastic gradient descent, I'll be using Adams, and let's see what difference it gives me in the accuracy. So we'll keep this in mind. So stochastic gradient descent gave us an accuracy of 95.82%. So again, for the second model, I'll give the input layer, I'll give all of these dense layers, and then I'll set the output layer. So all of these are same. So the input shape, that's same, 784. The number of nodes for these hidden layers is same. The activation function is also same. So the only thing which I'm changing in the second model is the optimization algorithm. So over here, I'll be using keras.optimizers.adam, and I'll be passing the learning rate, and I'll store this in Adam. And I'll go ahead and tune this. So while tuning, I'll set the loss to be categorical cross entropy, and the one change which I'm making, that is the optimizer used by me, that is Adam. Now I'll click on run. Right. And I'll go ahead and fit this model on top of the train set, and I want to validate it on top of XCV and YCV. I'll click on run. Right, so the first epoch has started. Right, so we're done with the 20th epoch. And at the end of the 20th epoch, we get a validation accuracy of 97.92%. So this is a considerable increase. So when we use the stochastic gradient descent as the optimization algorithm, we got an accuracy of 95.82. And instead of SGD, when we used Adams, the accuracy increased from 95 to 97. So now we've understood that it is better to use Adams instead of SGD. Now we'll go ahead and build some other models where we'll change something else. So this time what we're going to do is, we're going to keep the same optimization algorithm, which is Adams, but we'll change the learning rate. So initially the learning rate was 0.1. Now instead of keeping it 0.1, I'm changing it to 0.01. Rest everything will be the same. So I'll click on run over here. And then I'll go ahead and fit this model on top of train and test, and I'll validate it on top of XCV and YCV. So the training has started, as we can see over here. Right, so we're done with the 20th epoch, and we get an accuracy of 97.60. So let's compare it with the previous model. So in the previous model, when the learning rate was 0.1, the accuracy is 97.92, and this time it's 97.60. So there's not much of a difference, but we see that when the learning rate is 0.1, we get a better accuracy than when the learning rate is 0.01. Now similarly again, let's try it out with a different learning rate. So this time I'm setting the learning rate to be 0.5. Again, rest everything would be the same. So we have the input, we have the same hidden layers which comprise of the same number of nodes, and then we have the output layer over here, and also the optimization algorithm is also the same. I'll click on run. Right, now I'll fit the model on top of X train and Y train and validate it on top of XCV and YCV. So we're done with the 20th epoch and we get an accuracy of 97.7. So when we compare these three models, we see that we get the highest accuracy when the learning rate is 0.1. Right. Now what we'll do is we'll add another layer. So till now we just had 4 hidden layers. So I'll add another hidden layer which comprises of 200 nodes. So again, the input layer, it comprises of 784 inputs. We have the first hidden layer comprising of 300 nodes, second hidden layer comprising of 100 nodes, third hidden layer comprising of 100 nodes again, fourth again 100 nodes, fifth would contain 200 nodes, and then we finally have the output layer which comprises of 10 nodes. Right, I'll click on run, and again for all of these 5 hidden layers, the activation function is relu, and each of these is connected with each other. So input is connected to first hidden layer, this is connected to second, second is connected to third, third is connected to fourth, fourth is connected to fifth, and this fifth hidden layer is connected to the output layer over here, and the activation function used for the output layer is softmax. Right, I'll click on run. So we have created the input data and we have also connected the layers. Now it's time to build the model. And to build the model, all we have to do is pass in the input layer and the output layer, and then I'll have a glance at the summary of the model which I've built. So I'll click on run. Right. So I have the input layer and then I have 5 hidden layers, and then I have the output layer, and these are the number of nodes corresponding to each of these hidden layers. So now again it's time to fine tune our model. So I'll be using the same Adams algorithm and I'll set the learning rate to be 0.01, and inside this compile method I'll set in these 3 factors. So the loss which I have to reduce is for categorical cross entropy, optimizer as Adams, and the metric which I have to calculate is accuracy. Right, and then I'll fit this model on top of training set and validate this on the validation set. Right, so we're done with all of the 20 epochs, and this time we get a validation accuracy of 97.31. So we see that actually this is the lowest accuracy of all of the models which we've built. So this means that adding another hidden layer did not really make much of an impact to our model. So now we'll do something different. So what we'll do is we'll add dropouts after each hidden layer. So again, we have the input layer over here and we have 4 hidden layers. These are the number of nodes corresponding to each of these hidden layers. And then this is the number of nodes for the output layer. I'll click on run. Right, so over here I'll start off by creating the input layer. I'll set the shape and the shape is 784, and then I'll create the first hidden layer. So the first hidden layer, the number of nodes are 300, the activation function is relu, and after this I will set a dropout layer. So the probability of this dropout layer is 0.3, and then I'll create the second hidden layer and I'll add a dropout to the second hidden layer, and then I'll create the third hidden layer. Again, I'll add a dropout to the third hidden layer, and then I'll create the final hidden layer, and after the final hidden layer, I'll create the output layer, and again this output layer would comprise of 10 nodes, and the activation function used is softmax, and this output layer is connected to the final fourth hidden layer over here. Right, so now that we've established the input layer and all of these hidden layers, let's go ahead and create a model. So all I have to do is pass in the input and output layers inside the model method, and I'll store this in model 4 instance, and I'll have a glance at the summary. Right. So we have the input layer, hidden layer, and a dropout layer after each of the hidden layers. So now that we've built the model, let's again fine tune it. So the loss which we have to reduce is categorical cross entropy, optimizer is Adam, and the metric which we've used is accuracy. And let me fit the model on top of training set and validate it on top of XCV and YCV. I'll again click on run. Right, so we're done with all of the 20 epochs, and this time we get a validation accuracy of 97.63. Right, so what we've done is we've basically built multiple models, and we were just trying to understand how does changing some of these parameters change the accuracy that we get. So now what we'll do is we'll use this final model, that is the model 4 which you built, and we are going to predict the values on top of the test set with this model 4 which we've created. So I'm going to use the predict method from this model 4 instance. So I'll just type in model 4.predict, and over here this takes in two parameters. So the first parameter is the data on which you want to predict the results, which is X test, and then we'll set the batch size, which is 200. So we'll basically predict the values on top of the test set, and I'm storing it in test pred. Alright, so now let's actually have a glance at the predicted results. So I'll have a glance at the head of this. So this is the image ID and this is the label which we've predicted. So the first image we predicted that this image represents number 2. Similarly, the second image we predicted that this image represents number 0. The third image represents number 9, fourth image represents number 9 again, and fifth image represents number 3. Right. So now what I'll do is I'll take these predicted results and I'll create a CSV file out of this. So test.pred.toCSV, this helps me to create a CSV file, and I'll name that file to be mnist submission.csv. So now we'll start by understanding how our computer actually reads the images that we provide to it. So let's say we have this image of 3 really cute dogs. So we as humans, when we see this image, we understand that there are 3 really cute dogs in this image and there is grass beneath these dogs, right? But then again, if I feed this image to a computer, what will it exactly see? Well, so there'll be 3 channels, which is actually known as the RGB channel. So there is this red channel, green channel, and the blue channel. And each of these 3 channels would have their own corresponding pixel values. Now, when I say that the image resolution is 32 cross 32 cross 3, I basically mean that there are 32 rows, 32 columns, and 3 channels. That is, the red channel would have its own 32 cross 32 matrix, the green channel would have its own 32 cross 32 matrix, and the blue channel itself would have its own 32 cross 32 matrix. And this is what a computer basically sees. So there are basically a list of pixel values. So these are basically numbers which are fed into the computer, and this is what the computer reads. Now we'll go ahead and understand what exactly is the problem with a fully connected network. So let's say I have this image whose dimensions are 28 cross 28 cross 3. Now, when I feed in this image to a fully connected network, so the first hidden layer would basically have 28 cross 28 cross 3 weights. That would amount to 2352 weights. Now that is a whole lot of weights, isn't it? So dealing with all of these weights would be sort of a difficult task for this network. And to be honest, this resolution is actually low. So 28 cross 28 is actually a small resolution image. Now what I'll do is, instead of this 28 cross 28 image, I'll feed in an image whose dimensions are 200 cross 200 cross 3. And when I multiply 200 into 200 into 3, I'll get 120,000 weights. And those are a whole lot of weights, aren't they? And dealing with all of these weights would be a really Herculean task for this fully connected network. And this is exactly where the fully connected network fails. And we'll have several such layers of neurons leading to several parameters. So thus this connectivity would be a waste, as the huge number of parameters would actually lead to overfitting, and we do not want any sort of overfitting for our model. So now that we understand what exactly is the problem with a fully connected network, let's see how can a convolutional neural network solve this. Alright. So CNNs are basically like your normal neural networks and are made up of neurons with weights and biases, and they take inputs, and those inputs are passed through a weighted sum, and then they are passed through an activation function, and then we finally get an output. But then again, the difference between a CNN and a normal fully connected network is this. So in a CNN, let's say if we take a neuron in one particular layer, then this neuron will not be connected with all of the inputs of the previous layer. So let me actually go back over here, and let's assume that this is a convolutional neural network. Then this neuron would only be associated with, let's say, the first and the second neuron. Similarly, if I take this second neuron over here, then let's say this would be associated with this fourth and the fifth neuron. Similarly, if I take this neuron over here, then this could be associated with the first and the third neurons from the first layer. Right? So this is what basically happens in a convolutional neural network. So a neuron in one layer is not connected to all of the neurons in the previous layer. Right. And rest of the things are actually pretty much same when it comes to the convolutional neural networks. So another difference when it comes to a convolutional neural network is, so a convolutional net actually perceives these images as volumes. That is, three-dimensional objects rather than as flat canvases to be measured only by width and height. Right. So now that we understand what exactly is a convolutional neural network, let's see what convolution means. So in simple terms, convolution basically means to roll together or to combine together. And when it comes to mathematical perspective, so let's say we have two functions f and g. Now, when we pass these two functions with each other, convolution basically means how much one function overlaps with the other function. So let's take this image over here. So this is our first function, which is f, and this is our second function, which is g. Now when I pass g with respect to f, so this is where the overlapping happens, and this is what we exactly mean by convolution. So a convolution is the integral. So convolution is the integral measuring of how much two functions overlap as one passes over the other. And again, in mathematical terms, you can consider convolution to be mixing two functions by multiplying them. So we have f and g, and we are mixing them by multiplying f with g. So this is what convolution basically means. So now we'll actually have a brief understanding about CNNs and then go through a use case. So what actually happens in a convolutional neural network is there are many filters, and each such filter is passed over the entire image. So let's say we have this image of a car, and we want to identify or classify this as a car among many such classes. So these are the different classes available to us. So there is horse, ship, airplane, truck, and car. And we want to label this properly as a car. Now, when we feed in this image of a car to this convolutional neural network, what basically happens is there are different filters which are passed through this image. So let's say there is one filter which identifies or maps all of the horizontal lines, and then there is a second filter which identifies all of the vertical lines, and then similarly there is a third filter which identifies all of the left diagonals, and there is another filter which identifies all of the right diagonals. Now what happens is a convolutional neural network takes all of these filters and a slice of the image's feature space and map them one by one. That is, they basically create a map of each place wherever feature occurs. So we take this filter, map it on top of the image's feature space, and basically understand if there is a match between the filter and the image's feature space or not. And a convolutional neural network basically comprises of these four layers. So there is a convolution layer, there is a ReLU layer, there is a pooling layer, and the final layer is the fully connected layer. Right. Now we'll actually go through a use case to understand CNNs. So let's say our task is to identify, so let's say we have this image of X and image of O, and we want to identify what exactly is this. So when we pass this image of X through this CNN, we want to identify or label this as X. And similarly, when we pass this image of O through the CNN, we want to identify or label this as O. Now this might actually seem simple. So if there is just one X or one O, it would be quite simple. You would just have to pass in this image of X through the CNN, and it will easily identify that this is X. And it would be the same case with letter O as well. But then again, let's say we are dealing with sort of a tricky situation. Now, let's say we have all of these images of X. So this is our original image of X. So here what we are doing is we are thickening it up. And over here we are actually shifting up to the top left corner. And over here we are distorting this a bit. But then again, all of these are nothing but images of X. And when we feed all of these images to a neural network, we want that neural network to properly identify these as X, right? And similarly the case with O as well. And similar is the case with O as well. So all of these are distorted images of O. So when I pass these images of O to a neural network, I want that neural network to properly identify these images as the letter O. So now to do this, let's actually understand how a computer reads an image. So as we've already seen, a computer basically reads an image like a two-dimensional array of pixels with a number in each position. So this is what a computer basically sees, right? So let's say when we feed in this image of letter X to the computer, this is what it basically sees. right? So these are all of the numbers which are present in these pixels. So we have minus ones all over here in the blue spaces and 1 over here in the white spaces, right? So let's say this is our original image of X and this is our distorted image of X, and it's pretty much the same, right? So wherever we have the white labels, there the value in the pixel is +1, and wherever we have blue colors, there we have the value of -1. Now let's say if we use the normal comparison and compare each of these pixel values, right? So let's say we compare this pixel value with this pixel value. Similarly, this pixel value with this pixel value, and this pixel value here with this pixel value. But what happens with that sort of comparison is you would get a lot of missing pixels, which actually means that this is not the optimal way of image classification, since it requires exactly the same images to classify. Right? So this is the original image. This is a distorted image, and these orange pixels which you see, so these are basically all of the values which are not there in the original image. And this is not really the right way to classify our image. So this is where we can use a convolutional neural network. So let's understand how does a CNN solve this problem. So what actually happens in a CNN is we compare these images patches by patches, or in other words, we compare them with respect to these pieces or features. So earlier I had talked of something known as a filter. So these boxes which you see, these are those filters over here. So what I'll do is, I will start off by creating a random filter, right? And this random filter is nothing but an image of a left diagonal. Now what I'll do is, I will map this filter on top of this original image and find out if there is any match between this filter and this new image. Similarly, this is my second filter. Now this second filter is basically a cross. Now what I'll do is, I will take this filter and map this on top of this input image, and again I'll see if there is any sort of match or not. Again I'll do the same thing. I'll take this third filter, which is basically the image of a right diagonal, and I will map this on top of this input image, and I'll again see if there is any sort of match or not. So this is what is known as feature matching, and what I'm actually doing is creating some random filters and mapping those random filters on top of this new image to see if there is any match with respect to that new image or not. And each of these features is sort of like a mini image. You can consider this to be a small two-dimensional array of values. And as I had already said, we'll be using these three filters. So this is our first filter, which basically represents a left diagonal. So all of these white values, they have been represented with +1, and all of these black values, they have been represented with -1. And then we have the second filter, which basically represents a cross. So we have this left diagonal and right diagonal, which are basically the white spaces, and those white spaces have been represented with +1, and the rest of the black spaces have been represented with -1. And then finally we have this third filter over here, which actually represents the right diagonal. So over here, the values in the right diagonal or the white spaces have been represented with +1, and the rest of the values have been represented with -1. So again, what we'll do is pass these filters on top of this new image and see if there's a match or not. So now we'll start off by understanding each of these layers one by one, and we'll start with the convolutional layer. So as I had already said, when presented with a new image, the CNN doesn't really know where exactly these features will match. So what it does is, it tries them everywhere in every possible position. So in calculating the match of a feature across the whole image, they act as filters. And the math which is used to perform this is called as convolution, which you've already seen, right? So basically you can consider this to be a multiplication of two functions. So let's say you have a function f and you have a function g, and when you multiply these two functions, you'll have the overlapping part, and this overlapping part is what is known as the convolution. So there are 4 steps involved in this convolutional layer. So in the first step, what we do is we line up the feature or the filter on top of the image, and then we multiply each image pixel by the corresponding feature pixel. Now once we do that, we'll add all of the values and find the sum, and finally we'll divide the sum by the total number of pixels in the feature. So let's understand these 4 steps with the same example over here. So we've got this filter over here, and this is the filter of the left diagonal. Now what I'll do is, I will place or map this filter on top of this image over here. Now once the mapping is done, what I have to do is multiply these corresponding pixel values. Now let's say if I take this pixel value at the bottom right hand corner. So what I have to do is just multiply these two pixel values and I'll get a +1. Now this is just for this pixel value. So I'll do this for all of the pixel values. So this is what basically happens. I have my filter over here or my feature over here, and I am placing this on top of this image space. So obviously I can't place this small filter on top of the entire image. I can place this only on one region of this image. So I'm taking this filter and I'm placing this over this region. Now this is the first step. In the second step, what we do is we multiply the corresponding values. So when we do that, what we get is 1 cross 1, which is 1, and then we'll do minus cross minus 1, which is again plus 1. Again it's minus cross minus 1, which is plus 1 again, and then we'll do minus cross minus 1, which is plus 1 again. So we are basically multiplying all of these corresponding values, and we'll get ones over here. And after this, what we'll do is we'll divide this with the number of pixels in this cell, and that is 9. So when we add this up, this is 9, and then we divide it by 9 again. So we'll get a final result of 1. So going ahead, what we'll do is we'll take this 1 and place this at the center of this frame. Now similarly, I'll take the same filter and place this over this region of the image. So this is the first step, and again in the second step, what we'll do is multiply the corresponding values. So 1 cross 1 is 1 again, minus 1 cross minus 1 is plus 1. Now over here, when you multiply minus 1 with plus 1, what you'll get is a minus 1 over here, right? And similarly, when you take this value over here, it is minus 1 and it is plus 1 over here. So when you multiply 1 with minus 1, you'll again get minus 1 over here. So in the summation process, you basically have 2 minus 1s and 7 positive 1s. So when you divide this value with this value, what you get is a final value of 0.55. So again, you'll take this value of 0.55 and place this over here at the center of the frame. And you'll repeat that process for all of the regions over here, right? So you'll take this filter, place it over here, multiply the corresponding pixel values, sum it up and divide it by the number of pixels and place the final value at the center. Similarly, you'll take this filter, place it over the second region, take this filter again, place it over some other region, take this filter again and place it in yet another region, right? And finally, you'll have this set of values after passing this filter through the entire image over here, right? But then again, that was just the first filter. When you notice, we actually had 3 filters. So there was a filter which basically denoted the left diagonal. There was a second filter which basically denoted across. And there was a third filter which basically denoted the right diagonal. Now, we were just done with the first filter. That is, we passed the first filter over the entire image and we got this 2-dimensional array. Now similarly, we'll pass the second filter on top of this entire image and we'll get this modified 2-dimensional array again. Similarly, we'll pass this third filter on top of this image and again we'll get this modified 2-dimensional array. So this is where the convolutional layer ends. So again, I'm repeating whatever happens in convolutional layer. So we'll start off by finding some random filters. So let's say there are 3 random filters. Now we will pass all of those 3 random filters on top of this entire image and multiply those corresponding pixels. After multiplying those corresponding pixels, we'll add them up, find the sum and divide it with the number of pixels present in the entire feature space. Right, so this is the end of the convolutional layer. Now let's understand what happens in the ReLU layer, which is basically the second layer over here. So in ReLU layer, what we actually do is pass in an activation function over the result which we obtained in the first layer. So this function basically activates a node only if the input is above a certain quantity. So when the input is below 0 over here, then the output is given as 0. But when the input rises above a certain threshold, then it will have a linear relationship with the dependent variable. And let's actually understand that with this table over here. So let's say when the input value is -2, then the output would be 0. Because whenever the input is negative, the output would be 0. Similarly, we have this input value of -6. Again, this -6 is fed through the activation function and we get a value of 0. Now, when we have this value of +2, this ReLU function actually acts like the identity function and would give the same value, which is 2 again. And again, similarly, if we pass in +6 or +6, then again the ReLU activation function would act as the identity function and again give the same value, which is 6 again. And this is the symbol for ReLU, which basically denotes that if we have any negative values all of those would be represented as 0, and if we have any positive values, then this function acts like the identity function. Right, now we have the same two-dimensional array which we got after passing in our first filter over the image. Alright, so now what we'll do is pass in this ReLU layer over this two-dimensional array. And when we pass in this ReLU layer, what it basically does is converts this negative value into 0, right? And that is what we basically saw in the previous slide. So whenever there is a negative input, that negative input is turned to 0. And since the value over here is basically minus 0.11, it'll be turned to 0. And similarly, wherever there are negative values, all of those negative values would be turned to 0 with the help of this ReLU layer. And that again was just the two-dimensional array that we got from our first filter. And again, we'd have to do the same process for all of the three filters. So these are the three two-dimensional arrays which we got after passing through those three filters. And now what we'll do is we will take in these three modified two-dimensional arrays and pass this through the ReLU layer. And what we'll get is again modified two-dimensional arrays. So this time these two-dimensional arrays have no negative values, right? So we have this two-dimensional arrays over here, and these two-dimensional arrays have no negative values in them. Now after we pass these two-dimensional arrays through the ReLU layer, what we have to do is we have to pass them through something known as the pooling layer. So let's understand what exactly is a pooling layer. So pooling is basically a way where we take large images and shrink them down while preserving the most important information in them. So I'm repeating it again. So what we do in the pooling layer is we take in really large images, pass them through the pooling layer and shrink them so that we can keep only the important information and discard the insignificant information. Now this pooling layer comprises of something known as a window, and we'll take only the maximum value which is part of the window. So normally the window size is either 2x2 or 3x3. And this what you see is the symbol for pooling. So this is our two-dimensional array after passing it through the ReLU layer. Now it's time to again pass this image through the pooling layer. So as we already know, what happens in the pooling layer is we pass this image through a window and we'll take the maximum value through that window. So over here the window size which I'm taking is 2x2, right? So I will pass this window over these values, and what I see is the maximum pixel value is 1, and that is what I'll take over here. Similarly, I'll take a step size of 2 and again pass this window through this region over here, and this region would give me a maximum value of 0.33. Similarly, I'll pass this window to these four values, and from here I'll get a maximum value of 0.55. So now if you actually note this properly, we actually started with a 7x7 matrix and we ended up with a 4x4 matrix. So this is how pooling layer actually helps us in reducing the dimensions of the image, right? So this was the image after the second stage. We passed this through the pooling layer and we got a 4x4 matrix. And again, this was just the result from the first filter. We'd have to do the same thing for the rest of the two filters as well, right? So we'll pass in all of these three two-dimensional arrays to this pooling layer and we'll get a modified array again. And these modified arrays are of 4x4 dimensions. Right, now we'll go ahead and combine whatever we did through the convolutional neural network. So we had this initial image of X. We passed this in through the convolutional layer where we had basically mapped the filters on top of the original image and then multiplied the corresponding pixel values, added them up and then divided it by the number of pixels present in the frame. Now after that, we had passed the modified two-dimensional array to the ReLU layer which removed out all of the negative values. Now again, that modified two-dimensional array was passed through the pooling layer where we got a subset of the original array. And this is what we get after passing the original image through these three layers. Now what we'll do is instead of having just one set of these three layers, we'll pass them through a multiple of convolutional, ReLU and pooling layers. So I have this image. I'll start off by passing this through a convolutional layer and a ReLU layer. Now again, I'll pass this through a convolutional layer, a ReLU layer and a pooling layer. And again, I'll do the same thing. I'll pass this through the convolutional layer, the ReLU layer and the pooling layer. So now after this process, the 4x4 matrix has reduced to 2x2 matrix. And this is the result after the final pooling layer. So we have something known as the fully connected layer where the actual classification happens. So these were our two-dimensional matrices. Now what happens in the fully connected layer is we'll not actually treat these inputs as a two-dimensional array, So they are actually treated as a single list, and each of these values are treated identical. So we start off with these two-dimensional arrays and we convert them into this list. So I'll take this one, place it over here. I'll take the 0.55, place it over here. Similarly, I'll take this 0.55, place it over here. I'll take this one, place it over here. And I'll do the same thing for these two-dimensional arrays as well. So I'm restating it. I had this two-dimensional array to start with, but then again I am converting this into a list, right? And these are the set of values which I'll get for the image X. And similarly, when I pass in the image O through the convolutional neural network, I'll again have a different set of values associated with it, right? So now let's actually take a look at this vector closely. What you see is a set of values which basically comprise of 1 and 0.5, and we'll be only focusing on the 1 values, that is only the values which are higher, that is the first value, 4th, 5th, 10th and 11th value over here. So wherever we have ones, we'll take only those. Now how the classification basically happens is, let's say we have a new image. So from that new image, what we'll do is we'll compare the value which is present at the first position, 4th position, 5th position, and similarly these two positions. So if in the new image those corresponding values are 1, then there is a greater probability for that new input image to be X, right? And that is what happens with O as well. So over here for this list, we'll only focus on the high values. So over here the 2nd, 9th and the 12th values are high. So whenever a new image comes in, we'll only compare these values over here. So wherever values are high, we'll compare only those values. And if those corresponding values are high in the new input image as well, then we can go ahead and say that there is a good probability for that new image to be equal to O, right? So let's say we have this new image over here and it comprises of all of these values. Now I will go ahead and sum up all of those high values in the vector for X in the input image. So in the vector for X, this is 1, 1, 1, 1 and 1. So I basically have 5 ones which basically corresponds to 5. Now I will add up the same corresponding values in the input image as well. So I have 1 over here, I'll take 0.9. Similarly, I have 1, I'll take the 0.7. I have 1, I'll take 0.96. I have 1 over here, I'll take 0.9. Again, I have 1, I'll take 0.94. So what I'll do is, I will add up these values. So that is basically 0.9 plus 0.87 plus 0.96 plus 0.89 plus 0.94. And that gives me a final value of 4.56. So when I sum up the values from input image, I get a value of 4.56. And from this vector for X, I get a value of 5. And when I divide these two values, I get a probability of 0.91. So there is basically 91% probability that this new image denotes the alphabet X. Similarly, let's say if I want to compare this input image with the vector for O. So again, I'll do the same thing. I will take all of the high values. So I have 1, 1, 1 and 1, which basically when I combine it adds up to 4. Now I'll take the same corresponding values. So over here it is 0.65, 0.45, 0.44 and 0.53. Now when I add up these values, it comes up to 2.07. And when I divide 2.07 with 4, I get a final probability value of 0.51. This is actually very less. Now let's actually look at the summary of this. So we had this input image X. Now we took this input image and passed this to this convolutional neural network. And this convolutional neural network again had 4 layers. So the first layer was the convolutional layer where we mapped the filters on top of the input space and we got a modified two-dimensional array. Now we took that modified two-dimensional array, passed it through the ReLU layer and removed out all of the negative values. Now again we took this modified two-dimensional array and passed it through the pooling layer where we got a subset of the original image. And then we finally passed it through the fully connected network, which basically gave us the classification probability. So over here we see that the probability for this image to be X is 0.92 and the probability for this image to be equal to O is 0.51. So this obviously means that the image basically denotes the alphabet X. And this is the entire theory behind convolutional neural networks.
So let's understand the issues with feed-forward network. So let's say this is our feed-forward network over here and we are trying to solve a simple classification problem. So let's say I given an image of a food item and it needs to label it properly. So what I'll do is first I will give this feed-forward network an image of chicken. So when I give in an image of a chicken to this feed-forward network, it correctly labels it as chicken. So let's say I gave this input at timestamp t. Now again after some time, let's say at timestamp t1, I'll give it an image of pizza. So it takes in this image of pizza and then it again labels it correctly as pizza. So till here all of this is fine. So first I give this an image of chicken and it is able to correctly label it as chicken. After a while at timestamp t+1, I'll give it the image of pizza and it is able to correctly label it as pizza. Now the problem is there is no relation between these two outputs. So first we get the output which basically states that the label associated with this image is chicken, and second we get that the label associated with this food item is pizza. Now the problem is there is no sequence or there is no relation between these two entities. So this is where feed-forward networks fail. So they can't really memorize previous inputs. Now there are a lot of cases where we actually want the network to remember all of the previous inputs. And this is not really possible with the feed-forward network. So let's actually take another example. So let's say I have this sentence over here which states recurrent neural. So this is the input and I want my feed-forward network to predict the next word in this sentence. Now my question to you guys would be, would this feed-forward network be able to predict the next word? Well, that really is not possible because as we already saw, a feed-forward network is not really able to memorize the previous inputs. So the answer for us humans is pretty obvious. We know that recurrent neural should be followed with network because we have already learned the previous words. So we know that after recurrent, the next word would be neural, and after neural, the next word would be network. And we are able to predict the next word because we are able to memorize the previous words, and that is how our brain functions. But then again, this is not really possible with the feed-forward network. So this is basically where the feed-forward network fails. So now let's understand how can we solve this with the recurrent neural network. So over here, let's take another example. So let's say there's this chef who only cooks 3 items and 1 item on each day. So let's say he cooks chicken on day 1, pizza on day 2 and noodles on day 3. And again he'll continue the same thing. That is, on day 4 he'll again cook chicken, on day 5 he'll cook pizza, and on day 6 he'll again cook noodles. So it's as simple as that. So basically he has a set pattern and he'll not break that pattern. So let's consider that this is output at timestamp t1. Now, since we know that the output at timestamp t1 is chicken and there is already a sequence which has to be followed, we can say that output at t+1 will be pizza. And similarly, since we know what the output is at t+1, we can also predict what the output is at t+2. So the output at t+2 would be noodles. So guys, keep this in mind, and this is how basically your recurrent neural network works. So a recurrent neural network is basically able to memorize this sequence between all of the outputs. Right. So now let's understand how a recurrent neural network works. So let's say on day 1 or on timestamp t1, I'll give this some input. And with respect to that input, this recurrent neural network would predict that the food to be prepared on day 1 is chicken. Now, this output at timestamp t1 is not just discarded. So this output over here is sent to the next neuron at timestamp t2. Now, for timestamp t2, we have an input, and along with that input, we also have the previous timestamp's output. So it'll take these two into consideration. And since it already knows what was prepared at timestamp t1, it is easily able to gauge that the output should be pizza at timestamp t2. Now again, this output is remembered as well. So this output which we've received at timestamp t2 is again sent to the third neuron over here. Now this third neuron has some input, and along with this input, it also takes in the output from the previous timestamp. So along with this output and the input, it is able to predict that the output should be noodles. So this is how a recurrent neural network works. So basically the outputs at all of these timestamps are dependent with each other, and this recurrent neural network is able to handle sequential data. So what you see, these neurons are really able to memorize the previous inputs. So I'm reiterating again, this is timestamp 1, and at timestamp 1, this RNN predicts that the output should be chicken. Now, this output at timestamp 1 is sent to the neuron at timestamp 2. Now, with the help of this output from the previous timestamp, it is easily able to predict that the output at timestamp 2 should be pizza. Now again, this output at timestamp 2 is sent to this neuron at timestamp 3. And with the help of this output, it is able to predict that the food item which has to be cooked is noodles. Right. So now that we've understood this example properly, let's understand RNNs in better way. So as we saw in the example, RNNs basically have something known as a memory which captures information from the previous timestamps. And RNNs are called recurrent because they basically perform the same task for every element of a sequence. So let's say this is our input at t minus 1. Now this is sent to the neuron over here and this will give us an output at t minus 1. Now whatever information that we get from timestamp t minus 1, that is sent to the neuron at timestamp t. Now, along with the input at timestamp t and along with the information from timestamp t minus 1, it is able to give an output over here. Now, similarly, this information from timestamp t is sent to this neuron over here, and along with this information, there is also an input at t plus 1. So, combining these two, this will give us an output at t plus 1. So, this is how the RNNs work. And if you roll this entire sequence, what we get is basically a loop. So we are performing the same thing at multiple timestamps, and that is why RNNs are called as recurrent. So we provide the input, the operation is done, and we get the output at, let's say, timestamp t minus 1. Now again, the same operation is done at timestamp t. Again, the same operation is done at timestamp t plus 1, and this goes on till we get our final optimal result. Right, so now that we've understood the theoretical part of RNNs, let's also understand the math behind it. So again, we have this RNN.
Here is a quiz question for you guys. The question is, what is a neural network? Your options are a type of computer processor used for high performance computing, a machine learning model inspired by the human brain, a type of encryption algorithm used for secure communication, or a software application for organizing and visualizing data. Please mention your answers in the comment section.
Guys, I have a special announcement for all of you. For all of you dedicated individuals who are looking forward to master data science, we are offering a straightforward 20% discount on our data science course, which is in collaboration with iHub IIT Roorkee. So do make sure to check the link given in the description and fill the inquiry form. Shortly, our team of course advisors will get in touch with you to activate the offer. Don't miss this chance and take your career to the next level. Click on the link given in the description right now.
And we've unfolded this RNN, and when we unfold it, we have something like this. So we have different timestamps. So we have 3 timestamps basically, t minus 1, t and t plus 1. So let's actually consider this. So xto here is basically the input at timestamp t. Now I'll send this input to this neuron over here. And the way we calculate the value of this node is pretty simple. So it's what we've always been doing. Is basically input into the weight associated with this link over here. So input is xt along with the weight over here, which is u. So this becomes xt into u. Now this is just the input. So this is timestamp t, and we've already seen that the current timestamp takes input from the previous timestamp. So over here we have information from the previous timestamp, and that information is basically w into st minus 1. So this st, what you see, this is basically what is known as the memory of the network. So for this node over here at timestamp t, we'll get this input and this information from the previous timestamp. So in total, it becomes xt into u plus st minus 1 into w. But this is just a linear equation. Now we have to pass this linear equation through an activation function. So that activation function could either be tanh, relu, or any other activation functions that we've seen till now. And that is how we get the value of st. So again, I'm reiterating it. So to get the value of st, it is basically this input and the information from the previous output. So that is xt into u plus w into st minus 1. And we'll pass it through an activation function, let's say relu. And that is when we'll get the output, which is st. Now again, we have to pass this st through another final activation function, which is mostly softmax, because softmax would give us a range of probabilities, and when you add up all of these range of probabilities, it would sum up to be 1. Right. So we'll pass this st through the softmax function and we'll get the output at timestamp t. Similarly, let's consider this node at timestamp t plus 1. So over here, to calculate st plus 1, we'd have to take this input and this information from the previous output. So it'll be xt plus 1 into u plus w into st. And again, we have to pass this through an activation function. And we'll get the value of st plus 1. Now, if we want the final output at timestamp t plus 1, we have to again pass this through the softmax function, and the softmax function would give us a range of probabilities between 0 and 1. So this is how we get the outputs at different timestamps. This was the part where we did the forward propagation, and in that forward propagation we had outputs for different timestamps. Now again, after forward propagation, we would also have to train the network. And while training the network, what we see is the actual values and the predicted values are not really similar. And there would be quite a bit of error between the actual values and the predicted values. So what we'll do is, once we're done with the forward propagation, we will calculate the error for each timestamp. So here, let's consider this case. So let's say there are 4 timestamps. So we'll start with T4 or timestamp 4 over here. So over here, let's say the actual value is O4 and the predicted value is P4. Now, if we want to know the error in prediction, we have to subtract P4 from O4 and that'll give us an error over here. So this is the error for timestamp T4. Similarly, we'd also have to calculate the error in prediction for timestamp T3. So this time the error in prediction would be O3 minus P3. And then over here we have to calculate the error in prediction for timestamp T2. So this will be O2 minus P2. And for timestamp T1, it'll be O1 minus P1. And for timestamp T0, it'll be O0 minus P0. So now we have errors for each of the timestamps. So E0 is the error at timestamp T0, E1 is the error at timestamp T1, and so on. So now we have the individual errors for individual timestamps. We'd have to calculate the total error. And to calculate the total error, all we have to do is just sum up all of these errors. And when we sum up all of these errors, we'll get E total. So this is the total error which we've got while forward propagating. So now that we know the error in prediction, what we have to do is back propagate and fine tune our weights and bias so that we get the optimal value. And we've already seen how can this be done through back propagation and stochastic gradient descent. So in back propagation, what we saw is we have to calculate the change in error with respect to the weight. But that was simple back propagation. But now we are dealing with RNNs. So in RNNs, we have modules or nodes for each timestamp. So this time we have to calculate the change in error with respect to all of the timestamps. So now let me again go back and see how can we back propagate over here. So now while back propagating, we have to update 3 parameters over here. So those 3 parameters are U, V and W. So what we have to do is we have to find out the change in total error with respect to U, V and W. Now again, the gradient of total error with respect to these 3 parameters is nothing but gradient of E0 with respect to those 3 parameters, gradient of E1 with respect to UVW, gradient of E2 with respect to UVW, and so on. So what we'll do is we'll find out the change of these individual errors at each of these timestamps with respect to each of the parameter. So for this link, the weight associated was V. For this link, the weight associated was U. And for this link, the weight associated was W. So let's go ahead and back propagate and find out the optimal value for V. And if we have to do that, then we have to do it for each of the timestamps. And what we have to do is we'd have to find out the gradient of E4 with V. After that, we'll go back a timestamp and then we'd have to find out the change of E3 with respect to V. Again, we'll go back a timestamp and this time we have to find out the change of E2 with respect to V. Again, we'll go back and this time we have to find out the change of E1 with respect to V. So now, once we have the individual changes of these errors with respect to the parameter V, then all we have to do is add them up. So that will be gradient of E0 with respect to V plus gradient of E1 with respect to V, gradient of E2 with respect to V, and gradient of E3 with respect to V. And when we add all of that up, we'll get the final change in error with respect to V. Now similarly, we'll do the same thing with respect to W over here. So first we'd have to find out the individual change in errors with respect to W. So that'll be gradient of E4 with respect to W, gradient of E3 with respect to W, gradient of E2 with respect to W, and so on. And then we'll have to add all of that up, and finally we'll get gradient of E total with respect to W. And then we'll do the same thing for U over here. So that'll be gradient of E4 with respect to U, gradient of E3 with respect to U, gradient of E2 with respect to U, and so on. And again we'll add all of that up and we'll get the gradient of E total with respect to U. So this is how we've calculated the change in error with respect to U, V, and W. So we'll use this in the stochastic gradient descent formula and we'll update the weights of U, V, and W, and then we'll get our final optimal result. So this entire procedure that we saw over here is what is known as backpropagation through time. So we have one-to-one, one-to-many, many-to-one, and many-to-many. So we'll start off with the first type of RNN, which is basically one-to-one. So this is what is known as the vanilla RNN, and this is the simplest form of recurrent neural network. So this basically takes in a single input and gives out a single output. So an example of this could be, let's say we given one image or a single word and we want to classify this into a single class. So let's say I given an image of a bird and the output which I want is yes or no. That is whether this is a bird or not. Or let's say I given a value 30, an integer number, and I want to classify whether this is a positive number or a negative number. So again, yes or no. So basically what I'm trying to say is this takes in a single input and gives out a single output. So this is the simplest form of RNN. And then after that we have something known as one-to-many RNN. So in this we have a single input, but that single input gives us multiple outputs. So an example of this one could be, let's say if I given the first word of a song, then this RNN has to predict the rest of the lyrics of the song. So let's say there's a song, Hello Darkness My Old Friend. And if I give the input, which is basically the first word hello, then what it does is this RNN, it starts off by predicting the second word, which would be hello darkness. Now again, this RNN remembers these two words, which is hello darkness. Now these two words are sent as the input to the third timestamp, which is T3, and then it basically predicts the third word, which is darkness. And this again goes on, and the next word predicts as my, and then it goes on to the next timestamp again, then it will predict the next word as old. So we just started off with one word, which was hello, and it went ahead and predicted the next three words, which were darkness, my old friend. Right? So this is how a one-to-many RNN works. And then next we have what is known as many-to-one RNN. So this many-to-one RNN basically takes in a sequence of inputs and gives out one final output. So an example of this could be sentiment analysis. So let's say I feed this RNN a sentence, Cristiano Ronaldo is the best footballer in the world. Now, what this will do is, it'll take in this entire sentence and this will tell me the final sentiment of the sentence, which is either positive, negative, or neutral. So I feed this the first word, which is basically Cristiano, and this will give me the output, which is either positive, negative, or neutral. And this information from the first output is sent to the node at timestamp T2. And there is also an input, which is Ronaldo. So Cristiano Ronaldo, and we also have the output, which is basically the sentiment. And again, for this timestamp, we'll get another output, which is basically the sentiment, which is either positive, negative, or neutral. So for the entire sentence, Cristiano Ronaldo is the best footballer in the world, will have a sequence of outputs which are basically positive, negative, or neutral. So at the final timestamp, what we'll do is we'll aggregate all of these final outputs and find out the final sentiment. So if the final sentiment is positive, then we'll predict that it's a positive sentence. And similarly, if the final sentiment is neutral, we'll predict it's a neutral sentence. And if it's negative, we'll predict that it's negative. And finally, we have what is known as a many-to-many RNN, which is actually the most frequently used RNN. So an example for this could be predicting the next word in a sentence. So let's take this sentence. I'm going to be the next president of United States of America. So this will take in the first word, which is I, and then it'll predict the second word, which is am. And this is sent to the node at timestamp 2, and this will predict the next word, which will be going. So we have 3 words till now, which is I am going. And this again over here is sent to the node at next timestamp, and this will predict 2. So this basically becomes I am going to, and this goes on, and we have a set of nodes for different timestamps, and this predicts the entire sentence, which is basically I am going to be the next president of United States of America. So now we'll see the issues with recurrent neural networks. So it's not that these recurrent neural networks are perfect. There are issues with these as well. So again, we'll take this same example. So we'll pass in this sentence recurrent neural to this network over here. Now we have to predict the next word with the help of this RNN. So this is pretty easy. So this RNN, it memorizes this sequence recurrent and neural, and it is easily able to predict the next word, which is network. And it is able to do so because this RNN does not need any further context. And since it does not need any further context, so it is easily able to predict the next word. But now let's take this second case over here. So now I'll pass a really long sentence to this RNN. So let's say the sentence is, I've been staying in Spain for the last 10 years. I can speak fluent dash. So now for this sentence, it's not really that easy for RNN to predict the next word. And that is because this needs the context from previous words. So this has to go back a lot in the sentence. So this RNN has to go back till over here, and it needs the context of this word Spain. And only when it realizes the context of this word Spain, it can predict the next word over here is Spanish, right? So the entire sentence is actually, I've been staying in Spain for the last 10 years. I can speak fluent Spanish. But then again, this is exactly the problem with normal RNNs, and this is known as long range dependencies. So this gap which you see between the word which you'd have to actually predict and the word from which you'd have to find out the context, that is really long. And this is known as a long range dependency. So what happens in long-term dependency is, while backpropagating, the chain rule becomes really long. So let's say we are done with the forward propagation for this, and we start with the backpropagation. Now over here, since the gap between this word and over here is really long, and there are a lot of timestamps between all of these words. Now if there are a lot of timestamps, this basically creates a really long chain rule. And when there is a really long chain rule, it's not really that easy to memorize the previous words for this RNN. And this is exactly what is known as vanishing gradient descent problem. Now if there is a really long dependency, there is actually a good probability that one of the gradients might approach 0. And this would lead to all the gradients rushing to 0 exponentially fast due to multiplication. So let's say we start backpropagating from over here. And when we start backpropagating, the gradient, it slowly starts to diminish. So let's say we start backpropagating over here, and the gradient somewhere over at timestamp 4 or timestamp 5, it gets to 0. And when the gradient at one timestamp, it gets to 0, all of the gradients for all of the timestamps will be 0, because all we are doing is multiplication. And when we multiply 0 with any other number, it is basically 0. So such states would no longer help the network to learn anything. And this is what is known as vanishing gradient problem. So this vanishing gradient problem basically arises due to long-term dependencies. So let's say if we start from over here, timestamp 1, and we go back till timestamp 7. So what happens is there is a really long-term dependency over here, and the gradient starts to diminish as we traverse back. So this is where we have to use a modified version of RNNs, which are basically known as long short-term networks. So long short-term networks are special kind of RNNs which are explicitly designed to avoid the long-term dependency problem. So what you see over here, this is a standard RNN. So normally the recurrent neural networks have a form of a chain with repeating modules. So all of these are the repeating modules over here, and each module is pretty much the same. So normally in standard RNNs, they have a pretty similar structure. So all of these repeating modules would have just a single tanh layer or containing just a single activation function over here, right? So this is a standard RNN where there'll be just one neural network for each of the timestamps. So as we see over here, we have 3 timestamps, t-1, t, and t plus 1, and all of these are just recurrent, or all of these are just repeating. So for timestamp t minus 1, we have the same activation function, which is tan h. For timestamp t, we have the same activation function, which is tan h again, and this would be the same for timestamp t plus 1 again. Now this is the standard RNN. So this is where the difference comes with LSTMs. So again, LSTMs also have a chain-like structure, but the repeating module, which you see over here, this is actually different. So instead of having just a single neural network layer, there are 4 layers interacting in a very special way. So these are the 4 neural networks over here. So what you saw in a standard RNN was there is just one neural network. But when it comes to an LSTM, there'll be 4 neural networks. So let's actually understand the core idea behind LSTMs. So this line which you see over here, this is what is known as the cell state. So this cell state, you can consider this to be a conveyor belt, and this cell state is where all of the information is stored. Now the idea behind LSTMs is to add or remove some information to this cell state so that we avoid the long-term dependency problem. So when it comes to long-term dependency problem, there might be some cases where we don't want to remember some words. So there are some words which don't really have an impact on the next prediction. So, those are some things which you'd have to forget. And again, there are some cases where we'd have to add some new information to the RNN. So all of this can be done with the help of this cell state over here. So again, I'm reiterating it. With the help of this cell state, we can either add or remove information from the LSTM. And these gates are what help us to optionally let information through. So this gate basically comprises of a sigmoid neural net layer and a pointwise multiplication operation. So let's again go back to this image over here. So what we see is we have 3 gates over here. So this is gate number 1, this is gate number 2, and this is gate number 3. Now, since this is a sigmoid layer, this basically helps us to pass information which is in the range of 0 to 1. So a value of 0 basically means that we don't let anything through this gate, and a value of 1 means that we let everything through the gate. So this is again a range of 0 to 1, and this is how we can calculate the amount of information which has to be sent through one particular gate. So if the value is closer to 0, then very little or almost no information is sent through this gate. And if the value is closer to 1, then almost the entire information is sent through the gate. So now let's actually understand the working of these LSTMs. So let's start with our first gate over here. So this gate is known as the forget layer. And this is where the LSTM decides which information are we going to throw away from the cell state, right? So this is the forget gate layer over here. So what it does is it takes information from the input and also from the previous output over here. So the input to this forget gate would be xt into w plus ht minus 1 into w. And then again, we'll pass this through the sigmoid layer over here. And this will give us what is known as ft, which is nothing but a value between 0 and 1. And this is where we decide which information are we going to remove away from the cell state. So let's take the same example of predicting the next word in the sentence. So let's say this LSTM might keep the gender of the current subject so that it can predict the current pronoun for the subject. But then again, when it encounters a new subject, you want the cell state to forget the old subject's gender and only remember the current subject's gender, right? So this is basically where we forget the information. So this is done with the help of the first gate. So now that we decide which information is to be thrown away, the second step is where we decide what new information we are going to store in the cell state over here. So this has 2 parts. First is the sigmoid layer, which is called as the input gate layer. So this input gate layer decides which values we'd have to update. After that, there is this tan h layer, which basically creates a vector of new candidate values that could be added to the state. And with respect to the language model, this is where we can add the information of the new subject's gender and remove the information of the old subject's gender. So we have 2 parts over here. So first is where we update the information. So this is basically where we take information from xt and ht minus 1 and pass it through the sigmoid layer. And after that, again, we'll take information from xt and ht minus 1 and pass it through the tanh value. So what we are doing over here is we are basically creating new set of candidate values, right? So we have IT and CT over here. So CT is basically the new candidate values which we want. So we are done with the first two steps. In the first step, we decided what is the information which you want to forget. In the second step, we decided what is the new information which we're going to add into this cell state. Now let's head on to the third state. So in the third state, we basically have to update the old cell state CT-1 into the new cell state CT. So what we do is we multiply the old cell state CT-1 by FT. So this means that this is where we are forgetting the old things, or we are removing the old information. So CT-1 into FT. So FT is basically that information which we got from the first gate, and first gate is nothing but the forget gate layer. So when we multiply FT with CT-1, what we are doing is we are forgetting the old information. Now we'll add this with IT into C cross T. So this term basically means what is the new information which we want to add to this layer, and by how much value do we need to scale this. So the first term is where we decide how much information are we forgetting, and the second term is where we decide how much new information are we adding to the cell state, and we then just add it up and get the new cell state which is CT. So from CT-1 we are going to CT. So I'm again reiterating it. So this consists of two parts. So in the first part, we basically forget all of the information which is not necessary or not significant. And in the second part, we update or add the new information. So from CT-1, we reach till CT. And then we've reached the final part. So this is where we'll decide what part of the cell state that we're going to output. It's not necessary that the entire output is useful to us. So only a range or only a part of the information or the output would be necessary. So this equation which you see, so this is where we decide what part of the cell state we're going to output. So now after that, what we'll do is we'll put the cell state through the tanh and multiply it with the output of the sigmoid gate. And this gives us HT, which is basically our final output. So first we decide which part of the cell state we are going to output, and then we'll pass the cell state through the tanh function. This tanh function gives us a range which is between -1 to 1, and we'll multiply this with the output, which is basically our final result. So these are the 4 steps which are involved in an LSTM. So first we forget all of the insignificant information, and then the second step we add the information which is needed. Now in the third step, we combine the first 2 steps, and finally in the fourth step, we only output the information which is necessary from the cell state. So this is the entire working of long short-term networks. So let's say if we have 5 numbers like this, 5 consecutive numbers actually, 1, 2, 3, 4 and 5. And our task is to predict the next number, which would be 6. So this is our task, and we'll be implementing this with the help of LSTM. So we'll go ahead and import all of the required packages. So we'll import sequential from keras.models, we'll import dense and LSTM from keras.layers, and we'd have to split our data. So we'll import train test split from sklearn.model selection. And we'd also require the numpy library and matplotlib library. So I'll go ahead and click on run, and I'll just wait till all of these packages load up. So now it's time to create my input data. So this code over here, it helps me to create 100 vectors of 5 consecutive values. So I'll store this in data, and let me have a glance at the first 5 vectors. So I'll click on run. So this is what I have over here. So this is the first vector where the consecutive numbers are 0, 1, 2, 3 and 4. And over here I have 1, 2, 3, 4 and 5. This is 2, 3, 4, 5, 6. So these are basically the first 5 vectors, and these comprise of consecutive values. Right. So this is basically my input data. Now I would also require my target data, which is basically the next number. So as I had already told you guys, what we want to do with respect to this model is we want to predict the next value for a consecutive sequence of inputs. So over here, this is our input, which is basically 1, 2, 3, 4 and 5. And we'd want to predict the next value with the help of our RNN, which will be 6. So what I'm doing is I'm creating the next number for each of these arrays. So over here, it'll be 5, for this it'll be 6, for this it'll be 7 and so on. So I'll click on run. Right, so this is what I have. So for the first vector, the target is 5. For the second vector, the target is 6. For the third vector, the target is 7, and so on. Now, I'll go ahead and convert this data and target into NumPy arrays. So for that purpose, I'll use np.array and pass in the data object inside this, and also similarly pass in the target object inside this, and store it in data with a small d, and similarly store it in target with a small t. I'll click on run. Right. So now I have my NumPy arrays with me. Now I'll also have a glance at the shape of data and target. So this is the shape of data and this is the shape of target. Now this is basically helpful to me when I am giving these as parameters when I'm building the model. So now since I have the data, it's time to finally divide this data into training and testing set. So for that purpose, I'll be using this train test split method, and it takes in these parameters. So first is basically the data or the features. Next is the target or the labels, and I'm setting the test size to be 0.2. So this means that 80% of the records would be in the training set and the rest 20% of the records would be in the test set. And I'll just give out a random state value of 4 so that I can get the same result when I want to run this model the next time. Right. So I'll click on run. And I have successfully divided this data into xtrain, xtest, ytrain, and ytest. So xtrain over here, this basically contains all the training values for the features. Xtest over here contains all the test values for the features. Similarly, ytrain over here consists of all the train values for the target, and ytest over here consists of all the test values for the target. Right. So now we've divided the data into training and testing. Now it's time to create a model, and we are basically creating a sequential model over here. So I'll use the sequential method and I'll create an instance and store it in this model object. Right. So now it's time to add the layer, and the layer which we'll be adding over here would be LSTM. So I'll use model.lstm. So I'll say model.add, and the layer which I'm adding is LSTM. So this takes in a parameter over here, and this is basically the output size. So I want the output size to be equal to 1, which is basically I'm predicting a single number or a single value over here. And then we have the batch input shape. So the batch input shape basically takes in 3 values. So the first value is the number of inputs, second is the input sequence, and third is the length of the input sequence. So over here, if you don't know the number of inputs which you have, you can say it as none. And since the input sequence is 5, I said it as 5, and the length of the input sequence is 1, and I've given it as 1. And then we have another parameter over here, which is basically return sequences. So this return sequences basically means that do I want the output for each timestamp, or do I just want the final output? So if I set it to be true, I'll get the output for each timestamp, and if I set it to be false, I'll just get a final result. So over here, I've set this to be false. Right. So now I have created the model. Now it's time to fine tune it. And to fine tune it, I'll use model.compile method, and it comprises of these 3 things. So first I'll set the loss which I want to minimize. So I want to minimize the mean absolute error. And then I'll set the optimization algorithm. So the optimization algorithm which I'm using is Adams. And then basically the evaluation metric which I want to use. So the evaluation metric which I'm using is accuracy. I'll click on run. Right, so now I've also compiled my model. Now let me just have a glance at the summary of this. I'll click on run now. Right, so we see that this is my LSTM model, and I have my output shape over here. Now since I've also compiled my model, it's finally time to fit the model on top of the train set. So for this, I'll use model.fit, and I'm basically fitting this model on top of xtrain and ytrain. And initially I'll set the number of epochs to be equal to 50, which is actually less. And I want this to evaluate on top of the validation data. So validation data is basically xtest and ytest. So I'm reiterating it. I'm fitting the data on top of xtrain and ytrain, and I'm validating it on top of xtest and ytest. I'll click on run. So the model fitting is done, and this is what we have, the final result over here. Now that we've fit the model, let me also go ahead and predict the values on top of the test set. So I'll use model.predict, and I'll pass in xtest as the parameter inside this. I'll click on run. Right. So I have predicted the values and I've stored the result in this results object. Now that is done, what I'll do is I will actually make a scatter plot which comprises of the actual values and the predicted values. So I'm representing the actual values which are present in ytest with green colored dots and the predicted results which are present in results with red dots. And I'll plot it out. Right. So these green dots which you see, these are the actual values, and these red dots which you see, these are the predicted values. So with the help of this graph, we understand that the prediction is totally wrong and our model is very bad. Now, along with this, we'll also make a plot of the loss. So plt.plot, and I'll make a loss plot. I'll click on run. Right. So we see that the loss of the model does not decrease at all, right? It stays constant. And that is why this is a very, very bad model. Now, this is because we have not normalized the data. So whenever we don't normalize the data, there might be chances of exploding gradient descent and the model turns out to be really bad. So that is why we have to make sure that our data is normalized. So I'll go ahead and do that. So I will basically divide the input data with 100. Similarly, I'll also divide the target data with 100. So what we are doing is normalizing the data. I'll click on run. Again, I'll click on run. Right, so now we have the normalized input and output data with us. Again, I'll go ahead and convert these into NumPy arrays. Again, I'll split this into training and testing set. Build the model, add this, compile this. Now I'll go ahead and fit the model. I'll click on run. Right, so all of the 50 epochs are done and I'll predict it on top of the X test. Now again, I'll go ahead and plot the actual values and the predicted values. I'll click on run. Right. So this time we see that there's a bit of improvement, but then again, this is not much. So initially all the red dots were scattered over here. Now it's just that they have come up a bit up, but then again, there is no correct prediction at all. Again, let me print out this loss plot. So this time it's okayish, it is reducing, but then again, the loss is not decreasing much. Now, what I'll do is I will go ahead and increase the number of epochs. So the number of epochs were 50. I'll change the number of epochs to 500. And let's see if there's a difference in the prediction or not. I'll click on run. Alright, so the model is being fit. Right, so all of the 500 epochs are done. Now I'll go ahead and predict this on top of the test set. And again make a scatter plot of actual values and predicted values. So this time the prediction is much better. But then again, this is not 100% accurate. So now let me print out the loss plot again. Right. So this time the loss reduces in a better way. Now again, what I'll do is I'll increase the number of epochs again. And this time I'll set the number of epochs to be equal to 1000. And let's see what happens. I'll click on run. So now we've fit the model. I'll predict this on top of the test set. And again, I'll make the scatter plot. I'll click on run. Right. So this time we see that the accuracy is very good. The predicted values and the actual values are very close. So the red dots are the predicted values and the green dots are the actual values. And we see that most of them are coinciding, right? And this is a very good result for us. So basically what we had to do was we had to normalize the data, and after that we had to increase the number of epochs. And this is how we could make correct predictions and reduce the loss. And just to be sure, let me again plot this loss. Right. So now we see that the loss is actually decreasing very well, and after that it stays constant, right? So this is the sort of loss plot we wanted. So this is how we could build an LSTM network which was able to predict the next number for a consecutive sequence of numbers.
Here's a quiz question for you guys. What is tokenization in text processing? Your options are converting text to lowercase, removing punctuation and special characters, breaking text into individual words or tokens, or translating text from one language to another. Please mention your answers in the comment section.
Guys, I have a special announcement for all of you. For all of you dedicated individuals who are looking forward to master data science, we are offering a straightforward 20% discount on our data science course, which is in collaboration with iHub IIT Roorkee. So do make sure to check the link given in the description and fill the inquiry form. Shortly, our team of course advisors will get in touch with you to activate the offer. Don't miss this chance and take your career to the next level. Click on the link given in the description right now.
Singular value decomposition, SVD plus Netflix project we are going to do. So see, as the name and the project and the agenda of the day is going to be lengthy, so we have to cover up together everyone. So I want each and everyone's complete attention over the screen, okay, as this project is going to be really interesting, and I hope we all are going to enjoy it while learning it, okay. And Netflix is what, like we are going to build a project, like sort of movie recommendation we are going to do. Okay, we are going to do some sort of movie recommendation. In the end, we'll be building such project. But before that, to do that, to achieve that goal, let's understand what SVD is first, everyone, right? Let's understand what SVD. The algorithm that we are going to cover is going to be our SVD. That stands for singular value decomposition. Singular value decomposition. What do we mean by decomposition? Matrix decomposition. Have you ever heard what's matrix decomposition? In your linear algebra, I hope everyone must have studied the concept of matrix decomposition. Correct? There we were studying various factor to decompose a matrix, right? Now, what was the goal behind that? What was the goal behind doing the decomposition of a matrix, so that we can get some valuable insights from it, like some other patterns also we can analyze from that matrix. Correct? Now, if not, if anyone have any confusion, tell me guys, are we aware what do we mean by factorization? Are we aware what's the meaning of factorization, guys? Factorization. Correct? Let's say if I will give you a number, let's say I give you a number, let's say 45. Now, can you tell me what will be the factors of 45? What will be the factors of 45? Can I say it's going to be 3 multiplied by 5 multiplied by 3? These are the factors of 45. One factors of 45. Am I correct or not, everyone? These are one factors of 45, right? 45, correct? 3 multiplied by 5 is 15. 15 multiplied by 3, you will get 45, right? So now here what I'm doing, like this single value, I'm decomposing it to 3 small values. So now see here, I'm able to get some new information. Like this number is divisible by 3, divisible by 5. It's a multiple of 3 as well, correct? These information I'm getting by doing the factorization. Am I correct or not, everybody? So see, in the same way, in SVD machine learning algorithm, now see, SVD is our algorithm name, and this algorithm uses the function of SVD. That's why it's known as SVD algorithm. It uses the function of SVD. Like SVD is a mathematical function that we use. Like in the same way, guys, have you studied naive Bayes algorithm? Are we aware about logistic regression, guys? If you remember, in logistic regression also, there's some, we have the sigmoid function. We have the sigmoid function, correct? In logistic regression, we have that, right? We have that sigmoid curve, right? And in logistic, there's probability also. We have via which we divide our data into two categories, via which we classify the data. Am I correct or not? There's probability also plays a role. Am I right or not, everyone? In logistic regression. So with the help of these mathematical tool, I am building my model logistic regression. Am I correct or not? Everybody, by using these mathematical tools, I am building my model a logistic regression. I'm building the algorithm of logistic regression. Correct? Now, in the same way, our SVD also, our SVD, singular value decomposition algorithm, also internally uses the working of SVD, which is what by singular value decomposition. It's a mathematical function that is used to decompose your matrix. Okay, so SVD is a mathematical function that is used to decompose a matrix and get valuable insights from it, right? Because from this function our algorithm is being generated. Okay, so like what we will be having in SVD, it's entirely what we have. Like we represent our data, like we have the data in rows and columns, correct or not, everyone? We have our data into rows and columns. What we do, we convert it into a matrix, then we pass it to the function, and it decomposes it and find various hidden patterns from it. Okay, find various hidden patterns from it. Okay, so now as SVD, what it is doing, it is doing decomposition as well, and along with that, it is helping us to find the hidden patterns in our data, the hidden relations in our data. Okay, it builds the relation with all the values we have. I will give you one example as well how it's going to work. Okay, we will discuss that as well, but it is going to build a hidden patterns. So now what we can do from the hidden pattern, it allows us to build or to give recommendation. SVD allows us to give recommendation. So it is used for collaborative filtering technique, we say. Okay, so SVD is used for, let me write here, SVD is used for collaborative filtering techniques. Okay, mainly for recommendation systems such as what do I mean by recommendation system? Now simple as that, guys. Let's say we'll consider a very simple example. Let's say I'm using Flipkart and I'm looking for some shoes. Okay, I'm using Flipkart, I'm looking for some shoes over there. I'm trying to buy some shoes over there. Now simple as that, if I will click on a product, just below it we get different recommendation. Am I correct or not? Everyone? Am I correct or not? Suggested products, correct everybody, we see that, right? Like along with shoes, sometime let's say with shoes, sometime let's say according to my preference, in suggestion we sometime get t-shirts as well. Am I correct or not? We get socks as the suggestion, right? Correct. First we will get shoes, we get different majority of shoes, and along with that we get different category of products as well. Correct or not? Let's say if we are looking for t-shirt, we get shirt in the recommendation, right? We are looking for a phone, we get adapter, we get the other things at the recommendation as well. Correct or not? So how that recommendation working, like previously, on the basis of previously, let's say a user who looked for the same product before, along with that that person might have bought some these product as well along with that. Am I correct or not? That can be a possibility. Like some other user who bought shoes, along with that they bought the socks as well, so that's why they will recommend it to me. Like other persons are also purchasing it, might be a possibility you will also purchase it, so that's why they give us recommendation. One factor can be that, and another factor is, now let's say I'm watching something. Now there's another example if I will give you, everyone. Let's say we watch something on YouTube. Now there, if I let's say I like to watch National Geography. Okay, let's say I like to watch National Geography, okay, on YouTube. Now if I will click on the video, you know, after that I will get all the recommendation from National Geographic videos. Am I correct or not? Different videos, different places. So whatever content we watch, on YouTube, let's say Netflix, Amazon Prime, we get suggestion, recommendation accordingly. Am I right or not, everyone? Everybody notices that, right? If you will go to your home page of your YouTube, there you will see the video that you like, that you generally watch, the genre that you prefer, that only you will get. Correct. So how it's working? It's working via the recommendation system. Like based on your previous input, it is recommending you the upcoming input. Based on the previous input, it is recommending you the upcoming input. So are you getting the idea what SVD is doing, guys? Everyone, first of all, what's recommendation system? Everybody is getting an idea. What do we mean by recommendation system? What's the idea behind that? Okay, like what we are going to do, so we are also going to build a project that will do such task. Okay, that is going to recommend the movies. Okay, but now along with that, now the question is how that SVD is doing that, right? How that SVD is doing that, like see, first of all, simple as that, like it is working, it is going to convert the data into a matrix, and from that matrix it will give us the valuable insights. Okay, now see, we know, like we don't need to go in mathematics because it's really complicated and it will take so much time to explain as well. Okay, so I will give you an overview, like I prepared this matrix for your reference so that you will understand, you will get the idea what SVD is and how it's going to help us. Okay, so now see, guys, what's the formula? Let's say if a particular matrix we have, let's say A is a particular matrix. For this, if I'll apply SVD, the formula we have is mu summation and the transpose of the matrix. and the transpose of the matrix. So what it is going to do, simple as that, if I have a matrix A, it will be decomposed into three factors. Here we can see the matrix will be decomposed into three factors, and from these three factors we will get some valuable insights. From these three factors we will get some valuable insights. Now let me give you an example. Now everyone pay attention, let me give an example. Let's say I have a matrix, guys. I have a matrix. Here I have three movies, movie 1 and movie 2, movie 3. Okay, these three metrics we have in our data, like these three columns we have in our data. Okay, and here we have, let's say, the user 1 who was watching the movie and user 2. Okay, and here I will be having the ratings. Like here the data will contain ratings. Okay, I'm creating a matrix over here. Let's say user 1 is giving rating to movie number 1 as 5 star. Okay, out of 5 we are talking, the user 1 is giving 5 stars over there. Okay, now for movie 2 user 1 is giving 3 stars. Okay, for user 1, for movie number 2 it is giving 3 stars, and movie number 3, let's say he didn't like or something, he's like, let's say he doesn't have any idea, he didn't watch the movie till now, so he didn't give any star, so by default I am filling 0 over here. Am I clear, everybody? These are the ratings my user is giving to movies. Like movie number 1, the user is giving 5 star. Movie number 2, the user was giving 3 star. Movie number 3, the user didn't watch, so he is not giving any star. And let me add one more thing. Let me add genre as well. Let's say movie number 1 categories. If I'll write here, let's say category of the movie, genre of the movie. Let's say here the movie number 1 was action. Okay, the movie number 2 was drama. Okay, and movie number 3 we are not aware, it might be some thrill. Okay, movie number 3 might be thrill, we are not aware, the user didn't see. Okay, now user number 2, let's say user number 2 to movie number 1 he is giving the star as 4. Okay, for movie number 2 he didn't see, 0. Movie number 3 also he didn't see, so the stars are 0. Right, now see, this is what the entire matrix is. What, see, now from this matrix what we are going to do, we are going to apply SVD. So SVD will decompose this matrix into these factors. Okay, so now let me tell you what are these factors are going to be. So first what we are doing, decompose the matrix. So from decompose, first thing I will get is u. Now u is what, in simple terms, u is what, the calculation, from the calculation I will get the u is going to be what, it is going to be my user preference, like what my user is liking, what's the preference of the user. Okay, u is what, my user preference. Like, so now let's see, like user is giving, now see what I am going to do. See, for this user, the user is giving ratings to these features. Now out of this I will create user preference, a matrix, new matrix will be created where it will be keeping importance of every feature, where it will be having the importance of every feature. So here see how my new matrix, like the u matrix, will look like. Here I will be having, let's say, feature 1 and feature 2. Okay, and here I will be having my user 1, user 2. Okay, now here see feature 1, it will give the feature 1, let's say feature 1 0.85. Okay, feature 2 it will give 0.53. Now what are these, see, these are the features that we got from the movie category. Feature you can consider as movie category. Okay, you can say movie category, like there are different feature. I won't say one feature, there can be multiple feature. Like let's say I was talking about category, so let's say feature 1 was action, right, and feature 2 was drama. Okay, and here I am seeing how much importance they are on the basis of their ratings, how much important they are according to user. Okay, like for action movie and drama movies. Okay, and here I won't keep the genre, okay, because it might be confusing. It might be confusing. Now let's consider it like this. Okay, now for user 2, let's say user 2 will give feature number 1 as 0.53, and here it will give as, let's say, 0.85, negative of 0.85. Okay, It is computing, like how important they are. How important they are according to user. Let's say, so here what we can say, like how much the user is liking those features. Okay, how much they are related with each other. So this is what we are going to get. Okay. Now after that, we are going to get the value of S, you can say, or you can say summation, that are known as your singular values. That are known as your singular values. Okay. That will be our singular values that we will get. Singular values. Now in singular values, what we will get? Okay. Just see, it means how, whether the person is liking it or not. Okay, whether the person is liking it or not. Okay. Now see, here, if I talk about the singular value, now here also simple as that, like I will get in singular values, I will get the importance of this feature. In singular values, I will get the importance of the feature. Now let's say here I will get the singular value, let's say 6.3, and for second feature I got the value as 1.5. Okay, so now guys, here which value is high? Which value is high? This 6.3 is larger, correct? 6.3 is larger, so this will become, I can say, like, let's say strength of primary feature. This is what the strength of primary feature. This will become my primary feature, right? This is the strength of the primary feature, I can say. In the same way, this 1.1 will be what? This will be my secondary feature. This will be my secondary feature because it is contributing less. Okay, so now it can be a possibility. It can be a possibility, like this can be my action movie and this can be my drama movie. Correct. This can be my action movie, this can be my drama movie. And along after this, what I will do, I will calculate the transpose of the matrix. Now you guys will see the transpose that I will create. Now VT is going to represent what? The movie characteristic. It is going to represent the movie characteristics. Movie characteristics. Now how it's going to represent? See, so here now we are going to do transpose of a matrix. So when I will do transpose, simple as that guys, what will happen? Feature will go as the column name, feature 1 and feature 2. Now what I will do, see, I am going to recommend the movies, or I am going to say the movies. I will make an estimate how my user is going to like the movies. How much are the chances the user will like the movies? Okay, let me show it to you. Let's say here we have the movie 1, here we have the movie 2, and here we have the movie 3. Previously we were getting the ratings from the user, right? And then we were estimating the movies. We were saying like how much the user liked the movie. But now on the basis of features, we are going to rate the movies. Okay, like movie number 1, let's say I will get value 0.93. Feature number 2 for movie number 1, 0.37. Now movie number 2, 0.37. Now movie number 2, let's say negative of 0.93. And here we will get, let's say movie number 3, did no one was, there was no rating, so it will be 0. It will be 0. Okay, but now here the thing is what to observe. Now guys, simple as that. Here if you will see, user number 2 has no ratings for movie number 2. Correct, we had no ratings for user number 2. Correct, but after performing my SVD, after performing the decomposition of the matrix, here you can see, like I got the features, I got the feature score as well, like how much the category, like feature number 1 is what? It can be action. Feature number 2 can be what? It can be drama. So how much that movie might be belong to that category as well, and how much my user can, and accordingly I will recommend to the user. If the person is looking for, let's say, drama movie, I can suggest movie number 2 because it has more feature of drama. Correct. So in this way, the SVD algorithm works. In this way, the SVD algorithm works. Like we will see how it's going to work, but everyone getting the idea what we are going to decompose the matrix. See, everything will happen internally. We don't need to do anything, right? But we should be aware an idea, like SVD uses the formula of, okay, here we can see mu s v transpose. You can call it s, you can call it summation. Okay, so what we do, we decompose the matrix into 3 matrix over there. Okay, so that we can fetch more information from the same, like in this way we are going to convert our data frame, that we are going to see and then we are going to pass this data to the SVD algorithm, okay, and then it is going to give us the estimate score, like this particular person will recommend or give ratings this much to this particular movie, correct? Now see, I know, I do understand some of you might be getting confused like what this algorithm is. So see, first of all, let me tell you, SVD is a singular value decomposition, an algorithm which help you to calculate estimate score by decomposing the matrix, okay, by decomposing the matrix. So now wherever we are having null values means like wherever we are not having any value, like user is not rating any value, like for that particular movie the user hasn't seen it, so it will be null. So SVD, from the previous value it is going to decompose, and from the inside it is going to recommend, like for that particular user this much ratings will be good, okay. So this is how SVD is going to work. This is how your SVD is going to work, and when we are going to build the model we will understand many new things from it, okay. So let me just add the screenshot over there, okay. Right now here we are going to build a Netflix project, guys. So date is 13/4/2025, okay. And guys, the data set is going to be really huge. Like right now we are not talking about thousands of rows or lakhs of rows. There are going to be crores of rows in our data, okay. There will be crores of rows in our data, okay. And the data is uploaded in my drive. So let me tell you and everyone, in this project we will be using a surprise library, okay. What that library is, like it contains your SVD module, okay. So it's over there. Now that doesn't work well in Jupyter notebook, guys, okay. The surprise library doesn't work good in Jupyter notebook. So what I will suggest everyone to go for Google Colab, okay. Like right now you don't need to write the code, okay. You don't need to do the hands-on, because then if you will try to do hands-on you will be giving more impact on coding over there, okay. And I want right now you guys to understand the program, what are the steps we are doing, each and everything, okay. So see guys, how we are going to load the data set. Now guys, that data set is uploaded in my drive. Now let me tell you one more concept, how you can connect your Google Colab with your Google Drive, okay. Let me tell you how we can connect our Google Colab with Google Drive. So what you need to do, everyone pay attention, like on the left hand side we have the file option, right here we can see from where we upload any data set, correct. From here we upload any data set, right, upload to session storage. Now from here what we will do, here you can see the third option, you can see mount drive, correct. We are going to mount our Google Drive over here. I will click enter on it. See, mounting Google Drive, it will ask for me as well. See, connecting to Google Drive will permit code executed in the notebook. So from here we will be able to access our Google Drive, okay. So I'm connecting it. Here you can see I'm just connecting it, okay. And meanwhile I'm going to import the necessary libraries such as pandas, such as numpy, matplotlib, such as seaborn. Right now, see what I'm going to do. Now here I'm going to read my data set, okay. It's connected. Now in the drive I will open it. Here's my drive, okay. Here is my Netflix data set. Now here we will be using two data sets, guys. We will be using two data sets. First is going to be my combined Netflix data. Second is going to be Netflix movie data, okay. We will see each and every one. First I'm going to use combined Netflix data. I'm going to copy the path, okay. I'm going to read over here. See, df is equal to pd dot read underscore csv, and here I'm going to pass the path, and here I'm going to look at my df, okay. Now the data set is really huge, so it will take good amount of time to execute, okay. And we will see how the data set is looking. And there are, see guys, the major issue we are going to face is with the eda, because the data set contains, like, there are many, the data set is so mixed up, okay. So we are going to clean it, okay guys. So now let us just wait for it to execute. Here you can see it's still executing, right? Here you can see, and you guys can clearly see how many rows we have. We have 2 crore 40 lakhs 58,262, right? Once 10,000 10,000 lakh 10 lakh crore 10 crore 24 lakhs 58,262. Correct or not, everyone? Here we can see, correct, the data set is really huge behavior right now, right? And guys, if you will observe over here, now it is showing you 1 over there. Am I correct or not, everyone? It is showing us 1 over here, right? But now the thing is, guys, the data set is something like this. Let me explain the data set, everyone. Then we will see what correction we need to do. Okay. And see, first of all, here what we have here, first of all, we don't have the column names, everything. We have the date as well. Okay. So here in this data set, we have few things. Okay. In this data set right now, we have the customer ID. Okay. We have the movie rating, like how much movie and the date. Okay, these three things we have with us right now. Customer ID is what, like ID of the customer. Like if you go on IMDb or something, we have we create our ID, right? And then we can rate movies, correct? So customer ID is the ID of the user ID. Okay, user ID, right? Movie rating is what, like how much person is rating any particular movie. So out of 5, we have the ratings. It can be 2, 1, 5, correct? So it can be ratings of the movie 1, 2, 3, 4, 5. And date. And date. Now date is what? Date is representing. Date is representing at what date the user gave us the rating. Okay, at what date user gave the rating. Now, first of all, tell me, guys, do you think the date column is important to us? Do you think, does it matter when the person was giving rating to the movie? Now, ask me, answer me honestly. When you go for a movie, you check the ratings online, right? Do you see like when the user gave the rating? Doesn't matter, right? Even if we find a 10-year-old movie with good rating, we watch it. Correct. So in the same way, we can see the data set is not, the column date is not important to us. And now one major issue, one more we have with this data set, guys, in this customer ID. See, now let me tell you how the data set will look like. Like here we have customer ID. Here we are going to have customer ID. Here we are going to have rating, correct? Here we will be having rating, right? And date we are going to remove and we are not considering. Now here I will be having different customer ID, right? 56, 200, 350. It can be any user ID, right? Randomly user ID, and rating such as 3, such as 4, such as 5, correct? Everyone, we will be having such values, right? Correct or not? So now first is what I am going to do. The very first thing I am going to do is what? If you will look at the data set, here you can see like I don't have my column names. Am I correct or not? I don't have my column names. And one more thing, guys, this one, you guys can see one and column. Here we can see one and column. This is my row. This is my row, but it is considering it as the heading of my column. When I'm reading the file, here you can see I'm reading a txt file over here. Okay, these are represented in my entirely text file because the data set was really huge. Okay, so here I am reading. The major issue is what, like it is considering my first row as the header, correct or not? As the header, it is considering my first row as the header. So to resolve that, what I will do here, I will pass the header is equal to none. Okay, I will pass the parameter, so it won't consider it as my header. And second thing is what I will do. See, I will pass like out of these three columns. Out of these three columns, I need the first two columns. Am I right or not, everyone? I need the zero index column and first index column. Correct. So what I will do here, I will pass the parameter. See, use columns. Here I will pass 0 and 1 because I want to use only these two columns. Okay. And the next thing what I will do, I will give them column name as well. So I will use the names parameter and here I will give them column. Let's say first is going to be my customer ID and second is going to be the ratings. Let me read the data set once again. Okay. It will take some time, but look at these three parameters. Header is equal to none because it was considering my row as the header. So I pass header is equal to none. So it won't consider it. Now I will see it as a row. We will see. Here you guys can see. You can see I'm getting it as a row now. Everybody, this one was at the very top. It was my header, correct? The first row. But now I'm seeing it as my very first row. Correct? It was my header. Right? In the same way, here I selected only two columns, 0 and 1. I removed the date column from here and I gave the column name as well. Customer ID ratings, which were missing, now they are. Okay. Now, guys, we have one issue with the data set. If I will talk about the customer ID column. Now, if we talk about the customer ID column, see what we have in customer ID columns. Here you can see we have this 1 and NaN. Am I correct or not? Here we can see we have 1 and it is showing NaN. 1 and it is showing as NaN, right? So what's this? So now guys, in our data we have this. This is what? This is the number of the movie. Let's say if I have 50 movies with me, so this is the first movie. Okay, like I have encoded it and first movie, and these are what? These are the ratings for movie number 1. These are all the ratings for movie number 1. Okay, like here I have, let's say, user ID is, let's say, 319 and giving the as 4 star. Now we have the user ID as 522 giving the rating as 3 star. Now we have, let's say, 614 giving the rating as 5 star. So now, and then we have, let's say, another ID, let's say, then we will be having 2. Okay, in your rating you will find none, because for a movie ID we can't have any rating, right? Now we have user, let's say, 500 who is giving the rating as, let's say, 4 star. Okay, 714 giving the rating as, let's say, 3, or let's say 5 star. Okay, now see guys, so what are these in my data? What are these in my data? These are the movie IDs. These are the movie IDs in my data present, and below that we have all the ratings for that particular movie. Like these 3 users are giving rating to movie number 1. These 2 users are giving rating to movie number 2. But the issue is what? This is mixed in my customer ID column. This is mixed in our customer ID column. We can see that. Am I correct or not? Am I correct or not, everybody? As we can see this one, as we can see this one as well, we can see this one. Now see, let me show you everybody how I can check all the ratings, all the movie IDs. Shall we see? Now let's check all the movie IDs. Okay, checking all the movie IDs present in our data. Now see what I will do. Now from this data frame I want to select the column customer ID. Am I correct or not? From this data frame, I will select the column customer ID. Right. Now here, I know all these values are numerical, but tell me what these values will be. These values will be string. Am I correct or not? These value will be string. Right. Or I can directly select, let's say, str dot contains, and here I will pass wherever it contains colon. Wherever it contains columns. So what I am doing, like in this customer ID column, I am selecting all the rows where it contains colon. Let's see it's going to work or not. Let's see. It's executing. No, let me explain you. Now see. Now here we can see. Correct. Let me explain once again. See, here we have the customer ID of the person. The data is look like this. Now these are what? These are the IDs of the customer. 319, 529, 614. Okay, till now it is clear. Everyone tell me, these are the customer IDs. 560, 714. Is it clear, Abhinav? Yes. Now here at the top you can see this. I have 2 written over here. What is this 2? 2 is the name of the movie, like encoded name, right? Like this, the movie number 2. For movie number 2, these users are giving rating. In the same way here, for movie number 1, these users are giving the rating. Are you understanding what it is? Right? These, so wherever we have column, these are the movie IDs we have. Okay, and the users are giving the ratings accordingly. For that particular movie, users are giving the ratings. So here, what I did, see, from the data, I selected my customer ID column, and there I checked all the string, like in all the rows I'm checking which contains the column. Okay, all the rows I am getting which contains the colon. So here you can see we have total, how many movie IDs we have in our data? Total 4,499 movie IDs we have. So the total user, it means these many people are rating these 4,500 movies. Everybody understanding now? Because we know for a one movie there will be thousands of ratings, right? There must be many users who have rated more than 1,000 movies. Correct or not, everyone? Correct. So this is what I have selected the rows. Okay, now what I need to do, first of all, now so we have get the count. So if I'll store it, let's say, now if I will select it, it will be a data frame. Can I get it count? See, here I will store it. So this is the count of the movie. So can I say movie count will be equal to and if I'll print movie count, here we will get the count of all the movies. Here we can see, correct everybody? Till now it is clear. I am getting the count, like how many movies we have in our data. These are the index, these are the my customer ID we have, one and something, right? I am just printing it. I'm just printing it. I can like it like this, no difference, right? It's just a movie count. See, it's the same thing, correct? So I'm just getting the count over here. Like I am getting, like I needed to select how many movies we have in our data. So here you can see, first I showed you, then I used the count function and I got the movie count, correct? Yes. See, then what I did over here, this cursor doesn't work. Sorry. Okay. Till now, what I did here, I was getting all the movie IDs, right? Then what I did here, I used the count function. I just wanted to see what this count function will return me. Now, when I use the count function, we know the count function give us all the values, correct? How many values we have in our data, correct or not? So here you can see, count gave me, like in customer ID, we have 4,499 values, and in ratings we have 0. Because in ratings we don't have any string which contains the columns, correct? And we are not checking the ratings column as well, but we are talking about my entire data frame, that's why, right? Now, which index value I need? The customer ID will be my 0th index, am I right or not? The customer ID is my 0th index. Am I correct or not, everyone? Yes. So that's why I selected 0th. And then I stored them in a variable named movie count. Now is it clear? Yes. Okay, perfect. Right. We can check df.info. Okay. Now here I will get the movie count. Here info you can see the customer ID is of object data types. Ratings are of float, numerical. Okay. Clear? Okay, it is of object because we have such strings in our data, right? We have the strings in our data, right? Here 1, then 2, and so on. We have the strings in our data. That's why. Okay. Now after this, what we are going to do now, if let's say now if I will get, guys, let's say now the question is, let's say I want to find how many customers I have in my data. How many customers we have in our data. Okay, number of unique customer IDs. It means number of unique customer ID in our data. So how can I do it, guys? Which function I can use? I can use the n unique function. So I can do over here something like that, like df customer ID, and I can get n unique, right? And I can store it in a variable, or let's say first check it. So number of unique values, we will get all the unique values in our data, like how many. So here we can see we have 4,75,257 people who have given the rating to the movies. Am I correct or not? We have total 4,75,000 who have like more than we have given to the rating. So first I will store it in a variable. Let's say customer count is equal to, I'm going to store it in a variable. Okay. Now guys, answer me this thing. Out of this total customer count, in this we have the movie IDs as well. The total movie count will be also counted. Am I correct or not, everybody? In this total customer ID count, the movie ID will be also counted. Correct or not? They will be also counted, right? And if I want to get actual customer count, what I can do? I can do customer count is equal to customer count and subtract movie count. Can I do that, guys? If I will subtract all the movie IDs, if I will subtract all the movie count, I will get the exact customer count we have in our data, which is 4,70,758. Correct? 4,70,758. Correct? And in the same way, now I want you guys to answer me. Let's say now I want to see how many users have given the ratings. How many users have given the ratings, like total number of users that have given the ratings. So how will I get? If I need to get, let's say, ratings count, what will be the logic? Like what I need to do, I need to subtract, see, simple as that. These are my total number of rows in my data. Am I correct or not, everybody? These are the total number of rows in my data. From this, if I will subtract my movie count, where I have NN values in ratings, I will get the total number of ratings we have for our movies. How many of you are understanding this point? Everyone? If from total movies we have, total number of rows we have, from this we subtract all the movie count we have, because here we have NN values. Wherever we have movie ID, here we have NN. It means those are not the ratings, right? Rest are all the ratings. So this is how I can compute. So see, rating count will be equal to length of my data frame minus movie count. And I can print the ratings count over here. Yes, let me repeat once again. Now see, I wanted to get how many ratings we have. Okay, I want to find out total number of ratings we have in our given data. This was the problem statement. Now I know one thing in my data frame. I know every customer is giving ratings. Every customer has given rating over there. Every customer has given some rating, but we have NN values in place of where we have movie ID. Am I correct or not? Tell me, Nikhil, others. Wherever we have movie ID, there will be NN. So if I get total number of movie ID, I know as many, let's say we have 5,000 movie IDs, it means at 5,000 rows in ratings, it will be null. There won't be any rating. Correct or not? For 5,000 rows, there won't be any rating, right? So, and I got the count by movie count, right? Here we got the count. So we know in our entire data frame, out of our entire data frame, there are 4,499 rows where we don't have any rating because it's the movie ID. And we know for movie ID, there won't be any rating. Correct? So that's why I subtracted from the length of my data frame. I subtracted the movie count. Now here you can see I got the ratings count. Like there are 2 lakh 24 crore 53,764 ratings for the movies. Clear? Okay. Now the question is, now after this, now I hope till now it was clear. Okay. Now we need to think something. Simple as that. Movie count should be equal to rating count. Okay. Now for a movie, let's say now out of these people, let's say the movie is equal to, let's say right now Chava movie came. Okay. Now there will be many audience, they have watched the movie. Am I correct or not? For this one particular movie, now for this the count will be 1. The count will be 1. Now let's say out of here 80 people, 40 people have seen the movie and 20 have given the rating. So here for this particular movie there will be 20 ratings. Am I correct or not? Now what we need to do, now we need to do segregation of our data. Now what we need to do, we need to do segregation of our data. Segregation of our data, what do we mean by segregation of our data? So now what we need to do, we need to do segregation of our data. We need to do segregation of our data. Now why we need to do segregation, what I need to do? Now simple as that, guys. First of all, wherever we have, like what I want, now my data frame is looking something like this. Let me create the data frame. Let me create a small data frame. We have customer ID, we have ratings. Let's say first we have 1, then we have null value. Right here we have, let's say user ID is 121, rating is 5, then 141, rating is 2, then 513, rating is 4. Okay. So now after this we have second will be your again null value, second movie ID we have. Then let's say 650 a user ID, then he has given let's say 4 star, and 670 where we have let's say 5 star, then 690, 609 doesn't matter where we have 3 star. Now we have the data which is looking like this. Correct or not, everybody? Till now we have the data which is looking like this. Now see, the thing is what I want to remove this movie ID from here, because we know, see, simple as that, we know, like first of all what I want, instead of this movie ID, I want to create a new column. What I want to do, I think it's going to ruin it. I will extend it. No, perfect. Now what I want to do here, I want to add one more column as movie ID. See guys, what my goal is, movie ID. And what I will do here, see, wherever there is 1, like I know the data is arranged, like first we have the movie ID 1, then all the ratings for movie number 1. This is how our data is, correct or not? Movie number 1, all the rating for movie number 1. So here I will add the ID along with my row. Like here I want 1, then here I will add 1, here I will add 1. Are we understanding what I'm trying to say? What I'm trying to do? Here I will add 2. I want to add with my column the movie IDs. Okay. In my column, I want to create a new ID. So wherever 1 for all the rows, wherever there is 1, I will add 1 for all the particular rows. Okay. So here I want to give them the ID, right? I want to give them the movie ID. Like, see, now how I'm going to do it. If the problem statement is clear, now the question is how I'm going to do it. See, first of all, okay, let me just tell you an approach. Now tell me whether it's going to work or not. Okay. I will run a for loop. I'm going to run a simple for loop in this customer ID. Okay, guys. I'm going to run a for loop in customer ID. What I will do, first I will check wherever in my column I found one colon. Colon means what? It's my movie ID, correct or not? Now what I am going to do then, I am going to remove this column. I am going to remove this column, and let's say I am going to remove this column, and I am going to store it in my list. Let's say I will create a list movie ID, and here I will store the number. So 1 will be stored for the first time. Am I correct or not, everyone? Am I correct or not? Now see, let me write the approach here. I should be able to see. I'm going to run a loop. Let's say first I'm going to create an empty list. Just pay attention. See, now here the thing is, the data is, first of all, you will never get this kind of data. Okay, if you will get, there will be each and every step mentioned, like what else you need to do, how you are going to segregate the data, how you are going to suppose what those values are representing. It will be mentioned to you. Okay, if you get such data in the problem statement. See, if you are getting a data set, there you will find each and every problem statement. Okay, you need to understand, and then you need to proceed. So everyone, that's why I will give you suggestion whenever you are done with the class. Let's say whenever you get some free time, whenever you feel like studying, don't go with the same file. Okay, browse online, get some data set and work on them. Okay, because the more data sets you will encounter, the more new problems you will overcome. Correct, everybody? So now see, to solve this issue, what I am going to do, everyone pay attention. I am creating an empty list here. I am creating an empty list, movie ID, correct? This is how we create an empty list. Am I correct or not, everyone? Movie ID is equal to an empty list, square brackets. Now I am going to run a loop in for x in my df, the column which is customer ID. I am going to run a for loop, customer ID. Correct? This is how we run a for loop. This is how we run a for loop, correct or not, everybody? This is how we run a for loop. Now here what I will do, if we have colon in our x, if we have colon in our x, now tell me guys, till now what x will be holding here? X will be at every row of customer ID colon 1 by 1. Am I correct or not? Am I correct or not, everybody? X will be at every row of the customer ID 1 by 1, 1 by 1, 1 by 1. Good. Now here I will say, if colon in x, then what I am going to do? If I have colon in x, I need to remove this colon. The very first thing is I need to remove this colon. Am I correct or not? I need to remove this colon because I am creating a movie ID new column. So what I will do, see, here I will create a variable. Let's say y, or let's say y is equal to, I'm creating a simple variable. There what I will do, x dot replace, we are not going to drop that particular value, and df at x, x df, x is holding value. Okay, don't be confused, it's absolutely fine. X is holding every value, so x means values. Let's say for 1 dot colon it contains, so this condition become true for x, 1 colon was it, right? So x dot replace, like wherever I have colon, I am going to replace with empty, nothing. This is what I am going to do. I am going to replace with inverted, so this will be removed. This will be removed. Am I correct or not, everybody? And it will be stored inside the y variable. It will be stored inside the y variable. And what I'm going to do next, now this is the best part, movie id dot append the y. Movie id, I'm going to append the y. Okay. Now, what do I mean by that? What do I mean by that? Now, see everyone, let's try to run the code. Movie ID, an empty list is created for X in customer ID. So my X will be here. My X will come over here, correct or not? My X will come over here, perfect. Now see, I will check if colon in X. Now tell me, in this X, do we have colon? In this X, do we have colon? Everyone, do we have colon in this X? Yes, yes, we have. Yes, we have colon. Okay, then replace this colon with empty. So in Y, in the value of Y, one will be stored. Am I correct or not? When I remove the colon, in the value Y, one will be stored. Correct, everybody? And let's say here I am representing my list movie ID. Now see, here I am representing the list movie ID. Okay, see, now in movie ID, see, if condition is over, right? Outside if condition, what I'm doing, I am adding Y in this. I am adding the value 1 in this. Am I correct or not? I am adding 1. So 1 will be added over here in this list. 1 will be added in this list, correct or not? Now it will be more clear. Now see second terms. Now after this, the value of X will increment. Now X will come over here. Am I correct or not? The value of X will increment. Now I will be at the second row. Now we will be at the second row. Now what? Now tell me, do we have colon in X? No, we don't. We don't have colon in X means the if condition won't execute. The if condition won't execute, it means the value of Y is not going to update. The value of Y will stay 1. Am I correct or not? The value of Y will stay 1. Am I correct or not, everybody? Yes. Then movie ID dot append Y. So again 1 will be added over here. Again 1 will be added over here, correct? Yes. Then again the value of X will increment. Again the value of X will increment. Do we have colon here? No, we don't. Okay, directly add your Y. What is the value of Y? 1. 1 will be added. Right? Again the value of X will increment. Do we have colon here? No, it's not. Okay, then add the value of Y. I will add the value of Y here, correct? Now see. Now again the value of X will increment. If you have any doubt remaining, it will be clear now. Okay, again the value of X will increment. Now see. Now X will run. Now do we have colon in X? Do we have colon in X? Yes, we do. We have colon in S. Okay, remove the colon and store in Y. Okay, fine. Remove the colon and store in Y. So now the value of Y will be 2. Now the value of Y will be 2. Am I correct or not? Now the value of Y will be 2. Correct. And what I am going to do when this will be over, I am going to add 2 over here. I am going to add 2 over here. Right. So again the value of X will increment. It will say no. Then 2 will be added. Correct. Okay, so now see here, when you encounter such data set, if you feel, now they will tell you like you need to segregate movie ID from it. Okay, they will tell you, but how you are going to do it, now you understood. Am I right or not, everyone? How to think of an approach, like we are not doing anything complex here. We are just running a loop one by one. We are finding where we have colon, we are replacing it, right? Then we are storing it in the list that I created outside the loop, right? Let's see the implementation now, whether we are able to get all the values or not. Let's see how we are going to do it. Okay, so here I will write as well for your reference. For every row in customer ID, we will run a loop. Run a loop and select the row where we have colon, and then store it in Y after replacing colon with nothing, or I can say an empty string, correct? An empty value. Let's do it. First, what I will create a list. Let's say movie. Okay, movie ID, but then we will give a data frame column name also movie ID. I will keep it as movie info. Okay, movie numbers, movie NP. Okay, I will keep it as movie NP. I'm going to create an empty list here. I'm going to run a loop. Let's say for X in df, my customer ID. In this particular column, I'm going to run a loop. Now, if we have this colon inside the X, it means what? We need to remove it. So X dot replace the colon with nothing. the colon with nothing, and we are going to store the result inside y. And then when the if condition will be over, I am going to add it inside the y. Am I correct or not, everyone? Look at this approach. The same thing we discussed. The same thing we have discussed, correct or not? Yes. Now when this will be over, let's see what we are going to get in the movie NP. Okay. Executed. Here we can see all the movie IDs as a string, correct or not, everyone? All the movie ID we got correct continuously, correct or not? Here we can see all the movie IDs we got. Okay. It's on, it continuously go on. Okay. Now what I will do, I will add it in my column. Let's say movie ID is equal to movie NP. I will add it in my data frame. I can add a column directly, right? And now if I look at my data frame, here we can see we have got all the IDs. Now you can see it's looking beautiful, right? We have got the movie ID directly over here from 1 up to 4499, all the movies. Correct, everybody? Till now, everyone clear? Now, guys, here now I can remove these null values from my data. Am I correct or not? Now, do I need these null values? Now, do I need the null values from my data? Tell me, what do you think? Do we need these null values now? No, right? No, right? I can directly delete. I will directly delete df dot drop na in place will be equal to true. And now after this, we will look at our data frame. Now we are left with 2405376 rows and all the null values are gone. Now the data set is looking beautiful. Let's check the info about the data now. So here we can see, now see customer ID, movie ID, like these are of object data type, correct or not? And now all those values are numerical. Now we know, like previously they were of string data type, they were string, but now they are of numerical, right? So what I will do, I will convert them into integer. So here let me do it. First I will select customer ID is equal to customer ID dot s type integer, correct? This is how we do it. The same thing I will do for my movie ID as well. Movie ID, I'm going to convert both the columns into numerical. Here. Executed, all the columns are numerical. Now after this, what we need to do? Now we need to filter our data. Now we need to do what? We need to filter our data. We are going to apply filtration, manual filtration we will do. Manual filtration. What do I mean by that? Let me explain it to everyone. Okay. Now guys, simple as that. Now see guys, now what the issue we have in our data, now we have done major cleaning, but now we need to do some filtration. Filtration is now guys simple as that. Tell me, now answer me this thing. Let's say there will be two filters we'll be applying. First we'll be applying on our movies, like movie IDs and all. Second we'll be applying on our customers. Okay. Now let me tell you what type of filter we are trying to apply here. Okay, what kind of filter we are trying to apply here, and what do we mean by that? Okay, see, so first of all, guys, simple as that. Tell me, there are rating given by every customer. Am I correct or not? Here we can see there in our data. We have ratings given by every customer, right? We have ratings given by every customer. Correct or not? I hope everyone agrees with me, right? We have, let me write here, there are ratings given by every customer, every user ID that we have, they have given the ratings, right? Now guys, let's say if I talk about, let's say a customer, like the customer A, okay, customer A is representing a user ID over there. Okay, let's say customer A has seen 500 movies and given, let's say A has seen 500 movies and given a rating, let's say 4 star, given a rating as 4 star to movie number, let's say to any movie, let's say movie X. Okay, so everybody understanding what I'm trying to say, like customer A has seen 500 plus movies. Okay, he has seen 500 plus movies and he has given a rating 4 star to movie number X. Let's say any movie it is, and this customer A is saying I will give 4 star to this movie. And now we have customer B who has seen 5 movies only, who has seen 5 movies, and let's say and given a rating 5 star to movie Z. Now tell me guys, which customer you will prefer, which customer you will find more legit, more practical, more better, sorry, better. Everyone, A guys, am I correct or not? A, right? A, am I correct or not? Because the person who has seen more movies, that will be having more experience and that must be giving better recommendation. And now if I want to build a model, obviously guys, I will pick such users, right? Why will I pick such users who have seen just 3 4 movies, right? And they are giving ratings. So will I pick such users? Tell me guys. No, right? I need to pick some good users who are who are really active, who watch all kind of movies, who give good ratings. Like good ratings means like good way rating to every genre movies, right? They have seen, they have a taste, they have a category. I will select such users for my recommendation, right? So now we need to select such rows now. So because I know the data is so huge, right? If I consider each and every user, there will be some user who's waiting for the very first time, right? So that can fluctuate my model. Definitely that can fluctuate our model, right? Because whatever values they will say, it can be hard for my model to understand because their rating can be so bad or so good. For let's say now here, if I will tell you simple as that, one more example. Now simple, let's say now customer A has seen the movie Y, okay? And he is giving the rating as, let's say, 2. And customer B also seen the movie Y and given the rating 5. Now tell me which one is more better, which one is more legit, which one will be more honest, which one will be more better. Rating given by customer A, the rating that's given by customer A, am I correct or not everyone? The ratings given by customer A will be more better because he is having more experience. Correct. So now I need to select. This is what I need to do. I need to select all the customer first of all with how much rating they are giving, and then I will select the customer who are giving good amount of rating, and I will remove the customer who are giving very less amount of ratings. So everybody, the idea is clear what I'm trying to do now. Now we need to select such customers who have seen good amount of movies, who have rated good amount of movies, and I am going to remove some customers who have seen very less movies. Okay, so let's see what I'm trying to do. Let's see what I will do. Now I need to select, first of all I need to get the count. I need to get the count of every customer with respect to ratings, correct or not? Like wherever I see same user ID is repeating and there's some rating, I want to increment the count so that I will get how much my user is giving the rating. So to do that, I can use group by function. Am I correct or not? To do that, I can use group by function, right? So see here, df dot group by, my customer ID, the customer ID, and here I will select ratings, and then what I need to get, I need to get their count. If I will do it, we are going to set a threshold over there. We are going to set a benchmark over there. Okay, so now here we can see, right? Like see here, let's say the customer ID 6, he has seen 153 movies. Customer ID 7, he has seen 195 movies, correct? And here you can see there's customer ID 25, which person who has only seen 4 movies. So now do you think that person will be good for recommending movies? The person here, you can see this person has only seen 3 movies. So shall I select these person who have seen less amount of movies? No, right? Because they can change my data. So what I will do here, first I will store it in my new variable, let's say data customer summary. Okay, I'm creating a data frame where I will get how many users are giving how much ratings, how many movies they have seen, and how many movies they have rated. So here we will get that data frame. Correct. Now see, here I can set a benchmark Now, how can I set a benchmark? Like I need to select a value. Let's say I want to select, let's say here I can see we have values like people have given rating to 3-4 movies. They have given rating up to 153 movies, 195 movies, 200 movies plus as well. Now see, how can I set a benchmark? Now, like it can be any number. So can I calculate percentile here, guys? Do we remember? Sorry, do we remember what's percentile, right? If I get any percentile, if I get some value, then let's say for this, let's say, see what I will do. I will get, let's say, data customer summary dot quantile. Let's say I selected 0.40. So here it is getting 16 movies. Am I correct or not? 0.60, it is giving me 16. Like if you I talk about 40 percentile, so it means there are 60% of the audience who have seen more than 16 movies. Correct or not? And there are 40% of the audience who have seen less than 16 movies or up to 16 movies, right? Now let's say if I calculate 0.70, it's coming to 52. 0.70 is coming to 52, right? And now let's say if I select 0.60, 36 movies. So can I select this as my threshold value, guys? 0.60, can we select that? So now what I will do, like from this selecting, what I mean, see, this is not a rule, but what I want good recommendation for my model. So what I'm selecting a criteria, like I want to select those customer who has seen more than 36 movies, who have seen more than 36 movies, so that the recommendation accordingly my model will learn will be better. Okay, so the user who have seen more than 36 movies, I am going to select that as my person. Okay, guys, so I will select only those customers who have seen more than 36 movies. Am I correct or not? Right, so now here, and guys, one more thing, how I'm going to select now, guys, if you are aware of group by function, here if you will see the column customer ID, this is what I want to select, the customer ID, right? First of all, let me show you how I'm going to select. See, I'm going to select from the customer summary, I'm going to select all the values, customer summary, see, which are less than, see here I will keep it as customer benchmarks I have selected. So I will get the value as 36, right? Customer benchmarks we have selected, and benchmark I have selected 36. So I am going to select all the values, all the rows where the customer has seen less than 36 movies. So I will select customer benchmark. So here you can see, correct? Here we can see, right? All the rows from my data where the user has seen less than 36 movies. Correct or not, everybody? So these are the movies that I'm going to reject. These will be the movies, these are the customers, sorry, that I'm going to reject. Correct or not? Rejected customers. Am I correct or not, everybody? These are the customers that I'm going to reject. Why? Because they have seen less than 36 movies. And see how many rows we have. Okay, you will say these are so many rows, like 2,82,000. But we have the data in crores. Still, we have lakhs and crores of people who have seen more than 36 movies. So I will use them because they are better for me. Correct or not? Right? And guys, if I am getting the rejected customer, I need their ID instead of this data frame. Correct or not, everyone? I need their ID instead of this entire data frame. I just need the ID so that I can remove it. We will see how we are going to remove, but I need the ID. So where this ID is stored? Can we see, guys, this is the drawback, or you can say like when we use group by function, the column we use to group by, that becomes my index. Am I correct or not? Here we can see, am I correct or not? When I use the group by function, it became my index. Here you can see customer ID is my index. Correct? Here we can see customer ID is working as an index, right? So when we use group by function, we write here. So when we use group by function, the column becomes index. So what I will do, see, I need the customer ID. The customer IDs are in my index. So from here, I will select the index. And when I'm going to print the rejected customer, this is what we are doing. Here you can see I got all the IDs and the data is stored inside a list. Here you can see all the rejected customer IDs I selected over here. Okay, so here we have selected the customer. Here we have filtered the customer. Now in the same way, we can have movies as well. In the same way, we will be having movies as well. Like in the same way there, simple as that, guys. There are movies rated by customers. Correct. And we know one user is rating thousands of movies, right? So now let's say if I say example, let's say movie number, let's say movie X, let's say movie X is rated as 5 star, or let's say as rated as 4 star by 300 people. Okay, movie X is rated as 4 star, sorry, not start, by 300 people, and movie Y is rated as 5 star by 10 people. By 10 people, like there are only these many reviews we have, like all over reviews. Like movie X, there are 300 people who gave the review, and by taking the average review we are getting 4 star. And for movie Y, only 10 people have given the ratings and they have given 5 star, right? And now 10 people, they can be of the crew as well. Am I correct or not? 10 people of the movie creators can be given rating to a movie, or it can be any people, right? Only 10 members. So now tell me which movie will is more legit here, which movie is more preferable, which movie is more recommendable. The movie X, the movie X, right? Am I correct or not? The movie X, everyone, Arvind, movie X, right? Why? Because that movie is rated by 300 people. So in the same way, in movie data also, in movie column also, in movie ID also, there will be ratings where there will be many movies where rating will be so small, where rating will be so less. Correct or not? So now I need to filter my movie data as well. Now we need to filter our movie data as well. So let's see, filtering our movie data. So first let's select, first is what we will do. First we will get the count of ratings for every movie. Correct. Previously we were getting the count of rating for every customer, like how many ratings they are giving, and now we are getting for movie, for particular movie, how much rating they are getting. Okay, so here I will create data movie summary, and df.group by I will use once again. Here I will pass the column movie ID. Correct. And here I will pass the column ratings, and then count we will use, right? And if we will look over here, let's see. So here we can see, here we can see movie ID 1 is rated by 547 people. Movie ID 2 is rated by 145 people, where movie ID 3 is rated by 2000 people. More than 2000 people have rated the movie. Correct. So now here also we can see, like with respect to this 2012, this 142 is very small, right? Everybody understanding what we are doing, how we are selecting the data movie summary. Correct. Here we can see, like for every movie ID, how much rating the user is giving, right? So now what we are going to do, now we are going to select. Here also I want to set a benchmark and I want to select. So let's see, let's say here what I will do, let's say I will select like data movie summary dot quantile. Let me see, let's say 40%. Okay, sorry, 0.4 I need to write. 40% is 350. Okay, if I talk about, let's say 90 percentile, it means, see guys, everyone, in our data we have such movies as well that are given as 1100 422 ratings. Am I correct or not, everyone? We have such movies present in our data that is rated by more than 11,000 people, and it is coming to 90th percentile. There will be more count as well, the count might be increasing as well. Am I right or not, everyone? So there are many movies that are rated by so many people, so I need to select a good benchmark. What if I select 60, the same? So there are 907 ratings, and I should round off it, right? Because I can't get a float value here, the ratings will be given by every member. 908, 908. So this is, I will select as the benchmark, movie benchmark. I will round it off, I will select it as the movie benchmark. Everybody clear? Here also I will round it off as well to make it exact 36. It's 36, but it's still 36. Okay, so now if I talk about movie benchmark, so what I will select, I will select all the movies which have rated by more than 908 members, right? Which ratings is given by more than 908 people. Am I correct or not, everybody? Right? So here also I will select the rejected movies. Here also I'm going to select the rejected movies. The same way we selected rejected customer, the logic is going to be same. Data movie summary. Here I am going to select my data movie summary, which are less than the movie benchmark, because these are the rejected movie. And again the index, right? Here we can see after using group by, the column became index. So now here I will get all the movies that I need to reject. Here you can see all the movies that I need to reject. Correct or not, everyone? Now what I am going to do, from my actual data frame, I am going to remove these rejected movies and rejected customers. Okay. Now we have selected the customers and movies that we need to reject. Okay. Now we will update the result in our actual data frame. Like we are going to update the result in our actual data frame, means removing these rejected values. This is what we are about to do. Okay. Now see what I am going to do. Are we aware about this negation? Note operator. Note operator, correct? What it will does? Yes, it's the wild operator. It does the opposite negative over there, right? If I will say simply print note of true, what I will get? I will get false. Okay, -2 it is using bitwise, it is doing over there. Okay, it is using bitwise over there. If I pass 1 here, you can see -2. Okay, it is applying bitwise operator over there, correct? Like if for simple we have the note operator, right? Note, see, note operator like this. Okay, so the negation we use, like if we don't want to select any specific value, okay, any specific value, let's say if I create a list 1 2 3 4 5, right? If I have a list 1 2 3 4 5, and if I will print, let's say li, okay, note li dot is in 3. Okay, I think with list we don't have, we use it with data frame. But the goal is what, like if I used a note operator that allow me to search a data, allow me to access a data without that value, see how I'm going to use it. Now see everybody, from this data frame I'm going to select, like I'm going to select movie id we have. Let's say first I'm selecting movie id. Okay, now here what I want to do, I want to is in rejected movies. If I will do it, I will select all the movies IDs that are in my rejected movies. Am I correct or not? Here you can see movie ID 1 2 4 7, they were in rejected, and here you can see I'm getting all the values. Am I correct or not? 4499. All the movies that need to be rejected. Am I correct or not, everybody? Tell me guys, here are all the movies that we need to reject, right? So to not select those movies, here I can use that operator. See, note operator I can use over here, and when I'm going to run it, here you will see all those movie IDs are gone. Correct or not? All those movie IDs are gone. Can we see that? Yes. So this is what we will do. I am keeping this for your reference. Here you can see all the movies we need to remove. Now see what I will do. I will select the note. So those movies that are not is in rejected movies, right? So all the movies ID that are not in my rejected movies will be selected, and I'm going to store the result in my actual data frame. In my actual data frame, I'm going to upload the result. Okay, and when I will look at the data frame, here you will see all those IDs are given. All those movie IDs are gone. Okay, all those movie ID with less ratings are gone, and here you can see still we have good amount of data. Am I correct or not? Still we have a very good amount of data. Correct? Yes, you can say in place. So that's here you can see I'm storing the result in my same data frame. DF is equal to, right? So I'm storing the result, all the result in the same data frame. Okay, now the same thing I will do for customer ID as well. Correct or not? The same thing I will do for customer ID as well. We had customer ID, and here what we had rejected customers as well, right? I will select it, and here we will see, here you can see we are left with these many rows at the very end. Correct? Now the data is clean. Now the data is entirely clean. And here we can see at the end we have ones, tens, 100,000, 10,000 lakh, 10 lakh crore. 1 crore 96 lakhs 95,836 crores after cleaning our data. Let's see our another data set. See, now I am going to read my another data frame. Okay, so here we are going to read the another data frame. We have Netflix movie data. Now what we have? We have Netflix movie data that I'm going to use. So see, df title is equal to pd dot read underscore csv. Here I will pass the path. Here I will pass the path. I will try to run the code. Here we can see the data. We can see we have the movie names. Every movie name we have here, correct? Every movie name we have here. And now what is the first issue? The very first issue, if you guys can clearly see, the very first issue we have is first row as the header once again, correct? The first row we have as the header. So here I will pass once again, header is equal to none. Header is equal to none, correct? And the second issue is you guys can see here in entire 3, 4, 5, these columns are unnecessary for us. Am I right or not? These columns are completely unnecessary. So what I need, I just need these 3 columns, right? And if you will observe, we don't have column name as well. We don't have column name as well. And if you will see, this is what, this is my movie ID. The very first you are seeing, these are the movie ID. These are the year when movie were released. Here you can see this is the year when movie were released, and these are the name of the movie: Dinosaur Planet, right? Rise and Fall, Sick, correct? The Company, Alien Hunter. These are the movie names. So here I will pass, simple as that. First of all, use the columns such as 0, 1 and 2. Okay, like 0, 1 and 2 means 0 means movie ID, first is year, second is movie name, right? And here I will give them names as well. Let's say names is equal to the movie ID I will give, correct? Then I can give them year, and third name I will give them name. Okay, here we can see, look smooth. Okay, now I am going to import the library, the surprise library. I said I am going to import it. So first let me try whether I'm able to import it or not. From surprise, I am going to import reader. We will see what are the data set and svt. Error, perfect. Now see guys, everybody, first of all, this surprise library doesn't work on Jupyter Notebook. In Google Colab also I need to install it. And see, pip install surprise. I'm going to install the library. Everybody, you guys also need to do the same. We need to install the library because this library is not something that is predefined. Okay, it's a large library as well. So we will just install it over here, and then we will try to run the code. Let me just write the code, the library that I'm going to import. From surprise, we are going to import reader, we are going to import dataset, and we are going to import svd. And from surprise dot model selection, I'm going to import cross validate, cv, cross validate. Cross validation techniques, everybody is aware, right? Not aware, let me tell you what are cross validate techniques. So simple as that guys, what a cross validate technique, let me explain it to you meanwhile it's installed. Okay, see how it works. Simple as that guys, listen to me. Here, if we have the data, let's say we have the data. Okay, now I am going to divide the data, like let's say I selected cross validate is equal to 3. What I selected cross validate equal to 3. It is going to divide our data into 3 segments. Like if we have, let's say 100 rows, so 33, 33, 33. Okay, like if I use cross validate is equal to 3, it is going to divide my rows 33, 33, 33, something like that. Okay guys, am I clear? 3 means it is going to divide your data into 3 parts. Now first is what, like first I will do what, like on these 2 data I'm going to train the model. On these 2 data, like the 33 and 33, 66 rows, I'm going to train the model, and I'm going to test my model on this data. I will test the model on this. Okay, like this was my first segment, second segment, third segment. Okay, everyone understanding what I'm doing? First, I'm training my data on these two segments and testing on this one. Now what I will do, I will train my data on these two segments. In second turn, I will train my data on these two segments, second and third, and I will test it on first one. I will test it on the first one. Okay, in the third time, what I will do, I will train my data with first and third. I will train my data with first and third, and on second I'm going to test. So what I'm doing here with my data, I'm using different values to perform train and test. And in the end, from whichever I will get the best accuracy, I will select that way to split my data. I will select that way to split my data. Now, is it clear? What do we mean by cross validate? See, cross validate techniques are simple as that. If I have a data, like if I want to find like which way of data is going to suit best to my model, which will give me best accuracy, right? So what I will do, I will divide my data, like if I'll pass cross validate is equal to 5 or 3, up to me. So I can pass 5 as well. If I want, I can pass 3 as well. Let's say I pass 3 over here. So my data will be divided into three segments. Okay, if there are, let's say, 300 rows, so 100, right? First two rows I will keep for training. First two data, like first 200 rows, you can say, for training, like these two segments for training. And I will test my data, check for accuracy on this one. Clear? I will check for accuracy in this one. Like generally, this is what we do when we split the data. We have the training data, we have the testing data, right? So training data and testing data, this is what we are doing. But now, as we are using cross validate, we are going to repeat the operation once again, but second time I will change the pattern. Like now I will select second and third rows for training. Now I will select these rows for training my model. Okay, and this one I will keep for testing the model. Correct. So now when I will change the data, there might be a possibility my accuracy will change. Am I correct or not? There's a possibility my accuracy will change, right? So in the same way, third time, what I will do, I will keep first and third for training, and second I will keep for testing. Okay. So as I will change the data, the accuracy will change. And now over there, like any parameter I can choose. I can choose MSE, mean squared error, RMSE, root mean squared error. I will select from where I will get the best accuracy. I will select that as to be my model, as my final model. Now I think it must have installed. Okay, and now when I'm going to run it, I will get error. Definitely I will. Why? NumPy. Now guys, everyone pay attention, because when you will try to implement the same in your system, you guys will be beating your head. You guys will be confused over here. Like see, surprise library is installed, but it is giving error when I'm trying to use it, when I'm trying to import something, because of the NumPy module. Now the issue is the updated version we have of NumPy, right? That doesn't work properly with surprise library. The updated version we have, the by default version we have, the default updated version of NumPy doesn't work properly with surprise library. Okay, this can be a possibility. Like see, I'm not saying everyone will get that error. Some of you might get that error, so I'm explaining why you are getting the error, so you won't be confused. So here what we are going to do, first I'm going to uninstall the NumPy library. Uninstall the NumPy library. Here you can see pip uninstall NumPy. Okay, exclamation mark, it will be uninstalled. Here you can see we have the NumPy version of 2.0.2. Okay, so it will be, and now it is asking me, do you want to really uninstall? Yes, I do. It will be uninstalled. Okay, NumPy version uninstalled. And now here I'm going to install NumPy, but with the version of 1.23.5, because see, the above version from this are all like they don't support good with surprise, so that's why. Okay, so here you can see I'm selecting a specified version of NumPy. Okay, here we can see. It can be. See, so here it's installed. Now it is asking me to restart the session. I will do it. So now my session will restart. Okay, and now after installing it, I'm not going to install it once again. I'm commenting this, right? And in the same way, I will comment this installation as well, because now after restarting, I need to run all the cells as well. So whatever cells that are not, like here, I'm just checking the values, right? or I won't comment. Okay, we will wait. Now I'm going to, the session has been restarted, right? And now I'm going to run all the cells. I hope it's restarted. That's what I'm saying. And now we are going to run all the cells. It will take some time. Okay. So everybody, if you do face difficulty, either in the beginning do it. Okay. In the beginning, try to import this library. If you get error, directly install the version of NumPy from here. Okay. And then proceed with the model so that you won't have to take a pause like this. So it is executing all the cells, and as we know that the data set is large, so okay, it's executed. Perfect, guys. Here we can see it's imported, right? The libraries are imported. So let's proceed. Okay, we have seen the data set as well that we have. Now let's proceed, guys. So now see what I'm going to do. Now I imported the library. First I will create the object of reader. Okay, here the library that I imported over here, I'm creating the object of the same. And now what I'm going to do, see, I am going to read the data. Like here we have the data set I'm imported, data set reader. Now you will understand why we are using it. See guys, as I told you about SVD, tell me how SVD works. Whatever I have explained to you, what SVD was doing over there, it was decomposing the matrix. It takes the data as a matrix, it decomposes it, and it finds the hidden patterns in the data. Am I correct or not, everyone? This is what we have understood. It takes the data as the matrix, right? It does the decomposition, correct, and then it finds the hidden patterns for us in the data. Now here, so to make my data as a matrix so that my model can understand, I need to use this data set, the function we have, the data set load from data frame. Okay, here you can see, okay, load from data frame. Okay, so we are going to load from the data frame. Here you can see. Okay, now here I will pass, like from my data frame I am going to pass the columns which are customer ID. I will pass, right, of the data frame. I will pass the movie ID and I will pass the ratings. Okay, and now here guys, simple as that. Like, okay, I can pass my entire data to train because I have the df title to predict, right? I can pass my entire data to train, but simple as that guys, just tell me, if I will pass these many data, it will keep on executing. Okay, it will take so much time to execute. So now right now I'm not passing the entire data, but if you are trying it, you can pass your entire data over there and build the model. Okay guys, like right now, as it can take so much amount of time and we don't have much time left, so I will suggest everyone, here I'm selecting a specific part of the data. Like here I will select, like first I've selected all the columns, then all the rows I'm selecting, let's say 10, 100,000, 10,000, lakh, 10 lakh, or 10,000, lakh, 10 lakh, crore. Let's say 1 crore rows I'm selecting. Okay, but it will be too much. I'm selecting 1 lakh rows for now, like because it can take so much time. So I'm selecting 10 lakh rows over here, correct? Here we are selecting 10 lakh rows over here. Okay, it's 10 lakh, correct. And then to convert, to read the data as a matrix, I need to use this reader. Okay, that will allow me to read the data as a matrix. Okay, here. Okay, let me execute it. See, for 10 lakh rows also it's executed fine. Okay, now what I will do, I will simply build the model. Nothing complex, I will build the model. Okay, and now see, I will apply the cross validate technique over here. The library data imported, I will pass the model, I will pass my data, I will pass the model, I am passing the data, I am passing here the data, right? Customer ID, movie rating up to 10 lakh rows, right? And then here, now if I'm applying cross validate, it means it is going to train and test. Am I correct or not? If I'm applying cross validate, it is going to train and test. Then I need to pass a measure, like which parameter I want to select. So here I will say, okay, measure it on the basis of RMSE, root mean squared error. And how many cross validation I will say? Okay, do 3 times. Okay, do 3 times. So here let me measure measures. So let it execute. Okay, let it execute now. We will wait. See, because while predicting errors, like as this is like the continuous value we will get first of all, right? So that's why the to get the, we check error while applying cross validate, we check for errors, right? So for errors, what we have MAC, we have MAE, we have RMSE, correct? Am I right or not? These three measures we have when we are doing for linear continuous value. So these three measures we have. Now MSE, if we go, the values can be so large. MSE can be, the values are so large. And when we go for MAE, mean absolute error, they don't consider, they just apply the modulus over there, right? So that's why we select RMSE. Okay. Now here we can see we got the time. You can see how much time it is taking, like every model if you will go with. And here you can see the RMSE we are getting 0.97, 0.96, 0.966. Correct. These are the RMSE we can get. Okay, guys. These are the RMSE we can get. I prepared the model. I passed the model. I passed the data. Right. I applied cross validate. My model has prepared. It has seen the training data. Correct or not, everyone? It has seen the training data over here. Now see everybody. Now see everyone what we are going to do. Okay, now tell me guys, we have in this data, if we see for this particular data, now these are the movies we have. Correct or not, everyone? Correct or not, everybody? Here we have all the movies, right? Here we have all the movies. Now what I want to do, I want to check, I want to do recommendation. I want to do recommendation for any particular user for all those movies that are stored in our df title. This is what I want to do. Like, let's say if I will look at df title, this is looking like this. Now what I want to do, I will select a user, I will select a randomly user, I will apply svd over there for this particular data. I will calculate the estimate score, like how much my user will give rating to all these movies one by one. Okay, so now user id, we have user id up to 1, it is going till anything, right? Any number. So let's select any number. Tell me guys, any user id we can select. Let's say I select 1331154. Okay, I am generating a number randomly, that will be my user id, right? Because we have a lot of user id, one to everything. Here first thing is what I will create the copy of this data. I'm going to store the copy of the data inside this user. Why? Because I will pass this data to the model, and then my model will give me rating for this particular data. For every movie, my user is going to give me the rating. Okay. Now see here, if we will look, we have the movie ID as well. Correct. Movie ID we have, and accordingly the user will give the ratings. Now what I'm going to do, see, I will calculate for this particular user. Okay, I will calculate the estimate score. Estimate score means how much prediction the user will give. Estimate, it will be equal to the user ID, movie ID. In movie ID, I need to apply SVD. Correct. For that movie ID, I will pass the movie ID column, like for whatever ID, give me the estimate score, like how many ratings you will give. Okay. So I'll apply the function. I will apply. How lambda function works? Lambda function of one line of function which take parameter, right? So how we write? If we need to create any lambda function, how we write? We use the lambda keyword, we use the parameter, then we write the expression. Am I correct or not? Lambda keyword, parameter, right? So here see lambda keyword, here I will write lambda keyword, then the expression that will be passed, expression like arguments, I can say, right? Arguments, here I'm passing an x. See what I will do, I will say model that is prepared predict what the values for this user ID. Now I will pass this user ID to the model, because the model has user IDs. Correct. In training data we passed all the user IDs. Am I correct or not? While training the data we passed all the user IDs. So now I am passing this user ID, and I will say predict the values for this. Okay, so x will be the prediction, x will be the prediction that I will get, and I'm going to store it in the estimate score. So x will be my estimate score, and what I need to calculate, I need to calculate estimate score. So I will use .est I will use in predict, so that it will calculate the estimate score. And now if I will execute it working, let's see now. Can you see guys, can we see the ratings guys? Here you guys can see. So this particular user will rate, let's say, Dinosaur Planet 3.67, Character 3.96, The rise and fall 3.86, 3.67. These are the ratings the user will give to these particular movies. Okay. Okay, now let's say guys, let's find some another user. Tell me guys some random user ID. Let's try to do the prediction for same. Let's say any user ID. Let's say I select user ID as, let's say what the time, 12:36. I select user ID as 12:36. I know there will be a customer ID of 12:36. There will be a user, right? So what I will do first, I will create the copy of my data frame because I need to store the result over here. Df title. And then what I will do, I will do the prediction. I will do the prediction like this. So for user 12:36, let's see how much what movies will be recommended. Okay, here I will pass 12:36, and for the user ID, here I will pass it's what, 12:36. Okay, and now let's see how much prediction we are getting. Here you can see. Here we can see the prediction. Now let's say if I want to select. Now if we want to select, okay, do we have that 2,64,000? We should have that, right? We should have that, correct? So let's try to do it. User underscore. Okay, let's see everybody. Will be equal to tf title dot copy. Why I'm creating a copy? Because I want to add estimate score for every user, right? That's why. And now I am going to use the same approach here. Let me just update the ID. 2643029. Okay, 2643029. 2643029, and here if I'll print, here we can see. Now the question is, now okay, it is recommending upload similar value. Let's see. Now guys, what I want to do, I want to select, let's say for this particular user, I want to select the movies that are liked by, that will be recommended. Now which movies will be recommended to the user? Tell me guys. The movies with highest rating will be recommended to the user. Correct. How I can select the user? Can I sort this data? Yes, we can sort the data, right? If I pass this data dot sort values, everyone see sort values. Here I will pass on the basis of what I'm sorting. On the basis of estimate score, I need to sort the data. Correct. And here what I will pass ascending is equal to false. So now I will get the highest weighted movies for this particular user. Here we can see Star Trek Voyager season 1 will be rated as 4.9. Correct. Right, here we can see Justice League will be recommended to the user with rating of 4.42. Correct. So these movies we will recommend, and the movies with bad ratings we are not going to recommend to the user. So now everybody is understanding how it's working. Okay, here we are. Correct. Now see what I am doing over here. Let's say if I'll pick this row, everyone, Sarath, others, pay attention. Here we are discussing this row. What we are doing, we are calculating the estimate score here, right? Now for that movie ID, for what I am doing here in the movie ID, so I am passing this column movie ID. Okay, I am passing the movie ID column over there where I will pass the ID of every movie one by one. Okay, and then I'm applying the function. I am saying model to predict for this user IDs all the value of X, and X is what it is going to predict an estimate score over there. Okay, this will be executed for all the users and highest weighted estimate score for them. Correct. Like all complete estimate score, all the estimate score it will give for every value, right? Then you can select the highest and lowest. Correct. So this is what it is doing over there. Okay. Here, let me tell you one more thing, guys. The reader. Let me explain you what the reader is doing here. Okay. Now, what that reader is going to do, if I'll explain you what that reader is going to do. See, reader is an object of surprise library that is going to make sure like the rating column we have, correct or not? here the rating columns, why I'm passing it in the last, so it will read it as the ratings. It will read it like these are the feedback given by the people for that particular thing. Okay, this is what the reader is doing. Correct, same, yes, these are same, correct, these are the name. Like the first movie ID here, so we were talking about Dinosaur Planet at that time. The second movie ID we were talking, it was the Isle of Man. Okay, third movie ID was character, so correct. Movie ID for movie name are same. Okay, so like you can change the CV technique, you can change the cross validation technique, you can pass it as 5. Okay, you can pass cross validation technique as 5. This is what you can do. Okay.
Guys, I have a special announcement for all of you. For all of you dedicated individuals who are looking forward to master data science, we are offering a straightforward 20% discount on our data science course, which is in collaboration with iHub IIT Roorkee. So do make sure to check the link given in the description and fill the inquiry form. Shortly, our team of course advisors will get in touch with you to activate the offer. Don't miss this chance and take your career to the next level. Click on the link given in the description right now.
So moving on with our first question. Explain the types of data science problems along with the datasets used for each problem. Data science problems can be grouped based on what we're trying to solve. For example, one common type is classification problems like fraud detection. Here the goal is to categorize data into classes such as fraudulent or non-fraudulent. The datasets here are usually highly imbalanced, meaning there are far more non-fraud cases than frauds. Sometimes these datasets can even have a time series structure. Another type is regression. This is where we predict a continuous value. For example, predicting house prices. Datasets here might have features like the number of bedrooms, location, and property size, and the target variable would be the price feature. Then there is time series forecasting. This is used to predict future values based on historical data. A common example is stock price prediction or sales forecasting. Another type is recommendation systems. This is where we suggest items like movies, products, or songs. The data sets often include user preferences, item characteristics, and sometimes behavior logs like clicks or purchase history. Lastly, we have clustering problems like customer segmentation. Here we group similar entities based on features like age, income, or spending habits. These datasets don't have labels, so we look for patterns. Each type of problem has its unique dataset structure and challenges, but it's all about understanding the data and the problem we're solving. Moving on to the second question. What are the common issues in raw datasets that require cleaning? One common issue in raw datasets is missing values. Some rows or columns might be incomplete. For example, in a dataset of customer records, you might not have some records in the contact number feature column. This can be solved by the following methods. For numerical columns, we can fill them with the mean where there are no outliers, whereas median in case of outliers. And for categorical data, we can fill with the mode. Another issue is duplicates. This is where the same data point appears multiple times. This often leads to skewed analysis. The duplicate function can be used to identify the duplicates. There could also be outliers in the data, like a few incomes could be way too high or way too low compared to the rest. This would again lead to inaccurate prediction. You can use scaling methods like standardization or normalization to deal with outliers. I have a separate video on standardization versus normalization. You can check it out in the description. Inconsistent formatting is another big one, like dates in different formats or text fields with varying capitalization. And then there's incorrect data where entries are just wrong. So say for example, a negative value in a column for age. All the above issues can be taken care of at the data cleaning stage itself. The data needs to be accurate, consistent, and reliable for analysis. Moving on to the third question. What are the different learning mechanisms in data science? So there are four main types: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. In supervised learning, the model is trained on labeled data, meaning we already know the outcome. It's like teaching a child with examples. So say in email spam detection, we know which emails are spam, so the model learns from those examples. Next is unsupervised learning. This is where we have data but no labels. The model tries to find patterns or groupings by itself. A good example is customer segmentation, where the algorithm groups customers based on their purchasing behavior without knowing what each group represents. And then there is something known as semi-supervised. This is a mix of both. There will be a small amount of labeled data and a large amount of unlabeled data. The model uses the labeled data to learn and then generalizes to the unlabeled data. It's useful when labeling data is costly. Finally, we have reinforcement learning. Here, the model makes decisions and gets feedback in the form of rewards or penalties. It's commonly used in gaming or robotics where the model has to learn to improve its actions through trial and error. Moving on to the fourth question. Why is standard deviation often preferred over variance when analyzing data? Both variance and standard deviation measure how spread out the data is. But the key difference is that variance is in squared units, while standard deviation is in the same units as the original data. Let's say we're looking at the test scores of a class of students measured on a scale from 0 to 100. If we calculate the variance, it would give us the number in the units of squared points, say something like 25,000. Now, this is not easy to relate to the actual scores. However, when we calculate standard deviation, it's in the same units as the original data. In this case, just points. So if the standard deviation is 50, it's much clearer because we can directly understand it as the spread of scores around the average score. Standard deviation just makes it easier to relate to real world values. Moving on to the fifth question. What is overfitting and underfitting, and explain how you can detect if your model is overfitting or underfitting. So overfitting happens when the model learns the training data too well, even the noise and the random fluctuation. It performs great on the training set, but struggles with new unseen data because it's too specific to the training data. It's like memorizing answers to a practice test without truly understanding the material. On the other hand, underfitting happens when the model is too simple to capture the patterns in the data. It fails to perform well on both the training set and the test set. It's like studying just the basics and missing out on the important details. In order to detect underfitting or overfitting in your model, you need to look at performance metrics like accuracy or error rates and compare them between the training and the test sets. To deal with overfitting, you can either reduce the number of features or use techniques like regularization or cross-validation. Whereas for underfitting, you would want to make the model more complex. This might involve adding more features and increasing the model's capacity. Moving on to the sixth question. Explain the concept of regularization in machine learning and why is it important for improving model performance. Regularization is used to prevent overfitting by adding a penalty to the model for being too complex. Essentially, it discourages the model from relying too much on specific features or learning noise in the data. There are two types of regularization techniques. First is L1 regularization or lasso regularization. It adds a penalty based on the size of the model's coefficients, making some of them shrink to 0. This way, it automatically selects only the most important features and ignores the rest. For example, in house price prediction, if the number of garage doors has little impact, L1 regularization might set its weight to 0 and exclude it from the model. The next one is L2 regularization or ridge regularization. It adds a penalty based on the square of the coefficients. This reduces their size but doesn't make them 0, so all features are kept but none dominate too much. For example, in predicting house prices, if the area feature has a large impact but the number of rooms has a smaller impact, L2 regularization will ensure that both are considered while preventing the area feature from overpowering the model. Regularization is important because it helps the model generalize better to unseen data by controlling complexity and preventing overfitting. Moving on to the seventh question. If a model performs well on training data but poorly on unseen data, what technique could you use to understand its generalization ability? This is a classic case of overfitting. To understand the model's generalization ability, we can use cross-validation. With cross-validation, we will split the data into multiple smaller sets or folds. The model is trained on some folds and tested on the others. This process is repeated multiple times and we average the results to see how the model performs across different subsets of data. It's a great way to check if the model is consistently good across various splits or if it's just memorizing the training data. Moving on to the next question. What is the role of activation functions in machine learning models like linear regression and logistic regression? Activation functions are used to introduce non-linearity into a model, which allows the model to learn complex patterns in the data. In linear regression, there's actually no activation function because the output is simply a linear combination of input features. It's used for predicting continuous values. In logistic regression, however, We use the sigmoid activation function, which squashes the output between 0 and 1, making it suitable for binary classification problems like predicting the yes or no outcomes. So the main role of activation function is to help the model make more accurate predictions by capturing complex relationships in the data. Moving on to the next question, what is the confusion matrix, and describe a situation where false positive is more important than false negative and vice versa. A confusion matrix is a tool that is used to evaluate the performance of a classification model. It shows how well the model's predictions match the actual outcomes by displaying the number of correct and incorrect predictions. It's basically a table with 4 values. One is true positive. These are the correctly predicted positive cases. Then there are true negatives. These are the correctly predicted negative cases. Third is the false positives. These are the incorrectly predicted values as positive, also known as type 1 error. Lastly, we have false negatives. They are incorrectly predicted values as negative, also known as type 2 error. From these values, we can calculate other performance metrics like accuracy, precision, recall, and F1 score, which give a clearer idea of how well our model is performing. False positives are more important than false negatives in cases like a medical test for a rare disease. A false positive that is incorrectly saying someone has a disease might lead to unnecessary tests, but it's safer because it ensures we do not miss any actual cases. Whereas for a spam filter, a false negative, which is a spam email getting through, is less risky because you can always delete it. But a false positive, where important emails are marked as spam, could cause you to miss important messages. Moving on to the 10th question, why do we prefer a decision tree over a random forest? A decision tree is a simple model that splits data into branches based on features, making decisions based on these splits. It's easy to understand and visualize and works well for smaller, less complex problems where interpretability is key. A random forest, on the other hand, is a collection of multiple decision trees where each tree is trained on a random subset of the data. It combines the results from all these trees, which usually gives better accuracy and reduces overfitting. You'd prefer a decision tree over a random forest when you need a simple, interpretable model or when computational resources are limited. But if you need better accuracy and robustness, especially for complex datasets, random forests are the better choice. Moving on to the 11th question, what is naive in naive Bayes theorem? Basically, what we're trying to understand here is what does the term naive stand for in this naive Bayes theorem? So, the word naive in naive Bayes basically refers to the assumption that all the features in a dataset are independent of each other. But if you consider real life scenarios or real life data sets, this assumption does not really apply. Why? Because say for example, you have a house price prediction data set. You will have feature columns like number of bedrooms, number of bathrooms, balcony, the area of the house and so on. Now in real life, if you consider the area and number of bedrooms, number of bathrooms, so are supposed to have some sort of correlation between each other. But what naive Bayes theorem does is, it is going to consider that these features are independent of each other, that is, they have zero correlation between each other. Now, this assumption will not apply in real life, but surprisingly, it works really well in many situations, especially for classification problems, right? So, naive Bayes has a major application in classification problems. Alright. So, naive Bayes basically calculates the class probabilities based on feature likelihoods, assuming no dependence between them. Clear? So, this is the formula for naive Bayes theorem. This is the posterior probability of the hypothesis. This is what the naive Bayes is trying to calculate. This is the likelihood probability, which basically is the estimated value for each feature, assuming that all the features are independent. Alright, so this is the assumed value. And then we have our hypothesis probability and our evidence probability. Alright, before we move to the next question, let me take you guys to my notebook and show you guys the implementation of naive Bayes. Alright, so the implementation in Python is very easy for any naive Bayes. So basically we have 4 types of naive Bayes theorems. First one is Gaussian naive Bayes. So this works well for continuous data. So the Gaussian naive Bayes basically calculates the mean and the variance, and then it goes for the probability. Then we have multinomial naive Bayes. So this works for the discrete data set. Like it is going to count the data and then it is going to go and calculate the probability. Then we have Bernoulli naive Bayes. This works for binary or Boolean features like yes, no, true, false. Then lastly, we have categorical naive Bayes. So the name itself suggests that it works for categorical data sets. So you can easily import your naive Bayes theorem, whichever one you want to apply from sklearn.naive Bayes, and then you have to call your function and simply train it using the fit method. Alright, so once that is done, you can go ahead and predict it, and this is what your output is going to look like. Alright, so basically this is how it has classified it as 0 and 1. So that is all about the naive Bayes theorem. Moving on with our 12th question. What is imbalanced data and how do we handle them? So I have already made a video on this particular topic and I have explained each and every concept in a lot of detail. So you guys can go ahead and check it out. But right now I'll just cover this concept in brief so that you guys get a basic idea. Alright, so imbalanced data basically happens when one class in a data set has a lot more samples than the other. Now what does that mean? So consider this example over here. So this is a balanced data set. Now why is this a balanced data set? So we have two classes over here, female and male. Let's call them A and B. Alright. Now class A, that is female, has 51% of samples in a data set, whereas class B, which is male, has 49% of samples in the data set. Now this is a pretty you can say balanced situation. Why? Because we have almost equal number of samples, right? 51% and 49% are not that far away. But if you consider this particular scenario, we have 98% of samples in class A, which is our normal. Okay, so this imbalanced data is basically for the fraud detection data set. Okay, so we have a fraud detection data set where we have two classes, which is normal transactions and fraudulent transactions. Now, our normal transactions are obviously going to be in a higher ratio compared to a fraudulent transaction. So, we only have 2% of transactions which were fraud, which is our class B. Alright. So, the number of samples of class B is comparatively very less as class A, right? So, this is going to lead in poor performance in the minority class. Basically, our model is going to be biased towards the majority class, right? So say for example, my model predicts not fraud or say normal each time. My model is going to be 98% accurate. Isn't that right? So now with a 98% accuracy, I can say my model is working pretty well. But the cases I am most interested in. Now, the entire purpose of training a model on fraud detection dataset is to detect the fraudulent transactions, right? But if my model is failing to do the one goal it was trained for, and it is giving me 98% accuracy, I can say my model is practically useless, right? So this is why we need to handle the imbalanced datasets using techniques like undersampling, oversampling, and lastly we have SMOT, right? So in undersampling, basically we take random samples from our majority class till they are equal in size with our minority class, right? So basically we are making our data smaller. So say we had 1000 samples over here in our majority class and 100 samples over here. Our final data set is going to contain 200 samples, right? We are randomly going to pick 100 samples from our majority class. Whereas in oversampling, if we have 1000 in our majority class and 100 in our minority class, we are going to keep duplicating these samples in our minority class until and unless they are equivalent to the size of our majority class. That is, initially we had 1100 samples. Now we are going to have 2000 samples in our entire data set, right? So this is how undersampling and oversampling works. Now over here in oversampling, we are simply duplicating the data randomly in our minority class, right? We are not exactly performing some sort of calculation. Now in our next technique, which is known as SMOT or synthetic minority oversampling technique, over here instead of randomly duplicating the data, we are going to perform some sort of calculation using this particular formula, and we are going to create synthetic data points, and these data points have one rule, that is they are always going to lie between the axis of two existing data points. Alright, so this is basically what SMART does. So these are some of the techniques that you can use to handle your imbalanced data. Moving on to the 13th question, state the scenarios when the different tests can be used and also explain the p-test. So now the different tests that we have are z-test, t-test, f-test, chi-square test. Like these are some of the tests that we'll be covering in this particular question. So the first one is z-test. Now this is used for the large samples, generally greater than 30. So whenever we have more than 30 samples, we will be using z-test. Now keep this condition in mind. I'm sure some of you guys must be having a doubt regarding 30 samples. We'll be talking about this in a few minutes, but first let's cover all the tests, right? And your population standard deviation should be known. So say for example, you want to compare the average heights of two cities. So this is a scenario where you would preferably be using z-test. So this is the formula for finding the value of z-test. So you subtract your population mean from your sample mean and you divide it by your standard deviation divided by the total number of observations. Alright. Then the next one that we have is a t-test. This is used for small samples, preferably less than 30, and you don't know your population standard deviation. So say for example, you want to test a new teaching method, whether it improves your test scores in a class or it doesn't. Right? So this is the formula for your t-test. So the next one that we have is an f-test. This basically compares the variances of two data sets. So say for example, you want to check the variability in scores from two teaching methods. This is when you'll be using an f-test. So this is the formula. You divide your larger sample variance by your smaller sample variance, and then you can look up the f-test table to find the value. Then we have a chi-square test. This is used for categorical data to test relationships between your features. So say for example, you want to analyze whether genders impact the product preference, right? So for cases like that, you would be using a chi-square test. This is the formula for your chi-square test. C is your degree of freedom, O is your observed value, and E is your expected value. Alright. Then lastly, we have our p-value. Now the p-value is not particularly a test, rather it is used to determine whether the result of a statistical test is significant or not. Right? So basically, a p-value is a decision rule that compares with alpha. Now, alpha is generally 0.05, right? This is the standard value of alpha. It could vary based on the problem, but in general, we keep it 0.05. Now, if our p-value is less than or equal to 0.05, we reject our null hypothesis. But if it is greater than 0.05, we fail to reject the null hypothesis, that is, we accept our null hypothesis. Alright, so say for example, we want to test a new drug, right, and its effects. So we'd be using a p-value in this case. Now before we go ahead, let me quickly take you to my Google Notebook. Alright, so we know the general rule of using a t-test and a z-test is whether a sample size is greater than 30 or less than 30. But if you take practical scenarios or real life scenarios, our data set usually has around 1000 samples, right? Whenever we go to train a model and we pick a data set, it is going to have at least 1000 samples. Now, out of those 1000 data points, if we try to take out only 30 samples, it does not make sense, right? Our data set is going to have at least 500 or 600 data points to be able to learn and have an accurate output, right? So in a problem statement, whenever there is mean or average mentioned, we use a t-test. And whenever there is a percentage or proportion mentioned, we use a z-test. Clear? So theoretically, we take the 30 sample rule. But when it comes to practical scenarios, this is the condition that we follow. Alright? So let me quickly show you how it is implemented. So I am going to implement t-test. So this is my data set and I have taken a sample size of 1000. I have decided my new sample data. And what I'm going to do is I'm simply going to perform a one sample t-test. So I'm going to import my t-test from scipy.stats. I've declared my variables t-stat and p-value, and I've passed my column purchase, and I've given the sample size over here. And after performing that, I have got my p-value as 2.8. right? Now this 2.8 is clearly greater than 0.05. This means we have to reject our null hypothesis. And over here we have given a conclusion, that is whatever was our alternate hypothesis has become our conclusion now. Alright, so this is basically how we perform any test in Python using the libraries. So moving on to the 14th question, what are eigenvalues and eigenvectors and why are they important? So let me quickly explain a scenario where we have a data set which is in a 3D form. Alright, now if I want to make my model simple and understand the data better, my goal would be to transform this 3D data into a 2D data, while also being able to retain the maximum information out of this particular data. Now, in order to do that, I can compress my data from any one of these dimensions, either from my height, my width, or my breadth. But if my goal is to retain the maximum information, I'm definitely going to compress it from an angle that has the largest area. And if I feel this particular side is going to give me the maximum information out of my data, I'm going to compress my data set from this particular angle. So now what eigenvalues and eigenvectors are? Eigenvalues are basically going to tell me how much my data set has shrinked or stretched during my transformation, whereas my eigenvectors are going to define the direction from which my data sets have been shrinked or stretched, right? And the direction is always going to remain unchanged during that transformation. So I hope this is clear, and this is the basic formula that is used to calculate the eigenvector, which is represented with the x vector, and we have eigenvalue represented by lambda. Alright, so let's quickly look at the example. So we have a matrix denoted by A, which is 2, 0 and 0, 3. Now in order to calculate the eigenvalue, this is the formula that we'll be using. Alright, we need to calculate our matrix A minus lambda into I. Now I is the identity matrix and it is represented using this particular matrix. Alright, so now we know the determinant of this particular matrix is going to result to 0. Alright, now this is going to help us give the final values of the lambda. Alright, so now to calculate A minus lambda I, this is the kind of calculation we'll be performing. We've already multiplied lambda with our identity matrix and this is going to be the resultant matrix after multiplication, right? So after subtraction, this is going to be our final matrix, 2 minus lambda and 3 minus lambda. Once we equate it with 0, we get the values of lambda, which is 2 and 3. Alright, so we get two eigenvalues, which is 2 and 3. Now in order to calculate the eigenvectors, we are simply going to multiply x with A minus lambda I. Alright, now we know the values of lambda, which is 2 and 3. So we are going to substitute these values in lambda, and once we do that, we're going to get a matrix like this, and after we multiply this matrix with x, our x value is going to be somewhat like this. Alright, so basically these are the steps that we follow in order to calculate the eigenvalues and eigenvectors. Alright, now why are they important in data science? So eigenvalues and eigenvectors are used for principal component analysis. Basically, they reduce the dimensions of large data and they're used to identify the important features using eigenvectors. Then they're used for graph analysis and stability analysis also. Alright. Moving on to the 15th question. How do you ensure that the sample chosen for a study truly represents the entire population? Now, in order to answer this particular question, first we need to understand what is sampling. So whenever we're conducting a study, it is not always going to be possible to include everyone in the population, right? So we're going to use sampling to study a smaller, more manageable group. So the first step is to define who or what you are studying. That is, we need to define the target population. So say for example, we want to know the opinions of college students for a particular study, right? So our target population is going to be only the college students, not their parents, not their siblings, right? So that is how we define the target population. The next step would be to choose the right sampling method. Now we have over here 4 different types of sampling methods. So the first one is simple random sampling. Over here, everyone in the population is going to have an equal chance of being selected, right? There is not going to be any particular bias towards any person. The next one is systematic sampling. So over here, every nth person or nth member from a list or sequence is going to be selected. So basically over here, we're going to apply some sort of algorithm or some sort of system that every third person that we meet or every third person that we interview is going to be part of our data set. Alright. Then what we have is a stratified sampling. Over here, we divide the population into groups, that is our strata, and take a random sample from each group. Alright. So say for example, I am interviewing college students. I'm going to divide the college students into groups, say depending on their streams, right? So maybe I make groups of computer science and MBA and other fields like that, right? So once I have divided the college students into groups, I'm randomly going to pick a student from each group. Alright, so this is what is known as stratified sampling. Then lastly, we have cluster sampling. Over here, we divide the population into clusters, randomly select the clusters and include all the members from those clusters. Alright, so over here, I'm not going to select an individual from a group, rather I'm going to select the entire group randomly. Alright, so this is known as cluster sampling. So depending on our problem statement, we need to choose the right sampling method. Then third is to ensure sample size is adequate. What this means is larger samples are better because they reduce the likelihood of errors. So say for example, if we are polling 10 people to understand a city's preference, we are going to miss the diversity of opinions, right? A sample of 1000 is going to be much more reliable and much more adequate. So this is what ensuring the right sample size means. Then lastly, we need to avoid bias. Bias occurs when certain groups are favored over the others. So say for example, we only survey people from urban areas and we ignore the rural areas. So our result is going to be completely skewed, right? Obviously, the opinions of urban people are not going to match with the ones of the rural people. So this is basically how bias enters the sample. So we need to avoid bias in order to have a sample that truly represents the entire population. Alright, moving on to the 16th question. What is a gradient and gradient descent? So gradient basically measures the slope or rate of change of a function. Alright, this is the formula for gradient. Basically, we have a function and we have a gradient with respect to x and with respect to y. Basically, all the independent variables of a function. So we perform differentiation and we get the final value. Alright, so gradient basically points in the direction of the steepest increase. Alright, so if in this case we had our y value as say positive and x value also positive, then this gradient would be signifying that in whatever direction we are moving so far is the direction of the steepest increase. That is, we are going in the increasing direction, right? It is leading us to the maxima. Alright, but say in case one of these value was negative instead of positive, this particular value was negative. Now this would indicate that the direction that we are heading to is the opposite of the direction of our increase. That is, we are leading towards the minima. Alright, so basically gradient tells us how much the function is increasing or decreasing as we move in different directions. Alright, then we have gradient descent. Now this is a method to find the minimum of a function by moving in the opposite direction of the gradient. Now we already discussed gradient is going to lead us in the direction of maximum value. And now gradient descent is a method to find the minimum of a function. So obviously gradient descent is going to move in the opposite direction of the gradient. Alright, so say for example, this is our function. Alright, now in order to reach the minimum point which lies over here, what we are going to do is at every point we are going to calculate the gradient. Alright, now if the gradient is telling us that this particular direction is going to lead us to the minima and this particular direction is going to lead us towards the maxima, we are obviously going to move in the direction that is leading us towards the minima, right? And we are going to check that at each particular point until and unless we reach a point which is the global minima. Alright, so basically we are trying to reach towards the bottom of a value. Now this optimize the models by minimizing error. Alright, so this is basically what gradient and gradient descent means. Okay, moving on to the next question. Define confounding variables. Now confounding variable is something that influences both the independent and the dependent variables. Alright, so confounding variables are often referred to as hidden variables, and they can make a relationship appear between an independent variable and a dependent variable even if there is none. Alright, so this is basically what confounding variables do. Now, say for example, you're studying the relationship between exercise and weight loss. You find that people who exercise tend to lose more weight. But if you don't account for people's diet, it could be the diet causing the weight loss as well, right? And not just the exercise. So in this case, diet becomes our confounding variable. Alright, so this is basically how confounding variables work. Moving on to the next question, define bias variance trade-off. Alright, now in order to understand bias variance trade-off, we need to understand these terms separately. So bias is basically an error due to oversimplistic models that don't capture all patterns in the data. Alright, so this is an example of high bias in our data. So these are our data points, and since we have a high bias in our data, we are not really trying to understand all the data points. Rather, due to the simplicity of our model, we are just going to fit a straight line where we assume that most of our data points are being touched. But this is a case of underfitting. Alright. Then the next thing that we have is variance. Now this is an error due to models that are too complex and overfit the training data. Now this is the opposite of high bias. So basically when we have a high variance or low bias, what we do is we try to learn each and every data point in the data set. This leads to overfitting, and this is also a case where the model performs really well on the training data but very poorly on the unseen data. Alright. So a simple example or simple analogy of a high bias would be a person studying for an exam, and the person is not really trying to understand the definition and the examples of each concept. Rather, he just looks at the headings of each concept. Right? This would be a case of underfitting. But if that same person tries to memorize each and every detail of a particular concept, so he even memorizes the numericals, the exact value of each numerical, the person is going to perform extremely well if the exact same questions appear in the data. But if the values of a particular numerical or a particular question are changed even slightly, the person is going to fail in that particular case. So this is an example of overfitting. Alright? And overfitting happens when there is a low bias or a high variance. And underfitting happens when there is a high bias or low variance. Alright? Now, the entire goal of bias variance trade-off is to find the right balance between bias and variance. Now, if we have a low bias and a high variance, our model is going to fit the data well, but it is not going to generalize it. Alright? Which basically means overfitting. But if we have a high bias and low variance, our model is going to be too simple and it is going to miss important patterns or even the general patterns, the basic learnings of the data. Alright? So the goal is to find a spot where the model is complex enough to capture patterns but simple enough to avoid the overfitting. Alright, so this is basically what it means. This is the kind of point that we're looking for, which gives us the optimal solution. Moving on to the 19th question, when do we use deep learning in a project? So in order to answer this question, we need to answer what is deep learning. The deep learning is basically a subset of machine learning which uses neural networks with many layers. Alright, so it can handle complex data which includes images, text and audio. Alright, so here is an image that indicates machine learning and deep learning. So in machine learning we have an input data, then we perform feature extraction and then we perform classification and then we get an output. But in deep learning we have an input data and our feature extraction and classification are performed all together with the help of neural networks and we straight away get the output. Alright. Now, when do we use deep learning in a project? So, we use deep learning if we have a very complex and large data set. So, when our data is large and unstructured, that is, our data includes images and videos, right? So, this basically makes our data complex and it would be better to use deep learning in such cases. Alright. So, say for example, we need to analyze the medical images. Alright, so say it is a cancerous cell data set, alright, and we need to define whether the cell contains cancer or not. So we can use deep learning and basically neural networks in cases like this. Then comes the need for feature extraction. So whenever we need to automatically learn useful features from raw data, say for example, we need to identify objects in a photo, alright, so we can use deep learning again. Then when our model needs high accuracy, So when a high level of accuracy is crucial for the task, we would go for deep learning. Alright, so say for example, self-driving cars will need precise object detection and in real time, right? So we would go for deep learning. So some projects that use deep learning would be image classification, speech recognition, and natural language processing. Some other would be a chatbot, traffic sign classification, newspaper summarizer, image caption generator, human age detection, and so on. Moving on to the 20th question, what is OOB error and how is it useful? So OOB error basically stands for out of bag error, which is a concept in random forest models. Now, this is a way to estimate the model's accuracy using the leftover data that isn't used during the training. Alright. Now, we have an original training data of size 5. Now, we are going to do sampling with replacement. So, we have multiple decision trees and we are going to use the sample size of 3 for each particular decision tree. The OOB error is basically when random forests build multiple decision trees, they train each tree on a random subset of data called a bootstrap sample. During this training, some data points are going to be left out. Now, these are called the out-of-bag data points or OOB error. Alright, so once the random forest model is trained, the out-of-bag error or the out-of-bag data is going to be used to test the predictions. By aggregating the errors from all the trees, we calculate the OOB error. This is an estimate of how well the model performs on unseen data. Alright, so OOB error is useful for internal validation, which basically provides an unbiased accuracy estimate without needing to separate validation data. Then it also saves resources. So it is going to eliminate the need completely to split the data set into training and testing sets. Right, since we are already leaving out some data to be tested on, we do not need to split our data set separately. Then it also provides performance check. So it is going to help identify if the model is overfitting or underfitting. Right? So some examples of OOB error are suppose a random forest model trains on 70% of the data, which is a bootstrap sample, and the remaining 30%, which is our out-of-bag data, is going to be used to test each tree's prediction. Now we aggregate these predictions to compute the OOB error in total. Alright. Moving on to the 21st question, define and differentiate between convex and non-convex functions. Now, as you can see in this image, we have two graphs. Let me tell you, this is a convex function and this is a non-convex function. Alright. Now, in order to understand convex and non-convex, let us recall gradient descent. Right. Now, the purpose of gradient descent was to find the minimum of a function, right? This was used to minimize the error or loss of a model, correct? Now, if we talk about this particular function, if we start from any point, say initially we have a point over here, or you can say we start from this particular point, we know that our minimum point or a minima lies somewhere over here. Is that correct? As you guys can see, this is going to be, or somewhere over here, this is where the minimum of our function is going to be located. Now, if we start from this particular point and we calculate the gradient, we are going to be led into a direction somewhere over here, correct? Then when we calculate the gradient over here, we are going to be again led in this particular direction. And this process is going to be continued until and unless we reach this particular point. Now, in a convex function, it does not matter what our starting point is, because no matter from wherever we start, we are somehow or the other going to be led to the minimum point of our function, right? So, convex functions are said to have one and only one global minima, right? Now, if we talk about non-convex functions over here, so say my starting point is somewhere over here. Now, if I try and calculate the gradient, I could be directed in this particular direction or this particular direction, right? Or I could be directed towards this particular direction depending on the exact slope of the function at that particular point, right? So say if I'm directed in this particular direction, then I calculate the gradient in this particular point again, I'm going to be led somewhere over here. And once I reach this particular point is going to be considered my global minimum. But is that correct? Is this my global minimum? No, it is not. This point is supposed to be my global minimum. But since I do not have any lower point than this at this particular point, This point is going to be considered my global minimum. So basically, convex functions are said to have multiple local minimas. Alright, as you can see over here, this is another minima, this is another minima, this is another minima. So whether or not you reach the global minima depends completely on your starting point. Alright, so say if you start somewhere over here, there is a higher chance you reach the global minima rather than some other local minima. Alright, so these are your local minimas. Alright. So this is a basic differentiation between convex and non-convex functions. So a convex function is where the line segment between any 2 points on the curve lies above or on the curve. There is only one and only one global minima, and it is easier to optimize. Alright. A non-convex function is a function where the line segment between any 2 points on the curve may lie below the curve. Alright. It has multiple local minima and maxima, and it is much harder to optimize. Moving on to the 22nd question, what is collaborative filtering? So collaborative filtering is basically a method that is used to make recommendations based on user behavior. It relies on similarities between the users or the items. So collaborative filtering is again divided into two types. First is user-based and second one is item-based. Alright, so user-based collaborative filtering is basically when items are suggested based on users with similar preferences. Alright, and item-based collaborative filtering is basically when the items are suggested similar to what the user has liked previously. Alright, let's understand this with the help of an example. So there are two users, user 1 and user 2. So both these users have several movies in common. That is, they have both liked these movies or they have highly rated these movies. Now, if user 1 has watched a particular movie that user 2 has not, there is a high chance that this particular movie is recommended to user 2. Alright, so this is basically how user-based collaborative filtering works. Then we have item-based filtering. So basically we have three users who go shopping. So user 1 has shopped for these particular items, whereas user 2 has shopped for these particular items. Now if a third user has shopped for this particular item, this user is going to be recommended items from the similar category. Now if this is not clear, let me give you another example. So say if you buy a book about machine learning. Now what the system is going to do is, the system is going to recommend similar books in the same category to you as well. Maybe you get recommendations of deep learning as well, right? So this is how item-based filtering works. Based on your previous preferences, based on your previous likings, you will be recommended items in the future. Clear? Moving on to the 23rd question, what is a lazy learning algorithm? Now, lazy learning basically refers to algorithms that postpone generalizing from the training data until they receive a query, that is a new data point. Now, they don't process the data during training, but instead they store it for later use. Alright. So basically they delay generalization data until a query is made. Alright. So in the training phase, lazy learning training is almost instant because the algorithm is going to store the data set without building a complex model. Whereas in the prediction phase, when a new query comes in, the algorithm is going to compare it to the stored data to make a prediction. This step is going to take time because this is going to involve looking through all the stored data. Alright. So one example of lazy learning algorithm is the k nearest neighbors algorithm. Alright. Now what k nearest neighbors does is, so say you have 5 data points about fruits. Alright, let's say these are apples, some are apples, some are oranges. Alright, they're already classified. Alright. Now say you have a new data point, which is basically a new fruit. Now in order to classify this new fruit, what KNN is going to do is, it is going to compare it to the stored data, right? These are your stored data points, right? All these are your stored data points. Now KNN is going to compare the stored data point and check the k closest neighbors for the new data point. Alright, so say if most of the neighbors of this new data point are apples, KNN is going to classify it as apples, otherwise it is going to classify it as oranges. Clear? So this is how KNN works, and this is basically what lazy learning algorithm works. Alright. Moving on to the 24th question, Describe the differences between bagging and boosting algorithms. Alright. So bagging basically works by creating multiple subsets of the training data. So bagging and boosting are basically two powerful techniques in machine learning that are used to improve the performance of models. Alright. So both of these models are basically going to combine multiple models, but their approach and goals are completely different. Okay. So first let's see bagging. Now what bagging does is it is going to create multiple subsets of the same training data, and it is going to train independently on each subset. Alright. So basically bagging works in parallel, whereas boosting trains the model sequentially, where each new model is going to focus on correcting the errors made by the previous model. Alright. So the final prediction is going to be a weighted combination of all the models. Clear? The basic difference is clear. So let's look at the approach. So bagging basically follows a parallel model training, whereas boosting follows sequential model training. The goal of bagging is to reduce variance, whereas boosting has the main goal of reducing bias and variance. Alright. The basic method of error handling in bagging is to have equal weights for all the models, whereas boosting corrects errors of the previous models. Alright. So bagging has a lower risk of overfitting, whereas boosting has a higher risk of overfitting if not controlled. Alright. So basic example of bagging would be random forest, where we have multiple decision trees working parallelly on each subset of the training data, whereas boosting algorithms would be AdaBoost, gradient boosting, and XGBoost. Alright. Moving on to the 25th question. Explain the central limit theorem and its importance in data science. CLT or central limit theorem basically states that the sampling distribution of the sample mean approaches a normal distribution as the sample size increases. Alright. So as you can see over here, as we increase the sample size, the distribution of our data approaches a more normal curve. Alright. So this basically enables the use of statistical methods that rely only and only on normal distribution. It's going to help make inferences about the population using sample data, and it is used in hypothesis testing, confidence intervals, and many more such inferences. Alright. So a basic example would be, say you want to measure the average height of students in a school. Now the individual heights might vary a lot and may not follow a normal pattern, right? But if you repeatedly take random samples of students, calculate the average height for each sample, and then plot these averages, the graph will eventually form a normal distribution as the sample grows. Alright. So the importance of CLT in data science is mainly the foundation for statistical analysis. So stats plays a major role in data science, and CLT is a basic foundation of stats, right? Many statistical methods assume normality, and CLT is going to ensure that we can apply these methods even when the original data isn't normal. Alright. Then comes sampling and efficiency. Alright. So instead of analyzing the entire population, we can work with smaller and more manageable samples and still get reliable results. Finally, we have hypothesis testing. Alright. So CLT is used to calculate confidence intervals and perform hypothesis tests, which are essential for making data-driven decisions. Alright. So this is the importance of CLT in data science. Moving on to the 26th question. How do you decide which learning algorithm to use for a given problem? Now, choosing the right learning algorithm depends on multiple factors, such as the problem type, okay, the size of the data set, then finally the outcome. That is the outcome you desire. Now here is how you can make a decision step by step. Alright. So you need to start by understanding whether you're solving a regression problem, that is you're predicting continuous values, or is it a classification problem where you have categorical data, or it could be a clustering problem where you have to group similar data. Alright. Then comes the data set size. So if you have a small data set, you can use algorithms like logistic regression or SVM that go better with the smaller data. But if you have larger data sets, you need to use algorithms like random forest or neural networks that can handle the complexity and the big scale, right? Then comes your computational power. So if you have limited resources, you can use simpler models like linear regression or decision trees, right? You should not go for something complex like random forest. But if you have computational intensive tasks like image recognition, you have to go for neural networks, right? Then if you need high accuracy, that is your outcome. If you need a higher accuracy, especially if you have a complex problem, then you need to choose an algorithm like gradient boosting or deep learning, right? If your data is very noisy, you need ensemble methods like random forest that can reduce the overfitting. And if you have imbalanced data, you need to go for algorithms like SMART, that is synthetic minority oversampling technique, or you can combine it with SPM. Alright? So this is basically how you choose your learning algorithm. Moving on to the 27th question. Now this is a sort of scenario based question which have a very high chance of being asked in an interview. So the question goes, your features have values ranging from 1 to 10,000. How would you prepare the data for machine learning? Alright. Now, in order to prepare the data with features ranging from 1 to 10,000, you'll need to scale it. Alright, so machine learning models work much better when features are on a similar scale, especially when ranges vary widely. Now, a typical example of a dataset containing values from 1 to 10,000, basically a dataset containing outliers would be, say we are analyzing the salaries of various groups of people. Alright. Now, there would be people who would be earning in thousands, somebody would be earning in lakhs, and there would be a very few people who would be earning in crores as well. Alright. So now the people who would be earning in crores would barely be either 4 or 5. Right. These people are basically the outliers in our data set. Now, before we go ahead and train our model, we need to take care of these outliers or these values that range widely, right? So, some of the techniques that can be used in scenarios like this would be normalization or standardization. Right. So again, I have a separate video covering these topics of normalization and standardization, their implementation, the theoretical aspects, when to use which particular concept in complete detail. So you can go ahead and check it out. All right. So normalization basically use methods like min-max scaling, which helps to bring the values between 0 and 1. All right. Whereas standardization uses mean of 0 and standard deviation of 1. Alright. So this basically helps models perform more efficiently. Right. So again, you need to choose your right scaling technique. So if your data has outliers, normalization is going to work better. But if your data does not have outliers, you need to perform standardization. Alright. Let's quickly look at one small implementation. So I have a cricket data set, and when I plot the various aspects of my data set, like my innings, my not outs, my runs, and the high score and so on, I can see a lot of outliers in my data set, right? Now to tackle this situation, what I'm going to do is I'm going to perform standard scaler, alright? So I've imported standard scaler from sklearn.preprocessing. I've called my function, and then I've simply fit and transformed it on my data, right? So once my data set is scaled, that is the values are arranged between the mean of 0 and standard deviation of 1. This is what my data set is going to look like. And after my data set is scaled, I can go ahead and train my model for a better accuracy, all right? Moving on to the 28th question, which is also a scenario based question. So the question goes, your data set has missing values. Now, what are the steps that you're going to take to handle them? Now, in order to deal with the missing values in a data set, you first need to understand the nature of your missing values, right? They could either be missing completely at random, or they could be missing at random, or they could be missing not at random. Now, what do these terms mean? So, missing completely at random basically means that there is no identifiable pattern. Alright. Missing at random means that the missing values are somehow correlated with other variables. Alright. And missing not at random means that they're related to the missing value itself. Alright, so say for example, customers are not reporting low satisfaction scores. Alright, so if a column consistently has missing values, that is, if a column has more than 50% of missing values, then the best option would be dropping the entire column itself. Alright, but if that is not the case, that is, our missing values do not exceed 50%, the other possible techniques would be ignoring the missing values. That is, we drop the particular rows or the particular columns. Now, when do we drop the rows or drop the column? Whenever we have minimal missing data, that is, our missing data is less than 30%. Alright, so if a small percentage of rows or columns have missing data, we can consider dropping them without losing the significant information. Alright, so in order to perform this step, all we have to do is, let's say our data is stored in df variable, all we have to do is call drop na function. So this function is basically going to drop all the rows that contain the missing values. Now the next technique is imputing missing values. That is, we can replace the missing values with mean, median or mode. Alright. So whenever we have a data set that contains outliers, that is, say if we are dealing with a feature like salary, where our salary could range from 0 to even crores or even billions, millions, alright? There is no end limit to this number, right? We could be considering the richest person in India, right? We could be considering his or her salary as well. So for features like this, we would have outliers, right? And if we were to take the mean or the average of this particular feature, our average would not be justified to the lowest and the highest value in this particular feature. So in cases like this, we would impute our missing values with something known as median. This would give us a more accurate representation or the more accurate imputation of our missing values. But if this is not the case, we are dealing with a regular feature, then we can go ahead and impute our missing values with our mean itself. Alright. And if we are dealing with categorical data, say we're dealing with a feature called fruits, right? We have apple, we have orange, and then we have some missing values. This is when we will use something known as mode. That is the most repeated value in that particular feature. Alright. So if we have minimal data missing, less than 30%, we just drop the rows or columns. If we have substantial data missing, then we impute the data. If we have categorical data, we use the mode or unknown for imputation. If we have predictive missingness, we create an indicator variable for missingness. And if we have mostly the entire column missing, that is more than 50%, we drop the entire column if it is non-critical. Alright. Moving on with the 29th question. An e-commerce website runs 2 designs for its homepage. How would you determine which one performs better? Now this is a classic scenario of A/B testing. Alright. A/B testing is basically a method that compares 2 versions, A and B, it could be of a website or any other scenario, to determine which one performs better. Alright. Now how does it work? So A/B testing is basically going to split the website visitors randomly into 2 groups. So group A is going to see design 1 and group B is only going to see design 2. Alright. So after the groups have seen the 2 designs, we are then going to measure the performance of both designs using a key metric like conversion rate. That is the percentage of users making a purchase. Alright. So we are going to separately calculate the conversion rate for group 1 and group 2. So whichever conversion rate is higher, we are then going to classify as that particular website page as more efficient than the other. Alright. So you need to define the goal. You need to identify the key performance metrics such as the click-through rate, purchases, and so on, right? It could be n number of factors depending on what kind of website you are building. Then you need to split the traffic. So you need to randomly divide the users into equal groups, right? Then you run the experiment, that is, you show each group their respective design for a set duration. Alright. Then lastly, you analyze the results, that is, you compare the metrics, that is the conversion rates, the click-through rate, or whatever other performance metric you have decided to determine the better design. Alright. So this is how you determine which one of the 2 versions you have made performs better. Alright. Moving on to the last question for this particular video. Your data set has 50 columns, but not all are useful. How would you choose the important ones? Alright. So this is a classic example of feature selection. So feature selection basically involves removing the irrelevant or redundant data, which is the main objective of our question over here, right? Out of the 50 columns, we need to keep only the relevant ones and remove the rest. Feature selection basically helps improve the model accuracy and performance, and it also reduces the computation time, right? So say for example, out of 50 columns, only 10 are useful. This is going to reduce the data size significantly, right? So the basic methods for feature selection are correlation analysis, right? You need to identify the highly correlated columns and remove the redundant ones, right? So basically, if two columns are highly correlated, one of them may be redundant or basically useless. So say for example, if age and years of experience are strongly correlated, you can keep either one of these, right? You can also use correlation heat maps in Python using the Seaborn library and the heat map function. Then comes feature importance using models. So you can use models like random forest or gradient boosting rank features by importance, right? So say for example, in predicting the house prices, your location feature might rank higher than paint color, alright? So there's a high probability that removing the paint color is just going to make your model better, right? Then comes statistical methods. So you can apply methods like ANOVA or chi-square to assess the feature significance. Then finally comes dimensionality reduction. So you can use techniques like PCA, principal component analysis, which as we discussed use eigenvalues and eigenvectors to reduce the features while retaining the key information. Alright.
Guys, I have a special announcement for all of you. For all of you dedicated individuals who are looking forward to master data science, we are offering a straightforward 20% discount on our data science course, which is in collaboration with iHub IIT Roorkee. So do make sure to check the link given in the description and fill the inquiry form. Shortly, our team of course advisors will get in touch with you to activate the offer. Don't miss this chance and take your career to the next level. Click on the link given in the description right now.